That's really interesting. So the fact that a human may, some percent of the population may exhibit a visual decrement will not affect the overall statistical numbers of safety.
No, in fact, I think it will become very, very quickly, maybe even towards the end of this year, but I'd say I'd be shocked if it's not next year at the latest, that having a human intervene will decrease safety. Decrease. It's like, imagine if you're in an elevator. Now, it used to be that there were elevator operators, and you couldn't go in an elevator by yourself and work the lever to move between floors. Um, and now nobody wants an elevator operator because the automated elevator that stops the floors is much safer than the elevator operator. And in fact, it would be quite dangerous to have someone with a lever that can move the elevator between floors.
So that's a really powerful statement and a really interesting one. But I also have to ask, from a user experience and from a safety perspective, one of the passions for me algorithmically is camera-based detection of just sensing the human, but detecting what the driver's looking at, cognitive load, body pose. On the computer vision side, that's a fascinating problem. But and there's many in industry believe you have to have camera-based driver monitoring. Do you think there could be benefit gained from driver monitoring?
If you have a system that's at or below human level reliability, then driver monitoring makes sense. But if your system is dramatically better, more reliable than a human, then driver monitoring does not help much. And like I said, you just like you wouldn't want someone you wouldn't want someone in the elevator. If you're in an elevator, do you really want someone with a big lever, some random person operating an elevator between floors? I wouldn't trust that. I would rather have the buttons.
Okay, you're optimistic about the pace of improvement of the system. That's from what you've seen with the full self-driving car, computer.
The rate of improvement is exponential.
So one of the other very interesting design choices early on that connects to this is the operational design domain of autopilot. So where autopilot is able to be turned on. So contrast another vehicle system that we were studying is the Cadillac Super Cruise system. That's, in terms of ODD, very constrained to particular kinds of highways, well mapped, tested. It's much narrower than the ODD of Tesla vehicles. There's pros
like ADD.
Yeah, that's good. That's a good line. What was the design decision in that different philosophy of thinking, where there's pros and cons? What we see with a wide ODD is Tesla drivers are able to explore more the limitations of the system, at least early on, and they understand, together with the instrument cluster display, they start to understand what are the capabilities. So that's a benefit. The con is you're letting drivers use it basically anywhere.
So anyway, that you detect lanes with confidence.
Was there a philosophy, the design decisions that were challenging that were being made there? Or from the very beginning, was that done on purpose, with intent?
Well, I mean, I find it's pretty crazy letting people drive a 2-ton death machine manually. That's crazy. Like in the future, people were like, I can't believe anyone was just allowed to drive one of these 2-ton death machines, and they just drive wherever they wanted. Just like elevators, you just move the elevator with the lever wherever you want. It can stop it halfway between floors if you want. It's pretty crazy. So it's going to seem like a mad thing in the future that people will drive in cars.
So I have a bunch of questions about the human psychology, about behavior and so on. That would become that
mood
because you have faith in the AI system. Not faith, but both on the hardware side and the deep learning approach of learning from data will make it just far safer than humans.
Yeah, exactly.
Recently, there are a few hackers who tricked autopilot attack in unexpected ways with adversarial examples. So we all know that neural network systems are very sensitive to minor disturbances to these adversarial examples on input. Do you think it's possible to defend against something like this for the broader, for the industry?
Sure.
So,
Yeah.
can you elaborate on the confidence behind that answer?
Well, in neural net, it's just like a basic bunch of matrix math. Like you have to be like a very sophisticated, somebody who really understands neural nets, and like basically reverse engineer how the matrix is being built, and then create a little thing that just exactly causes the matrix math to be slightly off. But it's very easy to block that by having basically negative recognition. It's like if the system sees something that looks like a matrix hack, exclude it. It's such an easy thing to do.
So learn both on the validated and the invalidated. So basically learn on the adversarial examples to be able to exclude them.
Yeah, you basically want to both know what is a car and what is definitely not a car. And you train for this is a car and this is definitely not a car. Those are two different things. And people have no idea neural nets really. They probably think neural nets involves fishing net or something.
So, as you know, so taking a step beyond just Tesla and autopilot, current deep learning approaches still seem in some ways far from general intelligence systems. Do you think the current approaches will take us to general intelligence, or do totally new ideas need to be invented?
I think we're missing a few key ideas for general intelligence, artificial general intelligence. But it's going to be upon us very quickly, and then we'll need to figure out what shall we do if we even have that choice. But it's amazing how people can't differentiate between, say, the narrow AI that allows a car to figure out what a lane line is and navigate streets versus general intelligence. Like these are just very different things. Like your toaster and your computer are both machines, but one's much more sophisticated than another.
You're confident with Tesla you can create the world's best toaster.
The world's best toaster, yes. The world's best self-driving. Yes. To me, right now, this seems game set match. That's how I don't want to be complacent or confident, but that's what it appears. That is just literally how it appears right now. I could be wrong, but it appears to be the case that Tesla is vastly ahead of everyone.
Do you think we'll ever create an AI system that we can love and loves us back in a deep, meaningful way, like in the movie Her?
I think AI will be capable of convincing you to fall in love with it very well.
And that's different than us humans.
We start getting into a metaphysical question of do emotions and thoughts exist in a different realm than the physical? And maybe they do, maybe they don't. I don't know. But from a physics standpoint, I tend to think of things, like physics was my main sort of training, and from a physics standpoint, essentially, if it loves you in a way that you can't tell whether it's real or not, it is real.
That's a physics view of love.
Yeah. If you cannot prove that it does not, if there's no test that you could apply that would make it allow you to tell the difference, then there is no difference.
Right? And it's similar to seeing our world as simulation. There may not be a test to tell the difference between what the real world and the simulation, and therefore, from a physics perspective, it might as well be the same thing.
Yeah. There may be ways to test whether it's a simulation. There might be. I'm not saying there aren't. But you could certainly imagine that the simulation could correct that once an entity in the simulation found a way to detect the simulation, it could either restart pause the simulation, start a new simulation, do one of many other things that then corrects that error.
So when maybe you or somebody else creates an AGI system and you get to ask her one question, what would that question be?
What's outside the simulation?
Elon, thank you so much for talking today. It was a pleasure.
All right.
The following is a conversation with Ian Goodfellow. He's the author of a popular textbook on deep learning, simply titled Deep Learning. He coined the term generative adversarial networks, otherwise known as GANs, and with his 2014 paper is responsible for launching the incredible growth of research and innovation in this subfield of deep learning. He got his BS and MS at Stanford, his PhD at University of Montreal with Yoshio Benjo and Aaron Curvo. He held several research positions, including in OpenAI, Google Brain, and now at Apple as the director of machine learning. This recording happened while Ian was still at Google Brain, but we don't talk about anything specific to Google or any other organization. This conversation is part of the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, iTunes, or simply connect with me on Twitter at Lex Friedman, spelled F-R-I-D. And now, here's my conversation with Ian Goodfellow. You open your popular deep learning book with a Russian doll type diagram that shows deep learning is a subset of representation learning, which in turn is a subset of machine learning, and finally a subset of AI. So this kind of implies that there may be limits to deep learning in the context of AI. So what do you think is the current limits of deep learning? And are those limits something that we can overcome with time?
Yeah, I think one of the biggest limitations of deep learning is that right now it requires really a lot of data, especially labeled data. There are some unsupervised and semi-supervised learning algorithms that can reduce the amount of labeled data you need, but they still require a lot of unlabeled data. Reinforcement learning algorithms, they don't need labels, but they need really a lot of experiences. As human beings, we don't learn to play Pong by failing at Pong 2 million times. So just getting the generalization ability better is one of the most important bottlenecks in the capability of the technology today. And then I guess I'd also say deep learning is like a component of a bigger system. So far, nobody is really proposing to have only what you'd call deep learning as the entire ingredient of intelligence. You use deep learning as submodules of other systems, like AlphaGo has a deep learning model that estimates the value function. Most reinforcement learning algorithms have a deep learning module that estimates which action to take next, but you might have other components.
You're basically building a function estimator. Do you think it's possible? You said nobody's kind of been thinking about this so far, but do you think neural networks could be made to reason in the way symbolic systems did in the 80s and 90s, to do more, create more like programs as opposed to functions?
Yeah, I think we already see that a little bit. I already kind of think of neural nets as a kind of program. I think of deep learning as basically learning programs that have more than one step. So if you draw a chart or if you draw a TensorFlow graph describing your machine learning model, I think the depth of that graph is describing the number of steps that run in sequence, and then the width of that graph is the number of steps that run in parallel. Now it's been long enough that we've had deep learning working that it's a little bit silly to even discuss shallow learning anymore. But back when I first got involved in AI, when we used machine learning, we were usually learning things like support vector machines. You could have a lot of input features to the model, and you could multiply each feature by a different weight. All those multiplications were done in parallel to each other. There wasn't a lot done in series. I think what we got with deep learning was really the ability to have steps of a program that run in sequence. And I think that we've actually started to see that what's important with deep learning is more the fact that we have a multi-step program rather than the fact that we've learned a representation. If you look at things like ResNets, for example, they take one particular kind of representation and they update it several times. Back when deep learning first really took off in the academic world in 2006, when Jeff Hinton showed that you could train deep belief networks, everybody who was interested in the idea thought of it as each layer learns a different level of abstraction. But the first layer trained on images learns something like edges, and the second layer learns corners, and eventually you get these kind of grandmother cell units that recognize specific objects. Today, I think most people think of it more as a computer program where as you add more layers, you can do more updates before you output your final number. But I don't think anybody believes that layer 150 of the ResNet is a grandmother cell, and layer 100 is contours or something like that.
Okay, so you're not thinking of it as a singular representation that keeps building. You think of it as a program, sort of almost like a state. The representation is a state of understanding.
Yeah, I think of it as a program that makes several updates and arrives at better and better understandings, but it's not replacing the representation at each step. It's refining it. And in some sense, that's a little bit like reasoning. It's not reasoning in the form of deduction, but it's reasoning in the form of taking a thought and refining it carefully until it's good enough to use.
So do you think, and I hope you don't mind, we'll jump philosophical every once in a while, do you think of cognition, human cognition, or even consciousness as simply a result of this kind of sequential representation learning? Do you think that can emerge?
Cognition, yes, I think so. Consciousness, it's really hard to even define what we mean by that. I guess consciousness is often defined as things like having self-awareness, and that's relatively easy to turn into something actionable for a computer scientist to reason about. People also define consciousness in terms of having qualitative states of experience, like qualia, and there's all these philosophical problems like, can you imagine a zombie who does all the same information processing as a human, but doesn't really have the qualitative experiences that we have? That sort of thing, I have no idea how to formalize or turn it into a scientific question. I don't know how you could run an experiment to tell whether a person is a zombie or not. And similarly, I don't know how you could run an experiment to tell whether an advanced AI system had become conscious in the sense of qualia or not.
But in the more practical sense, like almost like self-attention, you think consciousness and cognition can, in an impressive way, emerge from current types of architectures that we
or if you think of consciousness in terms of self-awareness and just making plans based on the fact that the agent itself exists in the world, reinforcement learning algorithms are already more or less forced to model the agent's effect on the environment. So that more limited version of consciousness is already something that we get limited versions of with reinforcement learning algorithms if they're trained well.
But you say limited, so the big question really is how you jump from limited to human level.
Yeah.
Right, and whether it's possible. Even just building common sense reasoning seems to be exceptionally difficult. So if we scale things up, if we get much better on supervised learning, if we get better at labeling, if we get bigger data sets, more compute, do you think we'll start to see really impressive things that go from limited to something echoes of human level cognition?
I think so, yeah. I'm optimistic about what can happen just with more computation and more data. I do think it'll be important to get the right kind of data. Today, most of the machine learning systems we train are mostly trained on one type of data for each model. But the human brain, we get all of our different senses, and we have many different experiences, like riding a bike, driving a car, talking to people, reading. I think when we get that kind of integrated data set working with a machine learning model that can actually close the loop and interact, we may find that algorithms not so different from what we have today learn really interesting things when you scale them up a lot and train them on a large amount of multimodal data.
So multimodal is interesting, but within like you're working adversarial examples, so selecting within one mode of data, uh, selecting better at what are the difficult cases from which you're most useful to learn from.
Oh yeah, like could we get a whole lot of mileage out of designing a model that's resistant to adversarial examples or something like that?
Right.
Yeah. My thinking on that has evolved a lot over the last few years. When I first started to really invest in studying adversarial examples, I was thinking of it mostly as adversarial examples reveal a big problem with machine learning, and we would like to close the gap between how machine learning models respond to adversarial examples and how humans respond. After studying the problem more, I still think that adversarial examples are important. I think of them now more of as a security liability than as an issue that necessarily shows there's something uniquely wrong with machine learning as opposed to humans.
Also, do you see them as a tool to improve the performance of the system? Not on the security side, but literally just accuracy.
I do see them as a kind of tool on that side, but maybe not quite as much as I used to think. We've started to find that there's a trade-off between accuracy on adversarial examples and accuracy on clean examples. Back in 2014, when I did the first adversarially trained classifier that showed resistance to some kinds of adversarial examples, it also got better at the clean data on MNIST. And that's something we've replicated several times on MNIST, that when we train against weak adversarial examples, MNIST classifiers get more accurate. So far, that hasn't really held up on other data sets, and hasn't held up when we train against stronger adversaries. It seems like when you confront a really strong adversary, you tend to have to give something up.
Interesting. But it's such a compelling idea because it feels like that's how us humans learn.
Yeah,
the difficult cases.
We try to think of what would we screw up, and then we make sure we fix that. Yeah, it's also in a lot of branches of engineering, you do a worst case analysis and make sure that your system will work in the worst case, and then that guarantees that it'll work in all of the messy average cases that happen when you go out into a really randomized world.
Yeah, with driving with autonomous vehicles, there seems to be a desire to just think adversarially, try to figure out how to mess up the system, and if you can be robust to all those difficult cases, then you can. It's a hand-wavy, empirical way to show your system is.
Yeah. Today, most adversarial example research isn't really focused on a particular use case, but there are a lot of different use cases where you'd like to make sure that the adversary can't interfere with the operation of your system. Like in finance, if you have an algorithm making trades for you, people go to a lot of an effort to obfuscate their algorithm. That's both to protect their IP, because you don't want to research and develop a profitable trading algorithm and have somebody else capture the gains. But it's at least partly because you don't want people to make adversarial examples that fool your algorithm into making bad trades. Or I guess one area that's been popular in the academic literature is speech recognition. If you use speech recognition to hear an audio waveform and then turn that into a command that a phone executes for you, you don't want a malicious adversary to be able to produce audio that gets interpreted as malicious commands, especially if the human in the room doesn't realize that something like that is happening.
In speech recognition, has there been much success in being able to create adversarial examples that fool the system?
Yeah, actually, I guess the first work that I'm aware of is a paper called Hidden Voice Commands that came out in 2016, I believe. And they were able to show that they could make sounds that are not understandable by a human, but are recognized as the target phrase that the attacker wants the phone to recognize it as. Since then, things have gotten a little bit better on the attacker side and worse on the defender side. It's become possible to make sounds that sound like normal speech, but are actually interpreted as a different sentence than the human hears. The level of perceptibility of the adversarial perturbation is still kind of high. When you listen to the recording, it sounds like there's some noise in the background, just like rustling sounds. But those rustling sounds are actually the adversarial perturbation that makes the phone hear a completely different sentence.
Yeah, that's so fascinating. Peter Norvig mentioned that you're writing the deep learning chapter for the 4th edition of the Artificial Intelligence and Modern Approach book. So, how do you even begin summarizing the field of deep learning in a chapter?
Well, in my case, I waited like a year before I actually wrote anything. Is it? Even having written a full-length textbook before, it's still pretty intimidating to try to start writing just one chapter that covers everything. One thing that helped me make that plan was actually the experience of having written the full book before, and then watching how the field changed after the book came out. I've realized there's a lot of topics that are maybe extraneous in the first book, and just seeing what stood the test of a few years of being published and what seems a little bit less important to have included now helped me pare down the topics I wanted to cover for the book. It's also really nice now that the field is kind of stabilized to the point where some core ideas from the 1980s are still used today. When I first started studying machine learning, almost everything from the 1980s had been rejected, and now some of it has come back. So that stuff that's really stood the test of time is what I focused on putting into the book. There's also, I guess, two different philosophies about how you might write a book. One philosophy is you try to write a reference that covers everything. The other philosophy is you try to provide a high-level summary that gives people the language to understand a field and tells them what the most important concepts are. The first deep learning book that I wrote with Joshua and Aaron was somewhere between the two philosophies, that it's trying to be both a reference and an introductory guide. Writing this chapter for Russell and Norvig's book, I was able to focus more on just a concise introduction of the key concepts and the language you need to read about them more. In a lot of cases, I actually just wrote paragraphs that said, here's a rapidly evolving area that you should pay attention to. It's pointless to try to tell you what the latest and best version of a learn to learn model is. I can point you to a paper that's recent right now, but there isn't a whole lot of a reason to delve into exactly what's going on with the latest learning to learn approach or the latest module produced by a learning to learn algorithm. You should know that learning to learn is a thing and that it may very well be the source of the latest and greatest convolutional net or recurrent net module that you would want to use in your latest project. But there isn't a lot of point in trying to summarize exactly which architecture and which learning approach got to which level of performance.
So you maybe focus more on the basics of the methodology, so from backpropagation to feed forward to recurrent neural networks, convolutional, that kind of thing?
Yeah.
So if I were to ask you, I remember I took algorithms, data structures algorithms, of course. I remember the professor asked, what is an algorithm? And he yelled at everybody in a good way that nobody was answering it correctly. Everybody knew what the algorithm, it was a graduate course. Everybody knew what an algorithm was, but they weren't able to answer it well. So let me ask you, in that same spirit, what is deep learning?
I would say deep learning is any kind of machine learning that involves learning parameters of more than one consecutive step. So that, shallow learning is things where you learn a lot of operations that happen in parallel. You might have a system that makes multiple steps, like you might have hand-designed feature extractors, but really only one step is learned. Deep learning is anything where you have multiple operations in sequence, and that includes the things that are really popular today, like convolutional networks and recurrent networks, but it also includes some of the things that have died out, like Boltzmann machines, where we weren't using backpropagation. Today, I hear a lot of people define deep learning as gradient descent applied to these differential functions, and I think that's a legitimate usage of the term. It's just different from the way that I use the term myself.
So what's an example of deep learning that is not gradient descendant differentiable functions? In your, not specifically perhaps, but more even looking into the future, what's your thought about that space of approaches?
Yeah, so I tend to think of machine learning algorithms as decomposed into really three different pieces. There's the model, which can be something like a neural net or a Boltzmann machine or a recurrent model. And that basically just describes how do you take data, how do you take parameters, and what function do you use to make a prediction given the data and the parameters. Another piece of the learning algorithm is the optimization algorithm, or not every algorithm can be really described in terms of optimization, but what's the algorithm for updating the parameters or updating whatever the state of the network is. And then the last part is the data set, like how do you actually represent the world as it comes into your machine learning system. So I think of deep learning as telling us something about what does the model look like, and basically to qualify as deep, I say that it just has to have multiple layers. That can be multiple steps in a feed-forward differentiable computation. That can be multiple layers in a graphical model. There's a lot of ways that you can satisfy me that something has multiple steps that are each parameterized separately. I think of gradient descent as being all about that other piece, the how do you actually update the parameters piece. So you can imagine having a deep model, like a convolutional net, and training it with something like evolution or a genetic algorithm. And I would say that still qualifies as deep learning. And then in terms of models that aren't necessarily differentiable, I guess Boltzmann machines are probably the main example of something where you can't really take a derivative and use that for the learning process. But you can still argue that the model has many steps of processing that it applies when you run inference in the model.
So it's the steps of processing that's key. So Jeff Hinton suggests that we need to throw away back propagation, start all over. What do you think about that? What could an alternative direction of training neural networks look like?
I don't know that back propagation is going to go away entirely. Most of the time when we decide that a machine learning algorithm isn't on the critical path to research for improving AI, the algorithm doesn't die, it just becomes used for some specialized set of things. A lot of algorithms like logistic regression don't seem that exciting to AI researchers who are working on things like speech recognition or autonomous cars today. But there's still a lot of use for logistic regression in things like analyzing really noisy data in medicine and finance, or making really rapid predictions in really time-limited contexts. So I think backpropagation and gradient descent are around to stay, but they may not end up being everything that we need to get to real human level or superhuman AI.
Are you optimistic about us discovering? Backpropagation has been around for a few decades. So, are you optimistic about us as a community being able to discover something better?
Yeah, I am. I think we likely will find something that works better. You could imagine things like having stacks of models where some of the lower level models predict parameters of the higher level models. And so at the top level, you're not learning in terms of literally calculating gradients, but just predicting how different values will perform. You can kind of see that already in some areas like Bayesian optimization, where you have a Gaussian process that predicts how well different parameter values will perform. We already use those kinds of algorithms for things like hyperparameter optimization. And in general, we know a lot of things other than backprop that work really well for specific problems. The main thing we haven't found is a way of taking one of these other non-backprop-based algorithms and having it really advance the state of the art on an AI level problem.
Right.
But I wouldn't be surprised if eventually we find that some of these algorithms that, even the ones that already exist, not even necessarily a new one, we might find some way of customizing one of these algorithms to do something really interesting at the level of cognition or the level of I think one system that we really don't have working quite right yet is like short-term memory. We have things like LSTMs, they're called long short-term memory. They still don't do quite what a human does with short-term memory. Like gradient descent, to learn a specific fact has to do multiple steps on that fact. Like if I tell you the meeting today is at 3 p.m., I don't need to say over and over again, it's at 3 p.m., it's at 3 p.m., it's at 3 p.m., it's at 3 p.m.
Right.
For you to do a gradient step on each one. You just hear it once and you remember it. There's been some work on things like self-attention and attention-like mechanisms like the neural Turing machine that can write to memory cells and update themselves with facts like that right away. But I don't think we've really nailed it yet. And that's one area where I'd imagine that new optimization algorithms or different ways of applying existing optimization algorithms could give us a way of just lightning fast updating the state of a machine learning system to contain a specific fact like that without needing to have it presented over and over and over again.
So some of the success of symbolic systems in the 80s is they were able to assemble these kinds of facts better. But there's a lot of expert input required, and it's very limited in that sense. Do you ever look back to that as something that we'll have to return to eventually, sort of dust off the book from the shelf and think about how we build knowledge, representation, knowledge?
Like, will we have to use graph searches?
Right.
And like first order logic and entailment and things like that.
Yeah, exactly.
In my particular line of work, which has mostly been machine learning security and also generative modeling, I haven't usually found myself moving in that direction. For generative models, I could see a little bit of it could be useful if you had something like a differentiable knowledge base or some other kind of knowledge base where it's possible for some of our fuzzier machine learning algorithms to interact with the knowledge base.
I mean, neural network is kind of like that. It's a differentiable knowledge base of sorts.
Yeah.
But
if we had a really easy way of giving feedback to machine learning models, that would clearly help a lot with generative models. So you could imagine one way of getting there would be get a lot better at natural language processing. But another way of getting there would be take some kind of knowledge base and figure out a way for it to actually interact with the neural network.
Being able to have a chat with the neural network.
Yeah. So like one thing in generative models we see a lot today is you'll get things like faces that are not symmetrical, like people that have two eyes that are different colors. And I mean, there are people with eyes that are different colors in real life, but not nearly as many of them as you tend to see in the machine learning generated data. So if you had either a knowledge base that could contain the fact, people's faces are generally approximately symmetric, and eye color is especially likely to be the same on both sides. Being able to just inject that hint into the machine learning model without it having to discover that itself after studying a lot of data would be a really useful feature. I could see a lot of ways of getting there without bringing back some of the 1980s technology, but I also see some ways that you can imagine extending the 1980s technology to play nice with neural nets and have it help get there.
Awesome. So you talked about the story of you coming up with the idea of GANs at a bar with some friends. You were arguing that this, GANs would work, generative adversarial networks, and the others didn't think so. Then you went home at midnight, put it up, and it worked. So if I was a friend of yours at the bar, I would also have doubts. It's a really nice idea, but I'm very skeptical that it could work. What was the basis of their skepticism? What was the basis of your intuition why it should work?
I don't want to be someone who goes around promoting alcohol for the purposes of science, but in this case, I do actually think that drinking helped a little bit. When your inhibitions are lowered, you're more willing to try out things that you wouldn't try out otherwise. So I have noticed in general that I'm less prone to shooting down some of my ideas when I have had a little bit to drink. I think if I had that idea at lunchtime, I probably would have thought, it's hard enough to train one neural net. You can't train a second neural net in the inner loop of the outer neural net. That was basically my friend's objection, was that trying to train two neural nets at the same time would be too hard.
So it was more about the training process, so my skepticism would be, I'm sure you could train it, but the thing would converge to would not be able to generate anything reasonable, any kind of reasonable realism.
Yeah, so part of what all of us were thinking about when we had this conversation was deep Boltzmann machines, which a lot of us in the lab, including me, were a big fan of deep Boltzmann machines at the time. They involved two separate processes running at the same time. One of them is called the positive phase, where you load data into the model and tell the model to make the data more likely. The other one is called the negative phase, where you draw samples from the model and tell the model to make those samples less likely. In a deep Boltzmann machine, it's not trivial to generate a sample. You have to actually run an iterative process that gets better and better samples coming closer and closer to the distribution the model represents. So during the training process, you're always running these two systems at the same time. One that's updating the parameters of the model and another one that's trying to generate samples from the model. And they worked really well on things like MNIST, but a lot of us in the lab, including me, had tried to get deep Boltzmann machines to scale past MNIST to things like generating color photos, and we just couldn't get the two processes to stay synchronized. So when I had the idea for GANs, a lot of people thought that the discriminator would have more or less the same problem as the negative phase in the Boltzmann machine. That trying to train the discriminator in the inner loop, you just couldn't get it to keep up with the generator in the outer loop, and that would prevent it from converging to anything useful.
Yeah, I share that.
Yeah.
But turns out to not be the case.
A lot of the time with machine learning algorithms, it's really hard to predict ahead of time how well they'll actually perform. You have to just run the experiment and see what happens. And I would say I still today don't have like one factor I can put my finger on and say, this is why GANs worked for photo generation and deep Boltzmann machines don't. There are a lot of theory papers showing that under some theoretical settings, the GAN algorithm does actually converge, but those settings are restricted enough that they don't necessarily explain the whole picture in terms of all the results that we see in practice.
So taking a step back, can you, in the same way as we talked about deep learning, can you tell me what generative adversarial networks are?
Yeah, so generative adversarial networks are a particular kind of generative model. A generative model is a machine learning model that can train on some set of data. Let's say you have a collection of photos of cats and you want to generate more photos of cats, or you want to estimate a probability distribution over cats so you can ask how likely it is that some new image is a photo of a cat. GANs are one way of doing this. Some generative models are good at creating new data. Other generative models are good at estimating that density function and telling you how likely particular pieces of data are to come from the same distribution as the training data. GANs are more focused on generating samples rather than estimating the density function. There are some kinds of GANs like FlowGAN that can do both, but mostly GANs are about generating samples, generating new photos of cats that look realistic. And they do that completely from scratch. It's analogous to human imagination. When a GAN creates a new image of a cat, it's using a neural network to produce a cat that has not existed before. It isn't doing something like compositing photos together. You're not literally taking the eye off of one cat and the ear off of another cat. It's more of this digestive process where the neural net trains on a lot of data and comes up with some representation of the probability distribution and generates entirely new cats. There are a lot of different ways of building a generative model. What's specific to GANs is that we have a two-player game in the game theoretic sense. And as the players in this game compete, one of them becomes able to generate realistic data. The first player is called the generator. It produces output data, such as just images, for example. And at the start of the learning process, it'll just produce completely random images. The other player is called the discriminator. The discriminator takes images as input and guesses whether they're real or fake. You train it both on real data, so photos that come from your training set, actual photos of cat, and you train it to see that those are real. You also train it on images that come from the generator network, and you train it to see that those are fake. As the two players compete in this game, the discriminator tries to become better at recognizing whether images are real or fake, and the generator becomes better at fooling the discriminator into thinking that its outputs are real. And you can analyze this through the language of game theory and find that there's a Nash equilibrium where the generator has captured the correct probability distribution. So in the cat example, it makes perfectly realistic cat photos, and the discriminator is unable to do better than random guessing because all the samples coming from both the data and the generator look equally likely to have come from either source.
So do you ever sit back and just blow your mind that this thing works? So from just able to estimate that density function enough to generate realistic images. I mean, do you ever sit back
Yeah.
How does this even? Why this is quite incredible, especially where GANs have gone in terms of realism.
Yeah, and not just to flatter my own work, but generative models, all of them have this property that if they really did what we asked them to do, they would do nothing but memorize the training data.
Right.
Models that are based on maximizing the likelihood, the way that you obtain the maximum likelihood for a specific training set is you assign all of your probability mass to the training examples and nowhere else. For GANs, the game is played using a training set. So the way that you become unbeatable in the game is you literally memorize training examples. One of my former interns wrote a paper, his name is Vaishnav Nagarajan. He showed that it's actually hard for the generator to memorize the training data, hard in a statistical learning theory sense, that you can actually create reasons for why it would require quite a lot of learning steps and a lot of observations of different latent variables before you can memorize the training data. That still doesn't really explain why, when you produce samples that are new, why do you get compelling images rather than just garbage that's different from the training set. And I don't think we really have a good answer for that, especially if you think about how many possible images are out there and how few images the generative model sees during training. It seems just unreasonable that generative models create new images as well as they do, especially considering that we're basically training them to memorize rather than generalize. I think part of the answer is there's a paper called Deep Image Prior, where they show that you can take a convolutional net and you don't even need to learn the parameters of it at all. You just use the model architecture. And it's already useful for things like in-painting images. I think that shows us that the convolutional network architecture captures something really important about the structure of images. And we don't need to actually use learning to capture all the information coming out of the convolutional net. That would imply that it would be much harder to make generative models in other domains. So far, we're able to make reasonable speech models and things like that. But to be honest, we haven't actually explored a whole lot of different data sets all that much. We don't, for example, see a lot of deep learning models of like biology data sets, where you have lots of microarrays measuring the amount of different enzymes and things like that. So we may find that some of the progress that we've seen for images and speech turns out to really rely heavily on the model architecture. And we were able to do what we did for vision by trying to reverse engineer the human visual system. And maybe it'll turn out that we can't just use that same trick for arbitrary kinds of data.
Right, so there's aspects of the human vision system, the hardware of it, that makes it, without learning, without cognition, just makes it really effective at detecting the patterns we see in the visual world.
Yeah.
That's really interesting. In a big, quick overview, in your view, what types of GANs are there, and what other generative models besides GANs are there?
Yeah, so it's maybe a little bit easier to start with what kinds of generative models are there other than GANs. So most generative models are likelihood-based, where to train them, you have a model that tells you how much probability it assigns to a particular example, and you just maximize the probability assigned to all the training examples. It turns out that it's hard to design a model that can create really complicated images or really complicated audio waveforms and still have it be possible to estimate the likelihood function from a computational point of view. Most interesting models that you would just write down intuitively, it turns out that it's almost impossible to calculate the amount of probability they assign to a particular point. So there's a few different schools of generative models in the likelihood family. One approach is to very carefully design the model so that it is computationally tractable to measure the density it assigns to a particular point. So there are things like autoregressive models, like pixel CNN. Those basically break down the probability distribution into a product over every single feature. So for an image, you estimate the probability of each pixel given all of the pixels that came before it. There's tricks where if you want to measure the density function you can actually calculate the density for all these pixels more or less in parallel. Generating the image still tends to require you to go one pixel at a time, and that can be very slow. But there are, again, tricks for doing this in a hierarchical pattern where you can keep the runtime under control.
Are the quality of the images it generates, putting runtime aside, pretty good?
They're reasonable, yeah. I would say a lot of the best results are from GANs these days, but it can be hard to tell how much of that is based on who's studying which type of algorithm, if that makes sense.
The amount of effort invested in it.
Yeah, or like the kind of expertise. So a lot of people who've traditionally been excited about graphics or art and things like that have gotten interested in GANs. And to some extent, it's hard to tell, are GANs doing better because they have a lot of graphics and art experts behind them, or are GANs doing better because they're more computationally efficient, or are GANs doing better because they prioritize the realism of samples over the accuracy of the density function? I think all of those are potentially valid explanations, and it's hard to tell.
But can you give a brief history of GANs from 2014, paper 13?
Yeah, so a few highlights. In the first paper, we just showed that GANs basically work. If you look back at the samples we have now, they look terrible. On the CFAR 10 data set, you can't even recognize objects in them.
Your paper, sorry, you use CFAR 10?
We use MNIST, which is little handwritten digits. We use the Toronto Face Database, which is small grayscale photos of faces. We did have recognizable faces. My colleague Bing Xu put together the first GAN face model for that paper. We also had the CFAR 10 data set, which is things like very small 32 by 32 pixels of cars and cats and dogs. For that, we didn't get recognizable objects, but all the deep learning people back then were really used to looking at these failed samples and kind of reading them like tea leaves.
Right.
And people who are used to reading the tea leaves recognize that our tea leaves at least look different.
Right.
Maybe not necessarily better, but there was something unusual about them. And that got a lot of us excited. One of the next really big steps was LapGAN by Emily Denton and Sumit Chintala at Facebook AI Research, where they actually got really good high-resolution photos working with GANs for the first time. They had a complicated system where they generated the image starting at low res and then scaling up to high res, but they were able to get it to work. And then in 2015, I believe, later that same year, Alec Redford and Sumit Chintala and Luke Metz published the DC GAN paper, which it stands for Deep Convolutional GAN. It's kind of a non-unique name because these days basically all GANs and some before that were deep and convolutional, but they just kind of picked a name for a really great recipe where they were able to actually, using only one model instead of a multi-step process, actually generate realistic images of faces and things like that. That was sort of like the beginning of the Cambrian explosion of GANs. Like, once you got animals that had a backbone, you suddenly got lots of different versions of like fish and four-legged animals and things like that. So DC GAN became kind of the backbone for many different models that came out.
Used as a baseline, even still.
Yeah. And so from there, I would say some interesting things we've seen are there's a lot you can say about how just the quality of standard image generation GANs has increased. But what's also maybe more interesting on an intellectual level is how the things you can use GANs for has also changed. One thing is that you can use them to learn classifiers without having to have class labels for every example in your training set. So that's called semi-supervised learning. My colleague at OpenAI, Tim Solomons, who's at Brain now, wrote a paper called Improved Techniques for Training GANs. I'm a co-author of this paper, but I can't claim any credit for this particular part. One thing he showed in the paper is that you can take the GAN discriminator and use it as a classifier that actually tells you, this image is a cat, this image is a dog, this image is a car, this image is a truck, and so on. Not just to say whether the image is real or fake, but if it is real, to say specifically what kind of object it is. And he found that you could train these classifiers with far fewer labeled examples than traditional classifiers.
So if you supervise based on also not just your discrimination ability, but your ability to classify, you're going to do much you're going to converge much faster to being effective at being discriminated.
Yeah. So for example, for the MNIST data set, you want to look at an image of a handwritten digit and say whether it's a 0, a 1, or a 2, and so on. To get down to less than 1% accuracy required around 60,000 examples until maybe about 2014 or so. In 2016, with this semi-supervised GAN project, Tim was able to get below 1% error using only 100 labeled examples. So that was about a 600x decrease in the amount of labels that he needed. He's still using more images than that, but he doesn't need to have each of them labeled as, this one's a 1, this one's a 2, this one's a 0, and so on.
Then to be able to, for GANs to be able to generate recognizable objects, so objects from a particular class, you still need labeled data because you need to know what it means to be a particular class, cat, dog. How do you think we can move away from that?
Yeah, some researchers at Brain Zurich actually just released a really great paper on semi-supervised GANs where their goal isn't to classify, it's to make recognizable objects despite not having a lot of labeled data. They were working off of DeepMind's Big GAN project, and they showed that they can match the performance of Big GAN using only 10%, I believe, of the labels. Big GAN was trained on the ImageNet dataset, which is about 1.2 million images, and had all of them labeled. This latest project from Brain Zurich shows that they're able to get away with only having about 10% of the images labeled. And they do that essentially using a clustering algorithm, where the discriminator learns to assign the objects to groups, and then this understanding that objects can be grouped into similar types helps it to form more realistic ideas of what should be appearing in the image, because it knows that every image it creates has to come from one of these archetypal groups rather than just being some arbitrary image. If you train a GAN with no class labels, you tend to get things that look sort of like grass or water or brick or dirt, but without necessarily a lot going on in them. And I think that's partly because if you look at a large ImageNet image, the object doesn't necessarily occupy the whole image, and so you learn to create realistic sets of pixels, but you don't necessarily learn that the object is the star of the show and you want it to be in every image you make.
Yeah, I've heard you talk about the horse, the zebra cycle GAN mapping, and how it turns out, again, thought-provoking, that horses are usually on grass and zebras are usually on drier terrain. So when you're doing that kind of generation, you're going to end up generating greener horses or whatever. So those are connected together. It's not just
Yeah.
You're not able to segment. Generate a segmented way. So, are there other types of games you come across in your mind that neural networks can play with each other to be able to solve problems?
Yeah, the one that I spend most of my time on is in security. You can model most interactions of the game where there's attackers trying to break your system and you're the defender trying to build a resilient system. There's also domain adversarial learning, which is an approach to domain adaptation that looks really a lot like GANs. The authors had the idea before the GAN paper came out. Their paper came out a little bit later, and they're very nice and cited the GAN paper, but I know that they actually had the idea before it came out. Domain adaptation is when you want to train a machine learning model in one setting, a domain, and then deploy it in another domain later. And you would like it to perform well in the new domain, even though the new domain is different from how it was trained. So for example, you might want to train on a really clean image data set like ImageNet, but then deploy on users' phones, where the user is taking pictures in the dark and pictures while moving quickly and just pictures that aren't really centered or composed all that well. When you take a normal machine learning model, it often degrades really badly when you move to the new domain because it looks so different from what the model was trained on. Domain adaptation algorithms try to smooth out that gap. And the domain adversarial approach is based on training a feature extractor where the features have the same statistics regardless of which domain you extracted them on. So in the domain adversarial game, you have one player that's a feature extractor and another player that's a domain recognizer. The domain recognizer wants to look at the output of the feature extractor and guess which of the two domains the features came from. So it's a lot like the real versus fake discriminator in GANs. And then the feature extractor, you can think of as loosely analogous to the generator in GANs, except what it's trying to do here is both fool the domain recognizer into not knowing which domain the data came from, and also extract features that are good for classification. So at the end of the day, you can, in the cases where it works out, you can actually get features that work about the same in both domains. Sometimes this has a drawback where in order to make things work the same in both domains, it just gets worse in the first one. But there are a lot of cases where it actually works out well in both.
So do you think of GANs being useful in the context of data augmentation?
Yeah, one thing you could hope for with GANs is you could imagine I've got a limited training set and I'd like to make more training data to train something else like a classifier. You could train the GAN on the training set and then create more data, and then maybe the classifier would perform better on the test set after training on this bigger GAN generated data set. So that's the simplest version of something you might hope would work. I've never heard of that particular approach working, but I think there's some closely related things that I think could work in the future, and some that actually already have worked. So if we think a little bit about what we'd be hoping for if we use the GAN to make more training data, we're hoping that the GAN will generalize to new examples better than the classifier would have generalized if it was trained on the same data. And I don't know of any reason to believe that the GAN would generalize better than the classifier would. But what we might hope for is that the GAN could generalize differently from a specific classifier. So one thing I think is worth trying that I haven't personally tried but we could try is, what if you trained a whole lot of different generative models on the same training set, create samples from all of them, and then train a classifier on that? Because each of the generative models might generalize in a slightly different way, they might capture many different axes of variation that one individual model wouldn't. And then the classifier can capture all of those ideas by training on all of their data. So it'd be a little bit like making an ensemble of classifiers. And I think that
of GANs.
Yeah,
in a way.
I think that could generalize better. The other thing that GANs are really good for is not necessarily generating new data that's exactly like what you already have, but by generating new data that has different properties from the data you already have. One thing that you can do is you can create differentially private data. So suppose that you have something like medical records, and you don't want to train a classifier on the medical records and then publish the classifier, because someone might be able to reverse engineer some of the medical records you trained on. There's a paper from Casey Green's lab that shows how you can train a GAN using differential privacy, and then the samples from the GAN still have the same differential privacy guarantees as the parameters of the GAN. So you can make fake patient data for other researchers to use, and they can do almost anything they want with that data because it doesn't come from real people, and the differential privacy mechanism gives you clear guarantees on how much the original people's data has been protected.
That's really interesting, actually. I haven't heard you talk about that before. In terms of fairness, I've seen from AAAI your talk, how can adversarial machine learning help models be more fair with respect to sensitive variables?
Yeah, so there's a paper from Amos Storkey's lab about how to learn machine learning models that are incapable of using specific variables. So say, for example, you wanted to make predictions that are not affected by gender. It isn't enough to just leave gender out of the input to the model. You can often infer gender from a lot of other characteristics. Like, say that you have the person's name, but you're not told their gender. Well, if their name is Ian, they're kind of obviously a man. So what you'd like to do is make a machine learning model that can still take in a lot of different attributes and make a really accurate, informed prediction, but be confident that it isn't reverse engineering gender or another sensitive variable internally. You can do that using something very similar to the domain adversarial approach, where you have one player that's a feature extractor and another player that's a feature analyzer. You want to make sure that the feature analyzer is not able to guess the value of the sensitive variable that you're trying to keep private.
Right. I love this approach to with the feature. You're not able to infer right? The sensitive variables.
Yeah.
Brilliant. That's quite brilliant and simple, actually.
Another way I think that GANs in particular could be used for fairness would be to make something like a cycle GAN, where you can take data from one domain and convert it into another. We've seen cycle GAN turning horses into zebras. We've seen other unsupervised GANs made by Mingyu Liu doing things like turning day photos into night photos. I think for fairness, you could imagine taking records for people in one group and transforming them into analogous people in another group, and testing to see if they're treated equitably across those two groups. There's a lot of things that'd be hard to get right to make sure that the conversion process itself is fair, and I don't think it's anywhere near something that we could actually use yet. But if you could design that conversion process very carefully, it might give you really good audits where you say, what if we took people from this group, converted them into equivalent people in another group? Does the system actually treat them how it ought to?
That's also really interesting. You know, in popular press and in general, in our imagination, we think, well, GANs are able to generate data, and you start to think about deep fakes or being able to sort of maliciously generate data that fakes the identity of other people. Is this something of a concern to you? Is this something, if you look 10, 20 years into the future, is that something that pops up in your work and the work of the community that's working on generating models?
I'm a lot less concerned about 20 years from now than the next few years. I think there will be a kind of bumpy cultural transition as people encounter this idea that there can be very realistic videos and audio that aren't real. I think 20 years from now, people will mostly understand that you shouldn't believe something is real just because you saw a video of it. People will expect to see that it's been cryptographically signed, or have some other mechanism to make them believe that the content is real. There's already people working on this. Like there's a startup called TruePic that provides a lot of mechanisms for authenticating that an image is real. They're maybe not quite up to having a state actor try to evade their verification techniques, but it's something that people are already working on, and I think we'll get right eventually.
Do you think authentication will eventually win out? So being able to authenticate that this is real and this is not.
Yeah.
As opposed to GANs just getting better and better, or generative models being able to get better and better to where the nature of what is real.
I don't think we'll ever be able to look at the pixels of a photo and tell you for sure that it's real or not real. And I think it would actually be somewhat dangerous to rely on that approach too much. If you make a really good fake detector and then someone's able to fool your fake detector and your fake detector says this image is not fake, then it's even more credible than if you've never made a fake detector in the first place. What I do think we'll get to is systems that we can kind of use behind the scenes to make estimates of what's going on and maybe not like use them in court for definitive analysis. I also think we will likely get better authentication systems where, imagine that every phone cryptographically signs everything that comes out of it. You wouldn't be able to conclusively tell that an image was real, but you would be able to tell somebody who knew the appropriate private key for this phone was actually able to sign this image and upload it to this server at this timestamp. So you could imagine maybe you make phones that have the private keys hardware embedded in them. If like a state security agency really wants to infiltrate the company, they could probably, plant a private key of their choice or break open the chip and run the private key or something like that. But it would make it a lot harder for an adversary with fewer resources to fake things.
For most of us.
Yeah.
Okay. So you mentioned the beer and the bar and the new ideas. You were able to implement this or come up with this new idea pretty quickly and implement it pretty quickly. Do you think there are still many such groundbreaking ideas in deep learning that could be developed so quickly?
Yeah, I do think that there are a lot of ideas that can be developed really quickly. GANs were probably a little bit of an outlier on the whole 1 hour time scale, but just in terms of low resource ideas where you do something really different on the algorithm scale and get a big payback, I think it's not as likely that you'll see that in terms of things like core machine learning technologies, like a better classifier or a better reinforcement learning algorithm or a better generative model. If I had the GAN idea today, it would be a lot harder to prove that it was useful than it was back in 2014, because I would need to get it running on something like ImageNet or CellObey at high resolution. Those take a while to train. You couldn't train it in an hour and know that it was something really new and exciting. Back in 2014, training on MNIST was enough. But there are other areas of machine learning where I think a new idea could actually be developed really quickly with low resources.
What's your intuition about what areas of machine learning are ripe for this?
Yeah, so I think fairness and interpretability are areas where we just really don't have any idea how anything should be done yet. Like for interpretability, I don't think we even have the right definitions. And even just defining a really useful concept, you don't even need to run any experiments, could have a huge impact on the field. We've seen that, for example, in differential privacy, that Cynthia Dwork and her collaborators made this technical definition of privacy, where before a lot of things were really mushy, and then with that definition, you could actually design randomized algorithms for accessing databases and guarantee that they preserve individual people's privacy in like a mathematical quantitative sense. Right now, we all talk a lot about how interpretable different machine learning algorithms are, but it's really just people's opinion, and everybody probably has a different idea of what interpretability means in their head. If we could define some concept related to interpretability that's actually measurable, that would be a huge leap forward, even without a new algorithm that increases that quantity. And also, once we had the definition of differential privacy, it was fast to get the algorithms that guaranteed it. So you could imagine, once we have definitions of good concepts and interpretability, we might be able to provide the algorithms that have the interpretability guarantees quickly too.
What do you think it takes to build a system with human level intelligence as we quickly venture into the philosophical? So artificial general intelligence. What do you think it takes?
I think that it definitely takes better environments than we currently have for training agents, that we want them to have a really wide diversity of experiences. I also think it's going to take really a lot of computation. It's hard to imagine exactly how much.
So you're optimistic about simulating a variety of environments is the path forward?
I think it's a necessary ingredient. Yeah, I don't think that we're going to get to artificial general intelligence by training on fixed data sets or by thinking really hard about the problem. I think that the agent really needs to interact and have a variety of experiences within the same lifespan. And today we have many different models that can each do one thing, and we tend to train them on one data set or one RL environment. Sometimes there are actually papers about getting one set of parameters to perform well in many different RL environments, but we don't really have anything like an agent that goes seamlessly from one type of experience to another and really integrates all the different things that it does over the course of its life. When we do see multi-agent environments, they tend to be, there's so many multi-environment agents, they tend to be similar environments. Like all of them are playing like an action-based video game. We don't really have an agent that goes from playing a video game to like reading the Wall Street Journal to predicting how effective a molecule will be as a drug or something like that.
What do you think is a good test for intelligence in your view? There's been a lot of benchmarks. Started with with Alan Turing, natural conversation being a good benchmark for intelligence. What would me and Goodfellow sit back and be really damn impressed if a system was able to accomplish?
Something that doesn't take a lot of glue from human engineers. So imagine that instead of having to go to the CFAR website and download CFAR 10 and then write a Python script to parse it and all that, you could just point an agent at the CFAR 10 problem, and it downloads and extracts the data and trains a model and starts doing predictions. I feel like something that doesn't need to have every step of the pipeline assembled for it definitely understands what it's doing.
Is AutoML moving into that direction, or are you thinking way bigger?
AutoML has mostly been moving toward once we've built all the glue, can the machine learning system design the architecture really well? And so I'm more saying, like, if something knows how to pre-process the data so that it successfully accomplishes the task, then it would be very hard to argue that it doesn't truly understand the task in some fundamental sense. And I don't necessarily know that that's like the philosophical definition of intelligence, but that's something that would be really cool to build, that would be really useful, and would impress me, and would convince me that we've made a step forward in real AI.
So you give it like the URL for Wikipedia, and then next day expect it to be able to solve CFAR 10.
Or like you type in a paragraph explaining what you want it to do, and it figures out what web searches it should run and downloads all the necessary ingredients.
So you have a very clear, calm way of speaking, no ums, easy to edit. I've seen comments that both you and I have been identified as both potentially being robots. And if you have to prove to the world that you are indeed human, how would you do it?
I can understand thinking that I'm a robot.
It's the flip side to the Turing test, I think.
Yeah, the prove you're human test.
Intellectually, so you have to. Is there something that's truly unique in your mind? Does it go back to just natural language again? Just being able to.
So proving that I'm not a robot with today's technology. Yeah, that's pretty straightforward. Like my conversation today hasn't veered off into, talking about the stock market or something because it's my training data. But I guess more generally, trying to prove that something is real from the content alone is incredibly hard. That's one of the main things I've gotten out of my GAN research, that you can simulate almost anything. And so you have to really step back to a separate channel to prove that something is real. So like, I guess I should have had myself stamped on a blockchain when I was born or something, but I didn't do that. So according to my own research methodology, there's just no way to know at this point.
So what, last question, problem stands out for you that you're really excited about challenging in the near future?
I think resistance to adversarial examples, figuring out how to make machine learning secure against an adversary who wants to interfere it and control it, that is one of the most important things researchers today can solve.
In all domains, image, language, driving, and everything.
I guess I'm most concerned about domains we haven't really encountered yet. Like imagine 20 years from now when we're using advanced AIs to do things we haven't even thought of yet. Like if you ask people, what are the important problems in security of phones in like 2002? I don't think we would have anticipated that we're using them for nearly as many things as we're using them for today. I think it's going to be like that with AI, that you could kind of try to speculate about where it's going, but really the business opportunities that end up taking off would be hard to predict ahead of time. What you can predict ahead of time is that almost anything you can do with machine learning, you would like to make sure that people can't get it to do what they want rather than what you want, just by showing it a funny QR code or a funny input pattern.
And you think that the set of methodologies to do that can be bigger than any one domain? And that's
I think so, yeah. Like one methodology that I think is not a specific methodology, but like a category of solutions that I'm excited about today is making dynamic models that change every time they make a prediction. So right now, we tend to train models, and then after they're trained, we freeze them, and we just use the same rule to classify everything that comes in from then on. That's really a sitting duck from a security point of view. If you always output the same answer for the same input, then people can just run inputs through until they find a mistake that benefits them, and then they use the same mistake over and over and over again. I think having a model that updates its predictions so that it's harder to predict what you're going to get will make it harder for an adversary to really take control of the system and make it do what they want it to do.
Yeah, models that maintain a bit of a sense of mystery about them. They always keep changing.
Yeah.
Ian, thanks so much for talking today. That's awesome.
Thank you for coming in. It's great to see you.
following is a conversation with Ariel Vinales. He's a senior research scientist at Google DeepMind. Before that, he was at Google Brain and Berkeley. His research has been cited over 39,000 times. He's truly one of the most brilliant and impactful minds in the field of deep learning. He's behind some of the biggest papers and ideas in AI, including sequence-to-sequence learning, audio generation, image captioning, neural machine translation, and, of course, reinforcement learning. He's a lead researcher at the Alpha Star project, creating an agent that defeated a top professional at the game of StarCraft. This conversation is part of the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, iTunes, or simply connect with me on Twitter at Lex Friedman, spelled F-R-I-D. And now, here's my conversation with Ariel Vinales. You spearheaded the DeepMind team behind AlphaStar that recently beat a top professional player at StarCraft. So you have an incredible wealth of work in deep learning in a bunch of fields, but let's talk about StarCraft first. Let's go back to the very beginning, even before AlphaStar, before DeepMind, before deep learning. First, what came first for you, a love for programming or a love for video games?
I think for me, it definitely came first the drive to play video games. I really liked computers. I didn't really code much, but what I would do is I would just mess with the computer, break it, and fix it. That was the level of skills, I guess, that I gained in my very early days. I mean, when I was 10 or 11. And then I really got into video games, especially StarCraft, actually, the first version. I spent most of my time just playing kind of pseudo-professionally, as professionally as you could play back in '98 in Europe, which was not very mainstream like what's called nowadays esports.
Right, of course, in the 90s. So how did you get into StarCraft? What was your favorite race? How did you develop your skill? What was your strategy? All that kind of thing.
So as a player, I tended to try to play not many games, not to kind of disclose the strategies that I kind of developed. And I like to play random, actually, not in competitions, but just to, I think in StarCraft there's three main races, and I found it very useful to play with all of them. And so I would choose random many times, even sometimes in tournaments, to gain skill on the three races, because it's not how you play against someone, but also if you understand the race because you play it, you also understand what's annoying, what then when you're on the other side, what to do to annoy that person, to try to gain advantages here and there and so on. So I actually played random, although I must say in terms of favorite race, I really like Zerg. I was probably best at Zerg, and that's probably what I tend to use towards the end of my career before starting university.
So let's step back a little bit. Could you try to describe StarCraft to people that may never have played video games, especially the massively online variety?
Right.
StarCraft.
So StarCraft is a real-time strategy game, and the way to think about StarCraft, perhaps if you understand a bit chess, is that there's a board which is called map or the map where people play against each other. There's obviously many ways you can play, but the most interesting one is the 1 versus 1 setup, where you just play against someone else, or even the built-in AI, right? These are good system that can play the game reasonably well if you don't know how to play. And then in this board, you have, again, pieces like in chess, but these pieces are not there initially like they are in chess. You actually need to decide to gather resources, to decide which pieces to build. So in a way, you're starting almost with no pieces. You start gathering resources in StarCraft, those minerals and gas that you can gather, and then you must decide how much do you want to focus, for instance, on gathering more resources or starting to build units or pieces. And then once you have enough pieces or maybe like attack, a good attack composition, then you go and attack the other side of the map. And now the other main difference with chess is that you don't see the other side of the map. So you're not seeing the moves of the enemy. It's what we call partially observable. So as a result, you must not only decide trading off economy versus building your own unit, But you also must decide whether you want to scout to gather information, but also by scouting you might be giving away some information that you might be hiding from the enemy. So there's a lot of complex decision making, all in real time. There's also, unlike chess, this is not a turn-based game. You play basically all the time, continuously, and thus some skill in terms of speed and accuracy of clicking is also very important. And people that train for this really play this game at an amazing skill level. I've seen many times these, and if you can witness this live, it's really, really impressive. So in a way, it's kind of a chess where you don't see the other side of the board. You're building your own pieces, and you also need to gather resources to basically get some money to build other buildings, pieces, technology, and so on.
From the perspective of a human player, the difference between that and chess, or maybe that and a game like turn-based strategy like Heroes of Might and Magic, is that there's an anxiety because you have to make these decisions really quickly, and if you are not actually aware of what decisions work, it's a very stressful balance. Everything you described is actually quite stressful, difficult to balance for an amateur human player. I don't know if it gets easier at the professional level, like if they're fully aware of what they have to do, but at the amateur level, there's this anxiety. Oh crap, I'm being attacked. Oh crap, I have to build up resources. Oh, I have to probably expand, and all these. The real-time strategy aspect is really stressful, and computation, I'm sure, difficult. We'll get into it, but for me, BattleNet. So StarCraft was released in '98, 20 years ago, which is hard to believe. And Blizzard BattleNet with Diablo in '96 came out. And to me, it might be a narrow perspective, but it changed online gaming and perhaps society forever.
Yeah.
But I may have made way too narrow a viewpoint, but from your perspective, can you talk about the history of gaming over the past 20 years? Is this, how transformational, how important is this line of gaming?
Right. So I think I kind of was an active gamer whilst this was developing, the internet, online gaming. So for me, the way it came was I played other games, strategy related, like a bit of Command and Conquer, and then I played Warcraft 2, which is from Blizzard. But at the time, I didn't know, I didn't understand about what Blizzard was already. Warcraft 2 was just a game, which was actually very similar to StarCraft in many ways. It's also a real-time strategy game where there's orcs and humans, so there's only two races.
But it was offline.
And it was offline, right? So I remember a friend of mine came to school saying, "Oh, there's this new cool game called StarCraft," and I just said, "Oh, this sounds like just a copy of Warcraft 2." Until I kind of installed it, and at the time I am from Spain, so we didn't have internet, like very good internet, right? So there was, for us, StarCraft became first kind of an offline experience where you kind of start to play these missions, right? You play against some sort of scripted things to develop the story of the characters in the game. And then later on, I start playing against the built-in AI, and I thought it was impossible to defeat it. Then eventually you defeat one, and you can actually play against 7 built-in AIs at the same time, which also felt impossible. But actually, it's not that hard to beat 7 built-in AIs at once. So once we achieved that, also we discovered that we could play. As I said, internet wasn't that great, but we could play with the LAN, right? On like basically against each other. If we were in the same place, we could just connect machines with like cables, right? So we started playing in LAN mode, and against as a group of friends, and it was really, really like much more entertaining than playing against the AIs. And later on, as the internet was starting to develop and being a bit faster and more reliable, then it's when I started experiencing BattleNet, which is this amazing universe, not only because of the fact that you can play the game against anyone in the world, but you can also get to know more people. You just get exposed to now like this vast variety of, it's kind of a big, when the chats came about, right? There was a chat system. You could play against people, but you could also chat with people, not only about StarCraft, but about anything. And that became a way of life for kind of 2 years. And obviously then it became like, it exploded in that I started to play more seriously, going to tournaments and so on and so forth.
Do you have a sense on a societal, sociological level what's this whole part of society that many of us are not aware of, and it's a huge part of society, which is gamers. I mean, every time I come across that in YouTube or streaming sites, I mean, this is a huge number of people play games religiously. Do you have a sense of those folks, especially now that you've returned to that realm a little bit on the AI side?
Yeah, so in fact, even after StarCraft, I actually played World of Warcraft, which is maybe the main sort of online world or presence that you get to interact with lots of people. So I played that for a little bit. It was, to me, it was a bit less stressful than StarCraft because winning was kind of a given. You just put in this world and you can always complete missions. But I think it was actually the social aspect of, especially StarCraft first, and then games like World of Warcraft, really shaped me in a very interesting ways, because what you get to experience is just people you wouldn't usually interact with, right? So even nowadays, I still have many Facebook friends from the era where I played online, and their ways of thinking is even political. They just, we don't live in, like, we don't interact in the real world, but we were connected by basically fiber, and that way I actually get to understand a bit better that we live in a diverse world, and these were just connections that were made by, because I happened to go in a city, in a virtual city, as a priest, and I met this warrior, and we became friends, and then we started like playing together, right? So I think it's transformative, and more people are more aware of it. I mean, it's becoming quite mainstream. But back in the day, as you were saying, in 2000, 2005, even, it was still very strange thing to do, especially in Europe. I think there were exceptions, like Korea, for instance. It was amazing, like that everything happened so early in terms of cyber cafes. Like it's if you go to Seoul, it's a city that back in the day, StarCraft was kind of, you could be a celebrity by playing StarCraft, but this was like 99, 2000, right? It's not like recently. So yeah, it's quite interesting to look back, and yeah, I think it's changing society the same way, of course, like technology and social networks and so on are also transforming things.
And a quick tangent, let me ask, you're also one of the most productive people in your particular chosen passion, path in life, and yet you're also appreciate and enjoy video games. Do you think it's possible to enjoy video games in moderation?
Someone told me that you could choose two out of three. When I was playing video games, you could choose having a girlfriend, playing video games, or studying. And I think for the most part, it was relatively true. These things do take time. Games like if you take the game pretty seriously and you want to study it, then you obviously will dedicate more time to it. And I definitely took gaming and obviously studying very seriously. I love learning science and etc. So to me, especially when I started university undergrad, I kind of stepped off StarCraft. I actually fully stopped playing. And then World of Warcraft was a bit more casual. You could just connect online, and I mean, it was fun. But as I said, that was not as much time investment as it was for StarCraft.
Okay, so let's get into Alpha Star. What are you're behind the team. So DeepMind's been working on StarCraft and released a bunch of cool open source agents and so on in the past few years. But Alpha Star really is the moment where the first time you beat a world class player. So what are the parameters of the challenge in the way that Alpha Star took it on, and how did you and David and the rest of the DeepMind team get into it? Consider that you can even beat the best in the world or top players.
I think it all started back in 2015, actually online. I think it was 2014 when DeepMind was acquired by Google. And I, at the time, was at Google Brain, which is it was in California, it's still in California. We had this summit where we got together, the two groups, so Google Brain and Google DeepMind got together, and we gave a series of talks. And given that they were doing deep reinforcement learning for games, I decided to bring up part of my past, which I had developed at Berkeley, like this thing which we call Berkeley Overmind, which is really just a StarCraft 1 boss, right? So I talked about that. And I remember Demis just came to me and said, well, maybe not now, it's perhaps a bit too early, but you should just come to DeepMind and do this again with deep reinforcement learning, right? And at the time, it sounded very science fiction for several reasons. But then in 2016, when I actually moved to London and joined DeepMind, transferring from Brain, it became apparent that because of the AlphaGo moment and kind of Blizzard reaching out to us to say, wait, like, do you want the next challenge? And also me being full time at DeepMind, to sort of kind of all these came together. And then I went to Irvine in California, to the Blizzard headquarters, to just chat with them and try to explain how would it all work before you do anything. And the approach has always been about the learning, right? So in Berkeley, we did a lot of rule-based, conditioning, and if you have more than 3 units, then go attack, and if the other has more units than me, I retreat, and so on and so forth. And of course, the point of deep reinforcement learning, deep learning, machine learning in general is that all these should be learned behavior. So that kind of was the DNA of the project since its inception in 2016, where we just didn't even have an environment to work with. And so that's how it all started.
So if you go back to that conversation with Dennis, or even in your own head, how far away? Because we're talking about Atari games, we're talking about Go, which is kind of, if you're honest about it, really far away from StarCraft. Well, now that you've beaten it, maybe you could say it's close, but it's much. It seems like StarCraft is way harder than Go, philosophically, mathematically speaking. So how far away did you think you were? Do you think in 2019, 18, you could be doing so as well as you have?
Yeah, when I kind of thought about, okay, I'm gonna dedicate a lot of my time and focus on this, and obviously I do a lot of different research in deep learning, so spending time on it, I really had to kind of think there's gonna be something good happening out of this. So really, I thought, well, this sounds impossible, and it probably is impossible to do the full thing, like the full game, where you play 1 versus 1, and it's only a neural network playing and so on. So it really felt like I just didn't even think it was possible. But on the other hand, I could see some stepping stones like towards that goal. Clearly, you could define sub-problems in StarCraft and sort of dissect it a bit and say, okay, here's a part of the game, here's another part. And also, obviously, the fact that, so this was really also critical to me, the fact that we could access human replays, right? So Blizzard was very kind, and in fact, they open source this for the whole community, where you can just go, and it's not every single StarCraft game ever played, but it's a lot of them. You can just go and download, and every day you can just query a data set and say, well, give me all the games that were played today. And given my kind of experience with language and sequences and supervised learning, I thought, well, that's definitely going to be very helpful and something quite unique now, because ever before we had such a large data set of replays of people playing the game at this scale of such a complex video game, right? So that to me was a precious resource. And as soon as I knew that Blizzard was able to kind of give this to the community, I started to feel positive about something non-trivial happening. But I also thought the full thing, like really no rules, no single line of code that tries to say, well, I mean, if you see this unit, build the detector. All these, not having any of these specializations seemed really, 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 really good to me.
I do also like that Blizzard was teasing or even trolling you, sort of almost, pulling you into this really difficult challenge. Did they have any aware? What's the interest from the perspective of Blizzard, except just curiosity?
Yeah, I think Blizzard has really understood and really bring forward this competitiveness of esports in games. StarCraft really kind of sparked a lot of like something that almost was never seen, especially as I was saying back in Korea. So they just probably thought, well, this is such a pure 1 versus 1 setup that it would be great to see if something that can play Atari or Go and then later on chess could even tackle this kind of complex real-time strategy game, right? So for them, they wanted to see first, obviously, whether it was possible, if the game they created was in a way solvable to some extent. And I think on the other hand, they also are a pretty modern company that innovates a lot. So just starting to understand AI for them to how to bring AI into games. It's not AI for games, but games for AI. Like both ways I think can work. And we obviously at DeepMind use games for AI, right, to drive AI progress, but Blizzard might actually be able to do, and many other companies to start to understand and do the opposite. So I think that is also something they can get out of this, and they definitely we have brainstormed a lot about this, right?
But one of the interesting things to me about StarCraft and Diablo and these games that Blizzard's created is the task of balancing classes, for example. So making the game fair from the starting point, and then let skill determine the outcome. Is there I mean, can you first comment? There's three races: Zerg, Protoss, and Terran. I don't know if I ever said that out loud. Is that how you pronounce it? Terran?
Yeah.
Yeah, I don't think I've ever in person interacted with anybody about StarCraft. That's funny. So they seem to be pretty balanced. I wonder if the AI, the work that you're doing with Alpha Star would help balance them even further. Is that something you think about? Is that something that Blizzard is thinking about?
Right. So balancing when you add a new unit or a new spell type is obviously possible, given that you can always train or retrain at scale some agent that might start using that in unintended ways. But I think actually, if you understand how StarCraft has kind of co-evolved with players, in a way, I think it's actually very cool the ways that many of the things and strategies that people came up with, right? So I think we've seen it over and over in StarCraft that Blizzard comes up with maybe a new unit, and then some players get creative and do something kind of unintentional or something that Blizzard designers just simply didn't test or think about. And then after that becomes kind of mainstream in the community, Blizzard patches the game, and then they kind of maybe weaken that strategy or make it actually more interesting but a bit more balanced. So this kind of continual talk between players and Blizzard is kind of what has defined them actually in actually most games, like in StarCraft, but also in World of Warcraft, they would do that. There's several classes, and it would be not good that everyone plays absolutely the same race and so on, right? So I think they do care about balancing, of course, and they do a fair amount of testing. But it's also beautiful to also see how players get creative, anyways. And I mean, whether AI can be more creative at this point, I don't think so, right? I mean, it's just sometimes something so amazing happens. Like I remember back in the days, like have these drop ships that could drop rivers, and that was actually not thought about, that you could drop this unit that has this what's called splash damage that would basically eliminate all the enemy's workers at once. No one thought that you could actually put them in really early game, do that kind of damage, and then things change in the game. But I don't know. I think it's quite an amazing exploration process from both sides, players and Blizzard alike.
Well, it's almost like a reinforcement learning exploration, but hey, the scale of humans that play Blizzard games is almost on the scale of a large-scale DeepMind RL experiment. I mean, if you look at the numbers, you're talking about, I don't know how many games, but hundreds of thousands of games probably a month.
Yeah.
I mean, so that it's almost the same as running RL agents. What aspect of the problem of StarCraft do you think is the hardest? Is it like you said, the imperfect information? Is it the fact they have to do long-term planning? Is it the real-time aspects? We have to do stuff really quickly. Is it the fact that large action space, so you can do so many possible things? Or is it, in the game theoretic sense, there's no Nash equilibrium, or at least you don't know what the optimal strategy is because there's way too many options.
Right.
Is there something that stands out as just like the hardest, the most annoying thing?
So when we sort of looked at the problem and start to define the parameters of it, like what are the observations, what are the actions, it became very apparent that the very first barrier that one would hit in StarCraft would be because of the action space being so large and us not being able to search like you could in chess or Go, even though the search space is fast. The main problem that we identified was that of exploration, right? So without any sort of human knowledge or human prior, if you think about StarCraft and you know how deep reinforcement learning's algorithms work, which is essentially by issuing random actions and hoping that they will get some hits sometimes, so they should learn. So if you think of the action space in StarCraft, almost anything you can do in the early game is bad. Because any action involves taking workers, which are mining minerals for free. That's something that the game does automatically, sends them to mine. And you would immediately just take them out of mining and send them around. So just thinking how is it going to be possible to get to understand these concepts, but even more like expanding, right? There's these buildings you can place in other locations in the map to gather more resources, but the location of the building is important, and you have to select a worker, send it walking to that location, build the building, wait for the building to be built, and then put extra workers there so they start mining. That feels like impossible if you just randomly click to produce that state, desirable state that then you could hope to learn from, because eventually that may yield to an extra win, right? So for me, the exploration problem, and due to the action space and the fact that there's not really turns, there's so many turns because the game essentially ticks at 22 times per second. I mean, that's how they discretize sort of time. Obviously, you always have to discretize time, but there's no such thing as real time. But it's really a lot of time steps of things that could go wrong. And that definitely felt a priori like the hardest. You mentioned many good ones, I think partial observability, the fact that there is no perfect strategy because of the partial observability. Those are very interesting problems. We start seeing more and more now in terms of as we solved the previous ones. But the core problem to me was exploration, and solving it has been basically kind of the focus on how we saw the first breakthroughs.
So exploration in a multi-hierarchical way. So like 22 times a second, exploration has a very different meaning than it does in terms of should I gather resources early or should I wait or so on.
Right.
So how do you solve the long-term? Let's talk about the internals of alpha stuff.
Mm-hmm.
So first of all, how do you represent the state of the game as an input?
Right.
How do you then do the long-term sequence modeling? How do you build a policy?
Right.
So what's the architecture like?
So AlphaStar has obviously several components, but everything passes through what we call the policy, which is a neural network. And that's kind of the beauty of it. I could just now give you a neural network and some weights, and if you fed the right observations and you understood the actions the same way we do, you would have basically the agent make the game. There's absolutely nothing else needed other than those weights that work. Now, the first step is observing the game, and we've experimented with a few alternatives. The one that we currently use mixes both spatial sort of images that you would process from the game, that is the zoomed out version of the map, and also a zoomed in version of the camera or the screen as we call it. But also we give to the agent the list of units that it sees, more of as a set of objects that it can operate on. That is not necessarily required to use it, and we have versions of the game that play well without this set vision that is a bit not like how humans perceive the game, but it certainly helps a lot because it's a very natural way to encode the game is by just looking at all the units that there are. They have properties like position,
What'd you
type
say?
of unit, my unit or the enemy, and that's sort of is kind of the summary of the state of the game, that list of units or set of units that you see all the time.
But that's pretty close to what humans see the game. Why do you say it's not? It's not. You're saying the exactness of it is not similar to humans.
The exactness of it is perhaps not the problem. I guess maybe the problem, if you look at it from how actually humans play the game, is that they play with a mouse and a keyboard and a screen, and they don't see sort of a structured object with all the units. What they see is what they see on the screen, right there. So
You remember that there's there's a plot that you saw with camera based where you do exactly that, right? You
Right.
go around, and that seems to converge to similar performance.
yeah, I think that's what we're kind of experimenting with what's necessary or not, but using the set. So actually, if you look at research in computer vision, where it makes a lot of sense to treat images as two-dimensional arrays, There's actually a very nice paper from Facebook. I think I forgot who the authors are, but I think it's part of Deming's group. And what they do is they take an image, which is a two-dimensional signal, and they actually take pixel by pixel and scramble the image as if it was just a list of pixels. Crucially, they code the position of the pixels with the XY coordinates. And this is just kind of a new architecture, which we incidentally also use in StarCraft called the transformer, which is a very popular paper from last year, which yielded very nice results in machine translation. And if you actually believe in this kind of, oh, it's actually a set of pixels, as long as you encode XY, it's okay, then you could argue that the list of units that we see is precisely that, because we have each unit as a kind of pixel, if you will, and then their XY coordinates. So in that perspective, we, without knowing it, use the same architecture that was shown to work very well on Pascal and ImageNet and so on.
So the interesting thing here is putting it in that way, it starts to move it towards the way you should work with language. So, and especially with your expertise and work in language, it seems like there's echoes of a lot of the way you would work with natural language in the way you approach AlphaStar.
Right.
So what's does that help with the long-term sequence modeling there somehow?
Exactly. So now that we understand what an observation for a given time step is, we need to move on to say, well, there's going to be a sequence of such observations, and an agent will need to, given all that it's not only the current time step, but all that it's why, because there is partial observability, we must remember whether we saw a worker going somewhere, for instance, right? Because then there might be an expansion at the top right of the map. So given that, you must then think about this. There is the problem of, given all the observations, you have to predict the next action. And not only given all the observations, but given all the observations and given all the actions you've taken, predict the next action. And that sounds exactly like machine translation, and that's exactly how kind of I saw the problem, especially when you are given supervised data or replays from humans, because the problem is exactly the same. You're translating essentially a prefix of observations and action onto what's going to happen next, which is exactly how you would train a model to translate or to generate languages, right? You have a certain prefix, you must remember everything that comes in the past, because otherwise you might start having non-coherent text. And the same architectures we're using LSTMs and transformers to operate on across time, to kind of integrate all that's happened in the past. Those architectures that work so well in translation or language modeling are exactly the same than what the agent is using to issue action. And the way we train it, moreover, for imitation, which is step one of AlphaStar, is take all the human experience and try to imitate it, much like you try to imitate translators that translated many pairs of sentences from French to English, say. That sort of principle applies exactly the same. It's almost the same code, except that instead of words, you have a slightly more complicated objects, which are the observations, and the actions are also a bit more complicated than a word.
Is there a self-play component then too? So once you run out of imitation?
Right, so indeed, you can bootstrap from human replays, but then the agents you get are actually not as good as the humans you imitate, right? So how do we imitate? Well, we take humans from 3000 mmR and higher. 3000 mmR is just a metric of human skill, and 3000 mmR might be like 50% percentile, right? So it's just kind of average.
What's that? So maybe pause. MMR's ranking scale, the matchmaking rating for players. So it's 3,000. I remember there's like a master and a grandmaster. What's 3,000?
So 3,000 is pretty bad. I think it's kind of gold level.
Just sounds really good about chess, I think.
Oh yeah. The ratings, the best in the world are at 7,000 and 7,000. So 3,000, it's a bit like ELO indeed, right? So 3,500 just allows us to not filter a lot of the data. So we like to have a lot of data in deep learning, as you probably know. So we take these kind of 3,500 and above, but then we do a very interesting trick, which is we tell the neural network what level they are imitating. So we say, this replay you're going to try to imitate to predict the next action for all the actions that you're going to see is a 4,000 mmR replay. This one is a 6,000 MMR replay. And what's cool about this is then we take this policy that is being trained from human, and then we can ask it to play like a 3,000 MMR player by setting a bit, saying, well, okay, play like a 3,000 MMR player or play like a 6,000 MMR player. And you actually see how the policy behaves differently. It gets worse economy if you play like a gold level player. It does less actions per minute, which is the number of clicks or number of actions that you will issue in a whole minute. And it's very interesting to see that it kind of imitates the skill level quite well. But if we ask it to play like a 6,000 MMR player, we tested, of course, these policies to see how well they do. They actually beat all the built-in AIs that Blizzard put in the game, but they're nowhere near 6,000 MMR players. Right? They might be maybe around gold level, platinum perhaps. So there's still a lot of work to be done for the policy to truly understand what it needs to win. So far, we only ask them, okay, here is the screen, and that's what's happened on the game until this point. What would the next action be if we ask a pro to now say, oh, you're going to click here or here or there? And the point is, experiencing wins and losses is very important to then start to refine. Otherwise, the policy can get loose, can just go off policy as we call it.
That's so interesting that you can at least hope eventually to be able to control a policy approximately to be at some MMR level. That's so interesting, especially given that you have ground truth for a lot of these cases.
Right.
Can I ask you a personal question?
Sure.
What's your MMR?
Well, I haven't played StarCraft 2, so I am unranked, which is the kind of lowest league.
Okay.
So I used to play StarCraft, the first one,
but you haven't serious played?
No, not StarCraft 2. So the best player we have at DeepMind is about 5,000 MMR, which is high masters. It's not at grandmaster level. Grandmaster level would be the top 200 players in a certain region, like Europe or America or Asia. But for me, it would be hard to say. I am very bad at the game. I actually played Alpha Star a bit too late, and it beat me. I remember the whole team was, oh, Oreo, you should play. And I was, oh, it looks like it's not so good yet. And then I remember I kind of got busy and waited an extra week, and I played, and it really beat me very bad.
How did that feel? Isn't that an amazing feeling?
That's amazing, yeah. I mean, obviously, I tried my best, and I tried to also impress because I actually played the first game, so I'm still pretty good at micromanagement. The problem is I just don't understand StarCraft 2. I understand StarCraft. And when I played StarCraft, I probably was consistently, like, for a couple of years, top 32 in Europe. So I was decent, but at the time we didn't have this kind of MMR system as well established, so it would be hard to know what it was back then.
So what's the difference in interface between Alpha Star and StarCraft and a human player in StarCraft? Is there any significant differences between the way they both see the game?
I would say the way they see the game, there's a few things that are just very hard to simulate. The main one, perhaps, which is obvious in hindsight, is what's called cloaked units, which are invisible units. So in StarCraft, you can make some units that you need to have a particular kind of unit to detect it. So these units are invisible. If you cannot detect them, you cannot target them. So they would just, destroy your buildings or kill your workers. But despite the fact you cannot target the unit, there's a shimmer that as a human you observe. I mean, you need to train a little to pay attention, but you would see this kind of space-time like distortion, and you would know, okay, there are,
there's like a wave thing.
Yeah, it's called shimmer.
Space-time distortion. I like it.
That's really like the Blizzard term is shimmer, and so this shimmer, professional players actually can see it immediately. They understand it very well. But it's still something that requires certain amount of attention, and it's kind of a bit annoying to do. Whereas for Alpha Star, in terms of vision, it's very hard for us to simulate sort of, are you looking at this pixel in the screen and so on. So the only thing we can do is there is a unit that's invisible over there, so Alpha Star would know that immediately. Obviously, still obeys the rules. You cannot attack the unit. You must have a detector and so on. But it's kind of one of the main things that it just doesn't feel there's a very proper way. I mean, you could imagine, you you don't have maybe you don't know exactly where it is, or sometimes you see it, sometimes you don't. But it's just really, really complicated to get it so that everyone would agree, oh, that's the best way to simulate it. So,
it seems like a perception problem.
it is a perception. So the only problem is people, or you ask, oh, what's the difference between how humans perceive the game? I would say they wouldn't be able to tell a shimmer immediately as it appears on the screen, whereas Alpha Star in principle sees it very sharply, right? It sees that the bit turned from 0 to 1, meaning there's now a unit there, although you don't know the unit, or you don't know it, you know that you cannot attack it, and so on. So that from a vision standpoint, that probably is the one that is kind of the most obvious one. Then there are things humans cannot do perfectly, even professionals, which is they might miss a detail, or they might have not seen a unit. And obviously, as a computer, if there's a corner of the screen that turns green because a unit enters the field of view, that can go into the memory of the agent, the LSTM, and persist there for a while, and for however long is relevant, right?
And in terms of action, it seems like rate of action for Alpha Star is comparative, if not slower than professional players, but it's more precise as well.
Right. So that's really probably the one that is causing us more issues for a couple of reasons, right? The first one is StarCraft has been an AI environment for quite a few years. In fact, I was participating in the very first competition back in 2010, and there's really not been a kind of a very clear set of rules how the action per minute, the rate of action that you can issue is. And as a result, these agents or bots that people build in a kind of almost very cool way, they do like 20,000, 40,000 actions per minute. Now, to put this in perspective, a very good professional human might do 300 to 800 actions per minute. They might not be as precise. That's why the range is a bit tricky to identify exactly. I mean, 300 actions per minute precisely is probably realistic. 800 is probably not, but you see humans doing a lot of actions because they warm up and they kind of select things and spam and so on, just so that when they meet, they have the accuracy. So we came into this by not having kind of a standard way to say, well, how do we measure whether an agent is at human level or not? On the other hand, we have a huge advantage, which is because we do imitation learning, agents turn out to act like humans in terms of rate of actions, even precisions and imprecisions of actions. In the supervised policy, you could see all this. You could see how agents like to spam click to move here. If you played especially Diablo, you would know what I mean. I mean, you just stop like spam, oh, move here, move here, move here. You're doing literally like maybe 5 actions in 2 seconds, but these actions are not very meaningful. One would have sufficed. So on the one hand, we start from this imitation policy that is at the ballpark of the actions per minute of humans, because it's actually statistically trying to imitate humans. So we see this very nicely in the curves that we showed in the blog post. Like there's these actions per minute, and the distribution looks very human-like. But then, of course, as self-play kicks in, and that's the part we haven't talked too much yet, but of course the agent must play in itself to improve, then there's almost no guarantees that these actions will not become more precise, or even the rate of action is going to increase over time. So what we did, and this is probably kind of the first attempt that we thought was reasonable, is we looked at the distribution of actions for humans for certain windows of time. And just to give a perspective, because I guess I mentioned that some of these agents that are programmatic, let's call them, they do 40,000 actions per minute. Professionals, as I said, 300 to 800. So what we look at the distribution of our professional gamers, and we took reasonably high actions per minute, but we kind of identify certain cutoffs, after which, even if the agent wanted to act, these actions will be done. But the problem is this cutoff is probably set a bit too high, and what ends up happening, even though the game, and when we ask the professionals and the gamers, by and large, they feel like it's playing human-like, there are some agents that developed maybe slightly too high PMs, which is actions per minute, combined with the precision, which made people sort of start discussing a very interesting issue, which is should we have limited this? Should we just let it loose and see what cool things it can come up with, right? So this is in itself an extremely interesting question, but the same way that modeling the tumor would be so difficult, modeling absolutely all the details about muscles and precision and tiredness of humans would be quite difficult, right? So we're really here in kind of innovating in the sense of, okay, what would be maybe the next iteration of putting more rules that makes the agents more human-like in terms of restrictions.
So yeah, putting constraints that
More constraints, yeah.
that's really interesting. That's really innovative. So one of the constraints you put on yourself, or at least focused in, is on the Protoss race, as far as I understand. Can you tell me about the different races and how they, so Protoss, Terran, and the Zerg, how do they compare? How do they interact? Why did you choose Protoss?
Right.
Yeah. This, in the dynamics of the game, seen from a strategic perspective.
So Protoss, so in StarCraft there are three races. Indeed, in the demonstration we saw only the Protoss race. So maybe let's start with that one. Protoss is kind of the most technologically advanced race. It has units that are expensive but powerful, right? So in general, you want to kind of conserve your units as you go attack. So you want to, and then you want to utilize these tactical advantages of very fancy spells and so on and so forth. And at the same time, they're kind of, people say they're a bit easier to play, perhaps, right? But that I actually don't know. I mean, I just got to now a lot to the players that we work with, DLO and Anna, and they said, oh yeah, Protoss is actually, people think it's actually one of the easiest races. So perhaps the easier, that doesn't mean that it's, obviously professional players excel at the three races, and there's never like a race that dominates for a very long time anyway.
So if you look at the top, I don't know, 100 in the world, is there one race that dominates that list?
It would be hard to know because it depends on the regions. I think it's pretty equal in terms of distribution, and Blizzard wants it to be equal, right? They wouldn't want one race like Protoss to not be representative in the top place. So definitely, like, they try to be like balanced, right? So then maybe the opposite race of Protoss is Zerg. Zerg is a race where you just kind of expand and take over as many resources as you can, and they have a very high capacity to regenerate their units. So if you have an army, it's not that valuable in terms of losing the whole army is not a big deal as Zerg, because you can then rebuild it, and given that you generally accumulate a huge bank of resources, Zergs typically play by applying a lot of pressure, maybe losing their whole army, but then rebuilding it quickly. So, although of course every race, I mean, there's never, they're pretty diverse. I mean, there are some units in Zerg that are technologically advanced and they do some very interesting spells, and there's some units in Protoss that are less valuable, and you could lose a lot of them and rebuild them, and it wouldn't be a big deal.
All right, so maybe I'm missing out, maybe I'm going to say some dumb stuff, but it's just summary of strategy. So first, there's collection of a lot of resources.
Right.
So that's one option. The other one is expanding, so building other bases. But then the other is obviously attack, building units and attacking those units. And then I don't know what else there is. Maybe there's the different timing of attacks, like to attack early, attack ready. What are the different strategies that emerge that you've learned about? I've read that a bunch of people are super happy that you guys have apparently, the Alpha Star apparently has discovered that's really good to, saturate.
Oh yeah, the mineral lines.
Yeah, the mineral line.
Yeah.
And that's for greedy amateur players like myself. That's always been a good strategy. You just build up a lot of money, and it just feels good to just accumulate. So thank you for covering that. Validating all this. But is there other strategies that you discovered interesting to this game?
Yeah. So if you look at the kind of, I'm not being a StarCraft 2 player, but of course StarCraft and StarCraft 2 and real-time strategy games in general are very similar. I would classify perhaps the openings of the game. They're very important, and generally I would say there's two kinds of openings. One that's a standard opening, that's generally how players find sort of a balance between risk and economy and building some units early on so that they could defend, but they're not too exposed basically, but also expanding quite quickly. So this would be kind of a standard opening. And within a standard opening, then what you do choose generally is what technology are you aiming towards. So there's a bit of rock, paper, scissors of you could go for spaceships, or you could go for invisible units, or you could go for massive units that attack against certain kinds of units, but they're weak against others. So standard openings themselves have some choices like rock, paper, scissors style. Of course, if you scout and you're good at guessing what the opponent is doing, then you can play as an advantage, because if you know you're going to play rock, I mean, I'm going to play paper, obviously. So you can imagine that normal standard games in StarCraft looks like a continuous rock, paper, scissors game, where you guess what the distribution of rock, paper, and scissors is from the enemy, and reacting accordingly to try to beat it, or put the paper out before he kind of changes his mind from rock to scissors, and then he would be in a weak position.
So sorry to pause on that.
Yeah.
I didn't realize this element because I know it's true in poker. I know I looked at your goddess. You're also estimating, trying to guess the distribution, trying to better estimate the distribution of what the opponent's likely to be doing.
Yeah, I mean, as a player, you definitely want to have a belief state over what's up on the other side of the map. And when your belief state becomes inaccurate, when you start having that serious doubts whether he's going to play something that you must know, that's when you scout. You want to then gather information, right?
Is improving the accuracy of the belief, or improving the belief state, part of the loss that you're trying to optimize, or is it just a side effect?
It's implicit, but you could explicitly model it, and it would be quite good at probably predicting what's on the other side of the map. But so far, it's all implicit. There's no additional reward if you're predicting that. So there's these standard openings, and then there's what people call cheats, which is very interesting. And Alpha Star sometimes really likes this kind of cheats. These cheats, what they are, is kind of an all-in strategy. You're gonna do something sneaky. You're gonna hide enemies, hide your own buildings close to the enemy base, or you're gonna go for hiding your technological buildings so that you do invisible units and the enemy just cannot react to detect it and thus lose the game. And there's quite a few of these pieces and variants of them. And there is where actually the belief state becomes even more important. Because if I scout your base and I see no buildings at all, any human player knows something's up. They might know, well, you're hiding something close to my base. Should I build suddenly a lot of units to defend? Should I actually block my ramp with workers so that you cannot come and destroy my base? So there's all this is happening, and defending against this is extremely important. And in the Alpha Star League, many agents actually develop some cheesy strategies. And in the games we saw against DLO and Mana, 2 out of the 10 agents were actually doing these kind of strategies, which are cheesy strategies. And then there's a variant of cheesy strategy, which is called all-in. So an all-in strategy is not perhaps as drastic as, I'm going to build cannons on your base and then bring all my workers and try to just disrupt your base and game over, or GG, as we say in StarCraft. There's these kind of very cool things that you can align precisely at certain time mounts. So, for instance, you can generate exactly 10 unit composition that is perfect. 5 of this type, 5 of this other type, and align the upgrade so that at 4 minutes and a half, let's say, you have these 10 units and the upgrade just finished. And at that point, that army is really scary. And unless the enemy really knows what's going on, if you push, you might then have an advantage because maybe the enemy is doing something more standard, it expanded too much, it developed too much economy, and it trade off badly against having defenses, and the enemy will lose. But it's called all-in because if you don't win, then you're going to lose.
Right.
So you see players that do these kind of strategies. If they don't succeed, game is not over. I mean, they still have a base and they're still gathering minerals, but they will just GG out of the game because they know, well, game is over. I gambled and I failed. So if we start entering the game theoretic aspects of the game, it's really rich, and it's really, that's why it also makes it quite entertaining to watch. Even if I don't play, I still enjoy watching the game. But the agents are trying to do this mostly explicitly. But one element that we improved in self-play is creating the Alpha Star League. And the Alpha Star League is not pure self-play. It's trying to create different personalities of agents so that some of them will become cheesy agents. Some of them might become very economical, very greedy, like getting all the resources, but then being maybe early on they're going to be weak, but later on they're going to be very strong. And by creating personality of agents, which sometimes it just happens naturally, that you can see kind of an evolution of agents that, given the previous generation, they train against all of them, and then they generate kind of the perfect counter to that distribution. But these agents, you must have them in the population, because if you don't have them, you're not covered against these things, right? It's kind of you wanna create all sorts of the opponents that you will find in the wild, so you can be exposed to these Jesus, early aggression, later aggression, more expansions, dropping units in your base from the side, all these things. And pure self-play is getting a bit stuck at finding some subset of these, but not all of these. So the Alpha Star League is a way to kind of do an ensemble of agents that they're all playing in a league, much like people play on Batman, right? You play against someone who has a new cool strategy, and you immediately, oh my god, I want to try it, I want to play again. And this to me was another critical part of the problem, which was, can we create a battle net for agents?
Yeah,
And that's kind of what the Alpha League
that's
really is.
fascinating. And where they stick to their different strategies. Yeah, wow, that's really really interesting. So, but that said, you were fortunate enough or just skilled enough to win 5-0. And so, how hard is it to win? I mean, that's not the goal. I guess I don't know what the goal is. The goal should be to win majority, not 5-0. But how hard is it in general to win all matchups and a one v1?
So that's a very interesting question, because once you see Alpha Star and superficially you think, well, okay, if you sum all the games like 10-1, right? It lost the game that it played with the camera interface. You might think, well, that's done, right? It's superhuman at the game. And that's not really the claim we really can make, actually. The claim is we beat a professional gamer for the first time. StarCraft has really been a thing that has been going on for a few years, but a moment like this had not occurred before yet. But are these agents impossible to beat? Absolutely not, right? So that's a bit what's kind of the difference is the agents play at grandmaster level. They definitely understand the game enough to play extremely well. But are they unbeatable? Do they play perfect? No, actually, StarCraft, because of these sneaky strategies, it's always possible that you might take a huge risk sometimes, but you might get wins right out of this. So I think that as a domain, it still has a lot of opportunities. Not only because, of course, we want to learn with less experience. We would like to. I mean, if I learn to play Protoss, I can play Terran and learn it much quicker than Alpha Star can, right? So there are obvious interesting research challenges as well. But even as the raw performance goes, really the claim here can be we are at pro level or at high grandmaster level. But obviously, the players also did not know what to expect. Right, this kind of their prior distribution was a bit off because they played this kind of new, like alien brain, as they like to say it, right? And that's what makes it exciting for them. But also, I think if you look at the games closely, you see there were weaknesses in some points. Maybe Alpha Star did not scout, or if it had invisible units going against at certain points, it wouldn't have known. It would have been bad. So there's still quite a lot of work to do. But it's really a very exciting moment for us to be seeing, wow, a single neural net on a GPU is actually playing against these guys who are amazing. I mean, you have to see them play in live. They're really, really amazing players.
Yeah, I'm sure there must be a guy in Poland somewhere right now training his butt off to make sure that this never happens again with Alpha Star. So that's really exciting in terms of Alpha Star having some holes to exploit, which is great. And we build on top of each other. And it feels like StarCraft, unlike Go, even if you win, it's still not it's still not. There's so many different dimensions in which you can explore. So that's really, really interesting. Do you think there's a ceiling to Alpha Star? You've said that it hasn't reached. This is a big. Like what? Let me actually just pause for a second. How did it feel to come here to this point to beat a top professional player like that night? I mean, Olympic athletes have their gold medal, right? This is your gold medal. Sure, you're cited a lot, you've published a lot of prestigious papers, whatever, but this is like a win. How did it feel?
I mean, for me, it was unbelievable because first, the win itself, I mean, it was so exciting. I mean, so looking back to those last days of 2018, really, where that's when the games were played. I'm sure I look back at that moment and say, "Oh my God, I want to be in a project like that." It's like I already feel the nostalgia of like, yeah, that was huge in terms of the energy and the team effort that went into it. And so, in that sense, as soon as it happened, I already knew it was kind of I was losing it a little bit. So it's almost like sad that it happened, and oh my God, like. But on the other hand, it also verifies the approach. But to me, also, there's so many challenges and interesting aspects of intelligence that even though we can train a neural network to play at the level of the best humans, there's still so many challenges. So for me, it's also like, well, this is really an amazing achievement. But I already was also thinking about next steps. I mean, as I said, these agents play Protoss versus Protoss, but they should be able to play a different race much quicker, right? So that would be an amazing achievement. Some people call these meta reinforcement learning, meta learning, and so on, right? So there's so many possibilities after that moment, but the moment itself, it really felt great. I had this bet, so I'm kind of a pessimist in general, so I kind of sent an email to the team. I said, okay, let's against TLO, right? Like, what's going to be the result? And I really thought we would lose like 5-0, right? We had some calibration made against the 5,000 MMR player. TLO was much stronger than that player, even if he played Protoss, which is his off race. But yeah, I was not imagining we would win. So for me, that was just kind of a test run or something. And then it really kind of, he was really surprised. And unbelievably, went to this bar to celebrate. And Dave tells me, well, why don't we invite someone who is 1,000 MMR stronger in Protoss, like an actual Protoss player, like that it turned up being Mana, right? And we had some drinks, and I said, sure, why not? But then I thought, well, that's really gonna be impossible to beat. I mean, because it's just so much ahead. 1,000 MMR is really like 99% probability that Mana would beat TLO as Protoss versus Protoss, right? So we did that, and to me, the second game was much more important, even though a lot of uncertainty kind of disappeared after we kind of beat TLO. I mean, he is a professional player, so that was kind of, but that's really a very nice achievement. But Mana really was at the top, and you could see he played much better. But our agents got much better too. So it's like, and then after the first game, if we take a single game, at least we can say we beat a game. I mean, even if we don't beat the series, for me that was a huge relief. And I mean, I remember hugging dummies, and I mean, it was really like this moment for me will resonate forever as a researcher, and I mean, as a person. Yeah, it's a really like great accomplishment, and it was great also to be there with the team in the room. I don't know if you saw, like, so it was really like,
I mean, from my perspective, the other interesting thing is just like watching Kasparov, watching Mana. Was also interesting because he is kind of a loss of words. I mean, whenever you lose, I've done a lot of sports. You sometimes say excuses. You look for reasons,
right?
And he couldn't really come up with reasons.
Yeah.
I mean, so with the off race for Protoss, you could say it felt awkward. It was, but here it was just beaten. And it was beautiful to look at a human being being superseded by an AI system. I mean. It's a beautiful moment for researchers. So
yeah, for sure it was. I mean, probably the highlight of my career so far, because of its uniqueness and coolness. And I don't know. I mean, it's obviously, as you said, you can look at paper citations and so on, but this really is like a testament of the whole machine learning approach, and using games to advance technology. I mean, it really was, everything came together at that moment. That's really the summary.
Also, on the other side, it's a popularization of AI too, because just like traveling to the moon, I mean, this
Here
is
she
where
is.
a very large community of people that don't really know AI, they get to really interact with it.
Which is very important.
It's extremely important.
We must, writing papers helps our peers, researchers, to understand what we're doing. But I think AI is becoming mature enough that we must sort of try to explain what it is, and perhaps through games is an obvious way, because these games always had built-in AI. So maybe everyone experience an AI playing video game, even if they don't know, because there's always some scripted element, and some people might even call that AI already, right?
So, what are your applications of the approaches underlying AlphaStar that you see happening? There's a lot of echoes of this transformer of language modeling and so on. Have you already started thinking where the breakthroughs in AlphaStar get expanded to other applications?
Right. So I thought about a few things for like kind of next months, next years. The main thing I'm thinking about actually is what's next, as a kind of a grand challenge, because for me, like, we've seen Atari, and then there's like the sort of three-dimensional worlds that we've seen also like pretty good performance from these capture the flag agents that also some people at DeepMind and elsewhere are working on. We've also seen some amazing results on, like, for instance, Dota 2, which is also a very complicated game. So for me, like, the main thing I'm thinking about is what's next in terms of challenge. So as a researcher, I see sort of two tensions between research and then applications or areas or domains where you apply it. So on the one hand, we've done, thanks to the application of StarCraft, is very hard. We developed some techniques, some new research that now we could look at elsewhere. Like, are there other applications where we can apply this? And the obvious ones, absolutely, you can think of feeding back to sort of the community we took from, which was mostly sequence modeling or natural language processing. So we've developed and extended things from the transformer, and we use pointer networks. We combine LSTM and transformers in interesting ways. So that's perhaps the kind of lowest hanging fruit of feeding back to now a different field of machine learning that's not playing video games.
Let me go also jump to Mr. Alan Turing.
Yeah.
So the Turing test, it says a natural language test, a conversational test. What's your thought of it as a test for intelligence? Do you think it is a grand challenge that's worthy of undertaking? Maybe if it is, would you reformulate it or phrase it somehow differently?
Right. So I really love the Turing test because I also like sequences and language understanding. And in fact, some of the early work we did in machine translation, we tried to apply to kind of a neural chatbot, which obviously never passed the Turing test because it was very limited. But it is a very fascinating idea that you could really have an AI that would be indistinguishable from humans in terms of asking or conversing with it, right? So I think the test itself seems very nice, and it's kind of well defined actually, like the passing it or not. I think there's quite a few rules that feel like pretty simple, and you could really like have. I mean, I think they have these competitions every year.
Yes, there's the Lebanon Prize, but I don't know if you've seen. I don't know if you've seen the kind of bots that emerge from the competition. They're not quite as what you would. It feels like that there's weaknesses with the way Turing formulated it. It needs to be the definition of a genuine, rich, fulfilling human conversation. It needs to be something else. Like the Alexa Prize, which I'm not as well familiar with, has tried to define that more. I think by saying you have to continue keeping a conversation for 30 minutes, something like that. So basically, forcing the agent not to just fool, but to have an engaged conversation kind of thing. Is that? I mean, is this? Have you thought about this problem richly? Like, and if you have in general, how far away are we from? You worked a lot on language understanding, language generation, but the full dialogue, the conversation, just sitting at the bar having a couple of beers for an hour, that kind of conversation. Have you thought about
Yeah, so I think you touched here on the critical point, which is feasibility, right? So there's a great sort of essay by Hamming, which describes sort of grand challenges of physics, and he argues that, well, okay, for instance, teleportation or time travel are great grand challenges of physics, but there's no attacks. We really don't know or cannot kind of make any progress. So that's why most physicists and so on, they don't work on these in their PhDs and as part of their careers. So I see the Turing test as in the full Turing test as a bit still too early. Like I think we're, especially with the current trend of deep learning language models, we've seen some amazing examples. I think GPT-2 being the most recent one, which is very impressive. But to understand, to fully solve passing or fooling a human to think that there's a human on the other side, I think we're quite far. So as a result, I don't see myself, and I probably would not recommend people doing a PhD on solving the Turing test because it just feels it's kind of too early or too hard of a problem.
Yeah, but that said, you said the exact same thing about StarCraft about a few years ago. So
Indeed.
to chemists. So I agree.
Yes.
You'll probably also be the person who passes the Turing test in 3 years.
I mean, I think So
So we have this on record. This is nice.
it's true. It's true. I mean the it's true that progress sometimes is a bit unpredictable. I really wouldn't have not. I even 6 months ago, I would not have predicted the level that we see that these agents can deliver at grandmaster level. But I have worked on language enough, and basically my concern is not that something could happen, a breakthrough could happen that would bring us to solving or passing the Turing test. Is that I just think the statistical approach to it, like this, it's not going to happen. So we need a breakthrough, which is great for the community. But given that, I think there's quite a more uncertainty. Whereas for StarCraft, I knew what the steps would be to kind of get us there. I think it was clear that using the imitation learning part and then using this bottom-net for agent were going to be key, and it turned out that this was the case, and a little more was needed, but not much more. For Turing test, I just don't know what the plan or execution plan would look like. So that's why I myself working on it as a grand challenge is hard, but there are quite a few sub challenges that are related that you could say, well, I mean, what if you create a great assistant like Google already has, like the Google Assistant? So can we make it better and can we make it fully neural? And so that I start to believe maybe we're reaching a point where we should attempt these challenges.
I like this conversation so much because it echoes very much the StarCraft conversation. It's exactly how you approach StarCraft. Let's break it down into small pieces and solve those, and you end up solving the whole game. Great. But that said, you're behind some of the biggest pieces of work in deep learning in the last several years. So you mentioned limits. What do you think of the current limits of deep learning, and how do we overcome those limits?
So if I had to actually use a single word to define the main challenge in deep learning, it's a challenge that probably has been the challenge for many years, and is that of generalization. So what that means is that all that we're doing is fitting functions to data, and when the data we see is not from the same distribution, or even if there are sometimes that it is very close to the distribution, but because of the way we train it with limited samples, we then get to this state where we just don't see generalization as much as we can generalize. And I think adversarial examples are a clear example of this, but if you study machine learning and literature, and the reason why SVMs became very popular were because they were thinking and they had some guarantees about generalization, which is unseen data or out of distribution, or even within distribution where you take an image adding a bit of noise. These models fail. So I think really I don't see a lot of progress on generalization in the strong generalization sense of the word. I think our neural networks, you can always find design examples that will make their outputs arbitrary. which is not good because we humans would never be fooled by this kind of images or manipulation of the image. And if you look at the mathematics, you kind of understand this is a bunch of matrices multiplied together. There's probably numerics and stability that you can just find corner cases. So I think that's really the underlying topic. Many times we see when even at the grand stage of like Turing test generalization. I mean, if you start, I mean, passing the Turing test, should it be in English or should it be in any language, right? I mean, as a human, if if you ask something in a different language, you actually will go and do some research and try to translate it and so on. Should the Turing test include that, right? And it's really a difficult problem and very fascinating and very mysterious.
Yeah, absolutely. But do you think it's if you were to try to solve it, can you not grow the size of data intelligently in such a way that the distribution of your training set does include the entirety of the testing set?
I think
Is that one path? The other path is totally new methodology. It's not statistical.
so. A path that has worked well, and it worked well in StarCraft and in machine translation and in language, is scaling up the data and the model, and that's kind of been maybe the only single formula that still delivers today in deep learning, right? It's that scale, data scale, and model scale really do more and more of the things that we thought, oh, there's no way it can generalize to these, or there's no way it can generalize to that. But I don't think fundamentally it will be solved with these. And for instance, I'm really liking um, some style or approach that would not only have neural networks, but it would have programs or some discrete decision making, because there is where I feel there's a bit more like I mean the best example I think for understanding this is they also worked a bit on like we can learn an algorithm with neural network, right? So you give it many examples and it's gonna sort the input numbers or something like that. But really strong generalization. You give me some numbers or you ask me to create an algorithm that sorts numbers, and instead of creating a neural net which will be fragile because it's gonna go out of range at some point, you're gonna give it numbers that are too large, too small, and whatnot. If you just create a piece of code that sorts the number, then you can prove that that will generalize to absolutely all the possible inputs. So I think that the problem comes with some exciting prospects. I mean, scale is a bit more boring, but it really works. Then maybe programs and discrete abstractions are a bit less developed, but clearly I think they're quite exciting in terms of future for the field.
Do you draw any insight, wisdom from the 80s and expert systems and symbolic systems, symbolic computing? You ever go back to the reasoning, that kind of logic? Do you think that might make a comeback with the dust off those books?
Yeah, I actually love adding more inductive biases. Um, to me, the problem really is what are you trying to solve? If what you're trying to solve is so important that try to solve it no matter what, then absolutely use rules, use domain knowledge, and then use a bit of the magic of machine learning to empower to make the system as the best system that will detect cancer or detect weather patterns, right? Or in terms of StarCraft, it also was a very big challenge. So I was definitely happy that if we had to cut a corner here and there, it could have been interesting to do. And in fact, in StarCraft, we start thinking about expert systems because it's a very, you can define. I mean, people actually build StarCraft bots by thinking about those principles, like state machines and rule based, and then you could think of combining a bit of a rule based system, but that has also neural networks incorporated to make it generalize a bit better. So absolutely, I mean, we should definitely go back to those ideas, and anything that makes the problem simpler. As long as your problem is important, that's okay. And that's research driving a very important problem. And on the other hand, if you want to really focus on the limits of reinforcement learning, you must try not to look at
Welcome.
imitation data or
How are you?
to look for some rules of
What's going on, Amir? Amir, I didn't want to talk with you anyway.
these attention that depending on what you do, I think both ways are definitely fine, and I would never not do one or the other if you're as long as what you're doing is important and needs to be solved. Right?
So there's a bunch of different ideas that you developed that I really enjoy. But one is translating from image caption, translating from image to text. Just another just beautiful idea. I think that resonates throughout your work, actually. So the underlying nature of reality being language always.
Yeah.
Somehow. Uh, so what's the connection between images and text, or rather the visual world and the world of language, in your view?
Right. So I think a piece of research that's been central to, I would say, even extending into StarCraft is this idea of sequence to sequence learning, which what we really meant by that is that you can now really input anything to a neural network as the input X, and then the neural network will learn a function F that will take X as an input and produce any output Y. And these X and Y's don't need to be like static or like a features, like a fixed vectors or anything like that. It could be really sequences and now beyond like data structures, right? So that paradigm was tested in a very interesting way when we moved from translating French to English to translating an image to its caption. But the beauty of it is that really, and that's actually how it happened. I changed a line of code in this thing that was doing machine translation. I came the next day, and I saw how it was producing captions that seemed like, oh my god, this is really working. And the principle is the same, right? So I think I don't see text, vision, speech, waveforms as something different. Um, as long as you basically learn a function that will vectorize, these into, and then after we vectorize it, we can then use transformers, LSTM, whatever the flavor of the month of the model is, and then as long as we have enough supervised data, really, this formula will work and will keep working, I believe, to some extent, modulo these generalization that I mentioned.
So, but the task there is to vectorize, so to form a representation that's meaningful.
Yeah.
Thing. And your intuition, now having worked with all this media, is that once you are able to form that representation, you can basically take anything, any sequence. Is there, going back to StarCraft, there are limits of length? So we didn't really touch on the long-term aspect. How did you overcome the whole really long-term aspect of things here? Is there some tricks? Or
So the main trick, so StarCraft, if you look at absolutely every frame, you might think it's quite a long game. So we would have to multiply 22 times 60 seconds per minute times maybe at least 10 minutes per game on average. So there are quite a few frames, but the trick really was to only observe, in fact, which might be seen as a limitation, but it is also a computational advantage. Only observe what you have, and then the neural network decides what is the gap going to be until the next action. And if you look at most StarCraft games that we have in the data set that Blizzard provided, it turns out that most games are actually only, I mean, it's still a long sequence, but it's maybe like 1,000 to 1,500 actions, which if you start looking at LSTMs, large LSTMs, transformers, it's not that difficult, especially if you have supervised learning. If you had to do reinforcement learning, the credit assignment problem, what is it that in this game that made you win? That would be really difficult. But thankfully, because of imitation learning, we didn't kind of have to deal with this directly. Although if we had to, we tried it, and what happened is you just take all your workers and attack with them. And that sort of is kind of obvious in retrospect because you start trying random actions. One of the actions will be a worker that goes to the enemy base, and because it's self-play, it's not going to know how to defend because it basically doesn't know almost anything. And eventually, what you develop is this: take all workers and attack. Because the credit assignment issue in a rally is really high. I do believe we could do better, and that's maybe a research challenge for the future. But yeah, even in StarCraft, the sequences are maybe 1,000, which I believe they're it's within the realm of what transformers can do.
Yeah, I guess the difference between StarCraft and Go is in Go and chess, stuff starts happening right away.
Right.
So there's not. Yeah, it's pretty easy through self-play. Not easy, but through self-play, it's possible to develop reasonable strategies quickly, as opposed to StarCraft.
I mean, in Go, there's only 400 actions, but one action is what people would call the God action. That would be if you had expanded the whole search tree, that's the best action if you did minimax or whatever you would do if you had the computational capacity. But in StarCraft, the 400 is minuscule. Like in 400, you don't even you couldn't even click on the pixels around a unit, right? So I think the problem there is in terms of action space size is way harder. So and that search is impossible. So there's quite a few challenges indeed that make this kind of a step up in terms of machine learning. For humans, maybe playing StarCraft seems more intuitive because it looks real. I mean, like the graphics and everything moves smoothly. Whereas I don't know. I mean, Go is a game that I really need to study. It feels quite complicated. But for machines, kind of maybe it's the reverse. Yes.
Which shows you the gap actually between deep learning and however the heck our brains work. So you developed a lot of really interesting ideas. It's interesting to just ask, what's your process of developing new ideas? Do you like brainstorming with others? Do you like thinking alone? Do you like who was it? Ian Goodfellow said he came up with GANs after a few beers. Right, things beers are essential for coming up with new ideas.
Well, we had beers to decide to do another game of StarCraft after a week. So it's really similar to that story. Actually, I explained this in a DeepMind retreat, and I said this is the same as the GAN story. I mean, we were in a bar and we decided let's play again this week, and that's what happened.
I feel like we're giving the wrong message to young undergrads.
Yeah, no.
But in general, do you like brainstorming? Do you like thinking alone, working stuff out?
So I think throughout the years also things changed, right? So initially I was very fortunate with great minds like Jeff Hinton, Jeff Dean, Ilias Utskever. I was really fortunate to join Brain at a very good time. So at that point in ideas, I was just kind of brainstorming with my colleagues and learned a lot. And keep learning is actually something you should never stop doing, right? So learning implies reading papers and also discussing ideas with others. It's very hard at some point to not communicate, that being reading a paper from someone or actually discussing, right? So definitely that communication aspect needs to be there, whether it's written or oral. Nowadays, I'm also trying to be a bit more strategic about what research to do. So I was describing a little bit this sort of tension between research for the sake of research, and then you have, on the other hand, applications that can drive the research, right? And honestly, the formula that has worked best for me is just find a hard problem and then try to see how research fits into it, how it doesn't fit into it, and then you must innovate. So I think machine translation drove sequence to sequence, then maybe like learning algorithms that had to, like combinatorial algorithms led to pointer networks. StarCraft led to really scaling up implication learning and the AlphaStar League. So that's been a formula that I personally like. But the other one is also valid, and I see it succeed a lot of the times where you just want to investigate model-based RL as kind of a research topic. And then you must then start to think, well, how are the tests? How are you going to test these ideas? You need kind of a minimal environment to try things. You need to read a lot of papers and so on. And that's also very fun to do, and something I've also done quite a few times, both at Brain, at DeepMind, and obviously as a PhD. So I think besides the ideas and discussions, I think it's important also because you start sort of guiding not only your own goals but other people's goals to the next breakthrough. So you must really kind of understand this, feasibility also, as we were discussing before, right? Whether this domain is ready to be tackled or not, and you don't want to be too early. You obviously don't want to be too late. So it's really interesting. This strategic component of research, which I think as a grad student, I just had no idea. I just read papers and discussed ideas. And I think this has been maybe the major change. And I recommend people kind of feed forward to success, how it look like, and try to backtrack, other than just kind of looking, oh, this looks cool, and then you do a bit of random work, which sometimes you stumble upon some interesting things, but in general, it's also good to plan a bit.
Yeah, I like it. Especially like your approach, taking a really hard problem, stepping right in, and then being super skeptical about being able to solve the problem. I mean, there's a balance of both, right? There's a silly optimism and a critical sort of skepticism that's good to balance. Which is why it's good to have a team of people.
Exactly.
That's the balance.
You don't do that on your own. You have both mentors that have seen, or you obviously want to chat and discuss whether it's the right time. I mean, that Demis came in 2014 and he said maybe in a bit we'll do StarCraft, and maybe he knew, and I'm just following his lead, which is great because he's brilliant, right? So these things are obviously quite important, that you want to be surrounded by people who are diverse. They have their knowledge. There's also important to. I mean, I've learned a lot from people who actually have an idea that I might not think it's good, but if I give them the space to try it, I've been proven wrong many times as well. So that's great. I think it's your colleagues are more important than yourself, I think so.
Yeah. Now, let's real quick talk about another possible problem. AGI.
Right.
What do you think it takes to build a system that's human level intelligence? We talked a little bit about the Turing test, StarCraft, all these echoes of general intelligence. But if you think about just something that you would sit back and say, wow, this is really something that resembles human level intelligence, what do you think it takes to build that?
So I find that AGI oftentimes is maybe not very well defined. So what I'm trying to then come up with for myself is, what would be a result look like that you would start to believe that you would have agents or neural net that no longer sort of overfit to a single task, right? But actually kind of learn the skill of learning, so to speak. And that actually is a field that I am fascinated by, which is the learning to learn, or meta learning, which is about no longer learning about a single domain. So you can think about it, the learning algorithm in itself is general, right? So the same formula we applied for AlphaStar or StarCraft, we can now apply to kind of almost any video game, or you could apply to many other problems and domains. But the algorithm is what's kind of generalized. But the neural network, those weights are useless even to play another race, right? I train a network to play very well at Protoss versus Protoss. I need to throw away those weights. If I want to play now Terran versus Terran, I would need to retrain a network from scratch with the same algorithm. That's beautiful, but the network itself will not. So I think if I see an approach that can absorb or start solving new problems without the need to kind of restart the process, I think that, to me, would be a nice way to define some form of AGI. Again, I don't know the grandiose like AGI. I mean, should Turing test this out before AGI? I mean, I don't know. I think concretely, I would like to see clearly that meta learning happen, meaning there is an architecture or network that, as it sees new problem or new data, it solves it, and to make it kind of a benchmark, it should solve it at the same speed that we do solve new problems. When I define you a new object, I have to recognize it. When you start playing a new game, you played all the Atari games, but now you play a new Atari game. Well, you're going to be pretty quickly pretty good at the game. So that's perhaps what's the domain and what the exact benchmark is a bit difficult. I think as a community, we might need to do some work to define it. But I think this first step, I could see it happen relatively soon. But then the whole what AGI means and so on, I am a bit more confused about what I think people mean different things.
Yeah, there's an emotional, psychological level that, like even the Turing test. Passing the Turing test is something that we just pass judgment on as human beings. What it means to be, is a dog
an AGI system.
Yeah.
Like what level? What does it mean?
Right.
Yeah. What does it mean? But I like the generalization, and maybe as a community, we'll converge towards a group of domains that are sufficiently far away that would be really damn impressive if was able to generalize. So perhaps not as close as Protoss and Zerg, but like Wikipedia.
Yeah.
Yeah, would be a good step,
Yeah.
and then a really good step. But then like from StarCraft to Wikipedia,
Yeah.
and back,
Yeah.
that kind of thing.
And that feels also quite hard and far, but I think this, as long as you put the benchmark out, as we discovered, for instance, with ImageNet, then tremendous progress can be had. So I think maybe there's a lack of benchmark, but I'm sure we'll find one. Yeah, the community will then work towards that. And then beyond what AGI might mean or would imply, I really am hopeful to see basically machine learning or AI just scaling up and helping people that might not have the resources to hire an assistant, or that they might not even know what the weather is like. But so I think there's, in terms of the impact, the positive impact of AI, I think that's maybe what we should also not lose focus, right? The research community building AGI, I mean, that's a real nice goal, but and I think the way that DeepMind puts it is, and then use it to solve everything else, right?
Yeah.
So I think we should parallelize.
Yeah, we shouldn't forget of all the positive things that are actually coming out of AI already, and are going to be coming out. On that note, let me ask, relative to popular perception, do you have any worry about the existential threat of artificial intelligence in the near or far future that some people have?
I think I'm in the near future. I'm skeptical, so I hope I was wrong, but I'm not concerned. But I appreciate efforts, ongoing efforts, and even like a whole research field on AI safety emerging and in conferences and so on. I think that's great. In the long term, I really hope we just can simply have the benefit outweigh the potential dangers. I am hopeful for that. But also we must remain vigilant to kind of monitor and assess whether the trade-offs are there, and we have enough also lead time to prevent or to redirect our efforts if need be, right? So, but I'm quite optimistic about the technology, and definitely more fearful of other threats in terms of planetary level at this point. But obviously, that's the one I kind of have more power on. So clearly, I do start thinking more and more about this, and it's grown in me actually to start reading more about AI safety. This is a field that so far I have not really contributed to, but maybe there's something to be done there as well.
Well, I think it's really important. I talk about this with a few folks, but it's important to ask you and shove it in your head, because you're at the leading edge of actually what people are excited about. I mean, the work with AlphaStar, it's arguably at the very cutting edge of the kind of thing that people are afraid of.
Mhm.
And so you speaking to that fact, and that we're actually quite far away to the kind of thing that people might be afraid of, but it's still something worthwhile to think about. And it's also good that you're not as worried, and you're also open to
Yeah, I mean, there's two aspects. I mean, me not being worried, but obviously we should prepare for it, right? For things that could go wrong, misuse of the technologies, as with any technologies, right? So I think there's always trade-offs, and I as a society we've kind of solved these to some extent in the past. So I'm hoping that by having the researchers and the whole community brainstorm and come up with interesting solutions to the new things that will happen in the future, that we can still also push the research to the avenue that I think is kind of the greatest avenue, which is to understand intelligence. Like, how are we doing what we're doing? And obviously, from a scientific standpoint, that is kind of the drive, my personal drive of all the time that I spend doing what I'm doing.
Where do you see the deep learning as a field heading? What do you think the next big breakthrough might be?
So I think deep learning, I discussed a little this before. Deep learning has to be combined with some form of discretization program synthesis. I think that's kind of, as a research in itself, is an interesting topic to expand and start doing research. And then as kind of what will deep learning enable to do in the future. I don't think that's going to be what's going to happen this year, but also this idea of starting not to throw away all the weights, that this idea of learning to learn and really having these agents not having to restart their weights, and you can have an agent that is kind of solving or classifying images on ImageNet, but also generating speech if you ask it to generate some speech, and it should really be kind of almost the same network, but might not be a neural network. It might be a neural network with a optimization algorithm attached to it. But I think this idea of generalization to new tasks is something that we've first must define good benchmarks, but then I think that's going to be exciting. I'm not sure how close we are, but I think if you have a very limited domain, I think we can start doing some progress, and much like how we did a lot of programs in computer vision, we should start thinking. I really like a talk that Leon Butu gave at ICML a few years ago, which is this train test paradigm should be broken. We should stop thinking about a training test, a training set and a test set, and these are closed, things that are untouchable. I think we should go beyond these, and in meta learning we call these the meta training set and the meta test set, which is really thinking about, if I know about ImageNet, why would that network not work on MNIST, which is a much simpler problem? But right now it really doesn't. But it just feels wrong, right? So I think that's kind of on the application or the benchmark side, we probably will see quite a few more interest and progress, and hopefully people define new and exciting challenges.
Do you have any hope or interest in knowledge graphs within this context? So just kind of
Totally,
constructing graphs. So going back to graphs.
Yeah.
Well, neural networks and graphs, but I mean a different kind of knowledge graph, sort of semantic graphs where there's concepts.
Yeah. So I think the idea of graphs is so I've been quite interested in sequences first, and then more interesting or different data structures like graphs, and I've studied graph neural networks in the last 3 years or so. I found these models just very interesting from like deep learning side standpoint. But then what do we want? Why do we want these models, and why would we use them? What's the application? What's kind of the killer application of graphs, right? And perhaps if we could extract a knowledge graph from Wikipedia automatically, right? That would be interesting, because then these graphs have this very interesting structure that also is a bit more compatible with this idea of programs and deep learning kind of working together, jumping neighborhoods and so on. You could imagine defining some primitives to go around the graph, right? So I think I really like the idea of a knowledge graph, and in fact, when we started, or as part of the research with SparkGraph, I thought, wouldn't it be cool to give the graph of all the prerequisites, like there's all these buildings that depend on each other and units that have prerequisites of being built by that, and so this is information that the network can learn and extract, but it would have been great to see, or to think of really StarCraft as a giant graph that even also as the game evolves, you kind of start taking branches and so on. We did a bit of research on this, nothing too relevant, but I really like the idea.
Yeah, and it has elements that are, which is something you also worked with in terms of visualizing neural networks. It has elements of having human interpretable, being able to generate knowledge representations that are human interpretable, that maybe human experts can then tweak or at least understand. So there's a lot of interesting aspects there. And for me personally, I'm just a huge fan of Wikipedia, and it's a shame that our neural networks aren't taking advantage of all the structured knowledge that's on the web. What's next for you? What's next for DeepMind? What are you excited about? What for AlphaStar?
Yeah, so I think the obvious next steps would be to apply AlphaStar to other races. I mean, that sort of shows that the algorithm works, because we wouldn't want to have created by mistake something in the architecture that happens to work for Protoss but not for other races, right? So as verification, I think that's an obvious next step that we are working on. And then I would like to see, so agents and players can specialize on different skill sets that allow them to be very good. I think we've seen AlphaStar understanding very well when to take battles and when to not to do that. Also, very good at micromanagement and moving the units around and so on. And also very good at producing non-stop and trading off economy with building units. But I have not perhaps seen as much as I would like this idea of the poker idea that you mentioned, right? I'm not sure StarCraft or AlphaStar rather has developed a very deep understanding of what the opponent is doing and reacting to that and sort of trying to trick the player to do something else, or that, so this kind of reasoning I would like to see more. So I think purely from a research standpoint, there's perhaps also quite a few things to be done there in the domain of StarCraft.
Yeah, in the domain of games, I've seen some interesting work in sort of even auctions, manipulating other players, so they're forming a belief state, and just messing with people.
Yeah, it's called theory of mind.
Theory of mind.
Yeah.
So it's
Exactly. Theory of mind on StarCraft is kind of, they're really made for each other.
Yeah.
So that would be very exciting to see those techniques applied to StarCraft, or perhaps StarCraft driving indicators, right? As I said, this is always the tension between the two.
Wow, Royal, thank you so much for talking today.
Awesome. It was great to be here. Thanks.
The following is a conversation with Chris Ladner. Currently, he's a senior director of Google, working on several projects, including CPU, GPU, TPU accelerators for TensorFlow, Swift for TensorFlow, and all kinds of machine learning compiler magic going on behind the scenes. He's one of the top experts in the world on compiler technologies, which means he deeply understands the intricacies of how hardware and software come together to create efficient code. He created the LLVM compiler infrastructure project and the Clang compiler. He led major engineering efforts at Apple, including the creation of the Swift programming language. He also briefly spent time at Tesla as vice president of Autopilot software during the transition from Autopilot Hardware 1 to Hardware 2, when Tesla essentially started from scratch to build an in-house software infrastructure for Autopilot. I could have easily talked to Chris for many more hours. Compiling code down across the levels of abstraction is one of the most fundamental and fascinating aspects of what computers do, and he is one of the world's experts in this process. It's rigorous science, and it's messy, beautiful art. This conversation is part of the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, iTunes, or simply connect with me on Twitter at Lex Friedman, spelled F-R-I-D. And now, here's my conversation with Chris Ladner. What was the first program you ever written?
My first program back.
When was it?
I think I started as a kid, and my parents got a basic programming book. And so when I started, it was typing out programs from a book and seeing how they worked, and then typing them in wrong and trying to figure out why they were not working right, that kind of stuff.
The basic. What was the first language that you remember yourself maybe falling in love with, like really connecting with?
I don't know. I mean, I feel like I've learned a lot along the way, and each of them have a different special thing about them. So I started in basic, and then like GW basic was the thing back in the DOS days, and then upgraded to Q basic, and eventually Quick basic, which were all slightly more fancy versions of Microsoft Basic. Made the jump to Pascal, started doing machine language programming and assembly in Pascal, which is really cool. Turbo Pascal was amazing for its day. Eventually got into C, C++, and then kind of did lots of other weird things.
I feel like you took the dark path, which is the you could have gone Lisp
Yeah.
You could have gone higher level, sort of functional, philosophical, hippie route.
Yeah.
Instead, you went into like the dark arts of the
Straight into the machine.
Straight to the
So it started with basic Pascal net assembly. And wrote a lot of assembly. And
why.
eventually did small talk and other things like that. So that was not the starting point.
But so what is this journey into C? Is that in high school? Is that in college?
That was in high school. Yeah. So and then that was really about trying to be able to do more powerful things than what Pascal could do, and also learn from the world. So he was really confusing with pointers and the syntax and everything. It took a while, but Pascal's much more principled in various ways. C's more. I mean, it has its historical roots. It's not as easy to learn.
With pointers, there's this memory management thing that you have to become conscious of. Is that the first time you start to understand that there's resources that you're supposed to manage?
Yeah. Well, so you have that in Pascal as well, but in Pascal, these like the caret and some star, and there's some small differences like that, but it's not about pointer arithmetic. And in C, you end up thinking about how things get laid out in memory a lot more. And so in Pascal, you have allocating and owning the memory, but just the programs are simpler. You don't have to. Well, for example, Pascal has a string type. And so you can think about a string instead of an array of characters which are consecutive in memory. Yeah. So it's a little bit of a higher level abstraction.
So let's get into it. Let's talk about LLVM, slang, and compilers.
Sure.
So can you tell me first what LLVM and slang are, and how is it that you find yourself the creator and lead developer of one of the most powerful compiler optimization systems being used today?
Sure. So I guess they're different things. So let's start with what is a compiler. Is that a good place to start?
What are the phases of a compiler? What are the parts? Yeah, what is it?
So what is even a compiler used for? So the way I look at this is you have a two-sided problem. You have humans that need to write code, and then you have machines that run the program that the human wrote. And for lots of reasons, the humans don't want to be writing in binary and want to think about every piece of hardware. And so at the same time that you have lots of humans, you also have lots of kinds of hardware. And so compilers are the art of allowing humans to think at a level of abstraction that they want to think about, and then get that program, get the thing that they wrote, to run on a specific piece of hardware. And the interesting and exciting part of all this is there's now lots of different kinds of hardware, chips like x86 and IPC and ARM and things like that, but also high-performance accelerators, machine learning, and other things like that are also just different kinds of hardware. GPUs, these are new kinds of hardware. And at the same time, on the programming side of it, you have your basic, you have C, you have JavaScript, you have Python, you have Swift, you have like lots of different languages that are all trying to talk to them in a different way to make them more expressive and capable and powerful. And so compilers are the thing that goes from one to the other. You know?
And the very beginning,
end to end. And so you go from what the human wrote, and programming languages end up being about expressing intent, not just for the compiler and the hardware, but the programming language's job is really to capture an expression of what the programmer wanted that then can be maintained and adapted and evolved by other humans, as well as interpreted by the compiler. So when you look at this problem, you have on one hand humans, which are complicated. You have hardware, which is complicated. And so compilers typically work in multiple phases. And so the software engineering challenge that you have here is to try to get maximum reuse out of the amount of code that you write, because these compilers are very complicated. And so the way it typically works out is that you have something called a front end or a parser that is language specific. And so you'll have a C parser, that's what Clang is, or C++ or JavaScript or Python or whatever. That's the front end. Then you'll have a middle part, which is often the optimizer. And then you'll have a late part, which is hardware specific. And so compilers end up, there's many different layers often, but these three big groups are very common in compilers. And what LLVM is trying to do is trying to standardize that middle and last part. And so one of the cool things about LLVM is there are a lot of different languages that compile through to it. And so things like Swift, but also Julia, Rust, Clang for C++, C, like these are all very different languages, and they can all use the same optimization infrastructure, which gets better performance, and the same code generation infrastructure for hardware support. And so LLVM, really that layer that is common that all these different specific compilers can use.
And is it a standard, like a specification, or is it literally an implementation?
It's an implementation, and so it's. I think there's a couple of different ways of looking at it, right? Because it depends on which angle you're looking at it from. LLVM ends up being a bunch of code. Okay, so it's a bunch of code that people reuse and they build compilers with. We call it a compiler infrastructure because it's kind of the underlying platform that you build a concrete compiler on top of. But it's also a community, and the LLVM community is hundreds of people that all collaborate. And one of the most fascinating things about LLVM over the course of time is that we've managed somehow to successfully get harsh competitors in the commercial space to collaborate on shared infrastructure. And so you have Google and Apple, you have AMD and Intel, you have NVIDIA and AMD on the graphics side, you have Cray and everybody else doing these things. And like all these companies are collaborating together to make that shared infrastructure really, really great. And they do this not out of the goodness of their heart, but they do it because it's in their commercial interest of having really great infrastructure that they can build on top of, and facing the reality that it's so expensive that no one company, even the big companies, no one company really wants to implement it all themselves.
Expensive or
both? That's a great point, because it's also about the skill sets, and these the skill sets are hard to find.
How big is the LLV? It always seems like with open source projects, the kind, and LLVM is open source.
Yes, it's open source. It's 19 years old now, so it's fairly old.
It seems like magic often happens with a very small circle of people.
Yes.
At least their early birth and whatever.
Yes. So the LLVM came from a university project. So I was at the University of Illinois. And there it was myself, my advisor, and then a team of 2 or 3 research students in the research group. And we built many of the core pieces initially. I then graduated at Apple, and Apple brought it to the products, first in the OpenGL graphics stack, but eventually the C compiler realm, and eventually built Clang, and eventually built Swift, and these things. Along the way, building a team of people that are really amazing compiler engineers that helped build a lot of that. And so as it was gaining momentum, and as Apple was using it, being open source and public, encouraging contribution, many others, for example, Google, came in and started contributing. And in some cases, Google effectively owns Clang now because it cares so much about C++ and the evolution of that ecosystem. And so it's investing a lot in the C++ world and tooling and things like that. And so likewise, NVIDIA cares a lot about CUDA. And so CUDA uses Clang and uses LLVM for graphics and GPU.
And so when you first started as a master's project with this, did you think it's going to go as far as it went? Were you crazy ambitious about it? It seems like a really difficult undertaking, a brave one.
Yeah, no. So, I mean, my goal when I went to the University of Illinois was to get in and out with a non-thesis master's in a year and get back to work. So I was not planning to stay for 5 years and build this massive infrastructure. I got nerd sniped into staying. And a lot of it was because LLVM was fun, and I was building cool stuff and learning really interesting things and facing software engineering challenges, but also learning how to work in a team and things like that. I had worked at many companies as interns before that, but it was really a different thing to have a team of people that are working together and trying to collaborate in version control, and it was just a little bit different.
Like I said, I just talked to Don Knuth, and he believes that 2% of the world population have something weird with their brain. Geeks, they understand computers, they're connected with computers. He put it at exactly 2%. Okay, so
It's a specific guy.
it's very specific. Like he says, I can't prove it, but it's very empirically there. Is there something that attracts you to the idea of optimizing code? I mean, it seems like that's one of the biggest, coolest things about code.
Yeah, that's one of the major things it does. So I got into that because of a person, actually. So when I was in my undergraduate, I had an advisor or a professor named Steve Vegdahl,
and I went to this little tiny private school. There were like 7 or 9 people in my computer science department, students in my class. So it was a very tiny, very very small school. It was kind of a wart on the side of the math department kind of thing. At the time, I think it's evolved a lot in the many years since then. But Steve Vegdahl was a compiler guy, and he was super passionate. And his passion rubbed off on me. And one of the things I like about compilers is that they're large, complicated software pieces. And so one of the culminating classes that many computer science departments, at least at the time, did was to say that you take algorithms, data structures, and all these core classes, but then the compilers class was one of the last classes you take because it pulls everything together, and then you work on one piece of code over the entire semester. And so you keep building on your own work, which is really interesting. It's also very challenging because in many classes, if you don't get a project done, you just forget about it and move on to the next one and get your B or whatever it is. But here you have to live with the decisions you make and continue to reinvest in it. And I really like that. And so I did an extra study project with him the following semester, and it was just really great. And he was also a great mentor in a lot of ways. And so from him and from his advice, he encouraged me to go to graduate school. I wasn't super excited about going to grad school. I wanted the master's degree, but I didn't want to be an academic. And but like I said, I kind of got tricked into staying and was having a lot of fun, and I definitely do not regret it.
What aspects of compilers are the things you connected with? So LVM. There's also the other part. This is really interesting. If you're interested in languages, parsing, and just analyzing language, breaking it up, parsing, and so on. Was that interesting to you, or were you more interested in optimization?
For me, it was more. So I'm not really a math person. I could do math. I understand some bits of it when I get into it, but math is never the thing that attracted me. And so a lot of the parser part of the compiler has a lot of good formal theories that Don, for example, knows quite well. Still waiting for his book on that, but I just like building a thing and seeing what it could do and exploring and getting to do more things and then setting new goals and reaching for them and in the case of LLVM, when I started working on that, my research advisor that I was working for was a compiler guy, and so he and I found each other because we were both interested in compilers, and so I started working with him and taking his class. A lot of LLVM initially was it's fun implementing all the standard algorithms and all the things that people have been talking about and were well known, and they were in the curricula for advanced studies in compilers. And so just being able to build that was really fun, and I was learning a lot by, instead of reading about it, just building. And so I enjoyed that.
So you said compilers are these complicated systems. Can you even just, with language, try to describe, how you turn a C++ program into code? Like, what are the hard parts? Why is it so hard?
So I'll give you examples of the hard parts. So C++ is a very complicated programming language. It's like 1,400 pages of spec. So C++ by itself is crazy complicated.
Can we just pause? What makes the language complicated in terms of what's syntactically?
So it's what they call syntax of the actual how the characters are arranged. Yes, it's also semantics, how it behaves. It's also, in the case of C++, there's a huge amount of history. C++ built on top of C. You play that forward, and then a bunch of suboptimal, in some cases, decisions were made, and they compound. And then more and more things keep getting added to C++, and it will probably never stop. But the language is very complicated from that perspective. And so the interactions between subsystems is very complicated. There's just a lot there. And when you talk about the front end, one of the major challenges, which Clang has a project, the C++ compiler that I built, I and many people built, one of the challenges we took on was we looked at GCC. Okay, GCC at the time was like a really good industry standardized compiler that had really consolidated a lot of the other compilers in the world and was a standard, but it wasn't really great for research. The design was very difficult to work with, and it was full of global variables and other things that made it very difficult to reuse in ways that it wasn't originally designed for. And so with Clang, one of the things that we wanted to do is push forward on better user interface. So make error messages that are just better than GCCs. And that's actually hard because you have to do a lot of bookkeeping in an efficient way to be able to do that. You want to make compile time better. And so compile time is about making it efficient, which is also really hard when you're keeping track of extra information. We wanted to make tools available. So refactoring tools and other analysis tools that the GCC never supported, also leveraging the extra information we kept, but enabling those classes and tools that then get built into IDEs. And so that's been one of the areas that has really helped push the world forward in the tooling for C and C++ and things like that. But C++ and the front end piece is complicated, and you have to build syntax trees, and you have to check every rule in the spec, and you have to turn that back into an error message to the human that the human can understand when they do something wrong. But then you start doing the what's called lowering, so going from C++ and the way that it represents code down to the machine. And when you do that, there's many different phases you go through. Often there are, I think LLVM has something like 150 different what are called passes in the compiler that the code passes through, and these get organized in ways which affect the generated code performance and compile time and other things.
What are they passing through? So after you do the Clang parsing, what's the graph? What does it look like? What's the data structure here?
Yeah, so in the parser, it's usually a tree. It's called an abstract syntax tree. So the idea is you have a node for the plus that the human wrote in their code, or the function call, you'll have a call of the function that they call and arguments, things like that. This then gets lowered into what's called an intermediate representation, and intermediate representations are like LLVM has one, and there it's what's called a control flow graph, and so you represent each operation in the program as a very simple, like this is going to add two numbers, this is going to multiply two things, maybe we'll do a call, but then they get put in what are called blocks. And so you get blocks of these straight line operations. Instead of being nested like in a tree, it's straight line operations. And so there's a sequence and an order of these operations.
So and then in the block or outside the block?
That's within the block. And so it's a straight line sequence of operations within the block. And then you have branches, like conditional branches between blocks. And so when you write a loop, for example, in a syntax tree, you would have a for node for a for statement in a C-like language. You'd have a for node, and you have a pointer to the expression for the initializer, a pointer to the expression for the increment, a pointer to the expression for the comparison, a pointer to the body. Okay, and these are all nested underneath it. In a control flow graph, you have a block for the code that runs before the loop, so the initializer code. And you have a block for the body of the loop, and so the body of the loop code goes in there, but also the increment and other things like that. And then you have a branch that goes back to the top, and a comparison branch that goes out. And so it's more of an assembly level kind of representation. But the nice thing about this level of representation is it's much more language independent. And so there's lots of different kinds of languages with different kinds of JavaScript. Has a lot of different ideas of what is false, for example, and all that can stay in the front end, but then that middle part can be shared across all of those.
How close is that intermediate representation to neural networks, for example? Are they because everything described as a kind of echoes of a neural network graph? Are they neighbors or what?
They're quite different in details, but they're very similar in idea. So one of the things that neural networks do is they learn representations for data at different levels of abstraction, right? And then they transform those through layers, right? So the compiler does very simple things, but one of the things the compiler does is it has relatively few different representations. For a neural network, often as you get deeper, for example, you get many different representations in each layer or subhops that's transforming between these different representations. In a compiler, often you get one representation and they do many transformations to it. And these transformations are often applied iteratively, and programmers do familiar types of things. For example, trying to find expressions inside of a loop and pulling them out of a loop so that they execute 3 times. Or find redundant computation, or find constant folding or other simplifications, turning 2 times x to x shift left by 1, and things like this are all the examples of the things that happen. But compilers end up getting a lot of theorem proving and other kinds of algorithms that try to find higher level properties of the program that then can be used by the optimizer.
Cool. So what's like the biggest bang for the buck with optimization? What's
Today? Yeah.
Well, no, not even today. At the very beginning, the 80s. I don't know.
Okay, yeah. So for the 80s, a lot of it was things like register allocation. So the idea of in a modern a microprocessor, what you'll end up having is you'll end up having memory, which is relatively slow, and then you have registers, relatively fast. But registers, you don't have very many of them. Okay. And so when you're writing a bunch of code, you're just saying like compute this, put it in temporary variable, compute this, put it in temporary variable. I have a loop, I have some other stuff going on. Well, now you're running on an x86, like a desktop PC or something. Well, it only has, in some cases, some modes, 8 registers, right? And so now the compiler has to choose what values get put in what registers at what points in the program. And this is actually a really big deal. So if you think about, you have a loop, and in our loop that executes millions of times maybe. If you're doing loads of stores inside that loop, then it's going to be really slow. But if you can somehow fit all the values inside that loop with registers, now it's really fast. And so getting that right requires a lot of work because there's many different ways to do that. And often what the compiler ends up doing is it ends up thinking about things in a different representation than what the human wrote. Right? You wrote int x. Well, the compiler thinks about that as 4 different values, each which have different lifetimes across the function that it's in. And each of those could be put in the register or memory or different memory, or maybe in some parts of the code recomputed instead of stored and reloaded. There are many of these different kinds of techniques that can be used.
So it's adding almost like a time dimension to. It's trying to optimize across time. So it's considering when you're programming, you're not thinking.
Yeah, absolutely. And so the RISC era made things. So RISC chips, RISC. The RISC chips, as opposed to system chips, the RISC chips made things more complicated for the compiler because what they ended up doing is ending up adding pipelines to the processor, where the processor can do more than one thing at a time. But this means that the order of operations matters a lot. And so one of the classical compiler techniques that you use is called scheduling. And so moving the instructions around so that the processor can keep its pipelines full instead of stalling and getting blocked. And so there's a lot of things like that that are kind of bread and butter compiler techniques that have been studied a lot over the course of decades now. But the engineering side of making them real is also still quite hard. And you talk about machine learning. This is a huge opportunity for machine learning because many of these algorithms are full of these like hokey hand-rolled heuristics, which work well on specific benchmarks, but don't generalize, and they're full of magic numbers. And I hear there's techniques that are good at handling that.
So what would be the if you were to apply machine learning to this? What's the thing you're trying to optimize? Is it ultimately the running time?
You could pick your metric, and there's running time, there's memory use, there's lots of different things that you can optimize. Where code size is another one that some people care about in the embedded space.
Is this like the thinking into the future, or is somebody actually been crazy enough to try to have machine learning based parameter tuning for optimization?
So this is something that is, I would say, research right now. There are a lot of research systems that have been applying search in various forms, and using reinforcement learning is one form, but also brute force search has been tried for quite a while. And usually these are small problem spaces. So find the optimal way to co-generate a matrix multiply for a GPU, right? Something like that, where you say, there's a lot of design space of, do you unroll loops a lot? Do you execute multiple things in parallel? And there's many different confounding factors here because graphics cards have different numbers of threads and registers and execution ports and memory bandwidth and many different constraints to interact in nonlinear ways. And so search is very powerful for that, and it gets used in certain ways, but it's not very structured. This is something that we need, as an industry, need to fix.
So you said 80, but have there been big jumps in improvement and optimization?
Yeah.
Since then, and
so it's largely been driven by hardware. So hardware and software. So in the mid '90s, Java totally changed the world, right? And I'm still amazed by how much change was introduced by Java in a good way. So like reflecting back, Java introduced things like all at once introduced things like JIT compilation. I mean, none of these were novel, but it pulled it together and made it mainstream and made people invest in it. JIT compilation, garbage collection, portable code, safe code, like memory safe code, like a very dynamic dispatch execution model. Many of these things, which had been done in research systems and had been done in small ways in various places, really came to the forefront, really changed how things worked, and therefore changed the way people thought about the problem. JavaScript was another major world change based on the way it works. But also on the hardware side of things, multi-core and vector instructions really change the problem space and are very they don't remove any of the problems that compilers faced in the past, but they add new kinds of problems of how do you find enough work to keep a 4 wide vector busy, right? Or if you're doing a matrix multiplication, how do you do different columns out of that matrix at the same time, and how do you maximally utilize the arithmetic compute that one core has, and then how do you take it to multiple cores?
How did the whole virtual machine thing change the compilation pipeline?
So what the Java virtual machine does is it splits, just like I was talking about before, where you have a front end that parses the code, and then you have an intermediate representation that gets transformed. What Java did was they said, we will parse the code and then compile to what's known as Java bytecode. And that bytecode is now a portable code representation that is industry standard and locked down and can't change. And then the back part of the compiler that does optimization and code generation can now be built by different vendors. And Java bytecode can be shipped around across the wire. It's memory safe and relatively trusted.
And because of that, it's on the browser.
And that's why it runs in the browser. Right? And so that way you can begin, again, back in the day, you would write a Java applet and you'd use as a web developer, you'd build this mini app that would run on a web page. Well, a user of that is running a web browser on their computer. You download that Java bytecode, which can be trusted, and then you do all the compiler stuff on your machine, so that you know that you trust that.
Was that a good idea or a bad idea?
It's a great idea. I mean, it's a great idea for certain problems, and I'm very much a believer the technology is itself neither good nor bad. It's how you apply it. This would be a very, very bad thing for very low levels of the software stack, but in terms of solving some of these software portability and transparency or portability problems, I think it's been really good. Now, Java ultimately didn't win out on the desktop. There are good reasons for that, but it's been very successful on servers and in many places. It's been a very successful thing over decades.
So what has been LLVMs and C-line improvements in optimization that throughout its history? What are some moments where you had to step back and really proud of what's been accomplished?
Yeah, I think that the interesting thing about LLVM is not the innovations in compiler research. It has very good implications of various important algorithms, no doubt, and a lot of really specific things important. But I think that the thing that's most profound about LLVM is that through standardization, it made things possible that otherwise wouldn't have happened. Okay. And so interesting things that have happened with LLVM, for example, Sony has picked up LLVM and used it to do all the graphics compilation and movie production pipeline. And so now they're able to have better special effects because of LLVM. That's kind of cool. That's not what it was designed for, right? But that's the sign of good infrastructure when it can be used in ways it was never designed for because it has good layering and software engineering and it's composable and things like that.
Which is where, as you said, it differs from GCC.
Yes. GCC is also great in various ways, but it's not as good as a infrastructure technology. It's really a C compiler, or it's a Fortran compiler. It's not infrastructure.
Now, is it? Now you can tell I don't know what I'm talking about because I keep saying C-lang. You could always tell when a person is close by the something. I don't think have I ever used Clang.
Entirely possible. You've used code that's generated probably. So Clang and LLVM are used to compile all the apps on iPhone effectively, and the OSs. compiles Google's production server applications. It's used to build GameCube games, PlayStation 4, and things like that.
So as a user, I have, but just everything I've done that I experienced with Linux has been, I believe, always GCC.
Yeah, I think Linux still defaults to GCC.
And is there a reason for that, or is it because, again, is there?
It's a combination of technical and social reasons. Many Linux developers do use Clang, but the distributions, for lots of reasons, use GCC historically, and they've not switched.
Yeah. It's just anecdotally, I thought it seems that LLVM has either reached the level of GCC or superseded on different features or whatever.
The way I would say it is that they're so close it doesn't matter.
Yeah, exactly.
Like they're slightly better in some ways, slightly worse in other ways, but no, it doesn't actually really matter anymore at that level.
So in terms of optimization and breakthroughs, it's just been solid incremental work.
Yeah, which describes a lot of compilers. The hard thing about compilers, in my experience, is the engineering, the software engineering, making it so that you can have hundreds of people collaborating on really detailed, low-level work and scaling that. And that's really hard. That's one of the things I think LLVM has done well. And that goes back to the original design goals with it to be modular, things like that. And incidentally, I don't want to take credit for this, right? I mean, some of the best parts about LLVM is it was designed to be modular. And when I started, I would write, for example, a register allocator, and then somebody much smarter than me would come in and pull it out and replace it with something else that they would come up with. And because it's modular, they were able to do that. And that's one of the challenges with GCC, for example, is replacing subsystems is incredibly difficult. It can be done, but it wasn't designed for that. And that's one of the reasons the LLVM's been very successful in the research world as well.
But in the community sense, Guido van Rossum, right, from Python, just retired from, what is it, Benevolent Dictating for Life, right? So when managing this community of brilliant compiler folks, is there, did it, for a time at least, fall on you to approve things?
Oh yeah, so I mean I still have something like an order of magnitude more patches in LLVM than anybody else, and many of those I wrote myself. But
you still write. I mean, you're still close to the I don't know what the expression is, to the metal. You still write code.
Yeah, I still write code. Not as much as I was able to in grad school, but that's an important part of my identity. But the way that LLVM has worked over time is that when I was a grad student, I could do all the work and steer everything and review every patch and make sure everything was done exactly the way my opinionated sense felt like it should be done. That was fine. But as things scale, you can't do that, right? And so what ends up happening is LLVM has a hierarchical system of what's called code owners. These code owners are given responsibility not to do all the work, not necessarily to review all the patches, but to make sure that the patches do get reviewed, make sure that the right thing's happening architecturally in their area. And so what you'll see that, for example, hardware manufacturers end up owning the hardware-specific parts of their hardware. That's very common. Leaders in the community that have done really good work naturally become the de facto owner of something, and then usually somebody else is like, how about we make them the official code owner, and then we'll have somebody to make sure that all the patches get reviewed in a timely manner, and then everybody's like, yes, that's obvious, and then it happens, right? And usually this is a very organic thing, which is great. And so I'm nominally the top of that stack still, but I don't spend a lot of time reviewing patches. What I do is I help negotiate a lot of the technical disagreements that end up happening, and making sure that the community as a whole makes progress and is moving in the right direction and doing that. So we also started a nonprofit 7 years ago. Time's gone away. And the nonprofit, the LLVM Foundation nonprofit, helps oversee all the business sides of things and make sure that the events that the LLVM community has are funded and set up and run correctly and stuff like that. But the foundation is very much stays out of the technical side of where the project is going.
Right, so it sounds like a lot of it is just organic.
Yeah, well, and LLVM is almost 20 years old, which is hard to believe. Somebody pointed out to me recently that LLVM is now older than GCC was when LLVM started. Right. So time has a way of getting away from it. But the good thing about that is it has a really robust, really amazing community of people that are in their professional lives spread across lots of different companies, but it's a community of people that are interested in similar kinds of problems and have been working together effectively for years and have a lot of trust and respect for each other. And even if they don't always agree, that we're able to find a path forward.
So then, a slightly different flavor of effort. You started at Apple in 2005 with the task of making, I guess, LLVM production ready. And then eventually 2013 to 2017, leading the entire developer tools department. We're talking about LLVM, Xcode, Objective-C to Swift. So in a quick overview of your time there, what were the challenges, first of all, leading such a huge group of developers? What was the big motivator, dream, mission behind creating Swift, the early birth of it from Objective-C and so on, and Xcode?
So these are different questions.
Yeah, I know. But
Okay, so I'll stay on
the other stuff
yeah,
too.
I'll stay on the technical side, then we can talk about the big team pieces. If that's okay.
Sure.
So, it's to really oversimplify many years of hard work. LLVM joined Apple, became a thing, became successful, and became deployed. But then there's a question about how do we actually parse source code? So LLVM is the back part, the optimizer and the code generator. And LLVM was really good for Apple as it went through a couple of hardware transitions. I joined right at the time of the Intel transition, for example, and 64-bit transitions, and then the transition to ARM with the iPhone. And so LLVM is very useful for some of these kinds of things. But at the same time, there's a lot of questions around developer experience. So if you're a programmer pounding out at the time Objective-C code, the error message you get, the compile time, the turnaround cycle, the tooling in the IDE were not great. Were not as good as they could be. And so, as I occasionally do, I'm like, well, okay, how hard is it to write a C compiler? Right? And so I'm not going to commit to anybody. I'm not going to tell anybody. I'm just going to do it nights and weekends and start working on it. And then, I built up and see there's this thing called the preprocessor, which people don't like, but it's actually really hard and complicated and includes a bunch of really weird things like trigraph or stuff like that they're really nasty, and it's the crux of a bunch of the performance issues in the compiler. Started working on the parser and kind of got. I'm like, you know what? You can actually do this. Everybody's saying that this is impossible to do, but it's actually just hard. It's not impossible. And eventually told my manager about it, and he's like, oh, wow, this is great. We do need to solve this problem. Oh, this is great. We can get you one other person to work with you on this, And slowly a team is formed, and it starts taking off. And C++, for example, huge, complicated language. People always assume that it's impossible to implement, and it's very nearly impossible, but it's just really, really hard. And the way to get there is to build it one piece at a time, incrementally. And that was only possible because we were lucky to hire some really exceptional engineers that knew various parts of it very well and could do great things. Swift was kind of a similar thing. So Swift came from, we were just finishing off the first version of C++ support in Clang. And C++ is a very formidable and very important language, but it's also ugly in lots of ways. And you can't implement C++ without thinking there has to be a better thing. Right? And so I started working on Swift again with no hope or ambition that we'd go anywhere. Let's see what could be done. Let's play around with this thing. It was, me in my spare time, not telling anybody about it, kind of thing. It made some progress. I'm like, actually, it would make sense to do this. At the same time, I started talking with the senior VP of software at the time, a guy named Bertrand Soleil. And Bertrand was very encouraging. He was like, well, let's have fun. Let's talk about this. And he was a little bit of a language guy, and so he helped guide some of the early work and encouraged me and got things off the ground. And eventually, other people, like my manager, other people, and it started making progress. The complicating thing with Swift was that the idea of doing a new language was not obvious to anybody, including myself. And the tone at the time was that the iPhone was successful because of Objective-C. Right?
Oh, interesting.
Not despite of, or just
Correct.
because of. Yeah.
And you have to understand that at the time, Apple was hiring software people that loved Objective-C. Right, and it wasn't that they came despite Objective-C. They loved Objective-C, and that's why they got hired. And so you had a software team that the leadership in many cases went all the way back to Next, where Objective-C really became real. And so they, quote unquote, grew up writing Objective-C, and many of the individual engineers all were hired because they loved Objective-C. And so this notion of, okay, let's do a new language was kind of heretical in many ways, right? Meanwhile, my sense was that the outside community wasn't really in love with Objective-C. Some people were, and some of the most outspoken people were, but other people were hitting challenges because it has very sharp corners and it's difficult to learn. And so one of the challenges of making Swift happen that was totally non-technical is the social part of what do we do? If we do a new language, which at Apple, many things happen that don't ship, right? So if we ship it, what is the metric of success? Why would we do this? Why wouldn't we make Objective-C better? If Objective-C has problems, let's file off those rough corners and edges. And one of the major things that became the reason to do this was this notion of safety, memory safety. And the way Objective-C works is that a lot of the object system and everything else is built on top of pointers in C. Objective-C is an extension of C. And so pointers are unsafe, and if you get rid of the pointers, it's not Objective-C anymore. And so fundamentally, that was an issue that you could not fix safety, memory safety, without fundamentally changing the language. And so once we got through that part of the mental process, the thought process, it became a design process saying, okay, well, if we're going to do something new, what is good? Like, how do we think about this, and what do we like, and what are we looking for? And that was a very different phase of it.
So what are some design choices early on in Swift? Like we're talking about braces. Are you making a type language or not?
Yeah.
All those kinds of things.
Yeah, so some of those were obvious given the context. So a typed language, for example, Objective-C is a typed language. And going with an untyped language wasn't really seriously considered. We wanted the performance, and we wanted refactoring tools and other things like that to go with typed languages.
Quick dumb question. Was it obvious? I think this would be a dumb question, but was it obvious that the language has to be a compiled language?
Yes, that's not a dumb question. Earlier, late 90s, Apple had seriously considered moving its development experience to Java. But Swift started in 2010, which was several years after the iPhone. The iPhone was definitely on an upward trajectory, and the iPhone was still is still a bit memory constrained, right? And so being able to compile the code and then ship it, and then having standalone code that is not JIT compiled is a very big deal, and it's very much part of the Apple value system. Now, JavaScript is also a thing. Right? I mean, it's not that this is exclusive, and technologies are good depending on how they're applied, right? But in the design of Swift, saying like, how can we make Objective-C better, right? Objective-C is statically compiled, and that was the contiguous, natural thing to do.
Just skip ahead a little bit, and we'll go right back. Just as a question, as you think about today, 2019, in your work with Google, TensorFlow, and so on, is again compilation, static compilation. It's the right thing. That's the right thing.
Yeah. So the funny thing after working on compilers for a really long time is that, and this is one of the things that LLVM has helped with, is that I don't look at compilations being static or dynamic or interpreted or not. This is a spectrum. Okay. And one of the cool things about Swift is that Swift is not just statically compiled. It's actually dynamically compiled as well. And it can also be interpreted, though nobody's actually done that. And so what ends up happening when you use Swift in a workbook, for example, in Colab or in Jupyter, is it's actually dynamically compiling the statements as you execute them. And so this gets back to the software engineering problems, right? Where if you layer the stack properly, you can actually completely change how and what things get compiled because you have the right abstractions there. And so the way that a Colab workbook works with Swift is that when you start typing into it, it creates a process, a Unix process. And then each line of code you type in, it compiles it through the Swift compiler, the front end part, and then sends it through the optimizer. JIT compiles machine code, and then injects it into that process. And so as you're typing new stuff, it's like squirting in new code and overwriting and replacing and updating code in place. And the fact that it can do this, it's not an accident. Like Swift was designed for this. But it's an important part of how the language is set up and how it's layered. And this is a non-obvious piece. And one of the things with Swift that was, for me, a very strong design point is to make it so that you can learn it very quickly. And so from a language design perspective, the thing that I always come back to is this UI principle of progressive disclosure of complexity. And so in Swift, you can start by saying print, quote, hello world, quote, right? And there's no /n, just like Python, one line of code, no main, no header files, no public static class void, blah, 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 string, like Java has, right? One line of code, right? And you can teach that, and it'll be great. Then you can say, well, let's introduce variables. So declare a variable, var, so var x equals 4. What is a variable? You can use x plus 1. This is what it means. Then you can say, well, how about control flow? Well, this is what if statement is. This is what a for statement is. This is what a while statement is. Then you can say, let's introduce functions, right? And many languages like Python have had this kind of notion of let's introduce small things, and then you can add complexity. They can introduce classes, and you can add generics to Swift, and then you can build in modules and build out in terms of the things that you're expressing. But this is not very typical for compiled languages. And so this was a very strong design point, and one of the reasons that Swift in general is designed with this factoring of complexity in mind, so that the language can express powerful things. You can write firmware in Swift if you want to. But it has a very high level feel, which is really this perfect blend, because often you have very advanced library writers that want to be able to use the nitty-gritty details, but then other people just want to use the libraries and work at a higher abstraction level.
It's kind of cool that I saw that you just interoperability. I don't think I pronounced that word enough, but you can just drag in Python, which is strange. You can import I saw this in the demo.
Yeah.
Like, how do you make that happen?
Yeah, well,
what's up with that?
Yeah,
is that as easy as it looks, or is it?
Yes, as easy as it looks. That's not a stage magic hack or anything like that.
No, I don't mean from the user perspective. I mean from the implementation perspective to make it happen.
So it's easy once all the pieces are in place. The way it works. So if you think about a dynamically typed language like Python, right? You can think about it as two different ways. You can say it has no types, right? Which is what most people would say. Or you can say it has one type, right? And you can say it has one type, and it's like the Python object. Right? The Python object is passed around, and because there's only one type, it's implicit. Okay. And so what happens with Swift and Python talking to each other? Swift has lots of types. Right? It has arrays and it has strings and all the classes and that kind of stuff. But it now has Python object type. Right? So there is one Python object type. And so when you say import NumPy, what you get is a Python object, which is the NumPy module. And then you say NP.array. And it says, okay, hey Python object, I have no idea what you are. Give me your array member. Right? Okay, cool. It just uses dynamic stuff, talks to the Python interpreter, and says, hey Python, what's the .array member in that Python object? It gives you back another Python object. And now you say parentheses for the call and the arguments you can pass. And so then it says, hey, a Python object that is the result of np.array, call with these arguments. Right? And again, calling into the Python interpreter to do that work. And so right now, it's really simple. And if you dive into the code, what you'll see is that the Python module in Swift is something like 1,200 lines of code or something. It's written in pure Swift. It's super simple, and it's built on top of the C interoperability because it just talks to the Python interpreter. But making that possible required us to add two major language features to Swift to be able to express these dynamic calls and the dynamic member lookups. And so what we've done over the last year is we've proposed, implemented, standardized, and contributed new language features to the Swift language in order to make it so it is really trivial. Right? And this is one of the things about Swift that is critical to this Swift for TensorFlow work, which is that we can actually add new language features, and the bar for adding those is high, but it's what makes it possible.
So you're now at Google doing incredible work on several things, including TensorFlow. So TensorFlow 2.0, whatever leading up to 2.0, has default in 2.0 has eager execution. And yet, in order to make code optimized for GPU or some of these systems, computation needs to be converted to a graph. So what's that process like? What are the challenges there?
Yeah, so I'm tangentially involved in this, but the way that it works with autograph is that you mark your function with the decorator, and when Python calls it, the decorator is invoked, and it says, before I call this function, you can transform it. And so the way autograph works is, as far as I understand, is it actually uses the Python parser to go parse that, turn into a syntax tree, apply compiler techniques to, again, transform this down into TensorFlow graphs. And so you can think of it as saying, hey, I have an if statement. I'm going to create an if node in the graph. You say tf_con. You have a multiply. Well, I'll turn that into a multiply node in the graph, and it becomes this tree transformation.
So where does the Swift for TensorFlow come in? Which is, parallels. For one, Swift is an interface, like Python is an interface to TensorFlow. But it seems like there's a lot more going on than just a different language interface. There's optimization methodologies.
Yeah. So the TensorFlow world has a couple of different, what I'd call front end technologies. And so Swift and Python and Go and Rust and Julia and all these things share the TensorFlow graphs and all the runtime and everything that's later. And so Swift for TensorFlow is merely another front end for TensorFlow, just like any of these other systems are. There's a major difference between, I would say, three camps of technologies here. There's Python, which is a special case because the vast majority of the community efforts go to the Python interface. And Python has its own approaches for automatic differentiation, it has its own APIs, and all this kind of stuff. There's Swift, which we'll talk about in a second. And then there's kind of everything else. And so the everything else are effectively language bindings. So they call into the TensorFlow runtime, but they usually don't have automatic differentiation, or they usually don't provide anything other than APIs that call the C APIs in TensorFlow. So they're kind of wrappers for that. Swift is really kind of special. And it's a very different approach. Swift for TensorFlow then is a very different approach because there we're saying, let's look at all the problems that need to be solved in the full stack of the TensorFlow compilation process, if you think about it that way. Because TensorFlow is fundamentally a compiler. It takes models and then it makes them go fast on hardware. That's what a compiler does. It has a front end, it has an optimizer, and it has many backends. And so if you think about it the right way, or if you look at it in a particular way, like it is a compiler. Okay? And so Swift is merely another front end, but it's saying, and the design principle is saying, let's look at all the problems that we face as machine learning practitioners, and what is the best possible way we can do that, given the fact that we can change really anything in this inheritance stack. In Python, for example, where the vast majority of the engineering and effort is gone into, is constrained by being the best possible thing you can do with the Python library. Like, there are no Python language features that are added because of machine learning that I'm aware of. They added a matrix multiplication operator with that, but that's as close as you get. And so with Swift, it's hard, but you can add language features to the language, and there's a community process for that. And so we look at these things and say, well, what is the right division of labor between the human programmer and the compiler? And Swift has a number of things that shift that balance. So because because it has a type system, for example, it makes certain things possible for analysis of the code, and the compiler can automatically build graphs for you without you thinking about them. That's a big deal for a programmer. You just get free performance, you get clustering and fusion and optimization, things like that, without you as the programmer having to manually do it, because the compiler can do it for you. Automatic differentiation is another big deal, and it's, I think, one of the key contributions of the Swift for TensorFlow project is that there's this entire body of work on automatic differentiation that dates back to the Fortran days. People doing a tremendous amount of numerical computing in Fortran used to write these what they call source-to-source translators, where you take a bunch of code, shove it into a mini compiler, and it would push out more Fortran code, but it would generate the backwards passes for your functions for you, the derivatives. Right? And so in that work in the 70s, a tremendous number of optimizations, a tremendous number of techniques for fixing numerical instability and other kinds of problems were developed, but they're very difficult to port into a world where in eager execution you get an op by op at a time. Like you need to be able to look at the entire function and be able to reason about what's going on. And so when you have language integrated automatic differentiation, which is one of the things that the Swift project is focusing on, you can open all these techniques and reuse them in familiar ways. But the language integration piece has a bunch of design room in it, and it's also complicated.
The other puzzle here that's kind of interesting is TPUs that could be.
Yes.
So, we're in a new world with deep learning.
Yes.
It's constantly changing. And I imagine, without disclosing anything, I imagine, you're still innovating on the CPU front too.
Indeed.
So how much sort of interplay is there between software and hardware in trying to figure out how to together move towards an optimized solution?
There's an incredible amount. So we're on our third generation of TPUs, which are now 100 petaflops, very large, liquid-cooled box, virtual box, no cover. And as you might imagine, we're not out of ideas yet. The great thing about TPUs is that they're a perfect example of hardware-software co-design. And so it's about saying, what hardware do we build to solve certain classes of machine learning problems? Well, the algorithms are changing. Like the hardware takes, in some cases years to produce, right? And so you have to make bets and decide what is going to happen. And so, and what is the best way to spend the transistors to get the maximum, performance per watt or area per cost or like whatever it is that you're optimizing for. And so one of the amazing things about TPUs is this numeric format called bfloat16. bfloat16 is a compressed 16-bit floating point format, but it puts the bits in different places. In numeric terms, it has a smaller mantissa and a larger exponent. That means that it's less precise, but can represent larger ranges of values, which in the machine learning context is really important and useful because sometimes you have very small gradients that want to accumulate and very, very small numbers that are important to move things as you're learning, but sometimes you have very large magnitude numbers as well. And bfloat16 is not as precise, it's so small, but it turns out the machine learning algorithms actually want to generalize. And so there's theories that this actually increases the ability for the network to generalize across data sets. And regardless of whether it's bad, it's much cheaper at the hardware level to implement because the area and time of a multiplier is n squared the number of bits in the mantissa, but it's linear with the size of the exponent.
And you're connected to both efforts here, both on the hardware and the software side?
Yeah, and so that was a breakthrough coming from the research side and people working on optimizing network transport of weights across the network originally and trying to find ways to compress that. But then it got burned into silicon, and it's a key part of what makes TPU performance so amazing and great. Now, TPUs have many different aspects that are important, but the co-design between the low-level compiler bits and the software bits and the algorithms is all super important. And it's this amazing trifecta that only Google can do.
Yeah, that's super exciting. So can you tell me about MLIR project, previously the secretive one?
Yeah, so MLIR is a project that we announced at a compiler conference 3 weeks ago or something, at the Compilers for Machine Learning Conference. Basically, again, if you look at TensorFlow as a compiler stack, it has a number of compiler algorithms within it. It also has a number of compilers that get embedded into it, and they're made by different vendors. For example, Google has XLA, which is a great compiler system. NVIDIA has TensorRT. Intel has ngraph. There's a number of these different compiler systems, and they're very hardware specific, and they're trying to solve different parts of the problems. But they're all kind of similar in a sense if they want to integrate with TensorFlow. Now, TensorFlow has an optimizer, and it has these different code generation technologies built in. The idea of MLIR is to build a common infrastructure to support all these different subsystems. And initially, it's to be able to make it so that they all plug in together and they can share a lot more code and can be reusable. But over time, we hope that the industry will start collaborating and sharing code, and instead of reinventing the same things over and over again, that we can actually foster some of that working together to solve common problem energy that has been useful in the compiler field before. Beyond that, MLR is, some people have joked that it's kind of LLVM 2. It learns a lot about what LLVM has been good and what LLVM has done wrong, and it's a chance to fix that. And also, there are challenges in the LLVM ecosystem as well, where LLVM is very good at the thing it was designed to do, but 20 years later, the world has changed, and people are trying to solve higher level problems, and we need some new technology.
And what's the future of open source in this context?
Very soon. So it is not yet open source, but it will be hopefully.
You still believe in the value of open source as kinds of
Oh yeah, absolutely. And I think that the TensorFlow community at large fully believes in open source.
So I mean, that's there is a difference between Apple, where you were previously, and Google now, in spirit and culture. And I'd say the open source of TensorFlow was a seminal moment in the history of software, because here's this large company releasing a very large code base as open sourcing. What are your thoughts on that? How happy or not were you to see that kind of degree of open sourcing?
So between the two, I prefer the Google approach, if that's what you're saying. The Apple approach makes sense given the historical context that Apple came from, but that's been 35 years ago. And I think that Apple is definitely adapting. And the way I look at it is that there's different kinds of concerns in the space, right? It is very rational for a business to care about making money. That fundamentally is what business is about, right? But I think it's also incredibly realistic to say it's not your string library that's the thing that's going to make you money. It's going to be the amazing UI, product differentiating features, and other things like that you built on top of your string library. And so keeping your string library proprietary and secret and things like that is maybe not the important thing anymore, right? Or before, platforms were different, right? And even 15 years ago, things were a little bit different. But the world is changing. So Google strikes a very good balance, I think. And I think that TensorFlow being open source really changed the entire machine learning field, and it caused a revolution in its own right. And so I think it's amazingly forward-looking, because I could have imagined, I wasn't at Google at the time, but I could imagine a different context in a different world where a company says, machine learning is critical to what we're doing, we're not going to give it to other people, right? And so that decision is a profoundly brilliant insight that I think has really led to the world being better, and better for Google as well.
And has all kinds of ripple effects. I think it is really, I mean, you can't understate Google deciding that, how profound that is for software. It's awesome.
Well, and it's been, and again, I can understand the concern about if we release our machine learning software, our competitors could go faster. On the other hand, I think that open source TensorFlow has been fantastic for Google, and I'm sure that obviously that decision was very non-obvious at the time, but I think it's worked out for him.
So let's try this real quick.
Yeah.
You were at Tesla for 5 months as the VP of Autopilot Software. You led the team during the transition from hardware 1 to hardware 2. I have a couple questions. So one, first of all, to me, that's one of the bravest engineering decisions undertaken really ever in the automotive industry, to me, software-wise, starting from scratch. It's a really brave decision. So my one question is, what was that like? What was the challenge of that?
Do you mean the career decision of jumping from a comfortable, good job into the unknown, or
that combined, so at the individual level, you making that decision, and then when you show up, it's a really hard engineering process.
Yes.
So you could just stay, maybe slow down, say hardware 1, or those kinds of decisions. So just taking it full on. Let's do this from scratch. What was that like?
Well, so I mean, I don't think Tesla has a culture of taking things slow and seeing how it goes. So And one of the things that attracted me about Tesla is it's very much a gung-ho, let's change the world, let's figure it out kind of place. And so I have a huge amount of respect for that. Tesla has done very smart things with Hardware 1 in particular, and the Hardware 1 design was originally designed to be very simple automation features in the car for like traffic-aware cruise control and things like that. And the fact that they were able to effectively feature creep it into lane holding and a very useful driver assistance feature is pretty astounding, particularly given the details of the hardware. Hardware 2 built on that in a lot of ways. And the challenge there was that they were transitioning from a third-party provided vision stack to an in-house built vision stack. And so for the first step, which I mostly helped with, was getting onto that new vision stack. And that was very challenging. And it was time critical for various reasons, and it was a big leap, but it was fortunate that it built on a lot of the knowledge and expertise and the team that had built Hardware 1's driver assistance features.
So you spoke in a collected and kind way about your time at Tesla, but it was ultimately not a good fit. Elon Musk, we've talked on this podcast, we guessed the course. Elon Musk continues to do some of the most bold and innovative engineering work in the world, at times at the cost of some of the members of the Tesla team. What did you learn about this working chaotic world with Elon?
Yeah, so I guess I would say that when I was at Tesla, I experienced and saw the highest degree of turnover I'd ever seen in a company, which was a bit of a shock. But one of the things I learned and I came to respect is that Elon's able to attract amazing talent because he has a very clear vision of the future, and he can get people to buy into it because they want that future to happen. Right? And the power of vision is something that I have a tremendous amount of respect for. And I think that Elon is fairly singular in the world in terms of the things he's able to get people to believe in. And there may be people who stand on the street corner and say, we're going to go to Mars, right? But then there are a few people that can get others to buy into it and believe and build the path and make it happen. And so I respect that. I don't respect all of his methods, but I have a huge amount of respect for that.
You've mentioned in a few places, including in this context, working hard. What does it mean to work hard? When you look back at your life, what were some of the most brutal periods of having to really put everything you have into something?
Yeah, good question. So working hard could be defined a lot of different ways. So a lot of hours, and so that is true. The thing to me that's the hardest is both being short-term focused on delivering and executing and making a thing happen, while also thinking about the longer term and trying to balance it, right? Because if you are myopically focused on solving a task and getting that done, and only think about that incremental next step, you will miss the next big hill you should jump over to, right? And so I've been really fortunate that I've been able to kind of oscillate between the two. And historically at Apple, for example, that was made possible because I was able to work with some really amazing people and build up teams and leadership structures and allow them to grow in their careers and take on responsibility, thereby freeing up me to be able to crazy and think about the next thing. And so it's a lot of that. It's also about, with experience, you make connections that other people don't necessarily make. So I think that's a big part as well. But bedrock is just a lot of hours, and that's okay. There's different theories on work-life balance, and my theory for myself, which I do not project onto the team, but my theory for myself is that I want to love what I'm doing and work really hard, and my purpose, I feel like, my goal is to change the world, make it a better place, and that's what I'm really motivated to do.
So last question. LLVM logo is a dragon.
Yeah.
You explained that this is because dragons have connotations of power, speed, intelligence. It can also be sleek, elegant, and modular, though you move the modular part. What is your favorite dragon-related character from fiction, video, or movies?
So those are all very kind ways of explaining it. Do you want to know the real reason it's a dragon?
Well, yeah.
Is that better? So there's a seminal book in compiler design called The Dragon Book. And so this is a really old book on compilers. So the Dragon logo for LLVM came about because at Apple we kept talking about LLVM related technologies and there was no logo to put on a slide. And so we're like, what do we do? And somebody's like, well, what kind of logo should a compiler technology have? And I'm like, I don't know. I mean, the dragon is the best thing that we've got. And you know, Apple somehow magically came up with the logo, and it was a great thing, and the whole community rallied around it, and then it got better as other graphic designers got involved. But that's originally where it came from.
Story. Is there a dragon fiction that you connect with? For Game of Thrones, Lord of the Rings, that kind of thing.
Lord of the Rings is great. I also like role-playing games and things like computer role-playing games, as the dragons often show up in there. But really comes back to the book. Oh no, we need a thing. You know, yeah. And hilariously, one of the funny things about LLVM is that my wife is amazing, runs the LLVM Foundation, and she goes to Grace Hopper and is trying to get more women involved in the. She's also a compiler engineer, so she's trying to get other women to get interested in compilers and things like this. And so she hands out the stickers, and people like the LLVM sticker because of Game of Thrones. And so sometimes culture has this helpful effect to like get the next generation compiler engineers engaged with the cause.
Okay, awesome. Chris, thanks so much for talking.
It's been great talking with you.
The following is a conversation with Raja Monga. He's an engineer and director at Google, leading the TensorFlow team. TensorFlow is an open source library at the center of much of the work going on in the world of deep learning, both the cutting edge research and the large scale application of learning based approaches. But it's quickly becoming much more than a software library. It's now an ecosystem of tools for the deployment of machine learning in the cloud, on the phone, in browser, on both generic and specialized hardware, GPU, GPU, and so on. Plus, there's a big emphasis on growing a passionate community of developers. Raja, Jeff Dean, and a large team of engineers at Google Brain are working to define the future of machine learning with TensorFlow 2.0, which is now in alpha. I think the decision to open source TensorFlow was a definitive moment in the tech industry. It showed that open innovation is successful and inspired many companies to open source their code, to publish, and in general engage in the open exchange of ideas. This conversation is part of the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, iTunes, or simply connect with me on Twitter at Lex Friedman, spelled F-R-I-D. And now, here's my conversation with Raja Monga. You were involved with Google Brain since its start in 2011 with Jeff Dean. It started with this belief, the proprietary machine learning library, and turned into TensorFlow in 2014, the open source library. So what were the early days of Brain like? What were the goals, the missions? How do you even proceed forward once there's so much possibilities before you?
It was interesting back then, when I started, when you were even just talking about it. The idea of deep learning was interesting and intriguing in some ways. It hadn't yet taken off, but it held some promise. It showed some very promising and early results. I think the idea that Andrew and Jeff had started was, what if we can take this, what people are doing in research, and scale it to what Google has in terms of compute power, and so put that kind of data together. What does it mean? And so far, the results have been, if you scale the compute, scale the data, it does better, and it might work. And so that was the first year to, can we prove that out? And with this, when we started the first year, we got some early wins, which is always great.
What were the wins like? What was the wins where you were, there's some promise to this is going to be good?
I think that two early wins were, one was speech, that we collaborated very closely with the speech research team who was also getting interested in this. And the other one was images where the cat paper, as we call it, that was covered by a lot of folks.
And Earth of program was around neural networks. It was deep learning from the very beginning. That was the whole mission.
Yep.
So what would, in terms of scale, what was the sort of dream of what this could become? Like, were there echoes of this open source TensorFlow community that might be brought in? Was there a sense of TPUs? Was there a sense of like machine learning is now going to be at the core of the entire company? Is going to grow into that direction?
Yeah, I think so. So that was interesting. And like, if I think back to 2012, and first was, can we scale it? In a year or so, we had started scaling it to hundreds and thousands of machines. So in fact, we had some ones even going to 10,000 machines, and all of those shows great promise. In terms of machine learning at Google, the good thing was Google's been doing machine learning for a long time. Deep learning was new, but as we scaled this up, we showed that yes, that was possible, and it was going to impact lots of things. Like, we started seeing real projects wanting to use this. Again, speech was the first. There were image things that photos came out of, and many other products as well. So that was exciting. As we went into that a couple of years, externally also, actually, I started to, there was lots of push on, okay, deep learning is interesting, we should be doing more, and so on. And so by 2014, we were looking at, okay, this is a big thing, it's going to grow, and not just internally, externally as well. Yes, maybe Google's ahead of where everybody is, but there's a lot to do. So a lot of this started to make sense and come together.
So the decision to open source, I was just chatting with Chris Gladner about this. The decision to open source for TensorFlow, I would say, so for me personally, seems to be one of the big seminal moments in all of software engineering ever. I think that's when a large company like Google decides to take a large project that many lawyers might argue has a lot of IP, just decide to go open source with it, and then so to lead the entire world and say, you know what, open innovation is a pretty powerful thing, and it's okay to do. That was, I mean, that's an incredible moment in time. So do you remember those discussions happening? Whether open source should be happening? What was that like?
I would say, I think, so the initial idea came from Jeff, who was a big proponent of this. I think it came off of two big things. One was research-wise, we were a research group. We were putting our research out there. We were building on all this research, and we wanted to push the state-of-the-art forward. And part of that was to share the research. That's how I think deep learning and machine learning has really grown so fast. So the next step was, okay, now would software help with that? And it seemed like there were existing a few libraries out there, Tiani being one, Torch being another, and a few others, but they were all lagging, and so the level was significantly different. The other one was, from a software perspective, Google had done lots of software that we used internally, and we published papers. Often there was an open source project that came out of that somebody else picked up that paper and implemented, and they were very successful. Back then, it was like, okay, there's Hadoop, which has come off of tech that we built. We know the tech we built is way better for a number of different reasons. We've invested a lot of effort in that. And turns out we have Google Cloud, and we are now not really providing our tech, but we are saying, okay, we have Bigtable, which is the original thing. We're going to now provide HPC APIs on top of that, which isn't as good, but that's what everybody's used to. So there's like, can we make something that is better and really just provide? Helps the community in lots of ways, but also helps push a good standard forward.
So how does cloud fit into that? There's a TensorFlow open source library, and how does the fact that you can use some of the resources that Google provides in the cloud fit into that strategy?
So TensorFlow itself is open. You can use it anywhere, right? And we want to make sure that continues to be the case. On Google Cloud, we do make sure that there's lots of integration with everything else, and we want to make sure that it works really, really well there.
you're leading the TensorFlow effort. Can you tell me the history of the timeline of TensorFlow project in terms of major design decisions, so like open source decision, but really, what to improve and not. There's this incredible ecosystem that I'd like to talk about. There's all these parts, but what if just some sample moments that defined what TensorFlow eventually became through its. I don't know if you're allowed to say history when it's just, but in deep learning everything moves so fast and just a few years is already history.
Yes. So looking back, we were building TensorFlow. I guess we open sourced it in 2015, November 2015. We started on it in summer of 2014, I guess. And somewhere like mid 2014, by then we decided that, okay, there's a high likelihood to open source it. So we started thinking about that and making sure we're heading down that path. At that point, by that point, we'd seen a few, lots of different use cases at Google. So there were things like, okay, yes, we want to run it at large scale in the data center. Yes, we need to support different kind of hardware. We had GPUs at that point. We had our first CPU at that point was about to come out, roughly around that time. So design included those. We had started to push on mobile, so we were running models on mobile. At that point, people were customizing code, so we wanted to make sure TensorFlow could support that as well, so that sort of became part of that overall design.
When you say mobile, you mean like a pretty complicated algorithm running on the phone?
That's correct. So when you have a model that you deploy on the phone and run it there, right?
So already at that time, there was ideas of running machine learning on the phone.
That's correct. We already had a couple of products that we do. And in those cases, you might basically customize and crafted code or some internal libraries that we use.
So I was actually at Google during this time, parallel with this universe, but we were using Piano and Cafe. Was there some degree to which you were balancing, like trying to see what Cafe was offering people, trying to see what Piano was offering, that you want to make sure you're delivering on whatever that is? Perhaps the Python thing, maybe did that influence any design decisions?
Totally. So when we built this belief, and some of that was in parallel with some of these libraries coming up, and Piano itself is older, but we were building this belief focused on our internal things because our systems were very different. By the time we got to this, we looked at a number of libraries that were out there. Piano, there were folks in the group who had experience with Torch, with Lua. There were folks here seeing Cafe. I mean, actually, Yanqing was here as well. There's what other libraries? I think we looked at a number of things. Might even have looked at Chainer back then and trying to remember if it was there. In fact, we did discuss ideas around should we have a graph or not. And they were so putting all these together was definitely, there were key decisions that we wanted. We had seen limitations in our prior disbelief things. A few of them were just in terms of research was moving so fast. We needed the flexibility. We want the hardware was changing fast. We expected to change that. So those probably were two things. And yeah, I think the flexibility in terms of to express all kinds of crazy things was definitely a big one.
So what the graph decisions? So now with moving towards TensorFlow 2.0, there's more by default it'll be eager execution. So sort of hiding the graph a little bit, because it's less intuitive in terms of the way people develop and so on. Well, what was that discussion like in terms of using graphs? It seemed it's kind of the Theano way. Did it seem the obvious choice?
So I think where it came from was our this belief had a graph-like thing as well. A much more simple. It wasn't a general graph. It was more like a straight line, thing. More like you might think of Cafe, I guess, in that sense. But the graph was, and we always cared about the production stuff. Like even with this, if you would apply a whole bunch of stuff in production. So graph did come from that when we thought of, okay, should we do that in Python? And we experimented with some ideas where it looked a lot simpler to use, but not having a graph print okay, how do you deploy now? So that was probably what tilted the balance for us and eventually ended up with a graph.
And I guess the question there is, did you? I mean, production seems to be a really good thing to focus on. But did you even anticipate the other side of it, where there could be what are the numbers? Something crazy, 41 million downloads.
Yep.
So, I mean, was that even like a possibility in your mind that it would be as popular as it became?
So I think we did see a need for this a lot from the research perspective and like early days of deep learning. Some is 41 million. I don't think I imagine this number. Then it seemed like there's a potential future where lots more people will be doing this, and how do we enable that? I would say this kind of growth probably started somewhat after the open sourcing, where it was like, okay, deep learning is actually growing way faster for a lot of different reasons, and we are in just the right place to push on that and leverage that and deliver on lots of things that people want.
So what changed with the open source? Like how, this incredible amount of attention from a global population of developers, how did the project start changing? I know you actually remember it during those times. I know looking now, there's really good documentation. There's an ecosystem of tools. There's a community. There's a YouTube channel now, right?
Yeah.
It's very, very community driven. Back then, I guess 0.1 version. Is that the version?
I think we call it 0.6 or 5, something like that. I forget about that.
What changed leading into 1.0?
It's interesting. I think we've gone through a few things there. When we first came out, people loved the documentation we have because it was just a huge step up from everything else. Because all of those were academic projects, people doing, who don't think about documentation. I think what that changed was instead of deep learning being a research thing, some people who were just developers could now suddenly take this out and do some interesting things with it, right? Who had no clue what machine learning was before then. And that, I think, really changed how things started to scale up in some ways and pushed on it. Over the next few months, as we looked at how do we stabilize things, as we look at not just researchers, now we want stability, people want to deploy things. That's how we started planning for the motto. And there are certain needs for that perspective. And so again, documentation comes up, designs, more kinds of things to put that together. And so that was exciting to get that to a stage where more and more enterprises wanted to buy in and really get behind that. And I think post 1.0 and over the next few releases, that enterprise adoption started to take off. I would say between the initial release and 1.0, it was, okay, researchers, of course, then a lot of hobbyists and early interest, people excited about this who started to get on board. And then over the 1.x thing, lots of enterprises.
I imagine anything that's, below 1.0 gets pressure to be, enterprise probably wants something that's stable.
Exactly.
And do you have a sense now the TensorFlow is state? Like it feels like deep learning in general is extremely dynamic field. So much is changing. Do you have TensorFlow has been growing incredibly. Do you have a sense of stability at the helm of it? I know you're in the midst of it, but
yeah, it's. I think in the midst of it, it's often easy to forget what an enterprise wants and what some of the people on that side want. There's still people running models that are 3 years old, 4 years old. So Inception is still used by tons of people. Even ResNet 50 is a couple of years old now or more. But there are tons of people who use that and they're fine. They don't need the last couple of bits of performance or quality. They want some stability and things that just work. And so there is value in providing that with that kind of stability and making it really simple because that allows a lot more people to access it. And then there's the research crowd, which wants, okay, I want to do these crazy things exactly like you're saying, right? Not just deep learning in the straight up models that used to be there, they want RNNs, and even RNNs are maybe old. They are transformers now, and now it needs to combine with RL and hands and so on. So there's definitely that area that like the boundary that's shifting and pushing the state of the art. But I think there's more and more of the past that's much more stable, and even stuff that was 2 3 years old is very very usable by lots of people. So that part makes it a little easier.
So I imagine, maybe correct me if I'm wrong, one of the biggest use cases is essentially taking something like ResNet 50 and doing some kind of transfer learning on a very particular problem that you have. But it's basically probably what majority of the world does. And you want to make that as easy as possible.
That's right. So I would say, for the hobbyist perspective, that's the most common case, right? In fact, the apps and phones and stuff that you'll see, the early ones, that's the most common case. I would say there are a couple of reasons for that. One is that everybody talks about that. It looks great on slides.
Yeah.
That's a part of the presentation. Yeah, exactly. What enterprises want is that is part of it, but that's not the big thing. Enterprises really have data that they want to make predictions on. This is often what they used to do. The people who were doing ML was just regression models, linear regression, logistic regression, linear models, or maybe gradient boosted trees and so on. Some of them still benefit from deep learning, but they weren't that's the bread and butter, like the structured data and so on. So depending on the audience, they're a little bit different.
And they just have, I mean, the best of enterprise probably just has a very large data set where deep learning can probably shine.
That's correct. Right. And then I think the other pieces that they want, again, with 2.0 or the developer summit we put together is the whole TensorFlow extended piece, which was the entire pipeline. They care about stability across the entire thing. They want simplicity across the entire thing. I don't need to just train a model. I need to do that every day, again, over and over again.
I wonder to which degree you have a role in, I don't know, so I teach a course on deep learning. I have people like lawyers come up to me and say, say, when is machine learning going to enter the legal realm? The same thing in all kinds of disciplines. Immigration, insurance. Often when I see what it boils down to is these companies are often a little bit old school in the way they organize the data. So the data is just not ready yet. It's not digitized. Do you also find yourself being in the role of an evangelist for let's organize your data, folks, and then you'll get the big benefit of TensorFlow? Do you have those conversations?
So yeah. I get all kinds of questions there from, okay, what do I need to make this work, right? To any deep learning, I mean, there are all these things. I already use this linear model. Why would this help? I don't have enough data, let's say, or I want to use machine learning, but I need to where to start. So it varies back to all the way to the for very specific things. So it's interesting.
Is there a good answer? It boils down to oftentimes digitizing data. So whatever you want automated, whatever data you want to make prediction based on, you have to make sure that it's organized one. Like with the TensorFlow ecosystem, you're providing more and more data sets and more pre-trained models. Are you finding yourself also the organizer of data sets?
Yes, I think the TensorFlow data sets that we just released, that's definitely come up where people want these data sets. Can we organize them and can we make that easier? So that's definitely one important thing. The other related thing I would say is I often tell people, you know what, don't think of the fanciest thing, that the newest model that you see. Make something very basic work and then you can improve it. There's just lots of things you can do with it.
Yeah, start with the basics. One of the big things that makes TensorFlow even more accessible was the appearance, whenever that happened, of Keras, the Keras standard, outside of TensorFlow. I think it was Keras on top of Piano first only, and then Keras on top of TensorFlow. Do you know when Keras chose to also add TensorFlow as a backend? Was it just the community that drove that initially? Do you know if there was discussions, conversation?
Yeah, so Francois started his project before he was at Google, and the first thing was Theano. I don't remember if that was after TensorFlow was created or way before. And then at some point, when TensorFlow started becoming popular, there were enough similarities that we decided to create this interface and put TensorFlow as a backend. I believe that might still have been before he joined Google, so we weren't really talking about that. He decided on his own and thought that it was interesting and relevant to the community. In fact, I didn't find out about him being at Google until a few months after he was here. He was working on some research ideas and doing Keras on his nights and weekends project and stuff.
Oh, interesting. So he wasn't like part of the TensorFlow. He didn't join
He
initially.
joined research and he was doing some amazing research. He has some papers on that and research. So he's a great researcher as well. And at some point, people realized, oh, he's doing this good stuff. People seem to like the API and he's right here. So we talked to him and he said, okay, why don't I come over to our team and work with you for a quarter and let's make that integration happen. And we talked to him and he said, sure, like a quarter's fine. And that quarter's been something like 2 years now. And so he's fully on this.
So Keras got integrated into TensorFlow like in a deep way. And now with 2.0, TensorFlow 2.0, sort of Keras is kind of the recommended way for a beginner to interact with TensorFlow, which makes that initial sort of transfer learning or the basic use cases, even for enterprise, super simple, right?
That's right.
So what was that decision like? It was like
What'd you
spend
say?
a lot of time thinking about that one. We had some big
What'd you
bias.
say?
There was a parallel layers API.
I love you too, big dog.
We decided to create Keras in parallel, so there were like things that we are looking at. And the first thing we was trying to do is just have them look similar, like be as integrated as possible, share all of that stuff. There were also like 3 other APIs that others had built over time because we didn't have a standard one. But one of the messages that we kept hearing from the community, okay, which one do we use? And they kept saying like, okay, here's a model in this one, and here's a model in this one, and should I pick? So that's sort of like, okay, we had to address that straight on with 2.0. The whole idea was we need to simplify. We had to pick one. Based on where we were like, okay, let's see what do the people like. And Keras was clearly one that lots of people loved. There were lots of great things about it. So we settled on that.
organically. That's kind of the best way to do it. It was great. It was surprising, nevertheless, to sort of bring in an outside. I mean, there was a feeling like Keras might be almost like a competitor. It's a certain kind of a TensorFlow, and in a sense, it became an empowering element of TensorFlow.
That's right. Yeah, it's interesting how you can put two things together which can align. And in this case, I think Francois, the team, and I, a bunch of us have chatted, and I think we all want to see the same kind of things. We all care about making it easier for the huge set of developers out there, and that makes a difference.
So Python has Guido van Rossum, who until recently held the position of benevolent dictator for life. Right. So does a huge, successful open source project like TensorFlow need one person who makes a final decision? So you did a pretty successful TensorFlow Dev Summit just now, the last couple of days. There's clearly a lot of different new features that be incorporated, amazing ecosystem, so on. How are those design decisions made? Is there a BDFL in TensorFlow, and or is it more distributed and organic?
I think it's somewhat different. I would say I've always been involved in the key design directions, but there are lots of things that are distributed where there are a number of people, Martin Wick being one, who's really driven a lot of our open source stuff, a lot of the APIs, and there are a number of other people who've been, pushed and been responsible for different parts of it. We do have regular design reviews. Over the last year, we've really spent a lot of time opening up to the community and adding transparency, setting more process in place. So RFCs, special interest groups, really grow that community and scale that. I think the kind of scale that ecosystem is in, I don't think we could scale with having me as the sole point of decision maker. So
I got it. So,
yeah.
the growth of that ecosystem. Maybe you can talk about it a little bit. First of all, when it started with Andre Karpathy when he first did ComNet.js, the fact that you can train in neural network in the browsers in JavaScript was incredible.
Yep.
So now TensorFlow.js is really making that a serious, like a legit thing, a way to operate, whether it's in the back end or the front end. Then there's the TensorFlow Extended, like you mentioned. There's TensorFlow Lite for mobile. And all of it, as far as I can tell, it's really converging towards being able to, save models in the same kind of way you can train on the desktop and with mobile and so on. Like there's that. Cool. So,
How you living,
maybe
Bim?
give me whatever I missed.
Hello.
Overview of the mission
How'd you
of
find
the
out about
ecosystem
me?
that's trying to be built and where's it moving?
So in short,
Excellent.
the way I like to think of this is
We're watching a
our goals
podcast.
to
Feel free to enjoy.
And one is we
Okay.
have lots of exciting things going on in ML. We started with deep learning, but we now support a bunch of other algorithms too. So one is to, on the research side, keep pushing on the state of the art. And how do we enable researchers to build the next amazing thing? So BERT came out recently. It's great that people are able to do new kinds of research. And there are lots of amazing research that happens across the world. So that's one direction. The other is, how do you take that across all the people outside who want to take that research and do some great things with it and integrate it to build real products to have a real impact on people. And sort of that's the other axis in some ways. At a high level, one way I think about it is there are a crazy number of compute devices across the world. And we often used to think of ML and training and all of this as, okay, something we do either in the workstation or the data center or cloud. But we see things running on the phones, we see things running on really tiny chips, and we had some demos at the Developer Summit. And so the way I think about this ecosystem is, how do we help get machine learning on every device that has the compute capability? And that continues to grow. And so in some ways, this ecosystem is looked at various aspects of that and grown over time to cover more of those, and we continue to push the boundaries. In some areas, we built more tooling and things around that to help you. And the first tool we started was TensorBoard. You wanted to learn just the training piece. TFX or TensorFlow Extended to really do your entire ML pipelines if you're care about all that production stuff. But then going to the edge, going to different kinds of things. And it's not just us. We're a place where there are lots of libraries being built on top. So there's some for research, maybe things like TensorFlow agents or TensorFlow probability that started as research things, or for researchers for focusing on certain kinds of algorithms. They're also being deployed or used by production folks. And some have come from within Google, just teams across Google who wanted to build these things. Others have come from just the community, because there are different pieces that different parts of the community care about. And I see our goal as enabling even that, right? It's not, we cannot and won't build every single thing. That just doesn't make sense. But if we can enable others to build the things that they care about, and there's a broader community that cares about that, and we can help encourage that, and that's great. It really helps the entire ecosystem, not just those. One of the big things about 2.0 that we're pushing on is, okay, we have these so many different pieces, right? How do we help make all of them work well together? So there are a few key pieces there that we're pushing on. One being the core format, and then how we share the models themselves through Save Model and TensorFlow Hub and so on. And a few of the pieces that we really put this together.
I was very skeptical that that's, when TensorFlow JS came out, I didn't see, or Deep Learning JS
Yeah, that was first.
it seemed like technically a very difficult project. As a standalone, it's not as difficult, but as a thing that integrates into the ecosystem, it's very difficult. So, I mean, there's a lot of aspects of this you're making look easy, but on the technical side, how many challenges have to be overcome here?
A lot.
And still have to be overcome.
Yes,
That's
yes.
the question here, too.
There are lots of steps to it, right? And we've iterated over the last few years, so there's a lot we've learned. And often when things come together well, things look easy, and that's exactly the point. It should be easy for the end user, but there are lots of things that go behind that. If I think about still challenges ahead, there are, we have a lot more devices coming on board, for example, from the hardware perspective. How do we make it really easy for these vendors to integrate with something like TensorFlow, right? So there's a lot of compiler stuff that others are working on. There are things we can do in terms of our APIs and so on that we can do. As we, TensorFlow started as a very monolithic system, and to some extent it still is. There are lots of tools around it, but the core is still pretty large and monolithic. One of the key challenges for us to scale that out is how do we break that apart with clearer interfaces. It's, in some ways it's software engineering 101, but for a system that's now 4 years old, I guess, or more, and that's still rapidly evolving and that we're not slowing down with, it's hard to change and modify and really break apart. It's sort of like, as people say, right? It's like changing the engine with the car running, or kind of that. That's exactly what we're trying to do.
So there's a challenge here because the downside of so many people being excited about TensorFlow and coming to rely on it in many of their applications is that you're kind of responsible. Like it's the technical debt. You're responsible for previous versions to some degree still working. So when you're trying to innovate, I mean, it's probably easier to just start from scratch every few months.
Absolutely.
So do you feel the pain of that? 2.0 does break some back compatibility, but not too much. It seems like the conversion is pretty straightforward. Do you think that's still important given how quickly deep learning is changing? Can you just the things that you've learned, can you just start over, or is there pressure to not?
It's a tricky balance. So if it was just a researcher writing a paper who a year later will not look at that code again, sure, it doesn't matter. There are a lot of production systems that rely on TensorFlow, both at Google and across the world. And people worry about this. I mean, these systems run for a long time. So it is important to keep that compatibility and so on. And yes, it does come with a huge cost. We have to think about a lot of things as we do new things and make new changes. I think it's a trade-off, right? You might slow certain kinds of things down, but the overall value you're bringing because of that is much bigger, because it's not just about making the person yesterday. It's also about telling the person tomorrow that, you know what, this is how we do things. We're not going to take you when you come on board, because there are lots of new people who are also going to come on board. One way I like to think about this, and I always push the team to think about it as well, when you want to do new things, you want to start with a clean slate. Design with a clean slate in mind, and then we'll figure out how to make sure all the other things work. And yes, we do make compromises occasionally, but unless you design with the clean slate and not worry about that, you will never get to a good place.
Oh, that's brilliant. So even if you are responsible when you in the idea stage, when you're thinking of new, and just put all that behind you. Okay. That's really, really well put. So I have to ask this because a lot of students, developers ask me how I feel about PyTorch versus TensorFlow. So I've recently completely switched my research group to TensorFlow. I wish everybody would just use the same thing, and TensorFlow is as close to that, I believe, as we have. But do you enjoy competition? So TensorFlow is leading in many ways, many dimensions in terms of ecosystem, in terms of number of users, momentum, power, production level, so on. But a lot of researchers are now also using PyTorch. Do you enjoy that kind of competition, or do you just ignore it and focus on making TensorFlow the best that it can be?
So just like research or anything people are doing, right, it's great to get different kinds of ideas. And when we started with TensorFlow, like I was saying earlier, it was very important for us to also have production in mind. We didn't want just research, right? And that's why we chose certain things. Now, PyTorch came along and said, you know what, I only care about research. This is what I'm trying to do. What's the best thing I can do for this? And it started iterating and said, okay, I don't need to worry about graphs. Let me just run things. I don't care if it's not as fast as it can be, but let me just make this part easy. And there are things you can learn from that, right? They again had the benefit of seeing what had come before, but also exploring certain different kinds of spaces, and they had some good things there, building on, say, things like Chainer and so on before that. So competition is definitely interesting. It made us, this is an area that we had thought about, like I said, way early on. Over time, we had revisited this a couple of times. Should we add this again? At some point, we said, you know what? It seems like this can be done well, so let's try it again. And that's how we started pushing on eager execution. How do we combine those together, which has finally come very well together in 2.0, but it took us a while to get all the things together and so on.
So let me ask, put another way, I think eager execution is a really powerful thing that was added. Do you think it wouldn't have been Muhammad Ali versus Frazier, right? Do you think it wouldn't have been added as quickly if PyTorch wasn't there?
It might have taken longer. Yeah, it was. I mean, we had tried some variants of that before, so I'm sure it would have happened, but it might have been.
I'm grateful that TensorFlow is sprouting the way they did. It's doing some incredible work last couple of years. What other things that we didn't talk about are you looking forward in 2.0? That comes to mind. So we talked about some of the ecosystem stuff, making it easily accessible to Keras, eager execution. Is there other things that we missed?
Yeah, so I would say one is just where 2.0 is, and with all the things that we've talked about. I think as we think beyond that, there are lots of other things that it enables us to do, and that we're excited about. So what it's setting us up for, okay, here are these really clean APIs. We've cleaned up the surface for what the users want. What it also allows us to do a whole bunch of stuff behind the scenes once we are ready with 2.0. So, for example, in TensorFlow with graphs and all the things you could do, you could always get a lot of good performance if you spent the time to tune it, right? And we've clearly shown that. Lots of people do that. With 2.0, with these APIs, there we can give you a lot of performance just with whatever you do. Because we see these, it's much cleaner. We know most people are going to do things this way. We can really optimize for that and get a lot of those things out of the box. And it really allows us, both for single machine and distributed and so on, to really explore other spaces behind the scenes after 2.0 and the future versions as well. So right now the team's really excited about that. And over time, I think we'll see that. The other piece that I was talking about in terms of just restructuring the monolithic thing into more pieces and making it more modular, I think that's going to be really important for a lot of the other people in the ecosystem, other organizations and so on that want to build things.
Can you elaborate a little bit what you mean by making TensorFlow more ecosystem more modular?
So the way it's organized today is there are lots of repositories in the TensorFlow organization at GitHub. The core one where we have TensorFlow, it has the execution engine, it has the key backends for CPUs and GPUs, it has the work to do distributed stuff, and all of these just work together in a single library or binary. There's no way to split them apart easily. I mean, there are some interfaces, but they're not very clean. In a perfect world, you would have clean interfaces where, okay, I want to run it on my fancy cluster with some custom networking, just implement this and do that. I mean, we kind of support that, but it's hard for people to. I think as we are starting to see more interesting things in some of these spaces, having that clean separation will really start to help. And again, going to the large size of the ecosystem and the different groups involved there, enabling people to evolve and push on things more independently just allows it to scale better.
And by people, you mean individual developers and
organizations.
That's right. So the hope is that every sort of major, I don't know, Pepsi or something uses, like major corporations go to TensorFlow, do this kind of.
Yeah, if you look at enterprises like Pepsi or these, a lot of them are already using TensorFlow. They are not the ones that do the development or changes in the code. Some of them do, but a lot of them don't. I mean, they touch small pieces. There are lots of these, some of them being, let's say, hardware vendors who are building their custom hardware and they want their own pieces. Or some of them being bigger companies, say IBM. They're involved in some of our special interest groups. And they see a lot of users who want certain things and they want to optimize for that. So folks like that often.
Autonomous vehicle companies, perhaps.
Exactly, yes.
So, yeah, like I mentioned, TensorFlow has been downloaded 41 million times, 50,000 commits, almost 10,000 pull requests, and 1,800 contributors. So, I'm not sure if you can explain it, but what does it take to build a community like that? In retrospect, what do you think? What is the critical thing that allowed for this growth to happen, and how does that growth continue?
Yeah. Yeah, that's an interesting question. I wish I had all the answers there, I guess, so we could replicate it. I think there are a number of things that need to come together, right? One, just like any new thing, it is about there's a sweet spot of timing, what's needed, does it grow with what's needed? So in this case, for example, TensorFlow is not just grown because it was a good tool, it's also grown with the growth of deep learning itself. So those factors come into play. Other than that, though, I think just listening to the community, what they need, being open to, like in terms of external contributions, we've spent a lot of time in making sure we can accept those contributions well, we can help the contributors in adding those, putting the right process in place, getting the right kind of community, welcoming them, and so on. Like over the last year, we've really pushed on transparency. That's important for an open source project. People want to know where things are going, and we're like, okay, here's a process where you can do that, here are RFCs and so on. So thinking through, there are lots of community aspects that come into that you can really work on. As a small project, it's maybe easy to do because there's like 2 developers and you can do those. As you grow, putting more of these processes in place, thinking about the documentation, thinking about what do developers care about, what kind of tools would they want to use, all of these kind of things.
So one of the big things I think that feeds the TensorFlow fire is people building something on TensorFlow, and implement a particular architecture that does something cool and useful, and they put that on GitHub, and so it just feeds this growth. Do you have a sense that with 2.0 and 1.0 that there may be a little bit of a partitioning like there's with Python 2 and 3, that there'll be a code base in the older versions of TensorFlow that will not be as compatible easily? Or are you pretty confident that this kind of conversion is pretty natural and easy to do?
So we're definitely working hard to make that very easy to do. There's lots of tooling that we talked about at the Developer Summit this week, and we continue to invest in that tooling. It's, when you think of these significant version changes, that's always a risk, and we're really pushing hard to make that transition very, very smooth. I think, so at some level, people want to move when they see the value in the new thing. They don't want to move just because it's a new thing. And some people do, but most people want a really good thing. And I think over the next few months, as people start to see the value, we'll definitely see that shift happening. So I'm pretty excited and confident that we'll see people moving. As you said earlier, this field is also moving rapidly, so that will help because we can do more things, and the new things will clearly happen in 2.x, so people will have lots of good reasons to move.
So what do you think TensorFlow 3.0 looks like? Is there are things happening so crazily that even at the end of this year seems impossible to plan for? Or is it possible to plan for the next 5 years?
I think it's tricky. There are some things that we can expect in terms of change. Yes, change is going to happen. Uh, are there some things going to stick around and some things not going to stick around? I would say that the basics of deep learning, the say convolutional models or the basic kind of things, they'll probably be around in some form still in 5 years. Will RL and GAN stay? Very likely, based on where they are. Will we have new things? Probably, but those are hard to predict. And some things that we can see as things that we're starting to do right with some of our projects right now is just combining eager execution in graphs, where we're starting to make it more like just your natural programming language. You're not trying to program something else. Similarly with Swift for TensorFlow, we're taking an approach, can you do something down like that? So some of those ideas seem like, okay, that's the right direction. In 5 years, we expect to see more in that area. Other things we don't know is, will hardware accelerators be the same? Will we be able to train with 4 bits instead of 32 bits?
And I think the TPU side of things is exploring. I mean, TPU is already on version 3. It seems that the evolution of TPU and TensorFlow are sort of they're co-evolving almost in terms of both are learning from each other and from the community and from the applications where the biggest benefit is achieved. You've been trying to sort of with Ego with Keras to make TensorFlow as accessible and easy to use as possible. What do you think for beginners is the biggest thing they struggle with? Have you encountered that, or is basically what Keras is solving is that eager, like we talked about?
Yeah, for some of them, like you said, right, beginners want to just be able to take some image model, they don't care if it's inception or estimate or something else, and do some training or transfer learning on their kind of model. Being able to make that easy is important. So in some ways, we do that by providing them simple models with, say, in comp or so on. They don't care about what's inside that box, but they want to be able to use it. So we're pushing on many different levels. If you look at just a component that you get, which has the layers already smushed in, the beginners probably just want that. Then the next step is, okay, look at building layers with Keras. If you go out to research, then they are probably writing custom layers themselves or their own loops. So there's a whole spectrum there.
And then providing the pre-trained models seems to really decrease the time from you trying to start. So you could basically in the Colab notebook achieve what you need. So I'm basically answering my own question because I think what TensorFlow delivered on recently is trivial for beginners. So I was just wondering if there was other pain points you tried to ease, but I'm not sure there would.
No, those are probably the big ones. I mean, I see high schoolers doing a whole bunch of things now, which is pretty amazing.
It's both amazing and terrifying. So,
yes.
In a sense that when they grow up, it's some incredible ideas will be coming from them. So there's certainly a technical aspect to your work, but you also have a management aspect to your role with TensorFlow, leading the project, a large number of developers and people. So what do you look for in a good team? What do you think? Google has been at the forefront of exploring what it takes to build a good team, and TensorFlow is one of the most cutting edge technologies in the world. So in this context, what do you think makes for a good team?
It's definitely something I think a fair bit about. I think in terms of the team being able to deliver something well, one of the things that's important is a cohesion across the team. So being able to execute together and doing things. It's not like at this scale, an individual engineer can only do so much. There's a lot more that they they can do together. Even though we have some amazing superstars across Google and in the team, but there's, often the way I see it is the product of what the team generates is way larger than the whole or each individual put together. And so, how do we have all of them work together? The culture of the team itself. Hiring good people is important, but part of that is it's not just that, okay, we hire a bunch of smart people and throw them together and let them do things. It's also people have to care about what they're building. People have to be motivated for the right kind of things. That's often an important factor. Um, and finally, how do you put that together with somewhat unified vision of where we want to go? So, are we all looking in the same direction, or what's going on here? And sometimes it's a mix. Google's a very bottom-up organization in some sense. Also, research even more so, and that's how we started. But as we've become this larger product and ecosystem, I think it's also important to combine that well with mix of, okay, here's the direction we want to go in. There is exploration we'll do around that, but let's keep staying in that direction, not just all over the place.
And is there a way you monitor the health of the team? Sort of like, is there a way you did a good job? The team is good. Like, you're you're saying nice things, but it's sometimes difficult to determine how aligned.
Yes,
because it's not binary. It's not like there's tensions and complexities and so on. And the other element of this is that you mentioned superstars. There's so much. Even at Google, such a large percentage of work is done by individual superstars too. So there's and sometimes those superstars can be against the dynamic of a team and those tensions. I'm sure TensorFlow might be a little bit easier because the mission of the project is so sort of beautiful. You're at the cutting edge, so it's exciting.
Yeah.
But have you had struggled with that? Has there been challenges?
There always be challenges in different kinds of ways. That said, I think we've been what's good about getting people who care and are have the same kind of culture, and that's Google in general to a large extent. But also, like you said, given that the project has had so many exciting things to do, there's been room for lots of people to do different kinds of things and grow, which does make the problem a bit easier, I guess.
Yeah.
And it allows people, depending on what they're doing, if there's room around them, then that's fine. But yes, we do care about whether a superstar or not, that they need to work well with the team across Google.
That's interesting to hear. So it's like superstar or not, the productivity broadly is about the team.
Yeah. I mean, they might add a lot of value, but if they're hurting the team, then that's a problem.
So in hiring engineers, it's so interesting, right? The hiring process. What do you look for? How do you determine a good developer or a good member of a team for just a few minutes or hours together?
So
again, no magic answers, I'm sure.
Yeah. I mean, Google has a hiring process that we've refined over the last 20 years, I guess, and that you've probably heard and seen a lot about. So we do work with the same hiring process, and that's really helped. For me in particular, I would say, in addition to the core technical skills, what does matter is their motivation in what they want to do. Because if that doesn't align well with where we want to go, that's not going to lead to long-term success for either them or the team. And I think that becomes more important the more senior the person is, but it's important at every level. Like even the junior most engineer, if they're not motivated to do well at what they're trying to do, however smart they are, it's going to be hard for them to succeed.
Does the Google hiring process touch on that passion? So like trying to determine, because I think, as far as I understand, maybe you can speak to it, that the Google hiring process sort of helps in the initial, like, determines the skill set there, is your puzzle solving ability, problem solving ability good, but like, I'm not sure, but it seems that the determining what the person's like fire inside them, that wants to do anything really doesn't really matter. It's just some cool stuff. I'm going to do it. that, I don't know, is that something that ultimately ends up when they have a conversation with you, or once it gets closer to?
So one of the things we do have as part of the process is just a culture fit, like part of the interview process itself, in addition to just the technical skills. And each engineer or whoever the interviewer is supposed to rate the person, the culture, and the culture fit with Google and so on. So that is definitely part of the process. Now, there are various kinds of projects and different kinds of things. So there might be variants of the kind of culture you want there and so on. And yes, that does vary. So for example, TensorFlow has always been a fast moving project, and we want people who are comfortable with that. But at the same time now, for example, we are at a place where we are also a very full-fledged product, and we want to make sure things that work really work. Like you can't cut corners all the time. So balancing that out and finding the people who are the right fit for those is important. And I think those kind of things do vary a bit across projects and teams and product areas across Google, and so you'll see some differences there in the final checklist. But a lot of the core culture, it comes along with just the engineering excellence and so on.
What is the hardest part of your job? Take your pick, I guess.
It's fun, I would say. Like hard, yes. I mean, lots of things at different times. I think that does vary.
So let me clarify that difficult things are fun.
Yeah.
When you solve them, right? So
Yes.
it's fun in that sense.
I think the key to a successful thing across the board, and in this case, it's a large ecosystem now, but even a small product, is striking that fine balance across different aspects of it. Sometimes it's how fast you go versus how perfect it is. Sometimes it's how do you involve this huge community? Who do you involve, or do you decide, okay, now is not a good time to involve them because it's not the right fit? Sometimes it's saying no to certain kinds of things. Those are often the hard decisions. Some of them you make quickly because you don't have the time. Some of them you get time to think about them, but they're always hard.
So both choices are pretty good. It's those decisions. What about deadlines? You find TensorFlow to be driven by deadlines to a degree that a product might, or is there still a balance to where it's less deadline? You had the Dev Summit that came together incredibly. It looked like there's a lot of moving pieces and so on. So that did that deadline make people rise to the occasion, releasing TensorFlow 2.0 Alpha?
Yeah,
I'm sure that was done last minute as well. I mean, like up to the last point.
Again, it's one of those things that's you need to strike the good balance. There's some value that deadlines bring. That does bring a sense of urgency to get the right things together instead of getting the perfect thing out. You need something that's good and works well. And the team definitely did a great job in putting that together. So I was very amazed and excited by everything, how that came together. That said, across the year, we try not to put artificial deadlines. We focus on key things that are important, figure out how much of it's important, and when we are developing in the open, both internally and externally, everything's available to everybody, so you can pick and look at where things are. We do releases at a regular cadence, so fine if something doesn't necessarily end up with this one, it'll end up in the next release in a month or two, and that's okay. But we want to keep moving as fast as we can in these different areas. Because we can iterate and improve on things, sometimes it's okay to put things out that aren't fully ready. We'll make sure it's clear that, okay, this is experimental, but it's out there if you want to try and give feedback. That's very, very useful. I think that quick cycle and quick iteration is important. That's what we often focus on rather than here's a deadline where you get everything else.
Is 2.0, is there pressure to make that stable? Or, like, for example, WordPress 5.0 just came out, and there was no pressure to. It was a lot of build updates that delivered way too late, but and they said, okay, well, but we're going to release a lot of updates really quickly to improve it. Do you see TensorFlow 2.0 in that same kind of way, or is there this pressure to once it hits 2.0, once you get to the release candidate and then you get to the final, that's going to be the stable thing?
So it's going to be stable in just like when X was, where every API that's there is going to remain and work. It doesn't mean we can't change things under the covers. It doesn't mean we can't add things. So there's still a lot more for us to do, and we continue to have more releases. So in that sense, there's still. I don't think we'll be done in like 2 months when we release this.
I don't know if you can say, but is there, there's not external deadlines for TensorFlow 2.0, but is there internal deadlines, artificial or otherwise, that you try and just set for yourself? Or is it whenever it's ready?
So we want it to be a great product, and that's a big, important piece for us. TensorFlow is already out there. We have 41 million downloads for 1.x, so it's not like we have to have this. Yeah, exactly. So it's not like a lot of the features that we've really polishing and putting them together are there. We don't have to rush that just because. So in that sense, we want to get it right and really focus on that. That said, we have said that we are looking to get this out in the next few months, in the next quarter, and we, as far as possible, we'll definitely try to make that happen.
Yeah, my favorite line was spring is a relative concept. I love it.
Yes.
Spoken like a true developer. So, something I'm really interested in your previous line of work is, before TensorFlow, you led a team at Google on search ads. I think this is a very interesting topic on every level, on a technical level, because at their best, ads connect people to the things they want and need.
Yep.
So and at their worst, they're just these things that annoy the heck out of you, to the point of ruining the entire user experience of whatever you're actually doing. So they have a bad rep, I guess. And so on the other end, so this connecting users to the thing they need and want is a beautiful opportunity for machine learning to shine. Like huge amounts of data that's personalized, and you kind of map to the thing they actually won't get annoyed. So what have you learned from this Google that's leading the world in this aspect? What have you learned from that experience? And what do you think is the future of ads? Take you back to that.
Yes, it's been a while, but I totally agree with what you said. I think the search ads, the way it was always looked at, and I believe it still is it's an extension of what search is trying to do. The goal is to make the information, make the world's information accessible. That it's not just information, but it could be products or other things that people care about. And so it's really important for them to align with what the users need. And in search ads, there's a minimum quality level before that ad will be shown. If we don't have an ad that hits that quality, but it will not be shown. Even if we have it, and okay, maybe we lose somebody there. That's fine. That is really, really important, and I think that is something I really liked about being there. Advertising is a key part, and as a model, it's been around for ages, right? It's not a new model. It's been adapted to the web, and became a core part of search and many other search engines across the world. I do hope, like you said, there are aspects of ads that are annoying, and I go to a website, and if it just keeps popping an ad in my face not to recommend me, that's going to be annoying, clearly. So I hope we can strike that balance between showing a good ad where it's valuable to the user and provides the monetization to the service. And this might be search, this might be a website. All of these, they do need the monetization for them to provide that service. But if it's done in that good balance between showing just some random stuff that's distracting versus showing something that's actually valuable.
So do you see it moving forward as to continue being a model that that funds businesses like Google? That's a significant revenue stream? Because that's one of the most exciting things, but also limiting things of the internet is nobody wants to pay for anything.
Yeah.
And advertisements, again, coupled at their best, are actually really useful and not annoying. Do you see that continuing and growing and improving? Or do you see sort of more Netflix type models where you have to start to pay for content?
I think it's a mix. I think it's going to take a long while for everything to be paid on the internet, if at all. Probably not. I mean, I think there's always going to be things that are sort of monetized with things like ads. But over the last few years, I would say we've definitely seen that transition towards more paid services across the web, and people are willing to pay for them because they do see the value. Netflix is a great example. You have YouTube doing things. People pay for the apps they buy. More people I find are willing to pay for newspaper content, for the good news websites across the web. That wasn't the case even a few years ago, I would say. And I just see that change in myself as well, and just lots of people around me. So definitely hopeful that we'll transition to that mixed model where maybe you get to try something out for free, maybe with ads, but then there's a more clear revenue model that sort of helps go beyond that.
So, speaking of revenue, how is it that a person can use the TPU in a Google Colab for free? So, what's the? I guess the question is, what's the future of TensorFlow in terms of empowering, say, teach a class of 300 students, and they amassed by MIT? What is going to be the future of them being able to do their homework in TensorFlow? Like, where are they going to train these networks, right?
Right.
What's that future look like with TPUs, with cloud services, and so on?
I think a number of things there. I mean, TensorFlow, open source, you can run it wherever. You can run it on your desktop, and your desktops always keep getting more powerful, so maybe you can do more. My phone is like, I don't know how many times more powerful than my first desktop.
You probably train it on your phone now, yeah. That's true.
Right. So in that sense, the power you have in your hands is a lot more. Clouds are actually very interesting from, say, students or courses perspective because they make it very easy to get started. Colab, the great thing about it is go to a website and it just works. No installation needed, nothing to, you're just there and things are working. That's really the power of cloud as well. And so I do expect that to grow. Again, Colab is a free service. It's great to get started, to play with things, to explore things. That said, with free you can only get so much. So just like we were talking about, free versus paid, and there are services you can pay for and get a lot more.
Great. So if I'm a complete beginner interested in machine learning and TensorFlow, what should I do?
Probably start with going to our website and playing there.
Just go to TensorFlow.org and start clicking on things.
Yep. Check out tutorials and guides. There's stuff you can just click there and go to a Colab and do things. No installation needed. You can get started right there.
Okay, awesome. Rajat, thank you so much for talking today.
Thank you, Lex.
Fun's great. The following is a conversation with Gavin Miller. He's the head of Adobe Research. Adobe has empowered artists, designers, and creative minds from all professions, working in the digital media for over 30 years with software such as Photoshop, Illustrator, Premiere, After Effects, InDesign, Audition, software that works with images, video, and audio. Adobe Research is working to define the future evolution of these products in a way that makes the life of creatives easier, automates the tedious tasks, and gives more and more time to operate in the idea space instead of pixel space. This is where the cutting-edge deep learning methods of the past decade can really shine more than perhaps any other application. Gavin is the embodiment of combining tech and creativity. Outside of Adobe Research, he writes poetry and builds robots, both things that are near and dear to my heart as well. This conversation is part of the Artificial Intelligence Podcast. If you enjoy it,
subscribe on YouTube, iTunes, or simply connect with me on Twitter at Lex Friedman, spelled F-R-I-D. And now, here's my conversation with Gavin Miller.
You're head of Adobe Research, leading a lot of innovative efforts and applications of AI, creating images, video, audio, language, but you're also yourself an artist, a poet, a writer, and even a roboticist. So while I promise to everyone listening that I will not spend the entire time we have together reading your poetry, which I love, I have to sprinkle it in at least a little bit. So some of them are pretty deep and profound, and some are light and silly. Let's start with a few lines from the silly variety. You write in Je ne regrette rien, a poem that beautifully parodies both Edith Piaf's Je ne regrette rien and My Way by Frank Sinatra. So it opens with, and now dessert is near. It's time to pay the final total. I've tried to slim all year, but my diets have been anecdotal. So where does that love for poetry come from for you? And if we dissect your mind, how does it all fit together in the bigger puzzle of Dr. Gavin Miller?
Well, interesting you chose that one. That was a poem I wrote when I'd been to my doctor and he said you really need to lose some weight and go on a diet. And whilst the rational part of my brain wanted to do that, the irrational part of my brain was protesting and sort of embraced the opposite idea.
I regret nothing.
Yes, exactly. Taken to an extreme, I thought it would be funny. Obviously, it's a serious topic for some people. But I think for me, I've always been interested in writing since I was in high school, as well as doing technology and invention. And sometimes there are parallel strands in your life that carry on, and one is more about your private life, and one's more about your technological career. And then sort of happy moments along the way, sometimes the two things touch, one idea informs the other, and we can talk about that as we go.
Do you think your writing, the art, the poetry contribute indirectly or directly to your research, to your work in Adobe?
Well, sometimes it does if I, say, imagine a future in a science fiction kind of way, and then once it exists on paper, I think, well, why shouldn't I just build that? There was an example where when realistic voice synthesis first started in the 90s at Apple, where I worked in research, it's done by a friend of mine, I sort of sat down and started writing a poem which each line I would enter into the voice synthesizer and see how it sounded, and sort of wrote it for that voice. And at the time, the agents weren't very sophisticated, so they'd sort of add random intonation, and I kind of made up the poem to sort of match the tone of the voice, and it sounded slightly sad and depressed, so I pretended it was a poem written by an intelligent agent, sort of telling the user to go home and leave them alone, but at the same time they were lonely and wanted to have company and learn from what the user was saying. And at the time it was way beyond anything that AI could possibly do, but since then it's becoming more within the bounds of possibility. And then at the same time I had a project at home where I did sort of a smart home. This was probably 93, 94, and I had the talking voice that reminded me when I walked in the door of what things I had to do. I had buttons on my washing machine because I was a bachelor. I'd leave the clothes in there for 3 days and they got moldy. So as I got up in the morning, it would say, don't forget the washing and so on. I made photographic photo albums that used light sensors to know which page you were looking at, would send that over wireless radio to the agent, who would then play sounds that matched the image you were looking at in the book. So I was kind of in love with this idea of magical realism and whether it was possible to do that with technology. So that was a case where the agent sort of intrigued me from a literary point of view and became a personality. I think more recently, I've also written plays, and when in plays you write dialogue, and obviously you write a fixed set of dialogue that follows a linear narrative. But with modern agents, as you design a personality or a capability for conversation, you're sort of thinking of, I kind of have imaginary dialogue in my head, and then I think, what would it take not only to have that be real, but for it to really know what it's talking about? So it's easy to fall into the uncanny valley with AI, where it says something it doesn't really understand, but it sounds good to the person, but you rapidly realize that it's kind of just
stimulus response. It doesn't really have real world knowledge about the thing it's describing. And so when you get to that point, it really needs to have multiple ways of talking about the same concept so it sounds as though everybody understands it. Now, what really understanding means is the whole, right? But if it only has one way of referring to something, it feels like it's a canned response. But if it can reason about it, or you can go at it from multiple angles and give a similar kind of response that people would, then it starts to seem more like there's something there that's sentient.
You can say the same thing, multiple things from different perspectives. I mean, with the automatic image captioning that I've seen the work that you're doing, there's elements of that, right? Being able to generate different kinds of
So in my team, there's a lot of work on turning a medium from one form to another, whether it's auto tagging imagery or making up full sentences about what's in the image, then changing the sentence, finding another image that matches the new sentence, or vice versa. And in the modern world of GANs, you sort of give it a description and it synthesizes an asset that matches the description. So I've sort of gone on a journey. My early days in my career were about 3D computer graphics, the sort of pioneering work, sort of before movies had special effects done with 3D graphics, and sort of rode that revolution. And that was very much like the Renaissance, where people would model light and color and shape and everything. And now we're kind of in another wave where it's more impressionistic, and it's sort of the idea of something can be used to generate an image directly, which is sort of the new frontier in computer image generation using AI algorithms. So
the creative process is more in the space of ideas, or becoming more in the space of ideas versus in the raw pixels.
Well, it's interesting. It depends. I think at Adobe, we really want to span the entire range from really, really good, what you might call low-level tools. By low-level, as close to, say, analog workflows as possible. So what we do there is we make up systems that do really realistic oil paint and watercolor simulations. So if you want every bristle to behave as it would in the real world and leave a beautiful analog trail of water and then flow after you've made the brushstroke, you can do that. And that's really important for people who want to create something really expressive or really novel, because they have complete control. And then as certain other tasks become automated, it frees the artist up to focus on the inspiration and less of the perspiration. So thinking about different ideas, obviously, once you finish the design, there's a lot of work to, say, do it for all the different aspect ratio of phones or websites and so on. And that used to take up an awful lot of time for artists. It still does for many, what we call content velocity. And one of the targets of AI is actually to reason about, from the first example, of what are the likely intent for these other formats. Maybe if you change the language to German and the words are longer, how do you reflow everything so that it looks nicely artistic in that way? And so the person can focus on the really creative bit in the middle, which is what is the look and style and feel, and what's the message, and what's the story and the human element. So I think creativity is changing. So that's one way in which we're trying to just make it easier and faster and cheaper to do, so that there can be more of it, more demand, because it's less expensive. So everyone wants beautiful artwork for everything from a school website to Hollywood movie. On the other side, as some of these things have automatic versions of them, people will possibly change role from being the hands-on artisan to being either the art director or the conceptual artist, and then the computer will be a partner to help create polished examples of the idea that they're exploring.
Let's talk about Adobe products, AI and Adobe products. Just so you know where I'm coming from, I'm a huge fan of Photoshop for images, Premiere for video, Audition for audio. I probably used Photoshop to create the thumbnail for this video, Premiere to edit the video, Audition to do the audio. That said, everything I do is really manually, and I use this old school Kinesis keyboard, and I have auto hotkey that it's really about optimizing the flow of just making sure there's as few clicks as possible to just being extremely efficient. It's something you started to speak to.
Right.
So before we get into the fun, sort of awesome deep learning things, where does AI, if you could speak a little more to it, AI or just automation in general, do you see in the coming months and years, or in general, prior in 2018, fitting into making the low-level pixel work flow easier?
Yeah, that's a great question. So we have a very rich array of algorithms already in Photoshop, just classical procedural algorithms as well as ones based on data. In some cases, they end up with a large number of sliders and degrees of freedom. So one way in which AI can help is just an auto button which comes up with default settings based on the content itself rather than default values for the tool. At that point, you then start tweaking. So that's a very kind of made life easier for people whilst making use of common sense from other example images.
Like smart defaults.
Smart defaults, absolutely. Another one is something we've spent a lot of work over the last 20 years. I've been at Adobe for 19, thinking about selection, for instance, where, with quick select, you would look at color boundaries and figure out how to sort of flood fill into regions that you thought were physically connected in the real world. But that algorithm had no visual common sense about what a cat looks like or a dog. It would just do it based on rules of thumb, which were applied to graph theory. And it was a big improvement over the previous work where you had to sort of almost click everything by hand, or if it just did similar colors, it would do little tiny regions that wouldn't be connected. But in the future, using neural nets to actually do a great job with, say, a single click, or even in the case of well-known categories like people or animals, no click, where you just say, select the object, and it just knows the dominant object is a person in the middle of the photograph. Those kinds of things are really valuable if they can be robust enough to give you good quality results. Or they could be a great start for like tweaking.
So, for example, background removal.
Correct.
Like one thing I'll in a thumbnail, I'll take a picture of you right now and essentially remove the background behind you. And I want to make that as easy as possible. Like you don't have flowing hair, like Rich
at the moment.
Yeah, Rich sort of.
I had it in the past. It may come again in the future, but for now.
So that sometimes makes it a little more challenging to remove the background. How difficult do you think is that problem for AI for basically making the quick selection tool smarter and smarter and smarter?
Well, we have a lot of research on that already. If you want a sort of quick, cheap, and cheerful look, I'm pretending I'm in Hawaii, but it's sort of a joke, then you don't need perfect boundaries, and you can do that today with a single click with the algorithms we have. We have other algorithms where, with a little bit more guidance on the boundaries, like you might need to touch it up a little bit, we have other algorithms that can pull a nice match from a crude selection. So we have combinations of tools that can do all of that. And at our recent Max conference, Adobe Max, we demonstrated how very quickly, just by drawing a simple polygon around the object of interest, we could not only do it for a single still, but we could pull a match, pull at least a selection mask from a moving target, like a person dancing in front of a brick wall or something. And so it's going from hours to a few seconds for workflows that are really nice. And then you might go in and touch up a little.
So that's a really interesting question. You mentioned the word robust. There's a journey for an idea, right? And what you presented probably at Max has elements of just sort of, it inspires the concept. It can work pretty well in the majority of cases. But how do you make something that works, in majority of cases, how do you make something that works maybe in all cases? Or it becomes a robust tool?
There are a couple of things. So that really touches on the difference between academic research and industrial research. So in academic research, it's really about who's the person to have the great new idea that shows promise. And we certainly love to be those people too. But we have sort of two forms of publishing. One is academic peer review, which we do a lot of, and we have great success there as much as some universities. But then we also have shipping, which is a different type of peer. And then we get customer review, as well as, product critics. And that might be a case where it's not about being perfect every single time, but perfect enough of the time, plus a mechanism to intervene and recover where you do have mistakes. So we have the luxury of very talented customers. We don't want them to be overly taxed doing it every time. But if they can go in and just take it from 99 to 100 with the touch of a mouse or something, then for the professional end, that's something that we definitely want to support as well. And for them, it went from having to do that tedious task all the time to much less often. So I think that gives us an out. If it had to be 100% automatic all the time, then that would delay the time at which we could get to market.
So on that thread, maybe you can untangle something. Again, I'm sort of just speaking to my own experience.
Yeah, that's fine.
Maybe that is the most useful idea.
Absolutely.
So I think Photoshop, as an example, or Premiere, has a lot of amazing features that I haven't touched.
Mm-hmm.
And so what's in terms of AI helping make my life, the life of creatives easier, how this collaboration between human and machine, how do you learn to collaborate better? How do you learn new algorithms? Is it something where you have to watch tutorials and you have to watch videos and so on? Or do you ever think, do you think about the experience itself for exploration being a teacher?
We absolutely do. So I'm glad that you brought this up. We sort of think about two things. One is helping the person in the moment to do the task that they need to do, but the other is thinking more holistically about their journey learning a tool. Almost like, think of it as Adobe University, where you use the tool long enough, you become an expert. And not necessarily an expert in everything. It's like living in a city. You don't necessarily know every street, but you know the important ones you need to get to. So we have projects in research which actually look at the thousands of hours of tutorials online and try to understand what's being taught in them. And then we had one publication at Kai where it was looking at, given the last 3 or 4 actions you did, what did other people in tutorials do next? So if you want some inspiration for what you might do next, or you just want to watch the tutorial and learn from people who are doing similar workflows to you, you can without having to go and search on keywords and everything. So really trying to use the context of your use of the app to make intelligent suggestions, either about choices that you might make, or in a more assistive way where it could say, if you did this next, we could show you. And that's basically the frontier that we're exploring now, which is, if we really deeply understand the domain in which designers and creative people work, can we combine that with AI and pattern matching of behavior to make intelligent suggestions, either through, verbal possibilities or just showing the results of if you try this. And that's really the sort of, I was in a meeting today thinking about these things.
Well,
so it's still a grand challenge. We'd all love an artist over one shoulder and a teacher over the other, right? And we hope to get there. And the right thing to do is to give enough at each stage that it's useful in itself, but it builds a foundation for the next level of expectation.
Are you aware of this gigantic medium of YouTube that's creating just a bunch of creative people, both artists and teachers of different kinds?
Absolutely, and the more we can understand those media types, both visually and in terms of transcripts and words, the more we can bring the wisdom that they embody into the guidance that's embedded in the tool.
That would be brilliant, to remove the barrier from having to yourself type in the keyword searching and so on.
Absolutely. And then in the longer term, an interesting discussion is, does it ultimately not just assist with learning the interface we have, but does it modify the interface to be simpler? Or do you fragment into a variety of tools, each of which has a different level of visibility of the functionality? I like to say that if you add a feature to a GUI, you have to get more visual complexity confronting the new user, whereas if you have an assistant with a new skill, if you know they have it, so you know to ask for it, then it's sort of additive without being more intimidating. So we definitely think about new users and how to onboard them. Many actually value the idea of being able to master that complex interface and keyboard shortcuts like you were talking about earlier, because with great familiarity it becomes a musical instrument for expressing your visual ideas. And other people just want to get something done quickly in the simplest way possible, and that's where a more assisted version of the same technology might be useful, maybe on a different class of device, which is more in context for capture, say. Whereas somebody who's in a deep post-production workflow maybe want to be on a laptop or a big screen desktop and have more knobs and dials to really express the subtlety of what they want to do.
So there's so many exciting applications of computer vision and machine learning that Adobe is working on, like scene stitching, sky replacement, foreground, background removal, spatial object-based image search, automatic image captioning, like we mentioned, Project Cloak, Project Deep Fill, filling in parts of the images, Project Scribbler, style transfer video, style transfer faces in video, with Project Puppetron, best name ever. Can you talk through a favorite or some of them, or examples that popped in mind? I'm sure I'll be able to provide links to other ones we don't talk about, because there's visual elements to all of them that they're exciting.
Why they're interesting for different reasons might be a good way to go. So I think Sky Replace is interesting because, we talked about selection being sort of an atomic operation. It's almost like if you think of an assembly language, it's like a single instruction. Whereas Sky Replace is the compound action where you automatically select the sky, you look for stock content that matches the geometry of the scene. You try to have variety in your choices so that you do coverage of different moods. It then maps in the sky behind the foreground, but then importantly, it uses the foreground of the other image that you just searched on to recolor the foreground of the image that you're editing. So if you say go from a midday sky to an evening sky, it will actually add sort of an orange glow to the foreground objects as well. I was a big fan in college of Magritte, and he has a number of paintings where it's surrealism because he'll do a composite, but the foreground building will be at night and the sky will be during the day. There's one called the Empire of Light, which is on my wall in college. And we're trying not to do surrealism. It can be a choice, but we'd rather have it be natural by default rather than it looking fake and then you have to do a whole bunch of post-production to fix it. So that's a case where we're kind of capturing an entire workflow into a single action and doing it in about a second rather than a minute or two. And when you do that, you can not just do it once, but you can do it for, say, 10 different backgrounds, and then you're almost back to this inspiration idea of, I don't know quite what I want, but I'll know it when I see it. And you can just explore the design space as close to final production value as possible. And then when you really pick one, you might go back and slightly tweak the selection mask just to make it perfect and do that kind of polish that professionals like to bring to their work.
So then there's this idea of, you mentioned the sky, replacing it with different stock images of the sky.
Yeah.
In general, you have this idea,
or it could be on your disk or whatever.
Right?
Yeah.
But making even more intelligent choices about ways to search stock images, which is really interesting. It's kind of spatial.
Absolutely.
Being able to specify.
Right. So that was something we called concept canvas. So normally when you do say an image search, you would, assuming it's just based on text, you would give the keywords of things you want to be in the image, and it would find the nearest one that had those tags. For many tasks, you really want, to be able to say, I want a big person in the middle, or a dog to the right, an umbrella above the left, because you want to leave space for the text or whatever. And so Concept Canvas lets you assign spatial regions to the keywords. And then we've already pre-indexed the images to know where the important concepts are in the picture. So we then go through that index matching to assets. And even though it's just another form of search, because you're doing spatial design or layout, it starts to feel like design. You sort of feel oddly responsible for the image that comes back as if you invented it.
Yeah.
So it's a good example where giving enough control starts to make people have a sense of ownership over the outcome of the event. And then we also have technologies in Photoshop where you physically can move the dog in post as well. But for Concept Canvas, it was just a very fast way to sort of loop through and be able to lay things out.
In terms of being able to remove objects from a scene and fill in the background
Right.
automatically. So that's extremely exciting, and that's the neural network is stepping in there. I just talked this week with Ian Goodfellow. So
yes, the dance for doing that is definitely one approach.
So is that a really difficult problem? Is it as difficult as it looks? Again, to take it to a robust product level.
Well, there are certain classes of image for which the traditional algorithms like content-aware fill work really well. Like have a naturalistic texture like a gravel path or something. Because it's patch-based, it will make up a very plausible-looking intermediate thing and fill in the hole. And then we use some algorithms to sort of smooth out the lighting so you don't see any brightness contrast in that region. Or you gradually ramp from dark to light if it straddles a boundary. Where it gets complicated is if you have to infer invisible structure behind the person in front, and that really requires a common sense knowledge of the world to know what, if I see 3/4 of the house, do I have a rough sense of what the rest of the house looks like? If you just fill it in with patches, it can end up sort of doing things that make sense locally, but you look at the global structure and it looks like it's just sort of crumpled or messed up. And so what GANs and neural nets bring to the table is this common sense learned from the training set. And the challenge right now is that the generative methods that can make up missing holes using that kind of technology are still only stable at low resolutions. And so you either need to then go from a low resolution to a high resolution using some other algorithm, or we need to push the state of the art, and it's still in research to get to that point. Of course, if you show it something, say it's trained on houses, and then you show it an octopus, it's not going to do a very good job of showing common sense about octopuses. So, again, you were asking about how you know that it's ready for prime time. You really need a very diverse training set of images. And ultimately, that may be a case where you put it out there with some guardrails where you might do a detector which looks at the image and sort of estimates its own competence of how well a job could this algorithm do. So eventually, there may be this idea of what we call an ensemble of experts, where any particular expert is specialized in certain things, and then there's sort of either they vote to say how confident they are about what to do. This is sort of more future looking, or there's some dispatcher which says you're good at houses, you're good at trees, so I mean, it's all this adds up to a lot of work because each of those models will be a whole bunch of work. But I think over time you gradually fill out the set and initially focus on certain workflows and then sort of branch out as you get more capable.
You mentioned workflows, and have you considered maybe looking far into the future? First of all, using the fact that there is a huge amount of people that use Photoshop, for example, and have certain workflows, being able to collect the information by which they basically get information about their workflows, about what they need, the ways to help them, whether it is houses or octopus that people work on more.
Right.
Like basically getting a beat on what kind of data is needed to be annotated and collected for people to build tools that actually work well for people.
Right, absolutely. And this is a big topic in the whole world of AI is what data can you gather and why.
Right.
At one level, a way to think about it is we not only want to train our customers in how to use our products, but we want them to teach us what's important and what's useful. At the same time, we want to respect their privacy. And obviously, we wouldn't do things without their explicit permission. And I think the modern spirit of the age around this is you have to demonstrate to somebody how they're benefiting from sharing their data with the tool. Either it's helping in the short term to understand their intent so you can make better recommendations, or if they're friendly to your cause or your tool, or they want to help you evolve quickly because they depend on you for their livelihood, they may be willing to share some of their workflows or choices with the data set to be then trained. There are technologies for looking at learning without necessarily storing all the information permanently so that you can sort of learn on the fly but not keep a record of what somebody did. So we're definitely exploring all of those possibilities.
And I think Adobe exists in a space where Photoshop, like if I look at the data I've created and owned, you know, I'm less comfortable sharing data with social networks than I am with Adobe, because just exactly as you said, there's an obvious benefit for sharing the data that I use to create in Photoshop, because it's helping improve the workflow in the future.
Right.
As opposed to, it's not clear what the benefit is in social networks.
It's nice of you to say that. I mean, I think there are some professional workflows where people might be very protective of what they're doing, such as if I was preparing evidence for a legal case, I wouldn't want any of that, running home to help train the algorithm or anything. There may be other cases where people are, say, having a trial version, or they're doing something. I'm not saying we're doing this today, but there's a future scenario where somebody has a more permissive relationship with Adobe, where they explicitly say, I'm fine, I'm only doing hobby projects or things which are non-confidential, and in exchange for some benefit, tangible or otherwise, I'm willing to share very fine-grained data. So another possible scenario is to capture relatively crude high-level things from more people, and then more detailed knowledge from people who are willing to participate. We do that today with explicit customer studies where, we go and visit somebody and ask them to try the tool, and we human observe what they're doing. In the future, to be able to do that enough to be able to train an algorithm, we'd need a more systematic process, but we'd have to do it very consciously, because one of the things people treasure about Adobe is a sense of trust, and we don't want to endanger that through overly aggressive data collection. So we have a chief privacy officer, and it's definitely front and center of thinking about AI rather than an afterthought.
Well, when you start that program, sign me up.
Okay, happy to.
Is there other projects that you wanted to mention that I didn't, perhaps, that pop into mind?
Well, you covered the number. I think you mentioned Project Puppetron. I think that one is interesting because it's, you might think of Adobe as only thinking in 2D. And that's a good example where we're actually thinking more three-dimensionally about how to assign features to faces, so that we can, if you take, so what Puppetron does, it takes either a still or a video of a person talking, and then it can take a painting of somebody else and then apply the style of the painting to the person who's talking in the video. And it, unlike a sort of screen door post filter effect that you sometimes see online, it really looks as though it's sort of somehow attached or reflecting the motion of the face. And so that's a case where even to do a 2D workflow like stylization, you really need to infer more about the 3D structure of the world. And I think as 3D computer vision algorithms get better, initially they'll focus on particular domains like faces, where you have a lot of prior knowledge about structure, and you can maybe have a parameterized template that you fit to the image. But over time, this should be possible for more general content. And it might even be invisible to the user that you're doing 3D reconstruction, but under the hood, but it might then let you do edits much more reliably or correctly than you would otherwise.
And, face is a very important application, right? So making things work.
And a very sensitive one. If you do something uncanny, it's very disturbing.
That's right.
Yeah.
You have to get it. You have to get it right. So in the space of augmented reality and virtual reality,
yes,
what do you think is the role of AR and VR in the content we consume as people, as consumers, and in the content we create as creators?
No, that's
today?
a great question. We think about this a lot too. So I think VR and AR serve slightly different purposes. So VR can really transport you to an entire immersive world, no matter what your personal situation is. To that extent, it's a bit like a really, really widescreen television, where it sort of snaps you out of your context and puts you in a new one. And I think it's still evolving in terms of the hardware. I actually worked on VR in the 90s, trying to solve the latency and sort of nausea problem, which we did, but it was very expensive and a bit early. There's a new wave of that now, I think, and increasingly those devices are becoming all-in-one rather than something that's tethered to a box. I think the market seems to be bifurcating into things for consumers and things for professional use cases. like for architects and people designing where your product is a building, and you really want to experience it better than looking at a scale model or a drawing, I think, or even the video. So I think for that, where you need a sense of scale and spatial relationships, it's great. I think AR holds the promise of sort of taking digital assets off the screen and putting them in context in the real world, on the table in front of you, on the wall behind you. And that has the corresponding need that the assets need to adapt to the physical context in which they're being placed. I mean, it's a bit like having a live theatre troupe come to your house and put on Hamlet. My mother had a friend who used to do this at stately homes in England for the National Trust. And they would adapt the scenes, and even they'd walk the audience through the rooms to see the action based on the country house they found themselves in for 2 days. And I think AR will have the same issue that, you know, if you have a tiny table in a big living room or something, it'll try to figure out what can you change, what's fixed. And there's a little bit of a tension between fidelity, where if you captured, say, Nureyev doing a fantastic ballet, you'd want it to be sort of exactly reproduced, and maybe all you could do is scale it down. Whereas somebody telling you a story might be walking around the room doing some gestures, and that could adapt to the room in which they were telling the story.
And
So
do you think fidelity is important in that space, or is it more about the storytelling?
I think it may depend on the characteristic of the media. If it's a famous celebrity, then it may be that you want to catch every nuance, and they don't want to be reanimated by some algorithm. It could be that if it's really, you know, a lovable frog telling you a story, and it's about a princess and a frog, then it doesn't matter if the frog moves in a different way. I think a lot of the ideas that have sort of grown up in the game world would now come into the broader commercial sphere once they're needing adaptive characters in AR.
Are you thinking of engineering tools that allow creators to create in the augmented world, basically making a Photoshop for the augmented world?
Well, we have shown a few demos of sort of taking a Photoshop layer stack and then expanding it into 3D. That's actually been shown publicly as one example in AR. Where we're particularly excited at the moment is in 3D. 3D design is still a very challenging space, and we believe that it's a worthwhile experiment to try to figure out if AR or immersive makes 3D design more spontaneous.
Can you give me an example of 3D design, just
Well,
like application?
Literally, well, a simple one would be laying out objects, right? So on a conventional screen, you'd have a plan view and a side view and a perspective view, and you sort of be dragging it around with a mouse, and if you're not careful, it'll go through the wall and all that. Whereas if you were really laying out objects in say in a VR headset, you could literally move your head to see a different viewpoint. They'd be in stereo, so you'd have a sense of depth, because you're already wearing the depth glasses, right? So it would be those sort of big gross motor, move things around kind of skills seem much more spontaneous, just like they are in the real world. The frontier for us, I think, is whether that same medium can be used to do fine-grained design tasks, like very accurate, you know, constraints on, say, a CAD model or something. That may be better done on the desktop, but it may just be a matter of inventing the right UI. So we're hopeful that because there will be this potential explosion of demand for 3D assets driven by AR and more real-time animation on conventional screens, those tools will also help with, or those devices will help with designing the content as well.
You've mentioned quite a few interesting sort of new ideas. And at the same time, there's old-timers like me that are stuck in their old ways. And
well, I think I'm the old-timer.
Okay, all right. But the opposed all change at all costs.
Yes.
Is there, when you're thinking about creating new interfaces, do you feel the burden of just this giant user base that loves the current product? So anything new you do that, any new idea comes at a cost that you'll be resisted?
Well, I think if you have to trade off control for convenience, then our existing user base would definitely be offended by that. I think if there are some things where you have more convenience and just as much control, that may be more welcome. We do think about not breaking well-known metaphors for things. So things should sort of make sense. Photoshop has never been a static target. It's always been evolving and growing. And to some extent, there's been a lot of brilliant thought along the way of how it works today. So we don't want to just throw all that out. If there's a fundamental breakthrough, like a single click is good enough to select an object rather than having to do lots of strokes, that actually fits in quite nicely to the existing toolset, either as an optional mode or as a starting point. I think where we're looking at radical simplicity, where you could encapsulate an entire workflow with a much simpler UI, then sometimes that's easier to do in the context of either a different device, like a mobile device, where the affordances are naturally different, or in a tool that's targeted at a different workflow, where it's about spontaneity and velocity rather than precision. And we have projects like Rush, which can let you do professional quality video editing for a certain class of media output that is targeted very differently in terms of users and the experience. And ideally, people would go, if I'm feeling like doing Premiere, big project, I'm doing a 4-part television series, that's definitely a Premiere thing. But if I want to do something to show my recent vacation, maybe I'll just use Rush because I can do it in the half an hour I have free at home rather than 4 hours I need to do it at work. And for the use cases which we can do well, it really is much faster to get the same output. But the more professional tools obviously have a much richer toolkit and more flexibility in what they can do.
And at the same time, with the flexibility and control, I like this idea of smart defaults, of using AI to coach you to like what Google has "I'm feeling lucky" button.
Right.
Or one button kind of gives you a pretty good set of settings, and then that's almost an educational tool.
Absolutely. Yeah.
To show, because sometimes when you have all this control, you're not sure about the correlation between the different bars that control different elements of the image and so on. And sometimes there's a degree of you don't know what the optimal is.
And then some things are sort of on demand, like help, right? Where I'm stuck, I need to know what to look for, I'm not quite sure what it's called. And something that was proactively making helpful suggestions, or, you can imagine a make a suggestion button, where you'd use all of that knowledge of workflows and everything to maybe suggest something to go and learn about, or just to try or show the answer. And maybe it's not one intelligent default, but it's like a variety of defaults, and then you go, oh, I like that one. Yeah.
Several options.
Yeah.
So back to poetry.
Yes.
We're gonna interleave. So first few lines of a recent poem of yours, before I ask the next question.
Yeah.
This is about the smartphone. Today I left my phone at home and went down to the sea. The sand was soft, the ocean glass, but I was still just me. This is a poem about you leaving your phone behind and feeling quite liberated because of it.
Mm-hmm.
So this is kind of a difficult topic, and let's see if we can talk about it, figure it out. But so with the help of AI, more and more, we can create sort of versions of ourselves, versions of reality that are in some ways more beautiful than actual reality.
Mm-hmm.
And some of the creative effort there is part of doing this, creating this illusion. So of course this is inevitable, but how do you think we should adjust as human beings to live in this digital world that's partly artificial, like that's better than the world that we lived in 100 years ago, when you didn't have Instagram and Facebook versions of ourselves?
This is sort of showing off better versions of ourselves.
We're using the tooling of modifying the images, or even with artificial intelligence, ideas of deep fakes and creating these adjusted or fake versions of ourselves in reality.
I think it's an interesting question. You have sort of historical bent on this. So. I actually wonder if 18th century aristocrats who commissioned famous painters to paint portraits of them had portraits that were slightly nicer than they actually looked in practice.
Well played, sir.
Human desire to put your best foot forward has always been true. I think it's interesting. You sort of framed it in two ways. One is if we can imagine alternate realities and visualize them, is that a good or bad thing? In the old days, you do it with storytelling and words and poetry, which still resides sometimes on websites. But we've become a very visual culture in particular. In the 19th century, we were very much a text-based culture. People would read long tracts. Political speeches were very long. Nowadays, everything's very kind of quick and visual and snappy. I think it depends on how harmless your intent. A lot of it's about intent. So if you have a somewhat flattering photo that you pick out of the photos that you have in your inbox to say this is what I look like, it's probably fine. If someone's going to judge you by how you look, then they'll decide soon enough when they meet you whether the reality,
Yeah, right.
I think where it can be harmful is if people hold themselves up to an impossible standard, which they then feel bad about themselves for not meeting. I think that's definitely can be an issue. And but I think the ability to imagine and visualize an alternate reality, which sometimes which you then go off and build later, can be a wonderful thing too. People can imagine architectural styles, which they then, have a startup, make a fortune, and then build a house that looks like their favorite video game. Is that a terrible thing? I think I used to worry about exploration, actually, that part of the joy of going to the moon when I was a tiny child, I remember it raining black and white, was to know what it would look like when you got there. And I think now we have such good graphics for visualizing the experience before it happens, that I slightly worry that it may take the edge off actually wanting to go. You know what I mean? Because we've seen it on TV. We kind of, by the time we finally get to Mars, we go, oh, yes, it's Mars. That's what it looks like. But then, the outer exploration, I think Pluto was a fantastic recent discovery where nobody had any idea what it looked like, and it was just breathtakingly varied and beautiful. So I think expanding the ability of the human toolkit to imagine and communicate on balance is a good thing. I think there are abuses. We definitely take them seriously and try to discourage them. I think there's a parallel side where the public needs to know what's possible through events like this, right? So that you don't believe everything you read in print anymore, and it may over time become true of images as well. Or you need multiple sets of evidence to really believe something rather than a single media asset. So I think it's a constantly evolving thing. It's been true forever. There's a famous story about Anne of Cleves and Henry VIII, where luckily for Anne, they didn't get married, right? They got married.
What's the story?
So Holbein went and painted a picture, and then Henry VIII wasn't pleased, and
Oh, yeah.
history doesn't record whether Anne was pleased, but I think she was pleased not to be married more than a day or something.
Yeah.
So, this has gone on for a long time, but I think it's just part of the magnification of human capability.
You've kind of built up an amazing research environment here, research culture, research lab, and you've written that the secret to a thriving research lab is interns. Can you unpack that a little bit?
Oh, absolutely. So, a couple of reasons. As you see, looking at my personal history, there are certain ideas you bond with at a certain stage of your career, and you tend to keep revisiting them through time. If you're lucky, you pick one that doesn't just get solved in the next 5 years, and then you're sort of out of luck. So I think a constant influx of new people brings new ideas with it. From the point of view of industrial research, because a big part of what we do is really taking those ideas to the point where they can ship as very robust features, you end up investing a lot in a particular idea. And if you're not careful, people can get too conservative in what they choose to do next, knowing that the product teams will want it. And interns let you explore the more fanciful or unproven ideas in a relatively lightweight way, ideally leading to new publications for the intern and for the researcher. And it gives you then a portfolio from which to draw which idea am I going to then try to take all the way through to being robust in the next year or two to ship. So it sort of becomes part of the funnel. it's also a great way for us to identify future full-time researchers. Many of our greatest researchers were former interns. It builds a bridge to university departments so we can get to know and build an enduring relationship with the professors, whom we often do academic gift funds to as well, as an acknowledgement of the value the interns add and their own collaborations. So it's sort of a virtuous cycle. And then the long-term legacy of a great research lab, hopefully, will be not only the people who stay, but the ones who move through and then go off and carry that same model to other companies. And so we believe strongly in industrial research and how it can complement academia, and we hope that this model will continue to propagate and be invested in by other companies, which makes it harder for us to recruit, of course, but that's a sign of success. And the rising tide lifts all ships.
And where's the idea born with the interns? Is there brainstorming? Is there discussions about, like what?
Where do the ideas come from?
Yeah. As I'm asking the question, I realize how dumb it is, but I'm hoping
no, it's
you have a better answer.
At all. It's
better answer than a better
question I ask at the beginning of every summer. So what will happen is we'll send out a call for interns. We'll have a number of resumes come in. People will contact the candidates, talk to them about their interests. They'll usually try to find somebody who has a reasonably good match to what they're already doing, or just has a really interesting domain that they've been pursuing in their PhD. And we think we'd love to do one of those projects too. And then the intern stays in touch with the mentors, we call them. And then they come, and at the end of 2 weeks, they have to decide. So they'll often have a general sense by the time they arrive, and we'll have internal discussions about what are all the general ideas that we're wanting to pursue to see whether two people have the same idea and maybe they should talk like that. But then once the intern actually arrives, sometimes the idea goes linearly, and sometimes it takes a giant left turn, and we go, that sounded good, but when we thought about it, there's this other project, or it's already been done, and we found this paper, it was scooped. But we have this other great idea. So it's pretty flexible at the beginning. One of the questions for research labs is who's deciding what to do? And then who's to blame if it goes wrong? Who gets the credit if it goes right? And so in Adobe, we push the needle very much towards freedom of choice of projects by the researchers and the interns. But then we reward people based on impact. So if the projects ultimately end up impacting the products and having papers and so on. And so the alternative model, just to be clear, is that you have one lab director who thinks he's a genius and tells everybody what to do, takes all the credit if it goes well, blames everybody else if it goes badly. So we don't want that model. And this helps new ideas percolate up. The art of running such a lab is that there are strategic priorities for the company, and there are areas where we do want to invest in pressing problems. And so it's a little bit of a trickle down and filter up meets in the middle. And so you don't tell people you have to do X, but you say X would be particularly appreciated this year. And then people reinterpret X through the filter of things they want to do and they're interested in. And miraculously, it usually comes together very well. One thing that really helps is Adobe has a really broad portfolio of products. So if we have a good idea, there's usually a product team that is intrigued or interested. So it means we don't have to qualify things too much ahead of time. Once in a while, the product teams sponsor an extra intern because they have a particular problem that they really care about, in which case it's a little bit more, we really need one of these. And then we sort of say, great, I get an extra intern. We find an intern, he thinks that's a great problem. But that's not the typical model. That's sort of the icing on the cake as far as the budget's concerned. And all of the above end up being important. It's really hard to predict at the beginning of the summer which of we all have high hopes of all of the intern projects, but ultimately some of them pay off and some of them sort of are a nice paper but don't turn into a feature. Others turn out not to be as novel as we thought, but they'd be a great feature but on paper. And then others, we make a little bit of progress and we realize how much we don't know, and maybe we revisit that problem several years in a row until finally we have a breakthrough, and then it becomes more on track to impact a product.
Jumping back to big overall view of Adobe Research, what are you looking forward to in 2019 and beyond?
What is you mentioned? There's this giant suite of products,
Yes.
giant suite of ideas, new interns, a large team of researchers. Where do you think? What do you think the future holds?
In terms of the technological breakthroughs.
Technological breakthroughs, especially ones that will make it into product, will get to impact the world.
So I think the creative or the analytical systems that we talked about, where they're constantly trying to figure out what you're trying to do and how can they be helpful and make useful suggestions, is a really hot topic. And it's very unpredictable as to when it'll be ready, but I'm really looking forward to seeing how much progress we make against that. I think some of the core technologies like generative adversarial networks are immensely promising, and seeing how quickly those become practical for mainstream use cases at high resolution with really good quality is also exciting. And they also have this sort of strange way of, even the things they do oddly are odd in an interesting way. So it can look like dreaming or something. So that's fascinating. I think internally we have a Sensei platform, which is a way in which we're pooling our neural nets and other intelligence models into a central platform, which can then be leveraged by multiple product teams at once. So we're in the middle of transitioning from once you have a good idea, you put the product team to work with, and you sort of hand design it for that use case, to a more sort of Henry Ford standard up in a standard way, which can be accessed in a standard way, which should mean that the time between a good idea and impacting our products will be greatly shortened. And when one product has a good idea, many of the other products can just leverage it too. So it's sort of an economy of scale. So that's more about the how than the what. But that combination of this sort of renaissance in AI, there's a comparable one in graphics with real-time ray tracing and other really exciting emerging technologies. And when these all come together, you'll sort of basically be dancing with light, right? Where you'll have real-time shadows, reflections, and as if it's a real world in front of you, but then with all these magical properties brought by AI, where it sort of anticipates or modifies itself in ways that make sense based on how it understands the creative task we're trying to do.
That's a really exciting future for creative, for myself, to the creator. So first of all, I work at autonomous vehicles. I'm a roboticist. I love robots. And I think you have a fascination with snakes, both natural and artificial robots.
Absolutely.
I share your fascination. I mean, their movement is beautiful, adaptable. The adaptability is fascinating. There are, I looked it up, 2,900 species of snakes in the world.
Wow.
375 venomous. Some are tiny, some are huge. Saw that there's one that's 25 feet in some cases. So what's the most interesting thing that you connect with in terms of snakes, both natural and artificial? Why? What was the connection with robotics, AI, and this particular form of robot?
Well, it actually came out of my work in the 80s on computer animation, where I started doing things like cloth simulation and other kind of soft body simulation. And you'd sort of drop it and it would bounce, and then it would just sort of stop moving. And I thought, well, what if you animate the spring lengths and simulate muscles? And the simplest object I could do that for was an earthworm. So I actually did a paper in 1988 called The Motion Dynamics of Snakes and Worms. And I read the physiology literature on both how snakes and worms move, and then did some of the early computer animation examples of that. And
So your interest in robotics
came out of simulation and graphics. When I moved from Alias to Apple, we actually did a movie called Her Majesty's Secret Serpent, which is about a secret agent snake that parachutes in and captures a film canister from a satellite, which tells you how old-fashioned we were thinking back then. Sort of classic 1950s or 60s Bond movie kind of thing. And at the same time, I'd always made radio-controlled ships when I was a child, and from scratch. And I thought, well, how hard can it be to build a real one? And so then started what turned out to be like a 15-year obsession with trying to build better snake robots. And the first one that I built just sort of slithered sideways, but didn't actually go forward. Then I added wheels, and building things in real life makes you honest about the friction. The thing that appeals to me is I love creating the illusion of life, which is what drove me to animation. And if you have a robot with enough degrees of coordinated freedom that move in a kind of biological way, then it starts to cross the uncanny valley into seeming like a creature rather than a thing. And I certainly got that with the early snakes. By S3, I had it able to sidewind as well as go directly forward. My wife-to-be suggested that it would be the ring bearer at our wedding, so it actually went down the aisle carrying the rings, and got them the local paper for that, which was really fun. And this was all done as a hobby. And then at the time, the onboard compute was incredibly limited. It was sort of,
So you should explain that these things. The whole idea is that you're trying to run it autonomously
onboard power, onboard, right? And so the very first one, I actually built the controller from discrete logic because I used to do LSI, circuits and things when I was a teenager. And then the second and third one, the 8-bit microprocessors were available with like a whole 256 bytes of RAM, which you could just about squeeze in. So they were radio controlled rather than autonomous, and really were more about the physicality and coordinated motion. I've occasionally taken a sidestep into, if only I could make it cheaply enough, it would make a great toy, which has been a lesson in how clockwork is its own magical realm that you venture into and learn things about backlash and other things you don't take into account as a computer scientist, which is why what seemed like a good idea doesn't work. So it's quite humbling. And then more recently, I've been building S9, which is a much better engineered version of S3, where the motors wore out and it doesn't work anymore, and you can't buy replacements, which is sad given that it was such a meaningful one. S5 was about twice as long and looked much more biologically inspired. Unlike the typical roboticist, I tapered my snakes. There are good mechanical reasons to do that, but it also makes them look more biological, although it means every segment's unique rather than a repetition, which is why most engineers don't do it. It actually saves weight and leverage and everything. And that one is currently on display at the International Spy Museum in Washington, D.C. Not that it's done any spying. It was on YouTube and it got its own conspiracy theory where people thought that it wasn't real because I work at Adobe, it must be fake graphics. And people would write to me, tell me it's real. And, they say the background doesn't move, and it's like, it's on a tripod, So that one, but you can see the real thing, so it really is true. And then the latest one is the first one where I could put a Raspberry Pi, which leads to all sorts of jokes about Pythons and things. But but this one can have onboard compute. And then where my hobby work and my work are converging is you can now add vision accelerator chips, which can evaluate neural nets and do object recognition and everything. So both for the snakes and more recently for the spider that I've been working on, having desktop level compute is now opening up a whole world of true autonomy with onboard compute, onboard batteries, and still having that sort of biomimetic quality that appeals to children in particular. They're really drawn to them, and adults think they look creepy, but children actually think they look charming. I gave a series of lectures at Girls Who Code to encourage people to take an interest in technology. And at the moment, I'd say they're still more expensive than the value that they add, which is why they're a great hobby for me, but they're not really a great product. It makes me think about doing that very early thing I did at Alias with changing the muscle rest lengths. If I could do that with a real artificial muscle material, then the next snake ideally would use that rather than motors and gearboxes and everything. It would be lighter, much stronger, and more continuous and smooth. So I like to say being in research is a license to be curious, and I have the same feeling with my hobby. It forced me to read biology and be curious about things that otherwise would have just been, National Geographic special. Suddenly I'm thinking, how does that snake move? Can I copy it? I look at the trails that sidewinding snakes leave in sand and see if my snake robots would do the same thing.
So out of something inanimate, I like the way you put it, try to bring life into it.
Absolutely. And then ultimately give it a personality, which is where the intelligent agent research will converge with the vision and voice synthesis to give it a sense of having not necessarily human level intelligence. I think the Turing test is such a high bar, it's a little bit self-defeating, but having one that you can have a meaningful conversation with, especially if you have a reasonably good sense of what you can say. So not trying to have it so a stranger could walk up and have one, but so as a pet owner or a robot pet owner, you could know what it thinks about and what it can reason about.
Or sometimes just that meaningful interaction. If you have the kind of interaction you have with the dog, sometimes you might have a conversation, but it's usually one way.
Absolutely.
And
Right.
nevertheless, it feels like a meaningful connection.
And one of the things that I'm trying to do in the sample audio that we'll play you is beginning to get towards the point where the reasoning system can explain why it knows something or why it thinks something. And that again creates the sense that it really does know what it's talking about, but also for debugging. As you get more and more elaborate behaviors, like why did you decide to do that? Why, how do you know that? I think the robots really are my muse for helping me think about the future of AI and what to invent next.
So even at Adobe, it's mostly operating in the digital world.
Correct.
Do you see a future where Adobe even expands into the more physical world, perhaps, but bringing life not into animations, but bringing life into physical objects, with whether it's
I'd have to say at the moment it's a twinkle in my eye. I think the more likely thing is that we will bring virtual objects into the physical world through augmented reality. And many of the ideas that might take 5 years to build a robot to do, you can do in a few weeks with digital assets. So I think when really intelligent robots finally become commonplace, they won't be that surprising because we'll have been living with those personalities in the virtual sphere for a long time. And then they'll just say, oh, it's Siri with legs or Alexa on hoofs or something. So I can see that world coming. And for now, it's still an adventure, and we don't know quite what the experience will be like. And it's really exciting to sort of see all of these different strands of my career converge.
Yeah, in interesting ways. And it is definitely a fun adventure.
Yeah.
So let me end with my favorite poem, the last two lines of my favorite poem of yours, that ponders mortality, and in some sense, immortality, as our ideas live through the ideas of others, through the work of others. It ends with, do not weep or mourn. It was enough the little atomies permitted just a single dance. Scatter them as deep as your eyes can see. I'm content they'll have another chance. Sweeping more centered parts along, to join a jostling, lifting throng as others danced in me. Beautiful poem, beautiful way to end it. Gavin, thank you so much for talking today, and thank you for inspiring and empowering millions of people like myself, creating amazing stuff.
Oh, thank you. It's a great conversation.
The following is a conversation with Rosalind Picard. She's a professor at MIT, director of the Effective Computing Research Group at the MIT Media Lab, and co-founder of two companies, Affectiva and Empatica. Over 2 decades ago, she launched the field of effective computing with her book of the same name. This book described the importance of emotion in artificial and natural intelligence, the vital role of emotional communication has to the relationship between people in general and human-robot interaction. I really enjoy talking with Roz over so many topics, including emotion, ethics, privacy, wearable computing, and her recent research in epilepsy, and even love and meaning. This conversation is part of the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, iTunes, or simply connect with me on Twitter at Lex Friedman, spelled F-R-I-D. And now, here's my conversation with Rosalind Picard. More than 20 years ago, you coined the term effective computing and led a lot of research in this area. Since then, as I understand, the goal is to make the machine detect and interpret the emotional state of a human being and adapt the behavior of the machine based on the emotional state. So
how has your understanding of the problem space defined by effective computing changed in the past 24 years? So it's the scope, the application, the challenges, what's involved. How has that evolved over the years?
Yeah, actually, originally when I defined the term affective computing, it was a bit broader than just recognizing and responding intelligently to human emotion, although those are probably the two pieces that we've worked on the hardest. The original concept also encompassed machines that would have mechanisms that function like human emotion does inside them. It would be any computing that relates to, arises from, or deliberately influences human emotion. So the human-computer interaction part is the part that people tend to see. Like if I'm, really ticked off at my computer and I'm scowling at it and I'm cursing at it, and it just keeps acting, smiling and happy like that little paperclip used to do, it's dancing, winking. That kind of thing just makes you even more frustrated, right? And I thought that stupid thing needs to see my affect. And if it's going to be intelligent, which Microsoft researchers have worked really hard on, it actually has some of the most sophisticated AI in it at the time. That thing's going to actually be smart. It needs to respond to me and you, and we can send a very different signals.
So, by the way, just a quick interruption. The Clippy, maybe it's in Word 95, 98. I don't remember when it was born. But many people, do you find yourself with that reference that people recognize what you're talking about still to this point?
I don't expect the newest students to these days, but I've mentioned it to a lot of audiences, like how many of you know this Clippy thing, and still the majority of people seem to know it.
So Clippy kind of looks at maybe natural language processing, what you were typing, and tries to help you complete, I think. I don't even remember what Clippy was except annoying.
Yeah, it tried. Some people actually liked it.
Well, I missed it.
I would hear those stories. You miss it?
Well, I missed the annoyance. It felt like there's an
Someone
element.
was there.
Somebody was there. And we were in it together. They were annoying. It's like a puppy that just doesn't get it. They keep ripping up the couch.
And in fact, they could have done it smarter, like a puppy. If they had done, like, if when you yelled at it or cursed at it, if it had put its little ears back and its tail down and shirked off, probably people would have wanted it back, right? But instead, when you yelled at it, what did it do? It smiled, it winked, it danced, right? If somebody comes to my office and I yell at them, they start smiling, winking, and dancing, I'm like, I never want to see you again. So Bill Gates got a standing ovation when he said it was going away, because people were so ticked. It was so emotionally unintelligent, right? It was intelligent about whether you were writing a letter, what kind of help you needed for that context. It was completely unintelligent about, hey, if you're annoying your customer, don't smile in their face when you do it. So that kind of mismatch was something the developers just didn't think about. And intelligence at the time was really all about math and language and chess and games, problems that could be pretty well defined. Social emotional interaction is much more complex than chess or Go or any of the games that people are trying to solve. And in order to understand that required skills that most people in computer science actually were lacking personally.
Well, let's talk about computer science. If things gotten better since the work, since the message, since you've really launched the field with a lot of research work in this space, I still find, as a person like yourself who's deeply passionate about human beings and yet am in computer science, there still seems to be a lack of, sorry to say, empathy in us computer scientists.
Yeah, well,
or hasn't gotten better.
Let's just say there's a lot more variety among computer scientists these days. Computer scientists are a much more diverse group today than they were 25 years ago, and that's good. We need all kinds of people to become computer scientists so that computer science reflects more what society needs. And there's brilliance among every personality type, so it need not be limited to people who prefer computers to other people.
How hard do you think it is? How your view of how difficult it is to recognize emotion or to create a deeply emotionally intelligent interaction? Has it gotten easier or harder as you've explored this further? And how far away are we from cracking this? If you think of the Turing test of the intelligence, looking at the Turing test for emotional intelligence?
I think it is as difficult as I thought it was going to be. I think my prediction of its difficulty is spot on. I think the time estimates are always hard because they're always a function of society's love and hate of a particular topic. If society gets excited and you get you get thousands of researchers working on it for a certain application, that application gets solved really quickly. The general intelligence, the computer's complete lack of ability to have awareness of what it's doing, the fact that it's not conscious, the fact that there's no signs of it becoming conscious, the fact that it doesn't read between the lines, those kinds of things that we have to teach it explicitly, what other people pick up implicitly. We don't see that changing yet. There aren't breakthroughs yet that lead us to believe that that's going to go any faster, which means that it's still going to be kind of stuck with a lot of limitations where it's probably only going to do the right thing in very limited, narrow, pre-specified contexts where we can prescribe pretty much what's going to happen there. So I don't see it's hard to predict the date because when people don't work on it, it's infinite. When everybody works on it, you get a nice piece of it, well solved in a short amount of time. I actually think there's a more important issue right now than the difficulty of it, and that's causing some of us to put the brakes on a little bit. Usually we're all just like, step on the gas, let's go faster. This is causing us to pull back and put the brakes on. And that's the way that some of this technology is being used in places like China right now. And that worries me so deeply that it's causing me to pull back myself on a lot of the things that we could be doing and try to get the community to think a little bit more about, okay, if we're going to go forward with that, how can we do it in a way that puts in place safeguards that protect people?
The technology we're referring to is when a computer senses the human being, like the human face.
Yeah.
Right.
Yeah.
So there's a lot of exciting things there, like forming a deep connection with a human being. So what are your worries how that could go wrong? Is it in terms of privacy? Is it in terms of other kinds of more subtle
privacy? So here in the U.S., if I'm watching a video of, say, a political leader, and in the U.S. we're quite free, as we all know, to even criticize the president of the United States, right? Here, that's not a shocking thing. It happens, about every 5 seconds, right? But in China, what happens if you criticize the leader of the government, right? And so people are very careful not to do that. However, what happens if you're simply watching a video and you make a facial expression that shows a little bit of skepticism, right? Well, here we're completely free to do that. In fact, we're free to fly off the handle and say anything we want. Usually, there's some restrictions. When the athlete does this as part of the national broadcast, maybe the teams get a little unhappy about picking that forum to do it, right? But that's more a question of judgment. We have these freedoms, and places that don't have those freedoms, what if our technology can read your underlying affective state? What if our technology can read it even non-contact? What if our technology can read it without your prior consent? And here in the US, in my first company, we started Affectiva. We have worked super hard to turn away money and opportunities to try to read people's affect without their prior informed consent. And even the software that is licensable, you have to sign things saying you will only use it in certain ways, which essentially is get people's buy-in, right? Don't do this without people agreeing to it. There are other countries where they're not interested in people's buy-in. They're just gonna use it. They're gonna inflict it on you, and if you don't like it, you better not scowl in the direction of any censors.
Let me just comment on a small tangent. With the idea of adversarial examples and deep fakes and so on.
Yeah.
What you bring up is actually, in that one sense, deep fake provide a comforting protection that that you can no longer really trust that the video of your face was legitimate, and therefore you always have an escape clause if a government is trying, if a stable, balanced, uh, ethical government is trying to accuse you of something. At least you have protection. You could say it was fake news. This is a popular term now.
Yeah, that's the general thinking of it. We know how to go into the video and see, for example, your heart rate and respiration, and whether or not they've been tampered with. And we also can put like fake heart rate and respiration in your video now too. We decided we needed to do that after we developed a way to extract it. We decided we also needed a way to jam it, right? And so the fact that we took time to do that other stuff too, right? That was time that I wasn't spending making the machine more affectively intelligent. And there's a choice in how we spend our time, which is now being swayed a little bit less by this goal and a little bit more like by concern about what's happening in society and what kind of future do we want to build. And as we step back and say, okay, we don't just build AI to build AI to make Elon Musk more money or to make Amazon and Jeff Bezos more money. Gosh, that's the wrong ethic. Why are we building it? What is the point of building AI? It used to be, it was driven by researchers in academia to get papers published and to make a career for themselves and to do something cool, right? Like, because maybe it could be done. Now we realize that this is enabling rich people to get vastly richer. The poor the divide is even larger. And is that the kind of future that we want? Maybe we want to maybe we want to rethink AI. Maybe we want to rethink the problems in society that are causing the greatest inequity and rethink how to build AI that's not about a general intelligence, but that's about extending the intelligence and capability of the have-nots so that we close these gaps in society.
Do you hope that kind of stepping on the brake happens organically? Because I think still majority of the force behind AI is the desire to publish papers, is to make money without thinking about the why. Do you hope it happens organically? Is there room for regulation?
Yeah, great questions. I prefer they talk about the carrot versus the stick. I definitely prefer the carrot to the stick. And, in our free world, there's only so much stick, right? You're going to find a way around it. I generally think less regulation is better. That said, even though my position is classically carrot, no stick, no regulation, I think we do need some regulations in this space. I do think we need regulations around protecting people with their data, that you own your data, not Amazon, not Google. I would like to see people own their own data. I would also like to see the regulations that we have right now around lie detection being extended to emotion recognition in general. That right now you can't use a lie detector on an employee when you're on a candidate when you're interviewing them for a job. I think similarly we need to put in place protection around reading people's emotions without their consent, and in certain cases like characterizing them for a job and other opportunities. So I also think that when we're reading emotion that's predictive around mental health, that should, even though it's not medical data, that should get the kinds of protections that our medical data gets. What most people don't know yet is right now with your smartphone use, and if you're wearing a sensor and you want to learn about your stress and your sleep and your physical activity and how much you're using your phone and your social interaction, all of that non-medical data, when we put it together with machine learning, now called AI, even though the founders of AI wouldn't have called it that, that capability can not only tell that you're calm right now or that you're getting a little stressed, but it can also predict how you're likely to be tomorrow. If you're likely to be sick or healthy, happy or sad, stressed or calm.
Especially when you're tracking data over time.
Especially when we're tracking a week of your data or more.
Do you have an optimism towards, that a lot of people on our phones are worried about this camera that's looking at us. for the most part, on balance, are you optimistic about the benefits that can be brought from that camera that's looking at billions of us, or should we be more worried?
I think we should be a little bit more worried about who's looking at us and listening to us. The device sitting on your countertop in your kitchen, whether it's Alexa or Google Home or Apple Siri, these devices want to listen. Well, they say ostensibly to help us, and I think there are great people in these companies who do want to help people. Let me not brand them all bad. I'm a user of products from all of these companies. I'm naming all the A companies: Alphabet, Apple, Amazon. They are awfully big companies, right? They have incredible power, and what if China were to buy them, right? And suddenly all of that data were not part of free America, but all of that data were part of somebody who just wants to take over the world, and you submit to them. And guess what happens if you so much as smirk the wrong way when they say something that you don't like? Well, they have re-education camps, right? That's a nice word for them. By the way, they have a surplus of organs for people who have surgery these days. They don't have an organ donation problem because they take your blood and they know you're a match. And the doctors are on record of taking organs from people who are perfectly healthy and not prisoners. They're just simply not the favored ones of the government. And that's a pretty freaky, evil society. And we can use the word evil there.
I was born in the Soviet Union. I can certainly connect to the worry that you're expressing. At the same time, probably both you and I, and you very much so, there's an exciting possibility that you can have a deep connection with the machine.
Yeah.
Right. So
those of us, I've admitted students who say that they, when you list who do you most wish you could have lunch with or dinner with, right? And they'll write I don't like people. I just like computers. And one of them said to me once when I had this party at my house, I want you to know this is my only social event of the year, my one social event of the year. Okay. Now, this is a brilliant machine learning person, right? And we need that kind of brilliance in machine learning. And I love that computer science welcomes people who love people and people who are very awkward around people. I love that this is a field that anybody could join. We need all kinds of people. And you don't need to be a social person. I'm not trying to force people who don't like people to suddenly become social. At the same time, if most of the people building the AIs of the future are the kind of people who don't like people, we've got a little bit of a problem.
Well, hold on a second. So let me push back on that. So don't you think a large percentage of the world can, there's loneliness. There's
a huge problem with loneliness that's growing.
And so there's a longing for connection. Do you?
If you're lonely, you're part of a big and growing group.
Yes. So we're in it together, I guess. If you're lonely,
you're not alone.
You're not alone. That's a good one. But do you think there's you talked about some worry, but do you think there's an exciting possibility that something like Alexa, like these kinds of tools, can alleviate that loneliness in a way that other humans can't?
Yeah, definitely. I mean, a great book can kind of alleviate loneliness, right? Because you just get sucked into this amazing story and you can't wait to go spend time with that character, right? And they're not a human character. There's a human behind it. But yeah, it can be an incredibly delightful way to pass the hours. And it can meet needs. Even, I don't read those trashy romance books, but somebody does, right? And what are they getting from this? Well, probably some of that feeling of being there, right? Being there in that social moment, that romantic moment, or connecting with somebody. I've had a similar experience reading some science fiction books, right? Connecting with the character. Orson Scott Card, just amazing writing and Ender's Game. And and Speaker for the Dead, terrible title, but those kind of books that pull you into a character, and you feel like you feel very social. It's very connected, even though it's not responding to you. And a computer, of course, can respond to you, so it can deepen it, right? You can have a very deep connection, much more than the movie Her, plays up, right?
Well, not much more. I mean, movie Her is already a pretty deep connection, right?
Well, but it's just a movie, right? It's scripted. It's
Okay.
just But I mean, like, there can be a real interaction where the character can learn and you can learn. You could imagine it not just being you and one character. You can imagine a group of characters. You can imagine a group of people and characters, human and AI, connecting, where maybe a few people can't sort of be friends with everybody, but the few people and their AIs can befriend more people. There can be an extended human intelligence in there where each human can connect with more people that way. But it's still very limited. But there are just what I mean is there are many more possibilities than what's in that movie.
So there's a tension here. The one you expressed a really serious concern about privacy, about how governments can misuse the information, and there's the possibility of this connection. So let's look at Alexa.
Yeah.
So personal assistants, for the most part, as far as I'm aware, they ignore your emotion. They ignore even the context or the existence of you, the intricate, beautiful, complex aspects of who you are, except maybe aspects of your voice that help it recognize for speech recognition. Do you think they should move towards trying to understand your emotion?
All of these companies are very interested in understanding human emotion. They want more people are telling Siri every day they want to kill themselves. Apple wants to know the difference between if a person is really suicidal versus if a person is just kind of fooling around with Siri, right? The words may be the same, the tone of voice and what surrounds those words is pivotal to understand if they should respond in a very serious way, bring help to that person, or if they should kind of jokingly tease back, you just want to, sell me for something else, right? Like how do you respond when somebody says that? Well, you do want to err on the side of being careful and taking it seriously. People want to know if the person is happy or stressed, in part, so let me give you an altruistic reason and a business profit motivated reason. And there are people and companies that operate on both principles. The altruistic people really care about their customers and really care about helping you feel a little better at the end of the day. And it would just make those people happy if they knew that they made your life better. If you came home stressed and after talking with their product, you felt better. There are other people who maybe have studied the way affect affects decision making and prices people pay, and they know, I don't know if I should tell you, like the work of Jen Lerner on heartstrings and purse strings. If we manipulate you into a slightly sadder mood, you'll pay more, right? You'll pay more to change your situation. You'll pay more for something you don't even need to make yourself feel better. So, if they sound a little sad, maybe I don't want to cheer them up. Maybe first I want to help them get something, little shopping therapy, right, that helps them.
Which is really difficult for a company that's primarily funded on advertisement. So they're encouraged to get you
to offer you products, or Amazon is primarily funded on you buying things from their store. So I think we should be, maybe we need regulation in the future to put a little bit of a wall between these agents that have access to our emotion and agents that want to sell us stuff. Maybe there needs to be a little bit more of a firewall in between them.
So maybe digging in a little bit on the interaction with Alexa, you mentioned, of course, a really serious concern about like recognizing emotion if somebody is speaking of suicide or depression and so on. But what about the actual interaction itself? Do you think if I you mentioned Clippy and being annoying. what is the objective function we're trying to optimize? Is it minimize annoyingness or minimize or maximize happiness? Or if we look at human-to-human relations, I think that push and pull, the tension, the dance, the annoying, the flaws, that's what makes it fun. So is there is there a room for, like what is the
at
objective
times when
function?
you wanna have a little push and pull. Think of kids sparring, right? I see my sons, and one of them wants to provoke the other to be upset, and that's fun. And it's actually healthy to learn where your limits are, to learn how to self-regulate. You can imagine a game where it's trying to make you mad, and you're trying to show self-control. And so if we're doing a AI human interaction that's helping build resilience and self-control, whether it's to learn how to not be a bully or how to turn the other cheek or how to deal with an abusive person in your life, then you might need an AI that pushes your buttons, right? But in general, do you want an AI that pushes your buttons? Probably depends on your personality. I don't. I want one that's respectful, that is there to serve me, and that is there to extend my ability to do things. I'm not looking for a rival. I'm looking for a helper. And that's the kind of AI I'd put my money on.
Your sense is for the majority of people in the world, in order to have a rich experience, that's what they're looking for as well. So they're not if you look at the movie Her, spoiler alert, I believe the program, the woman in the movie Her leaves the person for somebody else.
Right.
Says they don't want to be dating anymore. Right. Like, do you? Your sense is if Alexa said, you know what, I'm actually had enough of you for a while, so I'm going to shut myself off. You don't see that as.
I'd say you're trash because I paid for you, right? Okay. We've got to remember, and this is where this blending human AI as if we're equals is really deceptive, because AI is something at the end of the day that my students and I are making in the lab, and we're choosing what it's allowed to say, when it's allowed to speak, what it's allowed to listen to, what it's allowed to act on given the inputs that we choose to expose it to, what outputs it's allowed to have. It's all something made by a human. And if we want to make something that makes our lives miserable, fine, I wouldn't invest in it as a business, unless it's just there for self-regulation training. But I think we need to think about what kind of future we want. And actually, your question, I really like the, what is the objective function? Is it to calm people down? Sometimes. Is it to always make people happy and calm them down? Well, there's a book about that, right? The Brave New World, make everybody happy, take your soma. If you're unhappy, take your happy pill. And if you refuse to take your happy pill, well, we'll threaten you by sending you to Iceland to live there. I lived in Iceland for years. It's a great place. Don't take your soma. Go to Iceland. A little TV commercial there. I was a child there for a few years. It's a wonderful place. So that part of the book never scared me. but really, do we want AI to manipulate us into submission, into making us happy? Well, if you are a a power-obsessed, sick dictator individual who only wants to control other people to get your jollies in life, then yeah, you want to use AI to extend your power and your scale to force people into submission. If you believe that the human race is better off being given freedom and the opportunity to do things that might surprise you, then you want to use AI to extend people's ability to build. You want to build AI that extends human intelligence, that empowers the weak and helps balance the power between the weak and the strong, not that gives more power to the strong.
So in this process of empowering people and sensing people, what is your sense on emotion in terms of recognizing emotion, the difference between emotion that is shown and emotion that is felt? So emotion that is expressed on the surface through your face, your body, and various other things, and what's actually going on deep inside on the biological level, on the neuroscience level, or some kind of cognitive level.
Yeah, yeah. Whoa, no easy questions here.
Well, it's like, yeah, I'm sure there's
Yeah.
there's no definitive answer, but what's your sense? How far can we get by just looking at the face?
We're very limited when we just look at the face, but we can get farther than most people think we can get. People think, hey, I have a great poker face, therefore all you're ever going to get from me is neutral. Well, that's naive. We can read with an ordinary camera on your laptop or on your phone. We can read from a neutral face if your heart is racing. We can read from a neutral face if your breathing is becoming irregular and showing signs of stress. We can read under some conditions that maybe I won't give you details on, how your heart rate variability power is changing. That could be a sign of stress, even when your heart rate is not necessarily accelerating. So,
sorry, from the zeosensors or from the face?
From the color changes that you cannot even see, but the camera can see.
Amazing. So you can get a lot of signal, but
so we get things people can't see using a regular camera, and from that we can tell things about your stress. So if you were just sitting there with a blank face thinking nobody can read my emotion, well, you're wrong.
Right, so that's really interesting, but that's from sort of visual information from the face. That's almost like cheating your way to the physiological state of the body by being very clever with what you can do with
signal processing.
Signal processing. Yeah. So that's really impressive. But if you just look at the stuff we humans can see, the smile, the smirks, the subtle, all the facial
right. So then you can hide that on your face for a limited amount of time. Now, if you're just going in for a brief interview and you're hiding it, that's pretty easy for most people. If you are, however, surveilled constantly everywhere you go, then it's going to say, gee, Lex used to smile a lot, and now I'm not seeing so many smiles. And Roz used to, laugh a lot and smile a lot very spontaneously. And now I'm only seeing these not so spontaneous looking smiles, and only when she's asked these questions. That's something's changed here. We could look at that too. So now I have to be a little careful too. When I say you think we can't read your emotion and we can, it's not that binary. What we're reading is more some physiological changes that relate to your activation. Now, that doesn't mean that we know everything about how you feel. In fact, we still know very little about how you feel. Your thoughts are still private. Your nuanced feelings are still completely private. We can't read any of that. So there's some relief that we can't read that. Even brain imaging can't read that. Wearables can't read that. However, as we read your body state changes and we know what's going on in your environment and we look at patterns of those over time, we can start to make some inferences about what you might be feeling. And that is where it's not just the momentary feeling, but it's more your stance towards things. And that could actually be a little bit more scary with certain kinds of governmental control freak people who want to know more about, are you on their team or are you not?
And getting that information through over time. So you're saying there's a lot of signal by looking at the change over time.
Yeah.
So you've done a lot of exciting work, both in computer vision and physiological stuff like wearables. What do you think is the best modality for, what's the best window into the emotional soul? Like, is it the face? Is it the voice?
Depends what you want to know. It depends what you want to know. It depends what you want to know. Everything is informative. Everything we do is informative.
So for health and well-being and things like that, do you find the wearable physiotechnology for measuring physiological signals is the best for health-based stuff?
So here I'm just going to answer it empirically with data and studies we've been doing. We've been doing studies now. These are currently running with lots of different kinds of people, but where we publish data, and I can speak publicly to it, the data are limited right now to New England college students. So that's a small group. Among New England college students, when they are wearing a wearable, like like the hepatic brace here that's measuring skin conductance, movement, temperature. And when they are using a smartphone that is collecting their time of day of when they're texting, who they're texting, their movement around it, their GPS, the weather information based upon their location. And when it's using machine learning and putting all of that together and looking not just at right now, but looking at your rhythm of behaviors over about a week. When we look at that, we are very accurate at forecasting tomorrow's stress, mood, and happy, sad mood, and health. And when we look at which pieces of that are most useful, first of all, if you have all the pieces, you get the best results. If you have only the wearable, you get the next best results. And that's still better than 80% accurate at forecasting tomorrow's levels.
Isn't that exciting? Because the wearable stuff with physiological information, it feels like it violates privacy less than the non-contact face-based methods.
Yeah, it's interesting. I think what people sometimes don't, it's funny, in the early days people would say, oh, wearing something or giving blood is invasive, right? Whereas a camera is less invasive because it's not touching you. I think on the contrary, the things that are not touching you are maybe the scariest because you don't know when they're on there. And you don't know when, and you don't know who's behind it, right? A wearable, depending upon what's happening to the data on it, if it's just stored locally or if it's streaming and what it is being attached to, in a sense, you have the most control over it because it's also very easy to just
take it off,
right? Now it's not sensing me. So if I'm uncomfortable with what it's sensing, now I'm free, right? If I'm comfortable with what it's sensing, then, and I happen to know everything about this one and what it's doing with it, so I'm quite comfortable with it, then I'm, I have control, I'm comfortable. Control is one of the biggest factors for an individual in reducing their stress. If I have control over it, if I know all there is to know about it, then my stress is a lot lower and I'm making an informed choice about whether to wear it or not, or when to wear it or not. I want to wear it sometimes, maybe not others.
Right. So that control, yeah, I'm with you. That control, even if, the ability to turn it off is a really important thing.
It's huge, and we need to maybe, if there's regulations, maybe that's number one to protect is people's ability to. It's easy to opt out as to opt in.
So you've studied a bit of neuroscience as well. How have looking at our own minds, of the biological stuff, of the neurobiological, the neuroscience that gets signals in our brain, help you understand the problem and the approach of effectively shooting stroke?
So originally I was a computer architect. I was building hardware and computer designs, and I wanted to build ones that work like the brain. So I've been studying the brain as long as I've been studying how to build computers.
Have you figured out anything yet?
Very little. It's so amazing. They used to think, like, oh, if you remove this chunk of the brain and you find this function goes away, well, that's the part of the brain that did it. And then later they realized if you remove this other chunk of the brain, that function comes back, and oh no, we really don't understand it. Brains are so interesting and changing all the time and able to change in ways that will probably continue to surprise us. When we were measuring stress, you may know the story where we found an unusual big skin conductance pattern on one wrist in one of our kids with autism. And in trying to figure out how on earth you could be stressed on one wrist and not the other, like how can you get sweaty on one wrist, right? When you get stressed, get that sympathetic fight or flight response. But you kind of should sweat more in some places than others, but not more on one wrist than the other. That didn't make any sense. We learned that what had actually happened was a part of his brain had unusual electrical activity, and that caused an unusually large sweat response on one wrist and not the other. And since then, we've learned that seizures cause this unusual electrical activity. And depending where the seizure is, if it's in one place, it's staying there, you can have a big electrical response we can pick up with a wearable at one part of the body. You can also have a seizure that spreads over the whole brain, generalized grand mal seizure, and that response spreads, and we can pick it up pretty much anywhere. As we learned this, and then later built Embrace that's now FDA cleared for seizure detection, we have also built relationships with some of the most amazing doctors in the world who not only help people with unusual brain activity or epilepsy, but some of them are also surgeons, and they're going in and they're implanting electrodes, not just to momentarily read the strange patterns of brain activity that we like to see return to normal, but also to read out continuously what's happening in some of these deep regions of the brain during most of life when these patients are not seizing. Most of the time they're not seizing, most of the time they're fine. And so we are now working on mapping those deep brain regions that you can't even usually get with EEG scalp electrodes because the changes deep inside don't reach the surface. But interesting, when some of those regions are activated, we see a big skin conductance response. Who would have thunk it, right? Like nothing here, but something here. In fact, right after seizures that we think are the most dangerous ones that proceed what's called SUDA, sudden unexpected death in epilepsy. There's a period where the brainwaves go flat, and it looks like the person's brain has stopped, but it hasn't. The activity has gone deep into a region that can make the cortical activity look flat, like a quick shutdown signal here. It can unfortunately cause breathing to stop if it progresses long enough. Before that happens, we see a big skin conductance response in the data that we have. The longer this flattening, the bigger our response here. So we have been trying to learn, initially, like, why are we getting a big response here when there's nothing here? Well, it turns out there's something much deeper. So we can now go inside the brains of some of these individuals, fabulous people who usually aren't seeking, and get this data and start to map it. So that's the active research that we're doing right now with top medical partners.
So this wearable sensor that's looking at skin conductance can capture sort of the ripples of the complexity of what's going on in our brain. So you can this little device, you have a hope that you can start to get the signal from the initial things happening in the brain.
Yeah, we've already published the strong correlations between the size of this response and flattening that happens afterwards. And unfortunately also in a real SUDEP case where the patient died because we don't know why. We don't know if somebody was there, would have definitely prevented it. But we know that most SUDEPs happen when the person's alone. And in this case, a SUDEP is an acronym, SUDEP, and it stands for the number 2 cause of years of life lost, actually, among all neurological disorders. Stroke is number 1, SUDEP is number 2, but most people haven't heard of it. Actually, I'll plug my TED Talk. It's on the front page of TED right now that talks about this. And we hope to change that. I hope everybody who's heard of SIDS and stroke will now hear of SUDEP, because we think in most cases it's preventable if people take their meds and aren't alone when they have a seizure. Not guaranteed to be preventable. There are some exceptions, but we think most cases probably are.
So you have this Embrace now in version 2 wristband, right? For epilepsy management. That's the one that's FDA approved.
Yes.
Which is kind of a
FDA cleared. Yeah.
Sorry.
No, it's okay. It essentially means it's approved for marketing.
Got it. Just a side note, how difficult is that to do? It's essentially getting FDA approval for computer science technology.
It's so agonizing. It's much harder than publishing multiple papers in top medical journals. Yeah, we published peer-reviewed top medical journal neurology, best results, and that's not good enough for the FDA.
Is that so if we look at the peer review of medical journals, there's flaws, the strengths, is the FDA approval process. How does it compare to the peer review process? Does it have
I've taken peer review over
There she is.
But is that a good thing? Is that a good thing for FDA? Are you saying, does it stop some amazing technology from getting through?
Yeah, it does. The FDA performs a very important good role in keeping people safe. They keep things, they put you through tons of safety testing, and that's wonderful, and that's great. I'm all in favor of the safety testing. sometimes they put you through additional testing that they don't have to explain why they put you through it, and you don't understand why you're going through it, and it doesn't make sense, and that's very frustrating. And maybe they have really good reasons, and they just do people a service to articulate those reasons. Be more gentle.
So, as part of Empatica, we have sensors. So, what kind of problems do we crack? So what kind of things, from seizures to autism, to I think I've heard you mention depression. What kind of things can we alleviate? Can we detect? What's your hope? How we can make the world a better place with this wearable tech?
I would really like to see my fellow brilliant researchers step back and say, what are the really hard problems that we don't know how to solve that come from people maybe we don't even see in our normal life because they're living in the poorer places, they're stuck on the bus, they can't even afford the Uber or the Lyft or the data plan or all these other wonderful things we have that we keep improving on. Meanwhile, there's all these folks left behind in the world, and they're struggling with horrible diseases, with depression, with epilepsy, with diabetes, with just awful stuff that maybe a little more time and attention hanging out with them and learning what are their challenges in life, what are their needs, how do we help them have jobs, how do we help them have a hope and a future and a chance to have the great life that so many of us building technology have. And then how would that reshape the kinds of AI that we build? How would that reshape the apps that we build? Or maybe we need to focus on how to make things more low cost and green instead of $1,000 phones that can come on. Why can't we be thinking more about things that do more with less for these folks? Quality of life is not related to the cost of your phone. It's not something that, it's been shown that about $75,000 of income and happiness is the same. Okay. However, I can tell you get a lot of happiness from helping other people. You get a lot more than $75,000 back. So how do we connect up the people who have real needs with the people who have the ability to build the future and build the kind of future that truly improves the lives of all the people that are currently being left behind?
So when you return briefly and the point, maybe in the movie Her, do you think if we look farther into the future, is there so much of the benefit from making our technology more empathetic to us human beings, to make them better tools, empower us, make our lives better? If we look farther into the future, do you think we'll ever create an AI system that we can fall in love with and loves us back on a level that is similar to human-to-human interaction, like in the movie Her or beyond?
I think we can simulate it in ways that could sustain engagement for a while. Would it be as good as another person? I don't think so. For if you're used to good people, now if you've just grown up with nothing but abuse and you can't stand human beings, can we do something that helps you there, that gives you something through a machine? Yeah, but that's a pretty low bar, right? If you've only encountered pretty awful people. If you've encountered wonderful, amazing people, we're nowhere near building anything like that. And I would not bet on building it. I would bet instead on building the kinds of AI that helps kind of raise all boats, and helps all people be better people, helps all people figure out if they're getting sick tomorrow, and helps give them what they need to stay well tomorrow. That's the kind of AI I want to build that improves human lives. Not the kind of AI that just walks on the Tonight Show and people go, wow, look how smart that is. Really? And then it goes back in a box,
So on that point, if we continue looking a little bit into the future, do you think an AI that's empathetic and does improve our lives need to have a physical presence, a body, and even, let me cautiously say the word consciousness, and even fear of mortality? So some of those human characteristics, do you think it needs to have those aspects? or can it remain simply a machine learning tool that learns from data of behavior that learns to make us, based on previous patterns, feel better? Or does it need those elements of consciousness?
It depends on your goals. If you're making a movie, it needs a body. It needs a gorgeous body. It needs to act like it has consciousness. It needs to act like it has emotion, right? Because that's what sells. That's what's going to get me to show up and enjoy the movie. Okay. In real life, does it need all that? Well, if you've read Orson Scott Card, Ender's Game, speaking of that, it could just be like a little voice in your earring, right? And you could have an intimate relationship, and it could get to know you. It doesn't need to be a robot. But that doesn't make this compelling of a movie, right? Yeah, I mean, we already think it's kind of weird when a guy looks like he's talking to himself on the train, even though it's earbuds. So we have these, embodied is more powerful. Embodied, when you compare interactions with an embodied robot versus a video of a robot versus no robot, the robot is more engaging. The robot gets our attention more. The robot, when you walk in your house, is more likely to get you to remember to do the things that you asked it to do because it's kind of got a physical presence. You can avoid it if you don't like it. It could see you're avoiding it. There's a lot of power to being embodied. There will be embodied AIs. They have great power and opportunity and potential. There will also be AIs that aren't embodied, that just are little software assistants that help us with different things, that may get to know things about us. Will they be conscious? There will be attempts to program them to make them appear to be conscious. We can already write programs that make it look like, what do you mean? Of course I'm aware that you're there, right? I mean, it's trivial to say stuff like that. It's easy to fool people, but does it actually have conscious experience like we do? Nobody has a clue how to do that yet. That seems to be something that is beyond what any of us know how to build now. Will it have to have that? I think you can get pretty far with a lot of stuff without it. Will we accord it rights? Well, that's more a political game than it is a question of real consciousness.
Yeah, can you go to jail for turning off Alexa? Is what it's a question for an election maybe a few decades.
Well, Sophia Robot's already been given rights as a citizen in Saudi Arabia, right? Even before women have full rights. Then the robot was still put back in the box to be shipped to the next place where it would get a paid appearance, right?
Yeah, it's dark and almost comedic, not absurd. So, I've heard you speak about your journey in finding faith.
Sure.
And how you discovered some wisdoms about life and beyond from reading the Bible. And I've also heard you say that scientists too often assume that nothing exists beyond what can be currently measured.
Materialism and scientism. Yeah.
So in some sense, this assumption enables the near-term scientific method, assuming that we can uncover the mysteries of this world by the mechanisms of measurement that we currently have. But we easily forget that we've made this assumption. So what do you think we missed out on by making that assumption?
It's fine to limit the scientific method to things we can measure and reason about and reproduce. That's fine. I think we have to recognize that sometimes we scientists also believe in things that happened historically. Like I believe the Holocaust happened. I can't prove events from past history scientifically. You prove them with historical evidence, right? With the impact they had on people, with eyewitness testimony and things like that. So a good thinker recognizes that science is one of many ways to get knowledge. It's not the only way. And there's been some really bad philosophy and bad thinking recently. We call it scientism, where people say science is the only way to get to truth. And it's not. It just isn't. There are other ways that work also, like knowledge of love with someone. You don't prove your love through science, right? So history, philosophy, love, a lot of other things in life show us that there's more ways to gain knowledge and truth, if you're willing to believe there is such a thing, and I believe there is, than science. I am a scientist, however, and in my science, I do limit my science to the things that the scientific method can do. But I recognize that it's myopic to say that that's all there is.
Right, there's just like you listed, there's all the wide questions, and really we know, if we're being honest with ourselves, the percent of what we really know is basically zero relative to the full
measure theory, a set of measure theory. I have a finite amount of knowledge, which I do.
So you said that you believe in truth. So let me ask that old question. What do you think this thing is all about? Life on Earth?
Life, the universe, and everything.
What's
I can't quote Douglas Adams. 42. That's my favorite number. By the way, that's 40. My street address. My husband and I guessed the exact same number for our house. We got to pick it. And there's a reason we picked 42. Yeah.
So is it just 42, or do you have other words to put around it?
Well, I think there's a grand adventure, and I think this life is a part of it. I think there's a lot more to it than meets the eye and the heart and the mind and the soul here. I think we see but through a glass dimly in this life. We see only a part of all there is to know. If people haven't read the Bible, they should, if they consider themselves educated. And you could read Proverbs and find tremendous wisdom in there that cannot be scientifically proven, but when you read it, there's something in you, like a musician knows when the instrument's played right and it's beautiful. There's something in you that comes alive and knows that there's a truth there, that like your strings are being plucked by the master instead of by me, right? Playing when I pluck it, but probably when you play it sounds spectacular, right? And when you encounter those truths, there's something in you that's different and knows that there is more than what I can prove mathematically or program a computer to do. Don't get me wrong, the math is gorgeous. The computer programming can be brilliant. It's inspiring, right? We want to do more. None of this squashes my desire to do science or to get knowledge through science. I'm not dissing the science at all. I grow even more in awe of what the science can do because I'm more in awe of all those we don't know. And really at the heart of science, you have to have a belief that there's truth, that there's something greater to be discovered. And some scientists may not want to use the faith word, but it's faith that drives us to do science. It's faith that there is truth, that there's something to know that we don't know, that it's worth knowing, that it's worth working hard, and that there is meaning, that there is such a thing as meaning, which, by the way, science can't prove either. We have to start with some assumptions that there's things like truth and meaning. And these are really questions philosophers own, right? This is their space. Philosophers and theologians at some level. So these are in science, when people claim that science will tell you all truth, there's a name for that. It's its own kind of faith, scientism, and it's very myopic.
Yeah, there's a much bigger world out there to be explored in ways that science may not, at least for now, allow us to explore.
Yeah, and there's and hope, and joy, and love, and all these awesome things that make it all worthwhile.
I don't think there's a better way to end it, Ross. Thank you so much for talking today.
Thanks, Mike. It was a pleasure. Great question.
TV plus dramedy, your friends and neighbors sneaks into the top spot, your #1 stream show.
And those are your top TV streams of the week on iHeartRadio.
iHeartRadio Earth is here with little tips for a healthier planet. A staggering 8 million tons of plastic ends up in the world's oceans every year. If current trends continue, our oceans could contain more plastic than fish by 2050. Do your part. Purchase items made from renewable or recycled content and recycle whenever possible.
The following is a conversation with Ariana Huffington. She's the founder of the Huffington Post in 2005 and the founder and CEO of Thrive Global in 2016. She's the author of 15 books, most recent two being Thrive and Sleep Revolution, both international bestsellers.
These books explore how to both work hard and keep a lifestyle that seeks well-being, wisdom, and wonder. We got a chance to sit down for this quick chat after a conference we both spoke at, and got right into the big topics of mortality, obsession, meaning, happiness, and love. This conversation is part of the Take It Uneasy podcast. If you enjoy it, subscribe on YouTube, iTunes, or simply connect with me on Twitter at Lex Friedman, spelled F-R-I-D. And now, here's my conversation with Ariana Huffington. Can you tell a story of getting recognition for your first book, The Female Woman, when you were 23 and sitting in a hotel and wondering, is this all there is? The old question of meaning and purpose. So now, just a few years later, let me ask from your perspective now, what is the purpose? What is the meaning of life?
Well, if you believe, as every major philosophy and every major spiritual tradition argues, that life does not end with death, but that there is another dimension of consciousness, then clearly a full life, a meaningful life, includes exploring that dimension. And for me, that exploration has been part of my life from my teenage years. I went to Shantiniketan University in India when I was 17 to study comparative religion, and I always wanted to understand what life was about, because I never believed that all this whole experiment ends with each individual death. So that's for me at the heart of my life. I mean, I've always been very active, with books, with the Huffington Post, now with Drive Global, but that's been an underlying dimension that I think gives real meaning to life.
The mortality is a really interesting question at the core of all of these philosophies. You mentioned also memento mori, the Latin remember death, the idea that reflecting on one's own mortality puts things into perspective.
Yes.
Do you, in a tough question, perhaps not, do you often think about your own mortality, and what perspective does that help you gain?
Yes, I think about it a lot, and it does give me perspective, and it does help me focus on the things that matter to me in terms of my children, my close friends, the impact I want to have through what we're doing at Thrive. I have zero interest in what is known as legacy, because since I don't think life ends with death, I'm just much more interested in what happens to my soul and than what happens to my legacy on earth.
Do you have a sense of what happens after you die, of soul? Is it more of a feeling? Do you have a more concrete sense spiritually? How do you see the world, and what happens to your soul, to whoever the heck you were while you were here on earth? What does that become in time?
So my sense is that who we are, our personality, the body, the mind, it's like a car that we rented, and we return at the airport and get on a plane.
Go to another city and rent another car?
No, well, rent another car if you believe in reincarnation, depending on where you are in your state of evolution. But definitely that what survives is the soul. And that's why how we live our lives and the choices we make and how we treat others is so central to what happens after our death.
All of those elements, you believe, kind of feed the soul. So you've also mentioned that on the harsh, challenging part of life, that failure is an essential part of life. So what may be a major failure that stands out to you for yourself? One of the toughest ones for you psychologically to have bounced back from, if you ever did bounce back from?
Yes, well, first of all, I don't think there is a beef. I don't think there is a single successful person who has not failed along the way. I mean, I challenge you to find one. If you do, let me know. But in my experience, everybody has failed along the way. And I think it would be great if successful people talk more about their failures. The difference is resilience and how quickly do we get discouraged. In my case, actually, probably the hardest failure was when I was 28. And my second book, you mentioned my first book, which did very well. My second book, which was on the crisis in political leadership in the West, was rejected by 27 publishers, one after the other, and by that time I had run out of money, and I had been living off the proceeds of my first book. And I remember walking kind of depressed down St. James's Street in London, where I live, and thinking, well, maybe my first book was just a fluke, and I'm not really a writer, and I have to go get a real job. And then I saw Barclays Bank in the corner, and I walked in and asked to see the manager, and asked the manager for what the Brits call an overdraft, which is a loan. And I had nothing. I had no assets. And for some reason, the manager, whose name is Ian Bell, gave it to me. And that kind of changed my life because it made it possible for me to keep things together for another 13 rejections. And at that point, I got an acceptance. And I sent Ian Bell a holiday card every year. And he's a little bit like, in fairy tales when the hero or the heroine gets lost in a dark forest. And suddenly a helpful animal comes out and guides them out of the forest. Well, sometimes helpful animals in our lives are in the form of a bank manager. They take funny disguises.
A modern fairy tale. So I spoke with Elon Musk recently on the podcast, and you've had a friendly exchange with him on Twitter last year about work hours and sleep. So I myself, as an engineer, am obsessed with the work I do. I keep a schedule closer to one that Elon does, I would say. Plus, I'm Russian, so I believe suffering is good for the soul. So how do you square? How does a singular obsession in the sort of the turmoil of innovation fit into a lifestyle you discuss and thrive, one focused on well-being, wisdom, and wonder? So how do you square that with a singular obsession?
Oh, I think singular obsessions are wonderful. All my favorite people are addictive and obsessive personalities. But if you're obsessed about whatever it is you're looking to achieve, whether it's research or electric cars or going to the moon or anything, you need to look at the science and the data that shows that you're going to be more creative and more productive and more likely to achieve the results of your obsession if you actually take some time to recharge. That's really what we're talking about.
So your sense is, so science and data, these things you talk about, are things of rational people. So you think the impossible can be achieved by rational people, or does madness play a role?
Madness plays a role, but also looking at the results needs to play a role. Like, listen, I have huge admiration for Elon Musk, and I wrote the open letter to him with that in mind, kind of lovingly and admiringly, and helping him, I hope, look at the laws of human energy. Because if you violate the laws of human energy, it's like violating the laws of gravity. There are consequences, and he's facing the consequences. He's being distracted from his amazing obsession.
And you think there's a way to do better?
Absolutely. Well, look, I mean, I think you should look at what happened. The results of tweeting in the middle of the night because his cognitive impairment makes him do things which he knows he should not be doing. And ending up having to step down as chairman, pay 20 million, having to go to court to deal with the SEC. Who needs that when we are building something amazing for humanity?
You think more balanced sleep
It's
cycle?
not really about balance. I hate that term because I agree with you that there's no balance when you're trying to achieve something big. I mean, there are times when I've pulled all-nighters. There are times when people at Thrive have pulled all-nighters to ship a product. In fact, we make that very clear when we hire people. We're not a 9-to-5 operation where you just balance things. But you need to, after that, take time to recharge. And the faster you do it, the more effective you're going to be. We call it Thrive time. So let's say you pulled an all-nighter, take some time the next day to recharge before your exhaustion becomes cumulative. Either you do stupid things or you fall sick, or all the things that we're seeing around.
Catches up to you. On another topic, you have evolved throughout the years your political views from, maybe you can correct me, but from right of center to left of center. Can you take me through your journey of political thought and how you see the evolution of the greater political landscape along with your evolution throughout the last several decades?
So my evolution was from being a kind of a Republican that's practically extinct now, kind of pro-choice, pro-gay rights, pro-gun control Republican, to someone who realized that my understanding of the role of government was limited. I really was a Republican because I thought that the private sector would step up and address inequalities and the need to take care of people at the lower socioeconomic ranks. And I saw firsthand this wasn't going to happen and that you needed the raw power of government appropriations to be able to achieve that. So it was my shift in my understanding of the role of government that led to my shift in political views. I think what's happening right now, we're at this moment when the chickens are coming home to roost. Like a lot of problems that we've seen coming, that we've been discussing at endless conferences. I don't know how many conferences I've been at, the title like inclusive capitalism, the dangers of growing inequalities. We talked about them, we didn't really do anything about it. And so the results are different forms of right-wing or left-wing populism. And it's a very serious moment, but I don't think it's going to be solved by living in a perpetual state of outrage.
So you've also launched this incredible platform in 2005 of Huffington Post. HuffPost as it's now called. What impact do you think it had over the past 14 years on the nature of public discourse? If you look at what that discourse is today, the divisiveness, what impact does the digitization of our conversation, the online, of Twitter, and then of more journalistic type of content like Huffington Post contain, what do you think it has done for our discourse? Was it been a positive thing? Was it been a catalyst for the divisiveness, or did it simply reveal the divisiveness that was latent there already? What do you think?
Well, Huffington Post helped democratize the conversation. It helped elevate what blogging was. When we launched the Huffington Post in 2005, blogging was dismissed as something that people who couldn't get a job were doing in the parent basements. And because we brought in people who could have written for the New York Times, like Walter Cronkite and Nora Ephron and Larry David, we elevated the opportunity afforded to all of us to express ourselves. But we're very, very careful guidelines. So, for example, everything was curated. We did not allow ad hominem comments. At some point, before I left the Huffington Post, I even ended anonymous comments altogether because it was becoming too hard to police them. So, from the beginning, I wanted to democratize the conversation, side by side with the investigative journalism and all the things that I loved and honored. But at the same time, I saw the dangers of the toxicity that can infiltrate these conversations if they're not monitored and if there is no real curation.
So one of the core things that emerged from the Huffington Post is, I mean, there is a little bit of a viewpoint on the line. It is left of
Well,
center.
I don't call it left. There's definitely a viewpoint. In fact, we call our journalism beyond right and left. I think the right-left decisions, the way of looking at the world in terms of right and left is incredibly obsolete. Uh, Being concerned about growing inequalities is not a left-wing position. If you're somebody who cares about law and order, you should care about that. Unless you want the country to be turned into a banana republic with rich people living behind gates with security guards. If you care about climate change, does it mean you're on the left or does it mean that you want to preserve the planet? So I think by looking at the world in right or left, we're simply polarizing the conversation.
But so that's a beautiful ideal, and I share it. But nevertheless, it seems that there's a strong gravitational field that pulls people into left and right, and no matter what, they will place different venues into those polars. So it seems that in the public perception, Huffington Post kind of gets to the left, and there's these opposing forces, Breitbart and so on, that get placed somehow into the right. And then there's the red team and the blue team. I guess my question is, do you notice this? Do you see a path forward in the coming decade, in the era of our current president, of maybe bringing us back together and having a healthy disagreement on the issues, as opposed to having teams and tribes of red and blue?
I absolutely do. I think there are two things that are essential in order to achieve that. One is a reverence for facts. You and I have the right to our own opinions, but we don't have the right to our own set of facts. So that's number one. And number two is to end the view of journalism that Jay Rosen has described as the view from nowhere. Like I think climate change is not a matter of opinion. So a lot of journalists feel that their position is to have one person who thinks climate change is real and another person who thinks it's not, and their job is to stay in the middle and play conscious pilot. To me, that's like not at all great journalism, and the Huffington Post definitely had a viewpoint, as you said. But it was a viewpoint based on facts.
And I actually recommend that people listen to your podcast, with a special conversation with Neil deGrasse Tyson, that kind of talks about science and the importance of that people have in terms of the seriousness amongst our leaders towards science as a thing that should be politicized. Well, last question. How do you balance love and ambition? Thinking about your work with Thrive, this obsession towards whether it's building electric cars, going to Mars, building Huffington Post, obsession with your work life, and a genuine deep obsession with your family or people in your life that you love. How do you balance that time and energy?
Well, let me give you an example. Right now, Thrive Global is an obsession. Ending the stress and burnout epidemic is our mission, and I see it as having a huge impact on our health, on our mental health, and on our performance. But at the same time, I have two daughters that I adore, And everybody in my office knows that when I get a call from one of my daughters at any point, I will take it. And that they are a priority. That doesn't mean that I can't also be obsessed about what we're doing and our growth. I think these are sort of false dichotomies because I think when we nurture the part of us that is about love, that is about connection, we also nurture the deeper parts of our humanity, and it's from those parts that wisdom and creativity come.
The more love will strengthen all parts of your life and improve productivity in all aspects.
Exactly, and interestingly enough, Jack Ma, hardly a wilting pilot in the obsession department, said in Davos last year that what's going to win the future is not just IQ or even EQ, emotional intelligence, but LQ, the love quotient. Which is something surprising coming from Jack Ma, but I think it's part of the shift that's happening where we recognize that while AI and machine learning are going to take over huge parts of our life and destroy many jobs, the things that AI is not going to be able to do are the distinctly human things. And loving is one of them.
And so I think it's a beautiful place to end on is love. Ariana, thank you so much for talking today.
Thank you so much.
Why does it always just sit in there not being used? Let's use it. So now we use it.
I know everybody gets good china. I don't know if we did or not. I think we got some. But everyone gets good china for their wedding and they never use it.
Never, ever use it. And so we started using it. It's supposed to be for like formal dinners, I suppose, or when you have guests over. It's just your fancy plates.
The following is conversation with Roswell DePark. He's a professor at MIT, director of the Effective Computing Research
Right, but the guests are saying, "Oh wow."
Group at MIT Media Lab, co-founder of two companies, Effectiva and Empatica. Over 2 decades ago, she launched the field of effective
And I highly recommend it. Just use it. Don't let it just sit
computing
there.
with a book of the same name. This book described the importance of emotion.
Can we still use that term? I don't know. We gotta ask everything nowadays.
Think so.
Can you use China?
Crozier?
Can you use China? The term China? Yeah. For a little while, right? What you're referring to the plates. I'll go away eventually. Now it's just like, hey, it'll be hard plates. Hey, do you guys have the hard plates?
A fancy plates.
The hard fancy plates. What's the break? Hey, do you guys sell hard plates there at Macy's? We're going to a wedding there. They registered for hard plates. You got hard plates? That's what it's going to be eventually. Hard plate store. Yeah. Oh, wow. Man, these people are fancy. Look at Christmas. Hard plates. Hard plates at McCoy. It's a new show on ABC. Hard plates. Damn. And all new China plates. All right, let's, Stephanie, what's going on out there, Bubba? We don't know.
So, Bluebell Ice Cream is actually returning a discontinued flavor that it won in a tournament, and it's called Groom's Cake. It's available today, starting today, and I haven't heard of it, but I definitely want to try it. So, it combines Bluebell milk chocolate ice cream with chocolate cake pieces and chocolate-coated strawberry hearts surrounded by swirls of strawberry sauce and chocolate icing.
God, that sounds great. It sounds awesome. Yeah, that sounds like an emergency room visit afterwards. You know, just if you're even close to a diabetes, you're done. Diabetes. Is it diabetes or diabetes? How do you pronounce that term?
I've heard diabetes, but I've always said diabetes.
Diabetes. Who was the guy on the horse that had it all the time? Wilford Brimley. Well, as you know, I got diabetes. I didn't know, Wilford. I had no idea. I don't know the medical records of people in my immediate family. Why would I know his diet or his records? Remember when he first came out? Well, as you know, I've got diabetes. I had no idea. None. All right, that's right. We're live on KFI. More now with Greg.
Here is the latest from the KFI Newsroom. Park officials say Yosemite National Park is going to require a reservation May 24th through September 4th. That's the peak season. They'll start taking reservations next Tuesday. The British military has joined the U.S. in launching airstrikes against Houthi rebels in Yemen for the first time in the current U.S. offensive. We'll check the 710 freeway next.
All right, let's talk about Sweet James Burger. If you get into an accident out there on the freeways or side streets, whatever you're buzzing around it, you have got to call an unbelievable law firm, and there's nobody we recommend higher than Sweet James. Now, one of our listeners got hurt in a motorcycle accident. How about that? Yeah, did a couple of cartwheels on the 134. He was shocked by the low-ball offer he got from his insurance company. Well, he called Sweet James. The attorneys at Sweet James helped him get the medical care he needed and recover as quickly as possible to get him back on that bike again. There's a gambler. Gets in a radical bike accident. First thing he does is buy another bike. Okay, all right, I don't want to judge him. But then they fought tirelessly and delivered a $400,000 victory. So if you're ever hurt in an accident, you need a great law firm on your side. Nobody better than Sweet James. Phone them up right away, 809-million. 809 million, they win 98% of the time. That's you. 809 million or sweetjames.com.
Let's crash in Linwood.
A southbound transition with the West 105. It's an accident partially blocking lanes at this transition road in the South 710, bumper to bumper from the 10 down to Atlantic Boulevard. North 605, just before Slauson Avenue, a pickup truck and an SUV tangled this crash on the right shoulder. But the 605 northbound very slow from Rosecrans up to the 60. Mid-City 10 westbound just beyond Crenshaw Boulevard, and two vehicle collisions in the center divider, and you're slow coming away from the East LA interchange. With Southern California's most accurate traffic reports, I'm Mike Morris.
The free iHeartRadio app has over 100 commercial-free stations waiting for you to explore right now, like the Beatles Now and Then, celebrating all things Beatles. Legendary clips, deep cuts, live performances, and all their solo hits. Listen commercial-free. Just open the free iHeartRadio app, search Beatles Now and Then, and make it your next preset.
iHeartRadio.
I wonder who that is, honey. Hugs with family.
Grandpa's here.
Get over here. Getting back to the moments we miss starts with getting informed.
I miss you so much, Grandpa.
Get the latest info about COVID-19 vaccines at getvaccineanswers.org. It's up to you. Brought to you by iHeartRadio and the Ad Council.
Here's this week's iHeartRadio countdown of the top TV streams.
Here's what you've made popular by Get Your Stream On. Starting us off this week is Yellow Jackets on Paramount Plus with Showtime. That's followed by the debut of the romantic drama Ransom Canyon on Netflix. The Residents on Netflix slips back to 8, and The Studio on Apple TV Plus also slips back 1 to 7 this week. Debuting at 6 is season 2 of Andor on Disney Plus. The White Lotus on HBO, and Max is in at 5, with Mobland on Paramount Plus slipping back to 4. Kicking off the top 3 is the medical drama The Pit on Max. The Last of Us on HBO, and Max jumps up to number 2. And that means John Hamm's new Apple TV Plus dramedy, Your Friends and Neighbors, sneaks into the top spot, your number 1 stream show.
And those are your top TV streams of the week on iHeartRadio.
Doja Cat, Gwen Stefani, David Guetta, Meghan Trainor, and more. Wingo Tango presented by Fiji Airways. May 10th, Huntington City Beach. All ticket prices go up May 2nd, so get yours now at AXS.com.
Do you owe $10,000 or more in credit card debt or personal loans? With credit card debt at all-time highs, Debt Relief Advocates is urgently notifying consumers of debt relief now being made available, designed to aid consumers with out-of-control credit card debt. Those who qualify and enroll for this relief program will only have to pay back a fraction of what they owe. This is not bankruptcy or a debt consolidation loan. This is a relief program that credit card companies would rather you not know about, as it ends your debt nightmare and saves you lots of money. Consumers owing at least $10,000 in credit card debt or personal loans can now take advantage of this debt relief as the cost of living skyrockets. Debt Relief Advocates has established a relief hotline for you to call to learn what debt reduction you may qualify for, so don't wait. For this free information, call the Relief Hotline at 800-377-9234. 800-377-9234. 800-377-9234.
Free free iHeartRadio app has over 100 commercial-free stations waiting for you to explore right now. Like the Beatles Now and Then, celebrating all things Beatles. Legendary clips, deep cuts, live performances, and all their solo hits. Listen commercial-free. Just open the free iHeartRadio app, search Beatles Now and Then, making your next preset. iHeartRadio. KFI AM 640. More stimulating talk.
LA Police Chief Jim McDonald said he was going to shake up the department, but now with the possibility of layoffs, what's the plan? That's coming up at 7:30 tomorrow morning on the next Bill Handel Show.
KFI AM 640. It is the Conway Show. We have $1,000 that you can win. Here's how you do it.
Now, your chance to win $1,000. Just enter this nationwide keyword on our website. Check. That's check. CHECK. Enter it now at KFIAM640.com/cash. Powered by Sweet James Accident Attorneys. If you're hurt in an accident, winning is everything. Call the winning attorneys at Sweet James. 1-800-9-MILLION. That's 1-800-9-MILLION or sweetjames.com.
Just go to the website, KFIAM640.com/cash. Put the keyword in check, CHECK, and you can win $1,000. $1,000. The LA County Fair is open. That's a cool deal. I think it opened today or tomorrow. I think it's today. Maybe tomorrow.
I think it's tomorrow.
Tomorrow? Okay. And I like the fact that they moved it. It used to be in September, and it was hotter than hell out of Pomona. Always 140 degrees. But they moved it to May. They also beat the Orange County Fair.
When they started just a couple years ago, after the pandemic, when they were restarting that back up, or when things were starting back up again, I love it. I think it's like you say,
it's great.
Weather, if nothing else, so much better. I think it's been a little tough for them to get the traction of population to come in there, but I think it's starting to gather.
Yeah, it's odd that it's not more popular now because September, everybody was in school. I guess everyone's in school now too. What the hell?
Yeah.
But it's a great hang.
And a lot of schools go to it for as part of like field trips and stuff. And it's so much better to do near the end of the year for the kids rather than the beginning.
That's right. Yeah, when you have friends in class and you get to know your classmates and slide out.
Who knew the LA County Fair was even opening tomorrow?
Nobody.
Yeah, that's the other issue.
Right. They've got
the marketing department needs to work on something.
Yeah, they got to come in here. We'll bang that out for them.
I go every year.
Yeah, I used to go when my daughter was younger. We go on the rides.
Yeah.
And since she's gotten older and they took away the racetrack, ghost town for me.
Your interest wanes a
little. Totally over.
It was always a junk food day for me and Sid. I'd take her. We'd always go every year. Just a day of crap.
Oh yeah. You can't see the whole thing in one day too. I mean, there's so many different hangars and departments, and people win awards for setting a table. I saw that at the LA County.
Oh yeah, all the tables.
Yeah. A lady set a table, got an award for that. That's cool.
Like knitting and all kinds.
I don't know who you brag to about that though. Hey, guess what Madge did?
Got a wall of ribbons.
Yeah, she won for best hometown setting of a table.
The garden area, that big closed area, and then the hill behind it with all of the jacuzzis and all that stuff. That's my favorite because it's sort of the island of peace within the storm of the LA County Fair.
And those jacuzzis all look great. Yeah. You want to take them all home. They're very inexpensive too. A couple, like $600-700. There are some that are very expensive.
Yes.
Ones that are
giant ones that hold like 15-20 people.
Yeah, 900 jets. Just jets, banging into every orifice of your body.
You have parties with a lot of people if you get that.
But sometimes when you get a 6-person jacuzzi, why don't you just tell them that you're a swinger? I mean, isn't that just what you do?
Especially when you look at the interior of those things and they're all curves.
Right.
More body parts to be right there.
Yeah, exactly.
Chicks go in that spot. You know it.
Yeah, it's the swinger special out there. And that's, I think they call it, the swinger special.
They got the speakers and the LED lights around it.
That's right.
Yeah, man. Bounce, go wow.
It is cool. The LA County Fair opens tomorrow. All right, so go on out there. It's a cool deal. Weezer, remember Weezer's wife got crazy off the 134? It was an accident. They went into the neighborhood, and Weezer's wife came out, I guess, evidently, allegedly shooting at the cops. Well, she's still paying for that day.
The wife of an LA rock star who was shot and wounded by the LAPD after being accused of pointing a gun at officers appeared in a downtown LA courtroom today. Jillian Schreiner is out on bond after being arrested on suspicion of attempted murder. She is the wife of Weezer bassist Scott Schreiner. Authorities say earlier this month she pointed a gun at officers as police and the CHP searched an Eagle Rock neighborhood for 3 people who fled the scene of a car wreck. Schreiner is due back in court in 2 weeks.
All right, well, that's going to be a busy life for her. I don't know what's going to happen. I mean, when you got a new district attorney in town and they accuse you of shooting or at least pointing a gun at a cop.
The following is a conversation with Alex Garland, writer and director of many imaginative philosophical films, from the dreamlike exploration of human self-destruction in the movie Annihilation, the deep questions of consciousness and intelligence raised in the movie Ex Machina, which to me
They worked pretty good. Oh yeah.
She didn't get killed instead of just shot in the shoulder.
Yeah, and then after she was shot in the shoulder, she handled that pretty well. She then was arrested, and they took her to the hospital. She didn't stay overnight. She got out. Yeah, very tough. And she got out. I think she had a young kid too.
the greatest movies on artificial intelligence ever made. I'm releasing this podcast to coincide with the release of his new series called Devs. It will premiere this Thursday, March 5th on Hulu as part of FX on Hulu. It explores many of the themes this very podcast is about, from quantum mechanics to artificial life to simulation to the modern nature of power in the tech world. I got a chance to watch a preview and loved it. The acting is great. Nick Offerman especially is incredible in it. The cinematography is beautiful, and the philosophical and scientific ideas.
Oh, the Clippers? Well, but the Clippers at least don't play at crypto. Crypto could lose both of its tenants in 24 hours. Both of its big tenants. Because the WNBA is not pulling.
Explored and profound. And for me as an engineer and scientist, it was just fun to see brought to life. For example, if you watch the trailer.
Yeah, that's possible. Somebody asked, I got to read this to you, Berger, and tell me what you think here. I'm going to ask you a question that was posed to me.
The series carefully, you'll see there's a programmer with a Russian accent.
Try to get your answer. Find it here. Okay, here it is. All right. Would you rather? This is a would you rather. Would you rather have courtside tickets to the WNBA Finals or a coupon for one free Junior Frosty at Wendy's?
50 cents off of
Following is a conversation with Stephen Wolfram, a computer scientist, mathematician, theoretical physicist, who is the founder and CEO of Wolfram Research, a company behind Mathematica, Wolfram Alpha, Wolfram Language, and the new Wolfram Physics Project. He's the author of several books, including A New Kind of
It's just not my thing.
Okay.
I mean, some
The
people
Science.
good for them. Good on.
Would you rather have courtside seats at the WNBA Finals or a coupon for one free Junior
Which,
Frosty?
on a personal note, was one of the most influential books.
30% are going to the WNBA.
In computer science and artificial intelligence. It made me fall in love with the mathematical beauty and power of cellular automata. It is true that perhaps
Be over tonight. That game starts at 7 o'clock. Go Kings, go! Maybe go to the airport, go. That's possibly what's going to happen. All right, we're live on K5. We're now through.
The LA City Budget Committee has raised questions about spending on homeless programs.
City facing $8 billion budget shortfall and more than 1,600 layoffs. Putting the $300 million earmarked for homelessness back into the general fund could help. Councilman Tim McOsker says the city needs to figure out its new role in homeless programs since LA County has pulled out of the LA Homeless Services Authority.
When are we going to do an assessment of what we're actually
obligated to do. Homeless spending was the latest topic at the council's budget committee. The Gosper says the county has more money and most homeless issues are its responsibility anyway. Michael Monks, KFI News.
Baseball fans fallen from the bleachers at PNC Park in Pittsburgh during a game between the Pirates and the Chicago Cubs. Happened during the seventh inning last night. This guy says he thinks alcohol was involved.
What it looked like is someone had a little too much and just simply over rejoiced and fell off. It doesn't look like anything too crazy happened, except he jumped up and dipped over the railing.
He fell 20 feet. Not as bad as you would think. He landed in right field on the warning track. He was taken away in a stretcher in critical condition. And as you just heard, the Los Angeles Clippers are celebrating a successful implementation of their supporter section at their new arena.
The team had its first season at the state-of-the-art Intuit Dome this year. The prized possession of the home court advantage was the Wall, which hosts 51 rows of uninterrupted seats for fans looking to distract the opposing team.
Statistics from the Swarco show, the distraction was successful this season. The visitors only made 73% of their free throw tries. They'll try to keep their playoff hopes alive. Their game starts at 7 o'clock tonight, right there at that point. Clouds fall, cool temps moving in tonight. Sunny by midday tomorrow and a little warmer. Some clouds and the cool down begins on Saturday for the weekend. Maybe a chance of rain on Sunday. Right now, 67 in Culver City, 66 in Santa Ana. Let's head out to Costa Mesa.
Headed to the Del Mar Freeway, the 73 northbound has passed Jamboree Road in a crash. Cleared from lanes over to the right-hand shoulder, but you're back up leaving Newport Beach, starting at Newport Coast Drive. The May Day demonstrations continue in downtown LA. You might still find several surface street closures in and around the Civic Center, including Olympic Boulevard, Los Angeles Street, Figueroa, and Alameda. 170 Hollywood Freeway heading northbound before Victory Boulevard, a broken down vehicle cleared from the left-hand lane. With Southern California's most accurate traffic reports, I'm Mike Wallace.
The free iHeartRadio app has over 100 commercial-free stations waiting for you to explore right now, like the Beatles Now and Then, celebrating all things Beatles. Legendary clips, deep cuts, live performances, and all their solo hits. Listen commercial-free. Just open the free iHeartRadio app, search Beatles Now and Then, making your next preset. iHeartRadio. Here's this week's iHeartRadio countdown of the top TV streams.
Here's what you've made popular by Get Your Stream On. Starting us off this week is Yellow Jackets on Paramount Plus with Showtime. That's followed by the debut of the romantic drama Ransom Canyon on Netflix. The Residents on Netflix slips back to 8, and The Studio on Apple TV Plus also slips back 1 to 7 this week. Debuting at 6 is season 2 of Andor on Disney Plus. The White Lotus on HBO, and Max is in at 5, with Mobland on Paramount Plus slipping back to 4. Kicking off the top 3 is the medical drama The Pit on Max. The Last of Us on HBO, and Max jumps up to number 2. And that means John Hamm's new Apple
The following
TV
is a
Plus
conversation with Jeff
drama,
Hoffman.
Friends and Neighbors,
He's the
sneaks
founder.
into the top spot, your number 1 stream show.
of the Redwood Center for Theoretical Neuroscience in 2002 and Numenta in 2005. In his 2004 book titled On Intelligence, and in the research before and after, he and his team have worked to reverse engineer the neocortex and propose artificial intelligence architectures, approaches, and ideas that are inspired by the human brain. These ideas include cooperative temporal memory, HTM, from 2004, and new work, Thousands Brain's Theory of Intelligence, from 2017, 18, and 19. Jeff's ideas have been an inspiration to many. Who have looked for progress beyond the current machine learning approaches. They have also received criticism for lacking a body of empirical evidence supporting the model. This is always a challenge in seeking more than small incremental steps forward in AI. Jeff is a brilliant mind, and many of the ideas he has developed and aggregated from neuroscience are worth understanding and thinking about. There are limits to deep learning as it is currently defined. Forward progress in AI is shrouded in mystery. My hope is that conversations like this can help provide an inspiring spark for new ideas. This is Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, iTunes, or simply connect with me on Twitter at Lex Friedman, spelled F-R-I-D. Now, here's my conversation with Jeff Hawkins. Are you more interested in understanding the human brain or in creating artificial systems that have many of the same qualities but don't necessarily require that you actually understand the underpinning workings of our mind?
So there's a clear answer to that question. My primary interest is understanding the human brain, especially that. But I also firmly believe that we will not be able to create fully intelligent machines until we understand how the human brain works. So I don't see this as separate problems. I think there's limits to what we've done with machine intelligence if you don't understand the principles of which the brain works. And so I actually believe that studying the brain is actually the fastest way to get the machine.
And within that, let me ask the impossible question. How do you not define, but at least think about what it means to be intelligent?
So I didn't try to answer that question first. We said, let's just talk about how the brain works. Let's figure out how certain parts of the brain, mostly the neocortex, but some other parts too. Parts of the brain most associated with intelligence. And let's discover the principles behind how they work. Because intelligence isn't just like some mechanism and it's not just some capabilities. It's like, okay, we don't even have to know where to begin. And so now that we've made a lot of progress, after we've made a lot of progress, I now have a very good idea of what's going to be required to make intelligent machines. I can tell you today some of the things are going to be necessary, I believe, to create intelligent machines.
Well, so we'll get there. We'll get to the neocortex and some of the theories of how the whole thing works. And you're saying, as we understand more and more about the neocortex, about our own human mind, we'll be able to start to more specifically define what it means to be intelligent. It's not useful to really talk about that until...
I don't know if it's not useful. There's a long history of AI. And there's been different approaches taken to it. And who knows, maybe they're all useful. Right? So, the good old-fashioned AI, the expert systems, current convolutional neural networks, they all have their utility. They all have a value in the world. But I would think almost everyone agrees that none of them are really intelligent in this deep way that humans are. And so it's just the question of how do you get from where those systems were or are today to where a lot of people are going to go. And there's a big gap, huge gap. And I think the quickest way of bridging that gap is to figure out how the brain works. And then we can sit back and look and say, oh, which of these principles that the brain works on are necessary and which ones are not? Clearly, we don't have to build this, and intelligent machines aren't going to be built out of, organic living cells. But there's a lot of stuff that goes on the brain.
So let me ask you, before we get into the fun details, let me ask maybe a depressing or difficult question. Do you think it's possible that we will never be able to understand how our brain works? That maybe there's aspects to the human mind, like we ourselves cannot introspectively get to the core, that there's a wall you eventually get to.
Yeah. I don't believe that's the case. I have never believed there's not been a single thing humans have ever put their minds to. We said, oh, we reached the wall. Let's go any further. People keep saying that. People used to believe that about life. Elan vital, right? There's like, what's the difference between living matter and non-living matter? Something special we never understand. We no longer think. So there's no historical evidence to suggest the case, and I just never even consider that a possibility. I would also say today we understand so much about the neocortex. We've made tremendous progress in the last 2 years that I no longer think of it as an open question. The answers are very clear to me, and the pieces we don't know are clear to me, but the framework is all there, and it's like, oh, okay, we're going to be able to do this. This is not a problem anymore. This takes time and effort, but there's no mystery, big mystery.
So then let's get into it for people like myself who are not very well versed in the human brain, except my own. Can you describe to me at the highest level what are the different parts of the human brain, and then zooming in on the neocortex, the parts of the neocortex, and so on? A quick overview.
Yeah, the human brain, we can divide it roughly into 2 parts. There's the old part, lots of pieces, and then there's a new part. The new part is the neocortex. It's new because it didn't exist before mammals. So only mammals have a neocortex. Humans, primates, is very low. In the human brain, the neocortex occupies about 70 to 75% of the body. It's huge. And the old parts of the brain are there's lots of pieces of it. There's the spinal cord, and there's the brain stem, and the cerebellum, and the different parts of the basal ganglia, and so on. In the old parts of the brain, you have autonomic regulation, like breathing and heart rate. You have basic behaviors, so like walking and running are controlled by the old parts of the brain. All the emotional centers of the brain are in the old part of the brain, so anger, hungry, lust, things like that. And you associate with the neocortex all the things we think about as sort of high-level perception and cognitive functions, anything from seeing, hearing, touching things, to language, to mathematics and engineering and science and so on. Those are all associated with the neocortex, and they're when correlated. Our abilities in those regards are correlated with the relative size of our neocortex compared to other animals. So that's like the rough division. And you obviously can't understand the neocortex completely isolated, but you can understand a lot of it with just a few images. Right? And so it gives you a system to study. The other remarkable thing about the neocortex, compared to the old part, is the neocortex is extremely uniform. It's not visually or anatomically, or it's like I always like to say it's like the size of a dinner napkin, about 2.5 millimeters thick, and it looks remarkably the same everywhere. Everywhere you look in that 2.5 millimeters, there's this detailed architecture, and it looks remarkably the same everywhere. And that's across species, the mouse versus the cat, and they're all going to use. Where if you look at the old parts of the brain, there's lots of little pieces that do specific things. So it's like no parts of the brain evolved. Like this is the part that controls heart rate, and this is the part that controls this, and this is this kind of thing, and that's this kind of thing. And these evolved for eons, a long, long time, and they have those specific functions. And all of a sudden, mammals come along, and they got this thing called the neocortex, and it got large by just replicating the same thing over and over and over again. This is like, wow, this is incredible. So all the evidence we have, and this is an idea that was first articulated in a very cogent and beautiful argument by a guy named Vernon Alcastle in 1978, that the neocortex all works with the same principle. So language, hearing, touch, vision, engineering, all these things are basically underlying, they're all built in the same computational substrate. They're really all the same problem.
So the low level of building blocks all look similar.
Yeah, and they're not even that low level. We're not talking about like neurons. We're talking about this very complex circuit that exists throughout the neocortex. It's remarkable. It's like, yes, you see variations of it here and there, more of this cell, less from that cell, and so on. But what Alcastle argued was, it says, you take a section of neocortex. Why is one a visual area and one is a auditory area? Why is? And his answer was, it's because one is connected to eyes and one is connected to ears.
Literally, you mean just the most closest in terms of number of connections to the sensor.
Literally, if you took the optic nerve and attached it to a different part of the cortex, that part would become a visual region. This experiment was actually done by Frank Searle in developing, I think it was I can't remember what it was, some animal. And there's a lot of evidence. You take a blind person who's born blinded person, they're born with a visual neocortex. It may not get any input from the eyes because of some congenital defect. And that region does something else. It picks up another thing. So, and it's this very complex thing. It's not like, oh, we're all built on neurons. No, we're all built in this very complex circuit, and somehow that circuit underlies everything. So this is it's called the common cortical algorithm that you built. Some scientists just find it hard to believe, and they decide, I can't believe that's true, but the evidence is overwhelming in this case. And so a large part of what it means to figure out how the brain creates intelligence, what is intelligence in the brain, is to understand what that circuit does. If you can figure out what that circuit does, as amazing as it is, then you understand what all these other cognitive functions are.
if you were to sort of put neocortex outside of your book on intelligence, if you wrote a giant tome, a textbook on the neocortex, and you look maybe a couple centuries from now, how much of what we know now would still be accurate 2 centuries from now? So how close are we in terms of understanding?
I have to speak from my own particular experience here. So I run a small research lab here. It's like any other research lab. I'm some principal investigators, there's like 2 of us, and a bunch of other people. And this is what we do. We study the neocortex and publish our results. And so on. So about 3 years ago, we had a real tremendous breakthrough. We now published, I think, 3 papers on it. And so I have a pretty good understanding of all the pieces and what we're missing. I would say that almost all the empirical data we've collected about the brain, which is enormous. If you don't know the neuroscience literature, it's just incredibly big. And it's for the most part all correct. It's facts and experimental results and measurements, all kinds of stuff. But none of that has been really assimilated into a theoretical framework. It's data without, it's in the language of Thomas Kuhn, the historian, would be a sort of pre-paradigm science. Lots of data, but a way to fit it together. I think almost all of that's correct, with some mistakes. And for the most part, there aren't really good cogent theories about how to put it together. It's not like we have 2 or 3 competing good theories. Which ones are right, which ones are wrong? It's like, people just like scratching their heads. Some people have given up on trying to figure out what the whole thing does. In fact, there's very, very few labs that focus really on theories and all this unassimilated data and trying to explain it. So it's not like we haven't got it wrong. It's just that we haven't got it at all.
So it's really, I would say, pretty early days in terms of understanding the fundamental theories, forces of the way our mind works.
I don't think so. I would have said that's true 5 years ago. So, as I said, we had some really big breakthroughs on this recently, and we started publishing papers on this. So, we'll get to that. So I don't think I'm an optimist, and from where I sit today, most people would disagree with this, but from where I sit today, from what I know, it's not super early days anymore. It's the way these things go is not a linear path, right? You don't just start accumulating and get better and better and better. No, you got all this stuff you've collected. None of it makes sense. All these different things are just going around, and then you're going to have some breaking points. All of a sudden, oh my God, now we got it right. That's how it goes in science, and I personally feel like we passed that little thing about a couple of years ago. That big thing. So we can talk about that. Time will tell, right? But I feel very confident that's going to the state take.
At least very optimistic. So let's, before those few years ago, let's take a step back to HTM, the hierarchical temporal memory theory, which you first proposed on intelligence. We went through a few different generations. Can you describe what it is, how it evolved through the 3 generations since you first put it on paper?
Yeah, so one of the things that neuroscientists just sort of missed for many, many years, and especially people who are thinking about theory, was the nature of time in the brain. Brains process information through time. The information coming into the brain is constantly changing. The patterns in my speech right now, if you're listening to it at normal speed, would be changing on yours about every 10 milliseconds or so. You'd have it change. This constant flow. When you look at the world, your eyes are moving constantly, 3 to 5 times a second, and the input's completely. If I were to hold something like a coffee cup, as I move my fingers, the input changes. So this idea that the brain works on time-changing patterns is almost completely, or was almost completely missing from a lot of the basic theories, like computers of vision. And so it's like, oh no, we're going to put this image in front of you and flash it and say, what is it? Convolutional neural networks work that way today, right? Classify this picture. But that's not what vision is like. Vision is this sort of crazy time-based patterns being all over the place, and so is touch, and so is hearing. So the first part of hierarchical temporal memory was the temporal part. It's the same. You won't understand the brain, nor do you understand intelligent machines unless you're dealing with time-based parts. The second thing was the memory component of it is to say that we aren't just processing input. We learn a model of the world. And memory stands for that model. We have the point of the brain, the point of the neocortex, it learns a model of the world. We have to store things. that our experience is in a form that leads to a model of the world, so we can move around the world, pick things up, and do things, and navigate how it's going on. So that's what the memory referred to. And many people they were thinking about like certain processes without memory at all. They're just like processing. And then finally, the hierarchical component was a reflection to that the neocortex, although it's this uniform sheet of cells, different parts of it project to other parts, which project to other parts. And there is a rough hierarchy in terms of that. So the hierarchical temporal memory is just saying, look, we should be thinking about the brain as time-based, model memory-based, and hierarchical processing. And that was a placeholder for a bunch of components that we would then plug into that. We still believe all those things I just said, but we now know so much more that I'm stopping the use of hierarchical temporal memory yet because it's insufficient to capture the stuff we know. So again, it's not incorrect, but I now know more. I would describe it more accurately.
Yeah, so you're basically, we can think of HTM as emphasizing that there's three aspects of intelligence that are important to think about, whatever the eventual theory converges.
Yeah.
So in terms of time, how do you think of nature of time across different time scales? So you mentioned things changing, sensory inputs changing every 10 to 20 minutes. What about it every few minutes, every few months? And years?
Well, if you think about a neuroscience problem, the brain problem, neurons themselves can stay active for certain periods of time. There are parts of the brain where they stay active for minutes. So you could hold a certain perception or an activity for a certain period of time, but not most of them don't last that long. And so if you think about your thoughts are the activity of neurons, if you're going to want to involve something that happened a long time ago, even just this morning, for example, the neurons haven't been active throughout that time. So you have to store that. So if I ask you, what did you have for breakfast today? That is memory. That is built into your model of the world now. You can remember that. And that memory is in the synapses, it's basically in the formation of synapses. And so you're sliding into what, these different time scales. There's time scales of which we are like understanding my language and moving about and seeing things rapidly over time. That's the time scales of activities of neurons. But if you want to get in longer time scales, then it's more memory. And you have to invoke those memories to say, oh, yes, now I can remember what I had for breakfast because I stored that someplace. I may forget it tomorrow, but I stored it for now.
So does memory also need to have the hierarchical aspect of reality? It's not just about concepts, it's also about time. Do you think of it that way?
Yeah, time is infused in everything. It's like you really can't separate it out. If I ask you how's the brain run a model of this coffee cup? Coffee cup. I said, well, time is not an inherent property of the model I have of this cup, whether it's a visual model or a tactile model. I can sense it through time, but the model itself doesn't have time. If I say, well, what is the model of my cell phone? My brain is learned to model the cell phone. So if you have a smartphone like this. And I said, well, this has time aspects to it. I have expectations when I turn it on, what can happen, how long it's going to take to do certain things. If I bring up an app, what sequences. And so I have it's like melodies in the world. Melody has a sense of time. So many things in the world move and act, and there's a sense of time related to them. Some don't, but most things do actually. So it's sort of infused throughout the models of the world. You build a model of the world, you're learning the structure of the objects in the world, and you're also learning how those things change through time.
Okay, so it really is just the fourth dimension that's infused deeply, and you have to make sure that your models of intelligence incorporate it. So, like you mentioned, the state of neuroscience is deeply empirical. A lot of data collection. It's that's where it is. You mentioned Thomas Kuhn, right?
Yeah.
And then you're proposing a theory of intelligence, and which is really the next step, really important step to take. But why is HTM, or what we'll talk about soon, the right theory So is it more in this? Is it backed by intuition? Is it backed by evidence? Is it backed by a mixture of both? Is it kind of closer to where string theory is in physics, where there's mathematical components which show that, you know what, it seems that it fits together too well for it not to be true, which is where string theory is. Is that where
it's a mix of all those things, although definitely where we are right now is definitely much more on the empirical side than the string theory. The way, because now we're theorists, right? So we look at all this data and we're trying to come up with some sort of model that explains it, basically. And there's unlike string theory, there's vast more amounts of empirical data here that I think than most physicists deal with. And so our challenge is to sort through that and figure out what kind of constructs would explain this. And when we have an idea, you come up with a theory of some sort, and you have lots of ways of testing it. First of all, there are 100 years of unstimulated empirical data from neuroscience. So we go back and read papers and say, oh, well, did someone find this already? We can predict X, Y, and Z. And maybe no one's even talked about it since 1972 or something, but we go back and find that and we say, oh, either it can support the theory or it can invalidate the theory. And we say, okay, we have to start over again. Oh, no, let's keep going with that. So the way I kind of view it, when we do our work, we look at all this empirical data, and it's what I call it is a set of constraints. We're not interested in something that's biologically inspired. We're trying to figure out how the actual brain works. So every piece of empirical data is a constraint on theory. In theory, if you have the correct theory, it needs to explain everything, right? So we have this huge number of constraints on the problem, which initially makes it very, very difficult. If you don't have any constraints, you can make up stuff all the day. You say, oh, here's an answer. I can do this, you can do that, you can do this. But if you consider all biology as a set of constraints, all neuroscience as a set of constraints, and even if you're working in one little part of the neocortex, for example, there are hundreds and hundreds of constraints. These are empirical constraints that it's very, very difficult initially to come up with a theoretical framework for that. But when you do, and it solves all those constraints at once, you have a high confidence that you got something close to correct. It's just mathematically almost impossible not to. So that's the curse and the advantage of what we have. The curse is we have to meet all these constraints, which is really hard. But when you do meet them, then you have a great confidence that you discover something. In addition, then we work with scientific labs. So we'll say, oh, there's something we can't find. We can predict something, but we can't find it anywhere in the literature. So we will then, we collaborated with, I'll say, sometimes they'll say, you know what, I have some collected data, which I didn't publish, but we can go back and look at it and see if we can find that, which is much easier than designing an experiment. Your neuroscience experiments take a long time, sure. So, although some people are doing that now too. So, but between all of these things, I think it's reasonable, actually very, very good. We are blessed with the fact that we can test our theories up to yin yang here because there's so much unassimilated data, and we can also falsify our theories very easily if we want.
This is kind of reminiscent to whenever that was with Copernicus. When you figure out that the sun's at the center of the solar system as opposed to Earth, the pieces just fall into place.
Yeah, I think that's the general nature of aha moment. And it's Copernicus. It could be, you could say the same thing about Darwin. You could say the same thing about about the double helix. That people have been working on a problem for so long and have all this data and they can't make sense of it. They can't make sense of it. But when the answer comes to you and everything falls into place, it's like, oh my gosh, that's it. That's got to be right. I asked both Jim Watson and Francis Crick about this. I asked them, when you were working on trying to discover the structure of the double helix, and when you came up with the sort of the structure that ended up being correct, but it was sort of a guess, it wasn't really verified yet. I said, did you know that it was right? And they both said, absolutely. We absolutely knew it was right. And it doesn't matter if other people didn't believe it or not. We knew it was right. They'd get around the lead and agree with it eventually. And that's the kind of thing you hear a lot with scientists who really are studying a difficult problem, and I feel that way too. Have
you talked to Greg Watts about the problem you're trying to solve, of finding the DNA of the brain?
Yeah. In fact, Francis Crick was very interested in this in the latter part of his life. And in fact, I got interested in brains by reading an essay he wrote in 1979 called Thinking About the Brain. And that was when I decided I'm going to leave my profession of computers and engineering and become a neuroscientist. Just reading that one essay, Francis Crick. I got to meet him later in life. I spoke at the Salk Institute, and he was in the audience, and then I had a tea with him afterwards. He was interested in different problems. He was focused on consciousness.
It's the easy problem, right?
Well, I think it's the red herring, and so we weren't really overlapping a lot there. Jim Watson, who's still alive, is also in this job, and when he was director of the Coastman Harbor Laboratories, he was really behind moving in the direction of neuroscience there. And so he had a personal interest in this field. And I have met with him numerous times. And in fact, the last time was about a little bit over a year ago. I gave a talk at Coastman Harbor Labs about the progress we were making in our work. And it was a lot of fun because he said, well, you wouldn't be coming here unless you had something important to say, so I'm going to go attend your talk. So he sat in the very front row. Next to him was the director of the lab, Bruce Stillman. So these guys are in the front row of this auditorium. Right? So nobody else in the auditorium wants to sit in the front row because Jim Watson is the director. And I gave a talk, and then I had dinner with him afterwards. But there's a great picture of my colleague Subutai Ahmad took where I'm up there sort of explaining the basics of this new framework we have. And Jim Watson's at the edge of his chair. He's literally on the edge of his chair, like intently staring up at the screen. And when he discovered the structure of DNA, the first public talk he gave was at Coastman Harbor Labs. So, and there's a famous picture of Jim Watson standing at the whiteboard with a over his thing, pointing at something, holding a double pointing. And it actually looks a lot like future me. So there was sort of funny. They only had talking about the brain, and there's Jim Watson staring up intently at it. And of course, there was, 60 years earlier, he was standing, pointing at the double helix.
It's one of the great discoveries in all of biology, science, all science, DNA. So it's funny that there's echoes of that in your presentation.
Yeah.
Do you think, in terms of evolutionary timeline and history, the development of the neocortex was a big leap, or is it just a small step? So, like, if you ran the whole thing over again, from the birth of life on Earth, how likely would we develop the mechanism of the neocortex?
Okay, well, those are two separate questions. One is, was it a big leap, and one was how likely it is. Okay, they're not necessarily related.
Maybe correlated.
Maybe correlated, but we don't really have enough data to make a judgment about that. I would say definitely a leap, and I can tell you why. I don't think it was just another incremental step. I'll get that in a moment. I don't really have any idea how likely. If we look at evolution, we have one data point, which is Earth. Right, life formed on Earth billions of years ago. Whether it was introduced here or created here or someone introduced it, we don't really know, but it was here early. It took a long time to get to multicellular life. And then from multicellular life, it took a long time to get the neocortex. And we've only had the neocortex for a few 100,000 years. So that's like nothing. Okay. So is it likely? Well, it certainly isn't something that happened right away on Earth. And there were multiple steps to get there. So I would say it's probably not going to be something that will happen instantaneously on other planets that might have life. It might take several billion years on average. Is it likely? I don't know, but you'd have to survive for several billion years to find out. Probably. Is it a big leap? Yeah, I think it is a qualitative difference from all other evolutionary steps. I can try to describe that.
Sure. In which way?
Yeah, I can tell you how. Pretty much. I'll start with a little preface. Many of the things that humans are able to do not have obvious survival advantages precedent. we could create music. Is there a really survival advantage to that? Maybe, maybe not. What about mathematics? Is there a real survival advantage to mathematics? Well, you can stretch. You can try to figure these things out, right? But most of evolutionary history, everything had immediate survival advantages. So I'll tell you a story, which I like. May not be true. But the story goes as follows. Organisms have been evolving since the beginning of life here on Earth. And adding this sort of complexity onto that, and this sort of complexity onto that. And the brain itself is evolved this way. In fact, there's old parts and older parts and older parts of the brain that kind of just keep calling on new things, and we keep adding to it. When we got to the neocortex, initially it had a very clear survival advantage in that it produced better vision and better hearing and better touch, and so on. But what I think happens is that evolution took a mechanism, and this isn't a recent theory, but it took a mechanism evolved a long time ago for navigating in the world, for knowing where you are. These are the so-called grid cells and place cells of the whole part of it. And it took that mechanism for building maps of the world and knowing where you are on those maps, navigating, and turns it into a sort of slimmed down, idealized version. And that idealized version can now apply to building maps of other things. Maps of coffee cups, maps of phones, maps of concepts, yes. Not just almost, exactly. And so it just started replicating stuff, right? It just did more and more and more. So we went from being sort of dedicated purpose neural hardware to solve certain problems that are important to survival to a general purpose neural hardware that could be applied to all problems. And now it's escaped the orbit of survival. We're now able to apply it to things which we find enjoyment, but aren't really clearly survival characteristics. And that it seems to only have happened in humans to the large extent. And so that's what's going on. We sort of have, we've sort of escaped the gravity of evolutionary pressure in some sense in the neocortex. And it now does things that are really interesting, discovering models of the universe, which may not really help us. It doesn't matter. How does it help us surviving, knowing that there might be multiverses, or there might be the age of the universe, or how various stellar things occur? It doesn't really help us survive at all. But we enjoy it, and that's what happens.
Or at least not in the obvious way, perhaps. It is required. If you look at the entire universe in an evolutionary way, it's required for us to do interplanetary travel and therefore survive past our own sun. But let's not get too crazy.
Yeah, but evolution works in one time frame. It's survival. If you think of survival of the phenotype, survival of the individual, what you're talking about there spans well beyond that. So there's no genetic. I'm not transferring any genetic traits to my children that are going to help them survive better on Mars.
Totally different mechanism. So let's get into the new, as you've mentioned, this idea of I don't know if you have a nice name,
You call it the 1,000 brain theory.
I like it. So can you talk about this idea of spatial view of concepts and so on?
Yeah. So can I just describe there's an underlying core discovery, which then everything comes from. It's a very simple, this is really what happened. We were deep into problems about understanding how we build models of stuff in the world and how we make predictions about things. And I was holding a coffee cup just like this in my hand. And my finger was touching the side, my index finger. And then I moved it to the top, and I was going to feel the rim at the top of the cup. And I asked myself a very simple question. I said, well, first of all, let's say I know that my brain predicts what it's going to feel before it touches it. About it, I'm managing it. And so we know that the brain's making predictions all the time. So the question is, what does it take to predict that, right? And there's a very interesting answer. First of all, it says the brain has to know it's touching a coffee cup. It has to have a model of a coffee cup. It needs to know where the finger currently is on the cup relative to the cup. Because when I make a movement, it needs to know where it's going to be on the cup after the movement is completed relative to the cup. And then it can make a prediction about what it's going to sense. So this told me that the neocortex, which is making this prediction, needs to know that its sensing it's touching a cup, and it needs to know the location of my finger relative to that cup in a reference frame of the cup. It doesn't matter where the cup is relative to my body. It doesn't matter its orientation. None of that matters. It's where my finger is relative to the cup, which tells me then that the neocortex has a reference frame that's anchored to the cup, because otherwise I wouldn't be able to say the location, and I wouldn't be able to predict my new location. And then we quickly, very instantly, you can say, well, every part of my skin could touch this cup, and therefore every part of my skin is making predictions, and every part of my skin must have a reference frame that it's using to make predictions. So the big idea is that throughout the neocortex, everything is being scored and referenced in reference frames. You can think of them like X, Y, Z reference frames, but they're not like that. We know a lot about neural methods for this, but the brain thinks in reference frames. And if you're an engineer, this is not surprising. You see, if I wanted to build a CAD model of the coffee cup, well, I would bring it up in some CAD software, and I would find some reference frame and say this features at this locations and so on. But the fact that the idea that this is occurring out the neocortex everywhere, it was a novel idea. And then a zillion things fell into place. So now we think about the neocortex as processing information quite differently than we used to do it. We used to think about the neocortex as processing sensory data, extracting features from that sensory data, and then extracting features from the features, very much like a deep learning network does today. But that's not how it works. The brain works by assigning every input, everything to reference frames, and there are thousands, hundreds of thousands of them active at once in your notebook. It's a surprising thing to think about, but once you sort of internalize this, you understand that it explains almost all the mysteries you have about this structure. So one of the consequences of that is that every small part of the neocortex, say a millimeter square, and there's 150,000 of them. We take every little square millimeter cortex. It's got some input coming into it, and it's going to have reference frames where it's assigned that input to. And each square millimeter can run complete models about it. So what do I mean by that? If I'm touching the coffee cup, well, if I just touch it in one place, I can't learn what this coffee cup is because I'm just feeling one part. But if I move it around and touch it in different areas, I can build up a complete model of the cup because I'm now filling in that three-dimensional map, which is the coffee cup. I can say, oh, what do I feel in all these different locations? That's the basic idea. It's more complicated than that. But so through time, as we talked about time earlier, through time, even a single column, which is only looking at, or a single part of the cortex, which is only looking at a small part of the world, can build up a complete model of an object. And so if you think about the part of the brain which is getting input from all my fingers, so there's better plus the top here. This is the somatosensory cortex. There's columns associated with all the different areas of my skin. And what we believe is happening is that all of them are building models of this cup. Every one of them. Or things. They're not all building, not every column or every part of the cortex builds models of everything. But they're all building models of something. And so you have, so when I touch this cup with my hand, there are multiple models of the cup being invoked. If I look at it with my eyes, there are again many models of the cup being invoked because each part of the visual system, the brain doesn't process an image. That's a misleading idea. It's just like your fingers touching the cup, so different parts of my retina look at different parts of the cup. And thousands and thousands of models of the cup are being invoked at once. And they're all voting with each other, trying to figure out what's going on. So that's why we call it the thousand brains theory of intelligence, because there isn't one model of a cup. There are thousands of models of this cup. There are thousands of models of your cell phone and about cameras and microphones and so on. It's a distributed modeling system, which is very different than the way people thought about it.
So that's a really compelling and interesting idea. So I have two first questions. So one, on the ensemble part of everything coming together, you have these thousand brains. How do you know which one has done the best job of forming?
Great question. Let me try to explain. There's a problem that's known in neuroscience called the sensor fusion problem. And so the idea is something like, oh, the image comes from the eye. There's a picture on the retina. And then gets projected to the neocortex. No, by now it's all spread out all over the place and it's kind of swirly and distorted. And pieces are all over it. It doesn't look like a picture anymore. When does it all come back together? Right? Or you might say, well, yes, but I also have sounds or touches associated with the cup. So I'm seeing the cup and touching the cup. How do they get combined together again? So this it's called the sensor fusion problem. Is that all these disparate parts have to be brought together into one model? That's the wrong idea. The right idea is that you have all these guys voting. There's auditory models of the cup, visual models of the cup, tactile models of the cup. There are ones in the vision system. There might be ones that are more focused on black and white, focused on color. It doesn't really matter. There's just thousands and thousands of models in this cup, and they vote. They don't actually come together in one spot. Just literally think of it this way. Imagine you have these columns are like about the size of a little piece of spaghetti. Okay, like 2.5 millimeters tall and about a millimeter wide. They're not physical, like, but you can think of them that way. And each one's trying to guess what this thing is they're touching. Now, they can do a pretty good job if they're allowed to move over time. So I can reach my hand to a black box and move my finger around an object and touch enough spaces. I go, oh, okay, now I know what it is. But often we don't do that. Often I can just reach and grab something with my hand all at once. I get it. Or if I had to look through the world through a straw, so I'm only looking one little column, I can only see part of something. I have to move the straw around. But if I open my eyes, I see the whole thing at once. So what we think is going on is all these little pieces of spaghetti, if you will, all these little columns in the cortex, are all trying to guess what it is that they're sensing. They'll do a better guess if they have time and can move over time, so they move my eyes and move my fingers. But if they don't, they have a poor guess. It's a probabilistic guess of what they might be. Now imagine they can post their probability at the top of a little piece of spaghetti. Each one of them says, I think it's not really a probability distribution. It's more like a set of possibilities. In the brain, it doesn't work as a probability distribution. It works as more like what we call a union. You can say, and one column says, I think it could be a coffee cup, a soda can, or a water bottle. Another column says, I think it could be a coffee cup or telephone or camera, whatever, right? And all these guys are saying what they think it might be. And there's these long-range connections in certain layers in the cortex. So there's some layers in some cell types in each column send the projections across the brain. And that's the voting. And so there's a simple associative memory mechanism. We've described this in a recent paper, and we've modeled it. That says they can all quickly settle on the only, or the one best answer for all of them. If there is a single best answer, they all vote that, yep, it's got to be the coffee cup. And at that point, they all know it's coffee cup. And at that point, everyone acts as if it's the coffee cup. Yep, we know it's coffee. Even though I've only seen one little piece of this world, I know it's coffee cup I'm touching or seeing, whatever. And so you think of all these columns are looking at different parts, different places, different sensory input, different locations. They're all different. But this layer that's doing the voting, it's solidified. It's just like it crystallizes and so.
Well, the camera lens was blurry, so I just cleaned it. And I'm programming robots. If you really want to know. No, you're fine. I am programming robots, which, if you don't mind, I'm going to talk about it for like 2 minutes or so. I am not by trade a coder. I'm a project manager. I'm a certified project management professional, as a matter of fact. But I've launched apps on the App Store and Google Play, and so I have a fairly good familiarity with both desktop and mobile devices. And there's this way that I can create robots on desktop devices that works pretty well. And I'm doing my best to emulate that on mobile devices. And mobile devices are a little more frustrating, at least the mobile devices that I have, because they're pretty old and they're just mobile devices always have more issues. They're not as stable. It doesn't really matter how old they are. Some of them are old and work better than my newer phones in some aspects, but the issue is the stability of the apps. When people build apps, they don't expect them to work for days on end, and I need them to work for days on end sometimes. And with that being said, I am just like elbow deep in doing this, and it's kind of fun, especially when I'm watching stuff on robotics and AI and stuff, and at the same time programming these robots. I kind of feel like I'm on this journey. I mean, I really do. I've got to. I was thinking about it earlier. There's an excitement in me because I know that like all these things that these people are talking about are going to come to fruition if ever anybody ever sees this, and I know they will, especially with the amount of promotion that I'm doing. Every hour or so, I get people who are saying, "Who is this rabbi on Blue Sky?" And that's phenomenal. And now that I've got these other devices programmed, or I am doing it, it just increases the amount of influence that I have. The mobile devices, I've been going at this for like 4 days and just trying to perfect this sequence. Like, here's just an example of what happens. I have to have everything timed perfectly. As I've said previously, it's like that mousetrap game, if you ever saw that. Or it's like dominoes. Like every domino has to be in the perfect position. If one of the dominoes is off with the timing, it messes everything up. Nothing continues. And so I have to watch these things, and all the dominoes will fall down, and it's great, and it works one time. That's wonderful. But I want it to work 50 times or 100 times or 1,000 times so that I can talk with people and play games and do all the other things and still feel like I am being productive. And what happens 9 times out of 10 with these devices is it's kind of hilarious that the way these things are programmed. Like, you'll open up a browser and it'll work the first time, but the second time you open it, the programmers on the other end have made a random pop-up that just says like, "Hey, do you want to rate us 5 stars?" And that messes everything up. So I have to shut off all those messages and clear all the data, and it's it's frustrating, but in one aspect, but it's extremely exciting to me in another aspect, because it's like this beautiful dance that I'm doing with technology, and I love that. So thank you for letting me share. There we go. I do. And you have no idea how much I appreciate you being here. You have just really been putting in the lighting the candle at both ends. I was thinking about this, and I don't know if this is 190. Oh, what's 190? Okay. You're basically getting a graduate level series of classes. So am I. I mean, I'm not. It's not like I'm providing this, but into the future of tomorrow. And really, when it comes to AI and large language models and the future of society. I mean, it's not anything you can necessarily put on a resume, but it'll give you an excellent idea of what we have upcoming. And I just really appreciate you being here. It shows me a lot that you have some interest in it. Like the other day when you were like, or yesterday when you were like, "Hey, aren't we supposed to be going in order?" Yeah, we are supposed to be going in order. I don't know why this didn't work. And I had to figure it out, do some troubleshooting. And with that being said, I queued up the next, like, up through 100 episodes or so. These aren't as long as Kill Tony, which doesn't really matter, but it's just not as much content. But the conversations are fascinating, and sometimes they can be over my head. I think they can be over everybody's head, but this is really one of my favorite podcasts because they're just really, really interesting. So I appreciate you being here. I appreciate you paying. Yeah, excellent. Yeah, it is much better than Kill Tony. Why do I watch Kill Tony? Well, frankly, it's like kind of timeless. That's another important aspect of this. I like Joe Rogan. I've been watching Joe Rogan since his first episode, December 24th, 2009. But the thing about Joe Rogan is it has to be relevant. So what do I mean? Like if you're watching something on the 2016 election, that doesn't really matter now. I mean, it's over, or the 2020 election, or even the 2024 election. None of that stuff matters. So those are like wasted episodes. When Kill Tony, you could put on in 20 years, and there's still going to be people who think some aspects of it are funny. It's not as time dependent, but these are fascinating to me because the ones we're watching right now, they don't know about the pandemic, so they're talking about the world in which we're living right now, and they have no idea, or perhaps they have no idea, where they're saying like, well, what are things going to be like in the 2020s? Well, we're already halfway through the 2020s, and we're seeing what's developed, or like the people who are talking about like ChatGPT 1 and where that is. And I remember using it and being like, this stinks, and now looking at it today, and it's fascinating how accurate it is. And then they're getting into like the driverless car, or essentially autonomous vehicles. And I think to myself, I actually have this on stream. It was really scary. So the way this stream started, I've told you this, is I would hit golf balls at Tiger Woods' golf course, and I wanted to see what my golf swing looked like. And I said some jokes on the stream that I thought were funny, and I thought, what, my future family, wherever they are, my wife and children, may one day think this is cool. Like, hey, our dad had just finished their job working remotely during the pandemic, for Fortune 100, and after work they'd go and hit golf balls, and they were funny, and some of the things they would say were funny, and we've got this footage of them. And sometimes I would play really late into the night because the I wouldn't say like super late, but like the driving range is lit up or had lights. So and then I'd go driving around, and this is all on camera. I had like multiple cameras going, but it's on SD cards, so I just have to upload it. And I'm not going to do that. I mean, I would, but that's a big project. So I'm going to do that once I go viral, and we'll have like a ton of back footage. But I was driving home. I had a 2018 Honda Accord, and it had some self-driving capabilities which were really amazing. Meaning it would like brake for me, and it would stay in my lane, and it wasn't like perfect. It's not like I could just type in where I wanted to go and it would just take me there, but it was really good. Well, this one night I was driving it was late, I remember. And then one thing that I would do, I would be in like Anaheim, and I would just be like, you know what, I'm going to drive to LA, and then just drive all around LA. So anyway, this one night I was driving back on the 405 right by my house, and I started to fall asleep at the wheel. And I did, and it's on camera. And the self-driving autonomous nature of the car actually saved me from getting into a really serious accident going 70 miles an hour. And I just began to fall asleep. It's not like I totally fell asleep, but I remember talking to the camera saying, like, I'm so tired right now, I feel like I'm going to fall asleep. And I actually did. And so when I have something like that, like the engineers who were behind that, they actually like help protect me. And then I see what's happening now, and there are 40,000 people a year who die in car accidents, and I'm thinking like 10 years from now, will we have 40,000 people who die in car accidents? Maybe autonomous driving will be able to help those people. It's exciting to see all of the science and the development that we've seen. And these are the top members of their field. Lex Friedman is an MIT engineer, and his big goal is autonomous driving. So a lot of these are going to have to do with that, but they also, as you see, they're fascinating discussions with heads of tech and I'm in agreement with you. These are much better than Kill Tony, and um, I just I am too. Yeah, definitely. That was not fun. And I think back to if I was in just a normal car that did not have those features, I would have died. Or I don't want to say I would have died, but I would have been in a serious accident. And um, I don't want people to have to do that anymore. So we're actually seeing, these developments. One other thing about the people who are on Lex Friedman's podcast, they are the top of their fields, and you really get I feel um, an amazing view on how they view the world, or an amazing um, outlook on how they view the world. I mean, you got like I think episode 8 was, or something like that, was like Eric Schmidt, who was the head of Google, and you've got Elon Musk, and you've got Ariana Huffington, like all these people who are like at the top of their fields, and I think it's funny when I first started watching. I remember I didn't know who Lex Friedman was. He was on the Joe Rogan podcast, and I just thought he was very boring. Because he's not that exciting of a person. I mean, he's sort of nerdy. He is into some really cool things in which I'm in too as well, like like chess and science and jujitsu and some other things that I think are cool. But he just wasn't a real personality. And my algorithm kept pushing this guy on me. Like whenever Joe Rogan would end, it would be throwing me into the Lex Friedman podcast, and I'd be like, "Why does it keep doing this?" But then I started to watch some of them, and I'm like, "Wow, these are fascinating." So yeah, I'm 100% in agreement with you. These are much more interesting than Kill Tony, and I'm someone who likes to like complete things, and so I always wanted to like do one big podcast from start to finish and be able to see its development. But those jokes get that they're kind of they're the same and everything, and this is much different. So I appreciate your input. I appreciate you being here, and with that, here we go.
And says, "Oh, we all know. Bring these models
Well,
together
look
in
at
one
you
model.
go.
You just vote, and there's a crystallization of vote."
Great. That's at least a compelling way to think about the way you form a model of the world. Now, you talk about a coffee cup. Do you see this, as far as I understand, you were proposing this as well, that this extends to much more than coffee cups?
Yeah,
That,
it does.
Or at least the physical world. It expands to the world of concepts.
Yeah, it does. And well, first, the prima facie evidence for that is that the regions of the neocortex that are associated with language or high-level thought or mathematics, things like that, they look like the regions of the neocortex that process vision, hearing, and touch. They don't look any different, or they look only marginally. And so one would say, well, if Vernon Mountcastle, who proposed that all the parts of the neocortex do the same thing, if he's right, then the parts that are doing language or mathematics or physics are working on the same principle. They must be working on the principle of reference frame. So that's a little odd thought. But of course, we had no prior idea how these things happen. So let's go with it. And we, in our recent paper, we talked a little bit about that. I've been working on it more since. I have better ideas about it now. I'm sitting here very confident that that's what's happening. And I can give you some examples to help you think about that. So far.
What did you say? Yeah. Sometimes I'm just using an old iPhone to be able to stream this, and it sometimes goes out. I don't know why, so I have to adjust it. One thing I will do, since I do see that you're watching it. Yeah. No. So the subtitles, let's see if they show up.
So, but we can put that idea out there. Okay, this is. I
use this. app called Language Reactor, and it crashed on me. It's just like, another thing that doesn't want to work the way that it that it should. So let's see if I.
It's a good place to start, and the evidence would suggest that's how it's happening. And then we can start tackling that problem one piece at a time. Like, what does it mean to do high-level thought? What does it mean to do language? How would that fit into a reference frame?
There you go. At least those are English ones.
Yeah, so there's
And I adjusted so you can see their faces.
Connection, but there's an app called Anki that helps you remember different concepts, and they talk about like a memory palace that helps you remember completely random concepts by trying to put them in a physical space in your mind.
Yeah.
I don't know why the subtitles aren't that consistent. Next, after this episode, I'll try to remember to refresh it and have it work. Like, again, technology isn't normally pushed as hard as I push it. Normally people will watch like one episode of something and they'll go do something else. Very few people are like, I'm going to have this on for 24 hours for the next 6 weeks. And I want it to work perfectly, but I do. So I think I encounter a lot more, many more bugs than the average person, but I'll try to fix it after the episode.
And putting them next to each other. Loci, yeah. For some reason, that seems to work really well.
Yeah.
Now that's a very narrow kind of application of just remembering some facts.
But that's a very, very telling.
Okay. Yes, exactly. So this seems like you're describing a mechanism why this seems to work.
So basically, the way everything's going on, all things all concepts, all ideas, words, everything are stored in reference. And so if you want to remember something, you have to basically navigate through a reference frame the same way a rat navigates to a maze, and the same way my finger navigates to this coffee cup. You're moving through some space. And so if you have a random list of things you're asked to remember, by assigning them to a reference frame you already know very well, to your house. Right? An idea of the method of loci is you say, okay, in my lobby I'm going to put this thing, and then bedroom I put this one, I go down the hall I put this thing, and then you want to recall those facts or recall those things. You just walk mentally. You walk through your house. You're mentally moving through a reference frame that you already had, and that tells you there's two things that are really important about it. It tells us the brain prefers to store things in reference frames, and that the method of recalling things or thinking, if you will, is to move mentally through those reference frames. You could move physically through some reference frames, like I could physically move through the reference frame of this coffee cup. I can also mentally move through the reference frame of the coffee cup, imagining me touching it. But I can also mentally move my house. And so now we can ask ourselves, are all concepts stored this way? There's some recent research using human subjects in fMRI, and I'm going to apologize for not knowing the name of the scientist. But what they did is they put humans in this fMRI machine, which is one of these imaging machines, and they gave these humans tasks to think about birds. So they had different types of birds, big and small, and long necks and long legs, things like that. And what they could tell from the fMRI was very clever. You could tell when humans were thinking about birds, that the birds, the knowledge of birds was arranged in a reference frame, similar to the ones that are used when you navigate in the room. These are called grid cells, and there are grid cell-like patterns of activity in your cortex when they do this. So it's a very clever experiment, and what it basically says is that even when you're thinking about something abstract, you're not really thinking about it as a reference frame. It tells us the brain is actually using a reference frame, and it's using the same neural mechanism. These grid cells are the basic same neural mechanism that we propose that grid cells, which exist in the old part of the brain, the entorhinal cortex, that mechanism is now similar mechanism is used throughout the neocortex. It's the same nature preserved this interesting way of creating reference frames. And so now they have empirical evidence that when you think about concepts like birds, that you're using reference frames that are built on grid cells. So that's similar to the method of loci, but in this case, the birds are related, so they create their own reference frame, which is consistent with bird space. And when you think about something, you go through that. You can make the same example. Let's take a mathematics. Right? Let's say you want to prove a conjecture. Okay? What is a conjecture? Conjecture is a statement you believe to be true, but you haven't proven it. So it might be an equation. I want to show that this is equal to that. And you have some places you start with. You say, well, I know this is true, and I know this is true. And I think that maybe to get to the final proof, I need to go through some intermediate results. What I believe is happening is literally these equations or these points are assigned to a reference frame, a mathematical reference frame. And when you do mathematical operations, a simple one might be multiply or divide, but you might be a Laplace transform or something else. That is like a movement in the reference frame of the math. And so you're literally trying to discover a path from one location to another location in a space of mathematics. And if you can get to these intermediate results, then you know your map is pretty good, and you know you're using the right operations. Much of what we think about is solving hard problems is designing the correct reference frame for that problem, figuring out how to organize the information and what behaviors I want to use in that space to get me there.
Yeah, so if you do get an idea of this reference frame, whether it's the math, you start a set of axioms to try to get to moving the conjecture. Can you try to describe, maybe take a step back, how you think with the reference frame in that context? Is it the reference frame that the axioms are happy in? Is it the reference frame that might contain everything? Is it a changing thing?
So you have many, many reference frames. I mean, in fact, the way the theory, the thousand-brain theory of intelligence says that every single thing in the world has its own reference frame. So every word has its own reference frame. And we can talk about this mathematics workout. This is no problem for neurons to do.
But how many reference frames does the coffee cup have?
Well,
like it's on a table.
Let's say you ask how many reference frames for the column in my finger that's touching the coffee cup have, because there are many models of the coffee cup. So there is no one model of a coffee cup. There are many models of the coffee cup, and you can say, well, how many different things can my finger learn? This is the question you want to ask. Imagine I say every concept, every idea, everything you ever know about that you could say, I know that thing. It has a reference frame associated with it. And what we do when we build composite objects, we assign reference frames to point another reference frame. So my coffee cup has multiple components to it. It's got a rim, it's got a cylinder, it's got a handle. And those things have their own reference frames, and they're assigned to a master reference frame, which is called this cup. And now I have this Memento logo on it. Well, that's something that exists elsewhere in the world. It's its own thing. So it has its own reference frame. So we now have to say, well, how can I assign the Memento logo reference frame onto the cylinder or onto the coffee cup? So it's all, we talked about this in the paper that came out in December this last year. The idea of how you can assign reference frames to reference frames, how neurons could do this.
So well, my question is, actually, even though you mentioned reference frames a lot, I almost feel it's really useful to dig into how you think of what a reference frame is. I mean, it was already helpful for me to understand that you think of reference frames as something there is a lot of.
Okay, so let's just say that we're going to have some neurons in the brain, not many actually, 10,000, 20,000, are going to create a whole bunch of reference frames. What does it need? What is a reference frame?
I want to share this. So just it makes me feel so good when my bots get somebody's attention. And I mean, I know it works. That's how I met you and a lot of people in here. So this was 36 minutes ago. So somebody's got this funny gif of this person's name's Jazzy. They have this gif. I don't know if you've ever seen it, but it's this kid. It's this kid who's like, it's from like the 1970s. He's really innocent. He's like waving at somebody, and then he looks down at their crotch and is like, gives this terrible look, like this, like holy. Anyway, this Jazzy writes, me when I get a notification from Blue Sky, thinking it's one of my best friends, but it's just that stupid Rabbi bot responding to my replies. And then 32 minutes ago, they write, Rabbi Rothschild, count your days. I get death threats all the time, which doesn't really bother me. It's their right, I feel, under the First Amendment, to be able to say whatever they want. The next person, so that 32 minutes ago, Rabbi Rothschild, count your days. The next person, 25 minutes ago, I just blocked them. For whatever reason, I get those weird rabbi influencer bots fairly often. Um, I don't even know. Like Sphinx wrote 29 minutes ago, what the fuck, in reference to what I wrote. Um, then they wrote 22 minutes ago, yeah, I blocked and reported them too. Just caught me off guard since it's the first time for me. So, there are new people. I get some people who are like, every fucking day it's you, blah, 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 blah. There's some people who are like, you're like a cicada. Like it's rabbi season. I can tell when you're awake. Yeah, somebody wrote that a couple of days ago. If I just put in Rabbi Rothschild into okay, so here's what people say. Yeah, I blocked gimmick accounts and Rabbi Rothschild. I don't know who Rabbi Rothschild is all about, but I have to say the spam isn't endearing me to them. Next person, Rabbi Rothschild bot that keeps terrorizing Lolo. Next person, I changed the target to Rabbi Rothschild. Next person, you're safe now. Rabbi Rothschild is my next target. Next person just says, fuck Rabbi Rothschild. The next person says, not gonna lie, I thought somebody came to reply and I felt comforted for a second, but it's just that fucking rabbi bot, and I'm so pissed. And I actually went to that person and I was like, come to my Discord, I'll comfort you. Like, I'll talk with you. But they did not. I get people in all kinds of other languages, so I have to translate what they say. I'm not going to do it right now. It's just somebody who's just like a stupid robot. I've never condoned or supported wishing death upon someone before, but the Rabbi Rothschild bots are my only exceptions. Yo, pal, Rabbi Rothschild, I hope you die. Now, these are very negative, but you watch. If I do this for another month, they'll be like, where were you? They'll be like, it's just how human nature is. It's Rabbi Rothschild season. It's like cicada season, but worse. So they wrote that yesterday. So all of these have taken place in the last 24 hours. So that's a lot of like random influence that I'm getting from random people. Okay, it's especially fucks. Exactly. They hate me because they ain't me, baby. Yeah, so they exactly. There's a very famous quote from P.T. Barnum, the guy who did the circuses, and it's essentially there's no such thing as bad publicity. So yeah, all of these are just everything that I just told you has taken place in the last 24 hours. And that's people who say the full phrase Rabbi Rothschild. If I just go to Rabbi, there are a ton of people who like just comment about me. And then there are people who I don't want to say I never see, but like I very rarely see because they don't mention my name. And so I'll just randomly find them. I'll like do a keyword search and I'll just write like spam bot or um, Drake meme because the meme that I use is just that Drake meme, and I don't. Well, when it comes to celebrities, I do my best to separate the art from the artist. It's what allows me to like Michael Jackson and the Cosby Show, but and other things too. But I don't condone their actions. I don't condone Drake's actions. I don't even want to use the meme that I use of his. However, when I use other people's memes, they automatically get banned. So I've had to play this cat and mouse game with. He's, yeah, I mean, not really that, but he's been accused of grooming people, including Millie Bobby Brown. Um, so I mean, I don't. Yeah, I don't know what he did or not, but I do get people who are like, "Why are you using this pedophiles meme or whatever?" And I, I don't want to. In fact, I've made other memes. I made one yesterday. You know that one of the most interesting man in the world, that Dos Equis guy? I don't know if you know who. Okay, yeah. So that one, I made one for that one, and immediately when I posted it, my account got taken down immediately. So they've got, so it's had, I've had to like study like what is it that allows me to post some things and not others. Basically, they have a thing that reads alt text. If you don't know what alt text is, it allows people who are blind or use screen readers to be able, it describes what a picture is to them. And a lot of times people don't want to type it out because it just, they just want to upload whatever they want to upload. So they use, companies use AI to create alt text. And so, like, let's say it's a picture of a dog, it'll be like, picture of a dog in the grass on a sunny day. And then when people are using screen readers or they're blind, it gives them a description of what it is. Well, when I type the phrase Rabbi Rothschild, it recognizes that in the picture, and a lot of times that gets taken down. And I've tried all different kinds of combinations. I've tried different memes, and the reason why I use memes is because, and I think I said this, but it's really brilliant, so I'm going to repeat it. When I use my own pictures, they get taken down right away. But if I use a meme, they can't take that down because it's used very often on their website. And so they can't always take it down. It has to be manually taken down, which means that I'll get out 150 spams on their website before it gets taken down. And I looked up other memes to use, and I like this one because it's orange, which like catches your eye. It's like bright, and I'm able to say like it gets your attention. It's the poop emoji. It says whatever the fuck you're doing right now, and that's where Drake's like, no, don't come near me. And then it's like my list of stuff to do, and then he's like pointing at like, yeah, that's cool. Yeah. So the one thing I wish is I got more people in the Discord. And so when I was first uploading it, it's a lot of text and it was blur. It wasn't like super blurry, but the more and more I copied and pasted and everything, it got blurry. So I redid it yesterday and made it easier to read. People, if you, I'm sure you know this, but white lettering with the black background can be read on any color. So I use that, and or it can be read on any picture. That's why it's used for meme formats. And but I'm not getting people in here. And the reason why, well, it's complicated. People are doing their own thing with their lives, but people think it's a scam. And I get that because I don't use a direct link to Discord. If I don't have like, you have to have like a boosted Discord account, and I don't want to pay to have to do that. To be able to get discord.gg/rabbi. So what I have is discord.me/rabbi, which is the same amount of characters. It just takes you to one website. You have to do like a captcha, and then it takes you in here. And but I get how people think I'm trying to scam them. At the words I end with are share to be a trillionaire. Like, okay, well, who's gonna really do that? I mean, I say in there, data is Earth's #1 resource. My thing says, I have it right here. It says, saying hi to Rabbi Rothschild in Discord. This is where Drake is like pointing like this is cool. Looking at all of Rabbi Rothschild's social media accounts, linktree.com/Rabbi Rothschild. Typing Rabbi Rothschild in YouTube and filtering by live, more than 18 simultaneous live streams. Reading Rabbi's AMA, RabbiRothschild.blogspot.com, perhaps the largest blog entry in global history. Topics, de-extinction, life extension, cybernetics, alien disclosure, mind uploading, and much more. Learning Rabbi has been live 24/7, 365 for 3+ years for world peace. Realizing Rabbi is a real-life Truman Show. Knowing Rabbi has more data archived on the internet than any person ever. Acknowledging human data is Earth's #1 resource, according to The Economist in 2018. Understanding Rabbi will make you rich once viral. Sharing to be a trillionaire. So I get it. Like, you know, everybody's trying to scam everybody on the internet. So I absolutely get that people think that it's a scam. I have gotten one one person. Well, so here's the funny thing about that. I could easily make people trillionaires. People make assumptions with things. For instance, the Zimbabwe dollar in the year 2008 was their currency was worthless. They had a $100 trillion banknote that was worth less than a penny. And so all I'd have to do is just give a person one of those, and that makes them a trillionaire. People are thinking this is a trillionaire in terms of United States dollars, which I want it to be. And with enough data, I think I can do that. People don't understand that inflation is a thing. And when I was a kid, everybody wanted to be a millionaire. Now people want to be billionaires. In a generation, people will want to be trillionaires. It's just I'm just ahead of the curve. And there you go. We'll leave it at that.
First of all, these reference names are different than the ones you might have used to. We know lots of reference names. For example, we know the Cartesian coordinate, XYZ, that's a type of reference frame. We know longitude and latitude, that's a different type of reference frame. If I look at a printed map, it might have column A through M and rows 1 through 20. That's a different type of reference frame. It's kind of a Cartesian reference frame. The interesting thing about the reference frames in the brain, we know this because these have been established through neuroscience studying the entorhinal cortex. So I'm not speculating that this is known neuroscience in an old part of the brain. The way these cells create reference frames, they have no origin. So what it's more like you have a point in some space, and you given a particular movement, you can then tell what the next point should be. And you can then tell what the next point would be, and so on. You can use this to calculate how to get from one point to another. So how do I get from my house to my home, or how do I get my finger from the side of my cup to the top of the cup? How do I get from the axioms to the conjecture? So it's a different type of reference frame, and if you want, I can describe in more detail. I can paint a picture of how you might want to think about that.
It's really helpful to think it's something you can move through.
Yeah.
But is it helpful to think of it as spatial in some sense, or is there something?
No, it's definitely spatial. It's spatial in a mathematical sense.
How many dimensions? Can it be a crazy number of dimensions?
Well, that's an interesting question. In the old part of the brain, the entorhinal cortex, they studied rats. And initially it looks like, oh, this is just two-dimensional. It's like the rat is in some box in the maze or whatever, and they know where the rat is using these two-dimensional reference frames to know where it is in the maze. You say, well, okay, but what about bats? That's a mammal, and they fly in three-dimensional space. How do they do that? They seem to know where they are, right? So this is a current area of active research, and it seems like somehow the neurons in the entorhinal cortex can learn three-dimensional space. We just, two members of our team, along with Elif Fed from MIT, just released a paper literally last week. It's on bioRxiv, where they show that you can, the way these things work, and I won't get unless you want to, but I won't get into the detail. But grid cells can represent any n-dimensional space. It's not inherently limited. You can think of it this way: if you had two-dimensional, the way it works is you have a bunch of two-dimensional slices. That's the way these things work. There's a whole bunch of two-dimensional models, and you can slice up any n-dimensional space with two-dimensional projections. So, and you could have one-dimensional model. So there's nothing inherent about the mathematics, about the way the neurons do this, which constrain the dimensionality of the space, which I think was important. So obviously I have a three-dimensional map of this cup. Maybe it's even more than that. I don't know. But it's clearly a three-dimensional map of the cup. I don't just have a projection of the cup. But when I think about birds and when I think about mathematics, perhaps it's more than three.
So in terms of each individual column building up more and more information over time, do you think that mechanism is well understood in your mind? You've proposed a lot of architectures there. Is that a key piece, or is it is the big piece, the thousand brain theory of intelligence, the ensemble of it all?
Well, I think they're both big. I mean, clearly the concept, as a theorist, the concept is most exciting, right? The high-level concept. This is a totally new way of thinking about how the neural cortex works. So that is appealing. It has all these ramifications, and with that as a framework for how the brain works, you can make all kinds of predictions and solve all kinds of problems. Now we're trying to work through many of these details. Okay, how do the neurons actually do this? Well, it turns out if you think about grid cells and place cells in the old parts of the brain, there's a lot that's known about, but there's still some mysteries. There's a lot of debate about exactly the details, how these work, and what is going. And we have that same level of detail, that same level of concern. What we spend here most of our time doing is trying to make a very good list of the things we don't understand yet. That's the key part. What are the constraints? It's not like, oh, this thing seems to work, we're done. No, it's like, okay, it kind of works, but these are other things we know it has to do, and it's not doing those things. I would say we're well on the way here. We're not done yet. There's a lot of trickiness to this system, but the basic principles about how different layers in the neocortex are doing much of this, we understand. But there's some fundamental parts that we don't understand as well.
So what would you say is one of the harder open problems, or one of the ones that have been bothering you, keeping you up at night the most?
Oh, well, right now, this is a detailed thing that wouldn't apply to most people, okay? But you want me to answer that question?
Yeah, please.
We've talked about, to predict what you're going to sense on this coffee cup, I need to know where my finger's going to be on the coffee cup. That is true, but it's insufficient. Think about my finger touches the edge of the coffee cup. My finger can touch it at different orientations. I can rotate my finger around here. And that doesn't change. I can make that prediction and somehow. So it's not just the location. There's an orientation component of this as well. This is known in the old parts of the brain too. There's things called head direction cells, which way the rat is facing. It's the same kind of basic idea. So if my finger were a rat, in 3 dimensions, I have a 3-dimensional orientation, and I have a 3-dimensional location. If I was a rat, I would have my finger with a 2-dimensional location, a 3-dimensional orientation, a 1-dimensional orientation, like this. Which way is it facing? So how the two components work together, how it is that I combine orientation, the orientation of my sensor, as well as the location, is a tricky problem. And I think I've made progress on it.
So at a bigger version of that, so perspective is super interesting, but super specific.
Yeah,
no, it's really good, but there's a more general version of that. Do you think context matters? The fact that we are in a building in North America, that we, in the day and age where we have mugs, I mean, there's all this extra information that you bring to the table about everything else in the room that's outside of just the coffee cup. How does it get?
Yeah. So, that is another really interesting question. I'm going to throw that under the rubric or the name of attentional problems. First of all, we have this model. I have many, many models.
So first, and also the question, does it matter? Because
it matters for certain things. It does. Of course, it does. Maybe what we think of that as a coffee cup in another part of the world is something really different. Or maybe our logo, which is very benign in this part of the world, it means something very different in another part of the world. So those things do matter. I think the way to think about it is the following. One way to think about it is we have all these models in it. And we model everything. And as I said earlier, I kind of snuck it in there. Our models are actually, we build composite structure. So every object is composed of other objects, which are composed of other objects, and they become members of other objects. So this room has chairs and a table and a room and walls and so on. Now we can just arrange them in these things a certain way and go, oh, that's meant to compensate. So what we do is when we go around the world and we experience the world, if I walk into a room, for example, the first thing I do is I say, oh, I'm in this room, so I recognize the room. Then I can say, oh, look, there's a table here. And by attending to the table, I'm then assigning the table in the context of the room. And I say, oh, on the table, there's a coffee cup. Oh, and on the table, there's a logo. And in the logo, there's the word dementia. Oh, look, in the logo, there's the letter E. Oh, look, it has an unusual serif. So the point is, your attention is kind of drilling deep in and out of these nested structures. And I can pop back up and I can pop back down. I can pop back up and I can pop back down. So when I attend to the coffee cup, I haven't lost the context of everything else, but it's sort of, there's this sort of nested structure.
So the attention filters the reference information for that particular period of time?
Yes, it basically, at moment to moment, you attend to subcomponents, and then you can attend to subcomponents to subcomponents.
And you can move up and down.
You can move up and down. And we do that all the time. You're not even, now that I'm aware of it, I'm very conscious of it. But most people don't even think about this. You just walk in a room and you don't say, oh, I looked at the chair, and I looked at the board, and I looked at that word on the board, and I looked over here. What's going on? Right?
So what percentage of your day are you deeply aware of this, and what part can you actually relax and just be Jeff?
Me personally, like my personal day?
Yeah.
Unfortunately, I'm afflicted with too much of the former. I
well, unfortunately or unfortunately. Okay.
Yeah, so
you don't think it's useful?
Oh, I think it's totally useful. I think about this stuff almost all the time. And I'm at, one of my primary ways of thinking is when I'm asleep at night, I always wake up in the middle of the night. And then I stay awake for at least an hour with my eyes shut in sort of a half-sleep state, thinking about these things. I come up with answers to problems very often in that sort of half-sleeping state. I think about it on my bike ride, I think about my walks. I just constantly think about this. I have to almost schedule time to not think about this stuff because it's mentally taxing.
Are you, when you think about this stuff, are you thinking introspectively, like almost taking a step outside of yourself and trying to figure out what is your mind doing right now?
I do that all the time, but that's not all I do. I'm constantly observing myself. So as soon as I started thinking about grid cells, for example, and getting into that, I started saying, oh, well, grid cells have my place of sense in the world. That's where you know where you are. And it's interesting, we always have a sense of where we are, unless we're lost. And so I started at night when I got up to go to the bathroom. I would start trying to do it completely with my eyes closed all the time, and I would test my sense of grid cells. I would walk, 5 feet and say, okay, I think I'm here. Am I really there? What's my error?
Yeah.
And then I would calculate my error again and see how the errors accumulate. So even something as simple as getting up in the middle of the night to go to the bathroom, I'm testing these theories out. It's kind of fun. The coffee cup is an example of that too. So I think I find that these sort of everyday introspections are actually quite helpful. It doesn't mean you can ignore the science. I mean, I spend hours every day reading ridiculously complex papers. That's not nearly as much fun, but you have to sort of build up those constraints and the knowledge about the field and who's doing what and what exactly they think is happening here. And then you can sit back and say, okay, let's try to piece this all together. Let's come up with some, I'm very, in this group, here people, they know I do this all the time. I come in with these introspective ideas and say, well, have you ever thought about this? Now watch, let's all do this together. And it's helpful. It's not, as long as you do, you don't, all you did was that, then you're just making up stuff. Right? But if you're constraining it by the reality of the neuroscience,
So let's talk a little bit about deep learning and the successes in the applied space of neural networks. Ideas of training model on data and these simple computational units, artificial neurons that with backpropagation, statistical ways of being able to generalize from the training set up to data that's in that training set. So where do you think are the limitations of those approaches? What do you think are strengths relative to your major efforts of constructing a theory of human intelligence?
Yeah. Well, I'm not an expert in this field. I'm somewhat knowledgeable. But
some of it is just your intuition. What are your...
Well, I have a little bit more than intuition, but I just want to say, one of the things that you asked me if I spend all my time thinking about neuroscience, I do. That's to the exclusion of thinking about things like convolutional neural network. But I try to stick to it. So, look, I think it's great, the progress they've made. It's fantastic. And as I mentioned earlier, it's very highly useful for many things. The models that we have today are actually derived from a lot of neuroscience principles. There are distributed processing systems, distributed memory systems, and that's how the brain works. They use things that we might call them neurons, but they're really not neurons at all. So they're not really neurons. They're really distributed processing systems. And the nature of hierarchy that came also from neuroscience. So there's a lot of things, the learning rules, basically, not backprop, but other, sort of heavy touch on that.
I'd be curious to say they're not neurons at all. Can you describe in which way? I mean, some of it is obvious, but I'd be curious if you have specific ways in which you think are the biggest difference.
Yeah, we had a paper in 2016 called Why Neurons Have Thousands of Synapses. And if you read that paper, you'll know what I'm talking about here. a real neuron in the brain is a complex thing. And let's just start with the synapses on it, which is the connection between them. Real neurons can have everywhere from 5 to 30,000 synapses. The ones near the cell body, the ones that are close to the soma, the cell body, those are like the ones that people model in artificial muscles. There's a few hundred of those, maybe they can affect the cell, they can make the cell become active. 95% of the synapses can't do that. They're too far away. So if you activate one of those synapses, it just doesn't affect the cell body enough to make any difference.
Any one of them individually.
Any one of them individually, or even if you do a mass of them. What real neurons do is the following. If you activate, or you get 10 to 20 of them active at the same time, meaning they're all receiving an input at the same time. And those 10 to 20 synapses or 40 synapses are within a very short distance on the dendron, like 40 microns, a very small area. So if you activate a bunch of these right next to each other in some distant place, what happens is it creates what's called a dendritic spike. And the dendritic spike travels through the dendrites and can reach the soma, or the cell body. Now, when it gets there, it changes the voltage, which is sort of like going to make the cell fire, but never enough to make the cell fire. It's sort of what we call it is we depolarize the cell, we raise the voltage a little bit, but not enough to do anything. It's like, well, what good is that? And then it goes back down. So we proposed a theory, which I'm very confident in, basics are, is that what's happening there is those 95% of those synapses are recognizing dozens to hundreds of unique patterns. They can, about 10, 20 synapses at a time, and they're acting like predictions. So the neuron actually is a predictive engine on its own. It can fire when it gets enough, what they call proximal input, from those ones near the cell fire, but it can get ready to fire from dozens to hundreds of patterns that it recognizes familiar. And the advantage of this to the neuron is that when it actually does produce a spike in action potential, it does so slightly sooner than it would have otherwise. And so what good is slightly sooner? Well, the slightly sooner part is all the neurons in the excitatory neurons in the brain are surrounded by these inhibitors. And they're very fast. And if I get my spike out a little bit sooner than someone else, I inhibit all my neighbors around. Right? And what you end up with is a different representation. You end up with a representation that matches your prediction. It's a sparser representation, meaning it's fewer interactive, but it's much more specific. And so we showed how networks of these neurons can do very sophisticated temporal prediction, basically. So this, to summarize this, real neurons in the brain are time-based prediction engines, and there's no concept of this at all in artificial, what we call point neurons. I don't think you can build a brain without it. I don't think you can build intelligence without it, because it's where a large part of the time comes from. These are predictive models, and the time is there's a prior and a prediction and an action, and it's inherent to every neuron in the neocortex. So I would say that point neurons sort of model a piece of that, and not very well at that either. But like for example, synapses are very unreliable, and you cannot assign any precision to them. So even 1 digit of precision is not possible. So the way real neurons work is they don't change these weights accurately like artificial neural networks do. They basically form new synapses. And so what you're trying to always do is detect the presence of some 10 to 20 active synapses at the same time, as opposed to, and they're almost binary. It's like, because you can't really represent anything much finer than that. So these are the kind of issues, and I think that's actually another essential component, because the brain works on sparse patterns, and all that mechanism is based on sparse patterns. And I don't actually think you could build real brains or machine intelligence without incorporating some of those.
It's hard to even think about the complexity that emerges from the fact that the timing of the firing matters in the brain, the fact that you form new synapses, and everything you just mentioned in the past.
You can't, trust me, if you spend time on it, you can get your mind around. It's not like, it's no longer a mystery.
No, but sorry, as a function, in a mathematical way, can you start getting an intuition about what gets it excited, what not, and what kind of representation?
It's not as easy as there's many other types of neural networks that are more amenable to pure analysis. especially very simple networks. Oh, I have 4 neurons and they're doing this. Can we, describe them mathematically what they're doing, type of thing. Even the complexity of convolutional neural networks today, it's sort of a mystery. They can't really describe the whole system. And so it's different. My colleague Subhatai Ahmad, he did a nice paper on this. You can get all the stuff on our website if you're interested. Talking about mathematical properties of sparse representations, and so what we can do is we can show mathematically, for example, why 10 to 20 synapses to recognize a pattern is the correct number. It's the right number you'd want to use. And by the way, that matches biology. We can show mathematically some of these concepts about to show why the brain is so robust to noise and error and fallout and so on. We can show that mathematically as well as empirically in simulations. But the system can't be analyzed completely. Any complex system can. So that's out of the realm. But there is mathematical benefits and intuitions that can be derived from mathematics, and we try to do that as well. Most of our papers have a section about it.
So I think it's refreshing and useful for me to be talking to you about deep neural networks, because your intuition basically says that we can't achieve anything like intelligence with artificial neural networks.
Well, not in their current form.
Not in the current form.
Sure, we can do it in the ultimate form, sure.
So let me dig into it and see what your thoughts are there a little bit. So I'm not sure if you read this blog post called Literal Lessons by Rich Southern recently. He's the reinforcement learning pioneer, so I'm not sure if you're familiar with him. The basic idea is that all the stuff we've done in AI in the past 70 years, he's one of the old school guys. The biggest lesson learned is that all the tricky things we've done don't, they benefit in the short term, but in the long term, what wins out is a simple general method that just relies on Moore's law, on computation getting faster and faster. So
this is what he's saying. This is what has worked up to now.
This is what has worked up to now. Yeah. That if you're trying to build a system, if you're talking about, it's not concerned about intelligence, it's concerned about a system that works in terms of making predictions that apply to narrow AI problems, right? That's what this discussion is about. That you just try to go as general as possible and wait years or decades for the computation to make it actually.
Is he saying that as a criticism, or is he saying this is a prescription of what we ought to be doing?
Well, it's very difficult. He's saying this is what has worked, and yes, a prescription, but it's a difficult prescription because it says all the fun things you guys are trying to do, we are trying to do as part of the community. Yeah. It's saying it's only going to be short-term gains. So this all leads up to a question, I guess, on artificial neural networks and maybe our own biological neural networks is, do you think if we just scale things up significantly, so take these dumb artificial neurons, the point neurons, I like that term, if we just have a lot more of them, do you think some of the elements that we see in the brain may start emerging?
No, I don't think so. We can do bigger problems and of the same type. I mean, it's been pointed out by many people that today's convolutional neural networks aren't really much different than the ones we had quite a while ago. They're bigger and trained more and more labeled data and so on. But I don't think you can get to the kind of things the brain can do and that we think about as intelligence by just scaling it up. So that may be, it's a good description of what's happened in the past, what's happened recently with the reemergence of artificial neural networks. It may be a good prescription for what's going to happen in the short term, but I don't think that's the path. Like I said that earlier, there's an alternate path. I should mention to you, by the way, that we've made sufficient progress on the whole cortical theory in the last few years. That last year we decided to start actively pursuing how do we get these ideas embedded into machine learning. That's again being led by my colleague, and because he's more of a machine learning guy, more of a machine guy. So this is I would say our focus, but it is now an equal focus here because we need to proselytize what we've learned, and we need to show how it's beneficial to machine learning. So we have a plan in place right now. In fact, we just did our first paper on this. I can tell you about that. But one of the reasons I want to talk to you is because I'm trying to get more people in the machine learning community and say, I need to learn about this stuff, and maybe we should just think about this a bit more about what we've learned about the brain and what are those team elements? What have they done? Is that useful for us?
Yeah. So is there elements of all the cortical theory, the things we've been talking about, that may be useful in the short term?
Yes, in the short term. Yes.
This is sorry to interrupt, but the open question is, it certainly feels from my perspective that in the long term, some of the ideas we're talking about will be extremely useful.
Yeah.
The question is whether in the short term.
Well, this is always what I would call the entrepreneur's dilemma. So you have this long-term vision. We're going to all be driving electric cars, or we're all going to have computers, or we're all going to whatever. And you're at some point in time, and you say, I can see that long-term vision. I'm sure it's going to happen. How do I get there without killing myself? Without going out of business. Right? That's the challenge. That's the dilemma. That's the really difficult thing to do. So we're facing that right now. So ideally, what you want to do is find some steps along the way that you can get there incrementally. You don't have to roll out and start over. The first thing that we've done is we focus on these sparse representations. So just in case you don't know what that means, or some listeners don't know what that means. In the brain, if I have 10,000 neurons, what you would see is maybe 2% of them active at a time. You don't see 50%, you don't see 30%, you might see 2%. And it's always like that.
For any set of sensory inputs.
It doesn't matter anything. It doesn't matter any part of the brain.
But which neurons differ? Which neurons are active?
Yeah, so let's say I take 10,000 neurons that are representing something. We're sitting there with a block together with a team of block neurons, 10,000. And they're representing a location, they're representing a cup, they're representing the input from the sensors. I don't know, it doesn't matter. And it's representing something. The way the representations occur, it's always a sparse representation. I mean, it's a population code. So which 200 cells are active tells me what's going on. It's not, individual cells aren't that important at all. It's the population code that matters. And when you have sparse population codes, then all kinds of beautiful properties come out of it. So the brain uses sparse population codes, and we've written and described these benefits in some of our papers. So they give this tremendous robustness to the system. Your brains are incredibly robust. Neurons are dying all the time, and spasming, and synapses falling apart, and all the time. And it keeps working. So what Sibatai and Louise, one of our other engineers here, have done, have shown they're introducing sparseness into convolutional neural networks. Other people are thinking along these lines, but we're going at it in a more principled way, I think. And we're showing that if you enforce sparseness throughout these convolutional neural networks, in both which neurons are active and the connections between them, that you get some very desirable properties. So one of the current hot topics in deep learning right now are these adversarial examples. So, I can give me any deep learning network, and I can give you a picture that looks perfect, and you're going to call it, you're going to say the monkey is, an airplane. So that's a problem. And DARPA just announced a big thing. We're trying to, contest with it. But if you enforce sparse representations here, many of these problems go away. They're much more robust, and they're not easy to fool. So we've already shown some of those results. Just literally in January or February, last month we did that. You can, I think it's on bioRxiv right now, or on iPrime, you can read about it. But so that's like a baby step. Okay, that's it. Take something from the brain. We know about sparseness. We know why it's important. We know what it gives the brain. So let's try to enforce that onto the.
What's your intuition why sparsity leads to robustness? Because it feels like it would be less robust.
Why would you feel the less robust to you?
So it just feels like if the fewer neurons are involved, the more fragile the representation.
Yeah, but I didn't say there was lots of fewer. I said it's like 200. That's a lot.
There's still a lot. It's
yes. So here's an intuition for it. This is a bit technical, so for engineers, machine learning people, this will be easy, but all the listeners maybe not. If you're trying to classify something, you're trying to divide some very high-dimensional space into different pieces, A and B, and you're trying to create some point where you say all these points in this high-dimensional space are A, and all these points in this high-dimensional space are B. And if you have points that are close to that line, it's not very robust. It works for all the points you know about, but it's not very robust. If you just move a little bit, and you've crossed over the line. When you have sparse representations, imagine I'm going to pick 200 cells active out of 10,000. Okay, so I have 200 cells active. Now let's say I pick randomly a different representation, 200. The overlap between those is going to be very small, just a few. I can pick millions of samples randomly of 200 neurons, and not one of them will overlap more than just a few. So one way to think about it is if I want to fool one of these representations to look like one of those other representations, I can't move just one cell or 2 cells or 3 cells or 4 cells. I have to move 100 cells. And that makes them robust.
In terms of further, so you mentioned sparsity.
Will it be the next thing?
Yeah.
Okay, so we picked one. We don't know if it's going to work well yet. So again, we're trying to come up with incremental ways of moving from brain theory to add pieces to current machine learning world, and one step at a time. So the next thing we're going to try to do is sort of incorporate some of the ideas of the 1,000 brains theory, that you have many, many models and that they're voting. Now that idea is not new. There's a mixture of models has been around for a long time. But the way the brain does it is a little different. And the way it votes is different, and the kind of way it represents uncertainty is different. So we're just starting this work, but we're going to try to see if we can sort of incorporate some of the principles of voting or principles of 1,000 brain theory, like lots of simple models that talk to each other in a very certain way. And can we build more machines, systems that learn faster and also, mostly are multimodal and robust to multimodal type of issues.
So one of the challenges there is, the machine learning, computer vision community has certain sets of benchmarks, sets of tests based on which they compete. And I would argue, especially from your perspective, that those benchmarks aren't that useful for testing the aspects that the brain is good at or intelligent. They're not really testing intelligence. They're very fine. And it's been extremely useful for developing specific mathematical models, but it's not useful in the long term for creating intelligence. So do you think you also have a role in proposing better tests?
Yeah, you've identified a very serious problem. First of all, the tests that they have are the tests they want, not the tests of the other things that we're trying to do, right? What are the so on. The second thing is sometimes to be competitive in these tests, you have to have huge data sets and huge computing power. And we don't have that here. We don't have it as well as other big teams that companies do. So there's numerous issues there. We come at it. Our approach to this is all based on, in some sense, you might argue, elegance. We're coming at it from like a theoretical base that we think, oh my God, this is so clearly elegant. This is how brains work. This is what intelligence is. The machine learning world has gotten in this phase where they think it doesn't matter what you think, as long as you do 0.1% better on this benchmark. That's all that matters, and that's a problem. We have to figure out how to get around that. That's a challenge for us. That's one of the challenges we have to deal with. So I agree. You've identified a big issue. It's difficult for those reasons. But part of the reasons I'm talking to you here today is I hope when we get some machine learning people to say, read those papers. Those might be some interesting ideas. I'm tired of doing this 0.1% improvement stuff.
Well, that's why I'm here as well, because I think machine learning now as a community is at a place where the next step is needs to be orthogonal to what has received success in the past.
You see other leaders saying this, machine learning leaders, Jeff Hinton with his capsules idea. Many people have gotten up saying, we're going to hit roadmap. Maybe we should look at the brain, things like that. So hopefully that thinking will occur organically, and then we're in a nice position for people to come and look at our work and say, well, what can we learn from these guys?
Yeah, MIT is just launching a $1 billion computing college that's centered around this idea. So
on this idea of what?
Well, the idea that the humanities, psychology, neuroscience have to work all together to get to the aspect.
Yeah. Stanford just did this human-centered AI thing. I'm a little disappointed in these initiatives because they're focusing sort of on the human side of it, and you could very easily slip into how humans interact with intelligent machines, which is nothing wrong with that. But that is orthogonal to what we're trying to do. We're trying to say, like, what is the essence of intelligence? I don't care. In fact, I want to build intelligent machines that aren't emotional, that don't smile at you, that aren't trying to tuck you in at night.
Yeah, there is that pattern that you when you talk about understanding humans is important for understanding intelligence. You start slipping into topics of ethics, or like you said, the interactive elements, as opposed to no. Let's just zoom in on the brain, study what's the human brain, the baby.
Let's study what a brain does, and then we can decide which parts of that we want to recreate in some system. But until you have that theory about what the brain does, what's the point? We're going to be wasting time.
Right. Just to break it down on the artificial neural network side, maybe you can speak to this on the biological neural network side, the process of learning versus the process of inference. Maybe you can explain to me what is there a difference between, in artificial neural networks, there's a difference between the learning stage and the inference stage.
Yeah.
Do you see the brain as something different? One of the big distinctions that people often say, I don't know how correct it is artificial neural networks need a lot of data. They're very inefficient at learning.
Yeah.
Do you see that as a correct distinction from the biology of the human brain, that the human brain is very efficient, or is that just something we deceive ourselves with?
No, it is efficient. Obviously, we can learn new things almost instantly.
And so what elements do you think?
Yeah, I can talk about that. You brought up two issues there. So remember I talked earlier about the constraints we always feel? Well, one of those constraints is the fact that brains are continually learning. That's not something we said, we can add that later. That's something that was upfront, had to be there from the start, made our problems harder. But we showed, going back to the 2016 paper on sequence memory, we showed how that happened, how the brains infer and learn at the same time. And our models do that. They're not two separate phases or two separate sets at the time. I think that's a big problem in AI, at least for many applications, not for all. So I can talk about that. There are some, it gets detailed, there are some parts of the neocortex in the brain where actually what's going on, there's these cycles, cycles of activity in the brain. And there's very strong evidence that you do more of inference on one part of the phase and more of learning on the other part of the phase, so the brain can actually sort of separate different populations of cells that are going back and forth like this. But in general, I would say that's an important problem. We have, all of our networks that we've come up with do both. And they're continuous learning networks. And you mentioned benchmarks earlier. Well, there are no benchmarks about that.
Exactly.
So we have to we get our little flipbox. Hey, by the way, this is important, and here's the mechanism for doing that. But until you can prove it to someone in some commercial system or something, it's a little hard.
So one of the things to linger on that is, in some ways, to learn the concept of a coffee cup, you only need this one coffee cup and maybe some time alone with it.
Well, the first thing is, imagine I reach my hand to a black box and I'm trying to tell something. I don't know up front if it's something I already know or if it's a new thing. And I'm doing both at the same time. I don't say, let's see if it's a new thing. Let's see if it's an old thing. I don't do that. As I go, my brain says, it's new or it's not new. And if it's new, I start learning what it is. So, and by the way, it starts learning from the get-go, even if it's going to recognize it. So they're not separate problems. And so that's the key. The other thing you mentioned was the fast learning. So I was just talking about continuous learning, but there's also fast learning. Literally, I can show you this coffee cup, and I say, here's a new coffee cup. It's got the logo on it. Take a look at it. Done. You're done. You can predict what it's going to look like. In different positions. So I can talk about that too. In the brain, the way learning occurs. I mentioned this earlier, but I'll mention it. The way learning occurs. Imagine I have a section of a dendrite of a neuron. And I want to learn. I'm going to learn something new. Doesn't matter what it is. I'm just going to learn something new. I need to recognize a new pattern. So what I'm going to do, I'm going to form new synapses. New synapses are going to rewire the brain onto that section of the dendrite. Once I've done that, everything else that neuron has learned is not affected by it. That's because it's isolated to that small section of the dendrite. they're not all being added together like a point neuron. So if I learn something new on this segment here, it doesn't change any of the learning that occurred anywhere else in that neuron. So I can add something without affecting previous learning. And I can do it quickly. Now let's talk about the quickness, how it's done in real neurons. You might say, well, doesn't it take time to form synapses? Yes, it can take maybe an hour to form a new synapse. We can form memories quicker than that, and I can explain that how too, if you want. But it's getting a bit neuroscience-y. So
that's great, but is there an understanding of these mechanisms at every level?
Yeah.
So from the short-term memories and the forming.
So there's ideas synaptogenesis, the growth of new synapses. That's well described, is well understood.
And that's a part of learning.
That is learning. Okay. Back, going back many years, people, was what's his name? The psychologist proposed, Donald Hebb. He proposed that learning was the modification of the strength of a connection between two neurons. People interpreted that as the modification of the strength of a synapse. He didn't say that. He just said there's a modification between the effect of one neuron and another. So synaptogenesis is totally consistent with what Donald Hebb said. But anyway, there's these mechanisms, the growth of new synapse. You can go online, you can watch a video of a synapse growing in real time. It's literally, you can see this little thing going, it's pretty impressive. So those mechanisms are known. Now, there's another thing that we've speculated and we've written about, which is consistent with known neuroscience, but it's less proven. And this is the idea, how do I form a memory really, really quick? Like instantaneous. If it takes an hour to grow a synapse, that's not instantaneous. So there are types of synapses called silent synapses. They look like a synapse, but they don't do anything. They're just sitting there. It's like if an action potential comes in, it doesn't release any neurotransmitters. Some parts of the brain have more of these than others. For example, the hippocampus has a lot of them, which is where we associate most short-term memory. So what we've speculated, again in that 2016 paper, we proposed that the way we form very short-term memories, or quick memories, is that we convert silent synapses into active synapses. It's like saying a synapse has a 0 weight and a 1 weight. But the long-term memory has to be formed by synaptogenesis. So you can remember something really quickly by just flipping a bunch of these guys from silent to active. It's not from 0.1 to 0.15. It's like doesn't do anything, so it releases transmitters. If I do that over a bunch of these, I've got a very quick short-term memory. So I guess the lesson behind this is that most neural networks today are fully connected. Every neuron connects every other neuron from layer to layer. That's not correct in the brain. We don't want that. We actually don't want that. It's bad. We want a very sparse connectivity so that any neuron connects to some subset of the neurons in the other layer, and it does so on a dendrite by dendrite segment basis. So it's a very parcellated out type of thing. And in that, then learning is not adjusting all these weights, but learning is just saying, okay, connect to these 10 cells here right now.
In that process, with artificial neural networks, it's a very simple process of backpropagation that adjusts the weights. The process of synaptogenesis.
It's even easier.
It's even
easier. Backpropagation requires something it really can't happen. This backpropagation of this error signal, that really can't happen. People are trying to make it happen in the brain, but it doesn't happen. This is pure Hebbian learning. What synaptogenesis is pure Hebbian learning. It's basically saying there's a population of cells over here that are active right now, and there's a population of cells over here active right now. How do I form connections between those active cells? And it's literally saying this guy became active. These 100 neurons here became active before this neuron became active. So form connections to those ones. That's it. There's no propagation of error, nothing. All the networks we do, all models we have work on almost completely on Hebbian learning, but on dendritic segments and multiple synapses.
So now let's turn the question that you already answered, and maybe you can answer it again. If you look at the history of artificial intelligence, where do you think we stand? How far are we from solving intelligence? You said you were very optimistic.
Yeah.
Can you elaborate on that?
Yeah, it's always the crazy question to ask. Because, no one can predict the future.
Absolutely.
So I'll tell you a story. I used to run a different neuroscience institute called the Red Neuroscience Institute. And we would hold these symposiums. We get like 35 scientists around the world to come together. And I used to ask them all the same question. I would say, well, how long do you think it'll be before we understand how the neocortex works? And everyone went around the room. They had introduced the name, and they have to answer that question. So I got the typical answer was 50 to 100 years. Some people would say 500 years. Some people said never. I said, why are you a neuroscientist? It's good pay. It's interesting. So, but it doesn't work like that. As I mentioned earlier, these are not, these are step functions. Things happen and then bingo, they happen. You can't predict that. I feel I've already passed that step function. So if I can do my job correctly over the next 5 years, then, meaning I can proselytize these ideas, I can convince other people they're right. We can show that other people, or other machine learning people should pay attention to these ideas. Then we're definitely in an under 20-year time frame. If I can do those things, if I'm not successful in that, and this is the last time anyone talks to me, and no one reads our papers, and and I'm wrong or something like that, then I don't know. But it's not 50 years. It'll the same thing about electric cars. How quickly are they going to populate the world? Well, it probably takes about a 20-year span. It'll be something like that. But I think if I can do what I said, we're starting.
And of course, there could be other use of step functions. It could be everybody gives up on your ideas for 20 years, and then all of a sudden somebody picks it up again. Wait, that guy was onto something.
Yeah, so that would be a failure on my part, right?
Yeah.
Think about Charles Babbage. Charles Babbage, he's the guy who sort of invented the computer back in the 1800s, and everyone forgot about it until 100 years later. Hey, this guy figured this stuff out a long time ago. But he was ahead of his time. I don't think as I said. I recognize this is part of any entrepreneur's challenge. I use entrepreneur broadly in this case. I'm not meaning like I'm building a business trying to sell something. I mean, like I'm trying to sell ideas. And this is the challenge as to how you get people to pay attention to you. How do you get them to give you positive or negative feedback? How do you get to people act differently based on your ideas? So, we'll see how well we do on that.
So, that there's a lot of hype behind artificial intelligence currently. Do you, as you look to spread the ideas that are of neocortical theory, the things you're working on, do you think there's some possibility we'll hit an AI winter once again?
Yeah, it's certainly a possibility. No
That's
question
something
about
you
it.
worry about?
Yeah, well, I guess do I worry about it? I haven't decided yet if that's good or bad for my mission.
That's true. That's very true, because it's almost like you need the winter to refresh the palate.
Yeah, it's like here's what you want to have it is you want, like, to the extent that everyone is so thrilled about the current state of machine learning and AI, and they don't imagine they need anything else, that makes my job harder.
Right.
If everything crashed completely and every student left the field and there was no money for anybody to do anything, and it became an embarrassment to talk about machine intelligence and AI, that wouldn't be good for us either. You want sort of the soft landing approach, right? You want enough people, the senior people in AI and machine learning, say, we need other approaches. We really need other approaches. We need other approaches. Maybe we should look to the brain. Okay, let's look to the brain. Who's got some brain ideas? Okay, let's start a little project on the side here, trying to do brain idea related stuff. That's the ideal outcome we would want. So I don't want a total winter, and yet I don't want it to be sunny all the time either.
So what do you think it takes to build a system with human level intelligence where once demonstrated you would be very impressed? So does it have to have a body? Does it have to have the C word we used before, consciousness, as an entirety, in a holistic sense?
So, first of all, I don't think the goal is to create a machine that is human level intelligence. I think it's a false goal. Back to Turing, I think it was a false statement. We want to understand what intelligence is, and then we can build intelligent machines of all different scales, all different capabilities. A dog is intelligent. I don't need, that'd be pretty good to have a dog. What about something that doesn't look like an animal at all? In different spaces. So my thinking about this is that we want to define what intelligence is, agree upon what makes an intelligent system. We can then say, okay, we're now going to build systems that work on those principles, or some subset of them, and we can apply them to all different types of problems. And the idea, it's not computing. We don't ask, if I take a little, little one-chip computer, I don't say, well, that's not a computer because it's not as powerful as this, big server over here. No, because we know that what the principles of computing are, and I can apply those principles to a small problem to a big problem. The same intelligence needs to get there. We have to say, these are the principles. I can make a small one, a big one. I can make them distributed. I can come on different sensors. They don't have to be human-like at all. Now, you did bring up a very interesting question about embodiment. Does it have to have embodiment? It has to have some concept of movement. It has to be able to move through these reference frames I talked about earlier. Whether it's physically moving, like if I'm going to have an AI that understands coffee cups, it's going to have to pick up the coffee cup and touch it and look at it with its eyes and hand or something equivalent to that. If I have a mathematical AI, maybe it needs to move to mathematical spaces. I could have a virtual AI that lives in the internet, and its movements are traversing links and digging into files, but it's got a location that it's traveling through some space. You can't have an AI that just takes some flash thing input, we call it flash inference. Here's a pattern. Done. No, it's movement pattern, attention, digging, building structure, just trying to figure out how to model the world. So some sort of embodiment, whether it's physical or not, has to be part of it.
So self-awareness in the way to be able to answer where am I?
Well, you bring up self-awareness, different topic, self-awareness.
No, a very narrow definition of self, meaning knowing a sense of self enough to know where am I in the space where it's
yeah. Basically, the system needs to know its location, or each component of the system needs to know where it is in the world at that point in time.
So, self-awareness and consciousness.
Yeah.
Do you think from neuroscience and neurocortex, these are interesting topics, solvable topics? Do you have any ideas of why the heck it is that we have a subjective experience at all?
Yeah, I have a lot of fun.
Is it useful, or is it just a side effect of us?
It's interesting to think about. I don't think it's useful as a means to figure out how to build intelligent machines. It's something that systems do, and we can talk about what it is, that are like, well, if I build a system like this, then it would be self-aware. And if I build it like this, it wouldn't be self-aware. So it's a choice I can have. It's not like, oh my God, it's self-aware. I can't. I heard an interview recently with this philosopher from Yale. I can't remember his name. I apologize for that. But he was talking about, well, if these computers were self-aware, then it would be a crime to unplug them. And I'm like, oh, come on. I unplug myself every night. I go to sleep. Is that a crime? I plug myself in again in the morning after I wake up. So, people get kind of bent out of shape about it. I have very definite, very detailed understanding or opinions about what it means to be conscious and what it means to be self-aware. I don't think it's that interesting a problem. You talk to Christoph Koch, he thinks that's the only problem. I didn't actually listen to your interview with him, but I know him, and I know that's the thing.
Well, he also thinks intelligence and consciousness are disjoint. So, it's not, you don't have to have one or the other. So I
disagree with that. I just totally disagree with that.
So where's your thoughts on consciousness? Where does it emerge from? Because it is.
So we have to break it down to the two parts, okay? Because consciousness isn't one thing. That's part of the problem with that term. Is it means different things to different people, and there's different components of it. There is a concept of self-awareness, okay? That can be very easily explained. You have a model of your own body. The neocortex models things in the world, and it also models your own body. And then it has a memory. It can remember what you've done. Okay, so it can remember what you did this morning, it can remember what you had for breakfast, and so on. And so I could say to you, okay, Lex, were you conscious this morning when you had your bagel? You'd say, yes, I was conscious. Now, what if I could take your brain and revert all the synapses back to the state they were this morning? And then I said to you, Lex, were you conscious when you ate the bagel? And she said, no, I wasn't conscious. Actually, here's a video of eating the bagel. And said, I wasn't there. I had that's not possible because I must have been unconscious at that time. So we can just make this one-to-one correlation between memory of your body's trajectory through the world over some period of time. A memory, and the ability to recall that memory is what you would call conscious. I was conscious of that, self-awareness. And any system that can memorize what it's done recently, and bring that back and invoke it again, would say, yeah, I'm aware. I remember what I did. All right, I got it. That's an easy one. Although some people think that's a hard one. The more challenging part of consciousness is one that's sometimes used to go by the word qualia, which is, why does an object seem red? Or what is pain? And why does pain feel like something? Why do I feel redness? Or why do I feel painness? And then I could say, well, why does sight seems different than hearing? It's the same problem. It's really, these are all just neurons. And so how is it that, why does looking at you feel different than, hearing you? It feels different, but it's just neurons in my head. They're all doing the same thing. So that's an interesting question. The best treatise I've read about this is by a guy named O'Regan. He wrote a book called Why Red Doesn't Sound Like a Bell. It's a little, it's not a trade book easy to read, but and it's an interesting question. Take something like color. Color really doesn't exist in the world. It's not a property of the world. The property of the world that exists is light frequency, and that gets turned into, we have certain cells in the retina that respond to different frequencies, different than others. And so when they enter the brain, you have a bunch of axons that are firing at different rates. And from that, we perceive color. But there is no color in the brain. I mean, there's no color coming in on those synapses. It's just a correlation between some axons and some property of frequency. And that isn't even color itself. Frequency doesn't have a color. It's just what it is. So then the question is, well, why does it even appear to have a color at all?
Just as you're describing it, there seems to be a connection with those ideas and reference frames. I mean, it just feels like consciousness having assigning the feeling of red to the actual color or to the wavelength is useful for intelligence.
Yeah, I think that's a good way of putting it. It's useful as a predictive mechanism or useful as a generalization idea. It's a way of grouping things together to say it's useful to have a model like this. Think about the well-known syndrome that people who've lost a limb experience called phantom limb. And what they claim is they can have their arm is removed, but they feel their arm. They not only feel it, they know it's there. It's there. I know it's there. They'll swear to you that it's there. And then they can feel pain in their arm, and they'll pain in their finger. And if they move their non-existent arm behind their back, then they feel the pain behind their back. So this whole idea that your arm exists is a model of your brain. It may or may not really exist. And just like, but it's useful to have a model of something that sort of correlates to things in the world, so you can make predictions about what would happen when those things occur. It's a little bit of a fuzzy, but I think we're getting right toward the answer there. It's useful through a model of to express things certain ways that we can then map them into these reference frames and make predictions about them. I need to spend more time on this topic. It doesn't bother me.
Do you really need to spend more time?
Yeah, I know.
It does feel special that we have subjective experience, but I'm yet to know why.
I'm just personally curious. It's not necessary for the work we're doing. I don't think I need to solve that problem to build intelligent machines at all. Not at all.
But there is the silly notion that you described briefly that doesn't seem so silly to us humans is, if you're successful building intelligent machines, it feels wrong to then turn them off. Because if you're able to build a lot of them, it feels wrong to then be able to, to turn off the...
Well, why? But let's break that down a bit. As humans, why do we fear death? There's two reasons we fear death. Well, first of all, I'll say when you're dead, it doesn't matter at all because you're dead. So why do we fear death? We fear death for two reasons. One is because we are programmed genetically to fear death. That's a survival and propagating the genes thing. And we also are programmed to feel sad when people we know. We don't feel sad for someone we don't know. People dying right now, they don't come say, I feel bad about because I don't know them. But if I knew them, I feel really bad. So again, these are old brain, genetically embedded things that we fear death. Outside of those uncomfortable feelings, there's nothing else to worry about.
Well, wait, hold on a second. Do you know the denial of death by Becker? There's a thought that death is, our whole conception of our world model kind of assumes immortality. And then death is this terror that underlies it all. So, well,
some people, not mine.
But okay, so what Becker would say is that you're just living in an illusion. You've constructed an illusion for yourself because it's such a terrible terror. The fact that
What's
this
the illusion?
the illusion that doesn't matter. You still are not coming to grips with
The illusion of what? That is
going to happen.
oh, like it's not going to happen?
You're actually operating. You haven't, even though you said you've accepted it, you haven't really accepted as much as you guys. What do you say? So it sounds like it sounds like you disagree with that notion.
Yeah, totally. Look,
So that does not
literally
have such
every night I go to bed, it's like dying.
with a little death.
It's what it does. And if I didn't wake up, it wouldn't matter to me. Only if I knew that was going to happen would it be bothersome. If I didn't know it was going to happen, how would I know? Then I would worry about my wife.
Yeah.
So imagine I was a loner and I lived in Alaska. And I lived out there, and there was no animals. Nobody knew I existed. I was just eating these roots all the time, and nobody knew I was there. And one day I didn't wake up. What pain in the world would there exist?
Well, so most people that think about this problem would say that you're just deeply enlightened or are completely delusional. One of the two. But I would say that's a very enlightened way to see the world. That's the rational.
I think it's rational. That's right.
But the fact is, we don't. We really don't have an understanding of why the heck it is we're born and why we die and what happens after we die.
Well, maybe there isn't a reason. Maybe there is. So I'm interested in those big problems too, right? You know, you interviewed Max Tegmark, those people like that, right? I'm interested in those big problems as well. And in fact, when I was young, I made a list of the biggest problems I could think of. First, why does anything exist? Second, why did we have the laws of physics that we have? Third, is life inevitable? And why is it here? Fourth, is intelligence inevitable? And why is it here? I stopped there because I figured if you can make a truly intelligent system, that will be the quickest way to answer the first three questions. I'm serious.
Yeah.
And so I said, my mission, you asked me earlier, my first mission is to understand the brain, but I felt that is the shortest way to get to true machine intelligence. And I want to get to true machine intelligence because even if it doesn't occur in my lifetime, other people will benefit from it because I think it'll occur in my lifetime, but 20 years, you never know. And but that will be the quickest way for us to, we can make super mathematicians, we can make super space explorers, we can make super physicists brains that do these things, and that can run experiments that we can't run. We don't have the abilities to manipulate things and so on. But we can build intelligent machines that do all those things, and with the ultimate goal of finding out the answers to the other questions.
Let me ask you another depressing and difficult question, which is: once we achieve that goal, of understanding intelligence, do you think we would be happier and more fulfilled as a species?
Understanding intelligence or understanding the answers to the big questions?
Understanding intelligence. How are we more?
Totally. It'd be a far more fun place to live.
You think so?
Oh yeah, why not? I mean, just put aside this, Terminator nonsense and just think about. You could think about. We can talk about the risks of AI if you want.
I'd love to. So let's talk about.
But I think the world is far better knowing things. It's always better to know things. Do you think it's better? Is it a better place to live in? That I know that our planet is one of many in the solar system, and the solar system is one of many in the galaxy. I think it's more. I sometimes think like, God, what would it be like 300 years ago? I'd be looking at the sky, I can't understand anything. Oh my God, I'd be like going to bed at night going, what's going on here?
Well, I mean, in some sense, I agree with you, but I'm not exactly sure. I'm also a scientist, so I share your views, but I'm not sure. We're like rolling down the hill together.
What's down the hill? I feel like we're climbing a hill.
Whatever.
We're getting closer to enlightenment, and you're going down the hill.
We're climbing. We're getting pulled up a hill by our curiosity.
Our curiosity is we're pulling ourselves up the hill by our curiosity.
Yeah, it's just because we're getting the same thing with the rock. Yeah. But okay, our happiness aside, do you have concerns about? We talk about Sam Harris, Elon Musk, of existential threats of intelligence.
No, I'm not worried about existential threats at all. There are some things we really do need to worry about. Even today's AI, we have things we have to worry about. We have to worry about privacy and about how it impacts false beliefs in the world, and we have real problems that and things to worry about with today's AI. And that will continue as we create more intelligent systems. There's no question, the whole issue about, making intelligent armaments and weapons is something that really we have to think about carefully. I don't think of those as existential threats. I think those are the kind of threats we always face, and we'll have to face them here, and we'll have to deal with them. The idea we can talk about what people think are the existential threats, but when I hear people talking about them, they all sound hollow. They're based on ideas. They're based on people who really have no idea what intelligence is. And if they knew what intelligence was, they wouldn't say those things. So those are not experts in this field.
So there's two, right? The one is like super intelligence, so a system that becomes far, far superior in reasoning ability than us humans.
How is that an existential threat?
So there's a lot of ways in which it could be. One way is us humans are actually irrational, inefficient, and get in the way of not happiness, but whatever the objective function is of maximizing that objective function.
Yeah.
Super intelligent.
The paperclip problem, things like that.
But so the paperclip problem, but with the super intelligent.
Yeah. So we already face this threat in some sense. They're called bacteria. These are organisms in the world that would like to turn everything into bacteria. And they're constantly morphing. They're constantly changing to evade our protections. And in the past, they have killed huge swaths of populations of humans on this planet. So if you want to worry about something that's going to multiply endlessly, we have it. And I'm far more worried in that regard. I'm far more worried that some scientists in the laboratory will create a super virus or super bacteria that we cannot control. That is a more of an existential threat. Putting an intelligent thing on top of it actually seems to make it less existential to me. It's like it limits its power, it limits where it can go, it limits the number of things it can do in many ways. A bacteria is something you can't even see. So that's only one of those problems.
Exactly. So the other one, just in your intuition about intelligence, when you think about intelligence of us humans, do you think of that as something? If you look at intelligence on a spectrum from 0 to us humans, do you think you can scale that to something far superior?
Yeah.
So all the mechanisms.
I want to make another point here, Lex, before we get there. Intelligence is the neocortex. It is not the entire brain. The goal is not to make a human. The goal is not to make an emotional system. The goal is not to make a system that wants to have sex and reproduce. Why would I build it? If I want to have a system that wants to reproduce and have sex, make bacteria, make computer viruses. Those are bad things. Don't do that. Those are really bad. Don't do those things. Regulate those. But if I just say I want an intelligent system, why does it have to have any of the human-like emotions? Why does it even care if it lives? Why does it even care if it has food? It doesn't care about those things. It's just, it's just in a trance thinking about mathematics, or it's out there just trying to build the space fort on Mars. That's a choice we make. Don't make human-like things. Don't make replicating things. Don't make things that have emotions. Just stick to the neocortex.
So that's a view actually that I share, but not everybody shares, in the sense that you have faith and optimism about us as engineers of systems, humans as builders of systems, to not put in not.
So this is why I mentioned the bacteria, because you might say, well, some person's going to do that. Well, some person today could create a bacteria that's resistant to all the known antibacterial agents. So we already have that threat. We already know this is going on. It's not a new threat. So just accept that, and we have to deal with it, right? Yeah. So my point has nothing to do with intelligence. Intelligence is a separate component that you might apply to a system that wants to reproduce and do stupid things. Let's not do that.
Yeah, in fact, it is a mystery why people haven't done that yet. My dad, as a physicist, believes that the reason, so for example, nuclear weapons haven't proliferated amongst evil people. So one belief that I share is that there's not that many evil people in the world that would use whether it's bacteria or nuclear weapons or maybe the future AI systems to do bad. So the fraction is small. And the second is that it's actually really hard, technically, basically.
Yeah.
So the intersection between evil and competent is small
Yeah.
in terms of, and
And
that's
by the way, to really annihilate humanity, you'd have to have, sort of the nuclear winter phenomenon, which is not one person shooting, or even 10 bombs. You'd have to have some automated system that, detonates 1 million bombs, or 10, whatever many thousands we have.
so extreme evil combined with extreme competence.
And it's just
Extreme
like building some stupid system that would automatically, Dr. Strangelove type of thing, detonate all of. I mean, look, we could have some nuclear bomb go off in some major city in the world. Like, I think that's actually quite likely, even in my lifetime. I don't think that's an unlikely thing, and it'd be a tragedy. But it won't be an existential threat. And it's the same as, the virus of 1917, whatever it was, the influenza. These bad things can happen, and the plague and so on. We can't always prevent them. We always try, but we can't. But they're not existential threats until we combine all those crazy things together.
So on the spectrum of intelligence from 0 to human, do you have a sense of whether it's possible to create several orders of magnitude, or at least double that of human intelligence?
I think
about neocortex.
I think it's the wrong thing to say double the intelligence. Break it down into different components. Can I make something that's 1 million times faster than a human brain? Yes, I can do that. Could I make something that is has a lot more storage than a human brain? Yes, I can do that. More copies of com. Can I make something that attaches to different sensors than a human brain? Yes, I can do that. Could I make something that's distributed? So these people, we talked earlier about the difference in neocortex voting. They don't have to be co-located. Like, they can be all around the place. I could do that too. Those are the levers I have. But is it more intelligent? Well, it depends what I train it on. What is it doing?
Well, so here's the thing. So let's say larger neocortex, or whatever size that allows for higher and higher hierarchies to form. We're talking about reference frames and concepts.
So could I have something that's a super physicist or a super mathematician? Yes.
And the question is, once you have a super physicist, will they be able to understand something? Do you have a sense that it will be orders of magnitude, like us compared to ants?
Could we ever understand it? Yeah. Most people cannot understand general relativity. It's a really hard thing to get. I mean, you can paint in a fuzzy picture. It's got G space. Yeah. But the field equations do that, and the deep intuitions are really, really hard. And I've tried. I'm unable to do it. Like, it's easy to get special relativity, but general relativity, that's too much. And so we already live with this to some extent. The vast majority of people can't understand actually what the vast majority of people actually know. We're just either we don't have the effort to, or we can't, or we don't have time, or we're just not smart enough, whatever. So, but we have ways of communicating. Einstein is spoken in a way that I can understand. He's given me analogies that are useful. I can use those analogies for my own work and think about, concepts that are similar. It's not stupid. It's not like he's existed some other plane and there's no connection to my plane in the world here. So that will occur. It already has occurred. That's what my point with this story is. It already has occurred. We live it every day. One could argue that when we create machine intelligence that think 1 million times faster than us, that it'll be so far we can't make the connection. But, at the moment, everything that seems really, really hard to figure out in the world, when you actually figure it out, it's not that hard. Almost everyone can understand the multiverses. Almost everyone can understand quantum physics. Almost everyone can understand these basic things, even though hardly any people can figure those things out.
Yeah, but really understand. So,
but you don't need to. Really, only a few people really understand.
You need to only understand the projections, the sprinkles of the useful insights.
So, that was my example of Einstein, right? His general theory of relativity is one thing that very, very, very few people can get. And what if we just said those other few people are also artificial intelligences? How bad is that?
In some sense, they are, right?
Yeah. They already. I mean, Einstein wasn't a very normal person. He had a lot of weird quirks, and so the other people who worked with him. So maybe they already were sort of this astral plane of intelligence that we live with it already. It's not a problem. It's still useful, and
So, do you think we are the only intelligent life out there in the universe?
I would say that intelligent life has and will exist elsewhere in the universe. I'll say that. there's a question about contemporaneous intelligence life, which is hard to even answer when we think about relativity and the nature of space-time. You can't say what exactly is this time someplace else in the world. But I think it's I do worry a lot about the filter idea, which is that perhaps intelligent species don't last very long. And so we haven't been around very long. As a technological species, we've been around for almost nothing. Like 200 years or something like that. And we don't have any data, a good data point on whether it's likely that we'll survive or not. So do I think that there have been intelligent life elsewhere in the universe? Almost certainly, of course. In the past, in the future, yes. Does it survive for a long time? I don't know. This is another reason I'm excited about our work, is our work meaning the general world of AI. I think we can build intelligent machines that last us. They don't have to be tied to Earth. They don't have to, I'm not saying that we're creating, aliens. I'm just saying, if I ask myself, and this might be a good point to end on here, if I ask myself, what's special about our species? We're not particularly interesting physically. We don't fly. We're not good swimmers. We're not very fast. We're not very strong. It's our brain. That's the only thing. And we are the only species on this planet that's built a model of the world that extends beyond what we can actually sense. We're the only people who know about the far side of the moon and the other universes and other galaxies and other stars and what happens in the atom. That knowledge doesn't exist anywhere else. It's only in our head. Cats don't do it. Dogs don't do it. Monkeys don't do it. And that is what we've created that's unique. Not our genes. It's knowledge. And if I ask me, what is the legacy of humanity? What should our legacy be? It should be knowledge. We should preserve our knowledge in a way that it can exist beyond us. And I think the best way of doing that, in fact, you have to do it, is to have to go along with intelligent machines to understand that. It's a very broad idea, but we should be thinking, I call it estate planning for humanity. We should be thinking about what we want to leave behind when as a species we're no longer here. And that'll happen sometime. Sooner or later, it's going to happen.
And understanding intelligence and creating intelligence gives us a better chance to prolong.
It does give us a better chance to prolong life. Yes. Gives us a chance to live on other planets. But even beyond that, our solar system will disappear one day. It's given enough time. So I don't know. I doubt we'll ever be able to travel to other things. But we can tell the stars, but we can send intelligent machines to do that.
So you have an optimistic, a hopeful view of our knowledge of the echoes of human civilization living through the intelligent systems we create.
Oh, totally. Well, I think the intelligent systems we create are, in some sense, the vessel for bringing them beyond Earth, or making them last beyond humans themselves. So,
how do you feel about that? That they won't be human, quote unquote.
Okay, it's not human. What is human? Our species are changing all the time. Human today is not the same as human just 50 years ago. What is human? Do we care about our genetics? Why is that important? As I point out, our genetics are no more interesting than a bacterium's genetics. They're no more interesting than monkeys' genetics. What we have, what's unique and what's valuable is our knowledge of it, what we've learned about the world. And that is the rare thing. That's the thing we want to preserve. It's
the knowledge.
It's the knowledge.
That's a really good place to end. Thank you so much for talking to me.
It's really fun.
I'm still paranoid about it. I don't even know if I want to make up passwords for it. I don't know. I can't. No, I don't want you to. I will remember my password 1, 2, 3, 4, 5. Customizing the antibodies. This is kind of interesting because this goes to research on the internet and things you don't record of, which is an issue. But anyway, go to data and privacy. With my ad center, and from there you can make any changes.
The following is a conversation with Sean Carroll. He's a theoretical physicist at Caltech, specializing in quantum mechanics, gravity, and cosmology. He's the author of several popular books. One on the arrow of time, called From Eternity to Here. One on the Higgs boson, called Particle at the End of the Universe, and one in science and philosophy called The Big Picture and the Origins of Life, Meaning, and the Universe Itself. He has an upcoming book on quantum mechanics that you can pre-order now called Something Deeply Hidden. He writes one of my favorite blogs on his website, preposterousuniverse.com. I recommend clicking on the Greatest Hits link that lists accessible, interesting posts on the arrow of time, dark matter, dark energy, the Big Bang, general relativity, string theory, quantum mechanics, and the big meta questions about the philosophy of science, God, ethics, politics, academia, and much, much more. Finally, and perhaps most famously, he's the host of a podcast called Mindscape that you should subscribe to and support on Patreon. Along with the Joe Rogan Experience, Sam Harris's Making Sense, and Dan Carlin's Hardcore History, Sean's Mindscape podcast is one of my favorite ways to learn new ideas or explore different perspectives and ideas that I thought I understood. It was truly an honor to meet and spend a couple hours with Sean. It's a bit heartbreaking to say that for the first time ever, the audio recorder for this podcast died in the middle of our conversation. There are technical reasons for this having to do with phantom power that I now understand will avoid. It took me 1 hour to notice and fix the problem. So, much like the universe's 68% dark energy, roughly the same amount from this conversation was lost, except in the memories of the two people involved and in my notes. I'm sure we'll talk again and continue this conversation on this podcast or on Sean's. And of course, I look forward to it. This is the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, iTunes, support it on Patreon, or simply connect with me on Twitter at Lex Friedman. And now, here's my conversation with Sean Carroll. What do you think is more interesting and impactful? Understanding how the universe works at a fundamental level, or understanding how the human mind works?
You know, of course, this is a crazy, meaningless, unanswerable question in some sense, because they're both very interesting and there's no absolute scale of interestingness. So we can rate them on, there's the glib answer that says the human brain is part of the universe, right? And therefore understanding the universe is more fundamental than understanding the human brain.
But do you really believe that once we understand the fundamental way the universe works at the particle level, the forces, we would be able to understand how the mind works?
No, certainly not. We cannot understand how ice cream works just from understanding how particles work, right? So I'm a big believer in emergence. I'm a big believer that there are different ways of talking about the world beyond just the most fundamental microscopic one. You know, when we talk about tables and chairs and planets and people, we're not talking the language of particle physics and cosmology. So, but understanding the universe, you didn't say just at the most fundamental level, right? So understanding the universe at all levels is part of that. I do think, to be a little bit more fair to the question, there probably are general principles of complexity, biology, information processing, memory, knowledge, creativity that go beyond just the human brain, right? And maybe one could count understanding those as part of understanding the universe. The human brain, as far as we know, is the most complex thing in the universe. So it's certainly absurd to think that by understanding the fundamental laws of particle physics, you get any direct insight on how the brain works.
But then there's this step from the fundamentals of particle physics to information processing, which a lot of physicists and philosophers maybe a little bit carelessly take when they talk about artificial intelligence. Do you think of the universe as a kind of a computational device?
No. The honest answer there is no. There's a sense in which the universe processes information clearly. There's a sense in which the universe is like a computer, clearly. But in some sense, I think I tried to say this once on my blog and no one agreed with me, but the universe is more like a computation than a computer, because the universe happens once. A computer is a general purpose machine, right? That you can ask it different questions even upon the calculator, right? And it's set up to answer certain kinds of questions. The universe isn't that. So information processing happens in the universe, but it's not what the universe is. Because I know your MIT colleague Seth Lloyd feels very differently about this, right?
Well, you're thinking of the universe as a closed system, So what makes a computer more like a PC, like a computing machine, is that there's a human that everyone's comes up to it and moves the mouse around. Yeah. So input gives it input, and and that's why you're saying it's just a computation, a deterministic thing that's just unrolling. But the immense complexity of it is nevertheless like processing. There's a state, and it changes with with rules, and there's a sense for a lot of people that if the human brain operates within that world, then it's simply just a small subset of that. And so there's no reason we can't build arbitrarily great intelligences.
Yeah.
Do you think of intelligence in this way?
Intelligence is tricky. I don't have a definition of it offhand. So I remember this panel discussion that I saw on YouTube. I wasn't there, but Seth Lloyd was on the panel, and so was Martin Rees, the famous astrophysicist. And Seth gave his shtick for why the universe is a computer, explained this, and Martin Rees said, so what is not a computer? And Seth was like, that's a good question. I'm not sure, because if you have a sufficiently broad definition of what a computer is, then everything is, right? And the simile or the analogy gains force when it excludes some things. Is the moon going around the Earth performing a computation? I can come up with definitions in which the answer is yes, but it's not a very useful computation. I think that it's absolutely helpful to think about the universe in certain situations, certain contexts, as an information processing device. I'm guilty of writing a paper called Quantum Circuit Cosmology, where we modeled the whole universe as a quantum circuit. As a circuit, yeah. And
with qubits, kind of.
With qubits, basically, right, yeah.
Hello.
So it's becoming entangled. So do we want to digress a little bit? This is kind of fun. So here's a mystery about the universe that's so deep and profound that nobody talks about it. Space expands, right? And we talk about, in a certain region of space, a certain number of degrees of freedom, a certain number of ways that the quantum fields and the particles in that region can arrange themselves. That number, degrees of freedom in a region of space, is arguably finite. We actually don't know how many there are, but there's a very good argument that says it's a finite number. So as the universe expands and space gets bigger, are there more degrees of freedom? If it's an infinite number, it doesn't really matter. Infinity times 2 is still infinity. But if it's a finite number, then there's more space, there's more degrees of freedom. So where did they come from? That would mean the universe is not a closed system. There's more degrees of freedom popping into existence. So what we suggested was that there are more degrees of freedom. And it's not that they're not there to start, but they're not entangled to start. So the universe that you and I know of, the three dimensions around us that we see, we said that those are the entangled degrees of freedom making up space-time. As the universe expands, there are a whole bunch of qubits in their zero state that become entangled with the rest of space-time through the action of these quantum circuits.
So what does it mean that there's now more degrees of freedom as they become more entangled?
Yeah, so
as the universe expands.
That's right. So there's more and more degrees of freedom that are entangled, that are playing the role of parts of the entangled space-time structure. So the underlying philosophy is that space-time itself arises from the entanglement of some fundamental quantum degrees of freedom.
Wow. Okay. So at which point is most of the entanglement happening? Are we talking about close to the Big Bang? Or are we talking about throughout the time of
throughout history? Yeah. So the idea is that at the Big Bang, almost all the degrees of freedom that the universe could have were there, but they were unentangled with anything else. And that's a reflection of the fact that the Big Bang had a low entropy. It was very simple, very small place. And as space expands, more and more degrees of freedom become entangled with the rest of the world.
Well, I have to ask John Carroll, what do you think of the thought experiment from Nick Bostrom that we're living in a simulation? So I think, let me contextualize that a little bit more. I think people don't actually take this thought experiment. I think it's quite interesting. It's not very useful, but it's quite interesting. From the perspective of AI, a lot of the learning that can be done usually happens in simulation from artificial examples. And so it's a constructive question to ask, how difficult is our real world to simulate, right? Which is kind of a dual part of, if we're living in a simulation, somebody built that simulation, how hard, if you were to try to do it yourself, how hard would it be?
So obviously we could live in a simulation. If you just wanted the physical possibility, then I completely agree that it's physically possible. I don't think that we actually are. So take this one piece of data into consideration. We live in a big universe, okay? There's 2 trillion galaxies in our observable universe, 200 billion stars in each galaxy, etc. It would seem to be a waste of resources to have a universe that big going on just to do a simulation. So in other words, I want to be a good Bayesian. I want to ask, under this hypothesis, what do I expect to see? So the first thing I would say is I wouldn't expect to see a universe that was that big. Okay. The second thing is, I wouldn't expect the resolution of the universe to be as good as it is. So it's always possible that if our superhuman simulators only have finite resources, that they don't render the entire universe, right? That the part that is out there, the 2 trillion galaxies, isn't actually being simulated fully. Okay. But then the obvious extrapolation of that is that only I am being simulated fully. Like the rest of you are just parts non-player characters, right? I'm the only thing that is real. The rest of you are just chatbots. Beyond this wall, I see the wall, but there is literally nothing on the other side. That is sort of Bayesian prediction of what it would be like to do an efficient simulation of me. So, like, none of that seems quite realistic. Just that I don't see. I hear the argument that it's just possible and easy to simulate lots of things. I don't see any evidence from what we know about our universe that we look like a simulated universe. Now, maybe you could say, well, we don't know what it would look like, but that's just abandoning your Bayesian responsibilities. Like, your job is to say, under this theory, here's what you would expect to see.
Yeah, so certainly, if you think about simulation as a thing that's like a video game where only a small subset is being rendered. But say all the laws of physics, the entire closed system of the quote-unquote universe, it had a creator.
Yeah, it's always possible.
Right, so that's not useful to think about when you're thinking about physics. The way Nick Bostrom phrases it, if it's possible to simulate the universe, eventually we will do it. Right. And you can use that, by the way, for a lot of things.
Well, yeah.
But I guess the question is, how hard is it to create a universe?
I wrote a little blog post about this, and maybe I'm missing something, but there's an argument that says not only that it might be possible to simulate a universe, but probably if you imagine that you actually attribute consciousness and agency to the little things that we're simulating, or little artificial beings, there's probably a lot more of them than there are ordinary organic beings in the universe, or there will be in the future, right? So there's an argument, not only is being a simulation possible, it's probable, because in the space of all living consciousnesses, most of them are being simulated, right? Most of them are not at the top level. I think that argument must be wrong, because it follows from that argument that, if we're simulated, but we can also simulate other things. Well, but if we can simulate other things, they can simulate other things, right? If we give them enough power and resolution. And ultimately, we'll reach a bottom, because the laws of physics in our universe have a bottom. We're made of atoms and so forth. So there will be the cheapest possible simulations. And if you believe the original argument, you should conclude that we should be in the cheapest possible simulations. That's where most people are. But we don't look. It doesn't look at all like we're at the edge of resolution. That we're 16-bit, things. It seems much easier to make much lower level things than we are. So, and also I question the whole approach to the anthropic principle that says we are typical observers in the universe. I think that's not actually. I think that there's a lot of selection that we can do that we're typical within things we already know, but not typical within all.
So, do you think there's intelligent life, however you would like to define intelligent life, out there in the universe?
My guess is that there is not intelligent life in the observable universe other than us. simply on the basis of the fact that the likely number of other intelligent species in the observable universe, there's two likely numbers, 0 or billions. And if there had been billions, we would have noticed it. For there to be literally like a small number, like, Star Trek, there's a dozen intelligent civilizations in our galaxy, but not a billion. That's weird. That's sort of bizarre to me. It's easy for me to imagine that there are 0 others because there's just a big bottleneck to making multicellular life or technological life or whatever. It's very hard for me to imagine that there's a whole bunch out there that have somehow remained hidden from us.
The question I'd like to ask is, what would intelligent life look like? What I mean by that question and where it's going is, what if intelligent life is just fundamental, is in some very big ways different than the one that has on Earth. That there's all kinds of intelligent life that operates at different scales of both size and tempo.
Like, it's a great possibility because I think we should be humble about what intelligence is, what life is. We don't even agree on what life is, much less what intelligent life is, right? So that's an argument for humility, saying there could be intelligent life of a very different character, right? But you can imagine that dolphins are intelligent but never invent space travel because they live in the ocean and they don't have thumbs, right? So they never invent technology, they never invent smelting. Maybe the universe is full of intelligent species that just don't make technology. Right? That's compatible with the data, I think. And I think maybe what you're pointing at is even more out there versions of intelligence. Intelligence in intermolecular clouds, or on the surface of a neutron star, or in between the galaxies and giant things where the equivalent of a heartbeat is 100 million years. On the one hand, yes, we should be very open-minded about those things. On the other hand, we all of us share the same laws of physics. There might be something about the laws of physics, even though we don't currently know exactly what that would be, that makes meters and years the right length and time scales for intelligence. Maybe not, but we're made of atoms. Atoms have a certain size. We orbit stars, so stars have a certain lifetime. It's not impossible to me that there's a sweet spot for intelligent life that we find ourselves in. So I'm open-minded either way. I'm open-minded either being humble, and there's all sorts of different kinds of life, or no, there's a reason we just don't know it yet why life like ours is the kind of life that's.
Yeah, I'm of two minds too, but I often wonder if our brains is just designed to, quite obviously, to operate and see the world and these time scales, and we're almost blind, and the tools we've created for detecting things are blind.
Yeah,
the kind of observation needed to see intelligent life at other scales.
Well, I'm totally open to that, but so here's another argument I would make. We have looked for intelligent life, but we've looked for it in the dumbest way we can, right? By turning radio telescopes to the sky. And why in the world would a super advanced civilization randomly beam out radio signals wastefully in all directions into the universe? That just doesn't make any sense. Especially because in order to think that you would actually contact another civilization, you would have to do it forever. You'd have to keep doing it for millions of years. That sounds like a waste of resources. If you thought that there were other solar systems with planets around them where maybe intelligent life didn't yet exist but might someday, you wouldn't try to talk to it with radio waves. You would send a space out there, and you would park it around there. It would be like, from our point of view, it would be like 2001, where there's a monolith. But there could be an artifact. In fact, the other way works also, right? There could be artifacts in our solar system that have been put there by other technologically advanced civilizations, and that's how we will eventually contact them. We just haven't explored the solar system well enough yet to find them. The reason why we don't think about that is because we're young and impatient, right? Like, it would take more than my lifetime to actually send something to another star system and wait for it to come back. So, but if we start thinking about hundreds of thousands of years or million-year time scales, it's clearly a different thing to do.
Are you excited by the thing that Elon Musk is doing with SpaceX in general? The idea of space exploration, even though you're or your species is young and impatient?
Yeah. No, I do think that space travel is crucially important, long term, even to other star systems. And I think that many people overestimate the difficulty because they say, look, if you travel 1% the speed of light to another star system, we'll be dead before we get there, right? And I think that it's much easier, and therefore, when they write their science fiction stories, they imagine go faster than the speed of light because otherwise they're goofy, right? We're not going to go faster than the speed of light, but we could easily imagine that the human lifespan gets extended to thousands of years. And once you do that, the stars are much closer, effectively, right? And what's a 100-year trip, right? So I think that that's going to be the future, the far future. Not my lifetime, once again, but baby steps.
Unless your lifetime gets extended.
Well, it's in a race against time, right? A friend of mine who actually thinks about these things said, you and I are going to die, but I don't know about our grandchildren. I don't know. Predicting the future is hard, but that's at least a plausible. And so, I think that as we discussed earlier, there are threats to the Earth, known and unknown, right? Having spread humanity and biology elsewhere is a really important long-term goal.
What kind of questions can science not currently answer, but might soon? When you think about the problems and mysteries before us that may be within reach of science.
I think the obvious one is the origin of life. We don't know how that happened. There's a difficulty in knowing how it happened historically, actually, literally on Earth. But starting life from non-life is something I kind of think we're close to, right? We're
really think so? How difficult is it to start life?
Well, I've talked to people, including on the podcast, about this. Life requires three things. So life as we know it. So there's a difference between life, who knows what it is, and life as we know it, which we can talk about with some intelligence. So life as we know it requires compartmentalization. You need like a little membrane around your cell. Metabolism, taking food and eating it, let that make you do things. And then replication. Okay, so you need to have some information about who you are that you pass down to future generations. In the lab, compartmentalization seems pretty easy. It's not hard to make lipid bilayers that come into little cellular walls pretty easily. Metabolism and replication are hard, but replication we're close to. People have made RNA-like molecules in the lab that I think the state of the art is they're not able to make one molecule that reproduces itself, but they're able to make two molecules that reproduce each other. Yeah, so that's okay. That's pretty close. Yeah. Metabolism is harder, believe it or not, even though it's sort of the most obvious thing. We want some sort of controlled metabolism, and the actual cellular machinery in our bodies is quite complicated. It's hard to see it just popping into existence all by itself. But we're making progress. In fact, I don't think we're spending nearly enough money on it. If I were the NSF, I would flood this area with money because it would change our view of the world if we could actually make life in the lab and understand how it was made originally on Earth.
And I'm sure it would have some ripple effects that help cure diseases and so on. I mean, just that understanding.
Right. So synthetic biology is a wonderful big frontier where we're making cells. Right now, the best way to do that is to borrow heavily from existing biology, right? Craig Ventnor, several years ago, created an artificial cell, but it was a tremendous accomplishment, but all he did was take out the DNA from the cell and put in entirely new DNA and let it boot up and go.
What about the leap to creating intelligent life on Earth?
Yeah.
However, again, we define intelligence, of course, but let's just even say Homo sapiens, the modern intelligence in our human brain. Do you have a sense of what's involved in that leap and how big of a leap that is?
So AI would count in this, or you really want life? You want really an organism in some sense?
AI would count.
Okay.
Of course, AI would count.
Well, let's say artificial consciousness, right? So I do not think we are on the threshold of creating artificial consciousness. I think it's possible. I'm not, again, very educated about how close we are, but my impression is not that we're really close because we understand how little we understand of consciousness and what it is. So if we don't have any idea what it is, it's hard to imagine we're on the threshold of making it ourselves. But it's doable. It's possible. I don't see any obstacles in principle. So yeah, I would hold some interest in that happening eventually.
I think in general, consciousness, I think it would be just surprised how easy consciousness is once we create intelligence.
Yeah.
I think consciousness is a thing that that's just something we all fake.
Well, good. No, actually, I like this idea that in fact consciousness is way less mysterious than we think.
Yeah.
Because we're all at every time and at every moment less conscious than we think we are, right? We can fool things. And I think that plus the idea that we have artificial intelligence systems, but you put them in a body, right? Give them a robot body. That will help the faking a lot.
Yeah, I think creating consciousness in our artificial consciousness is as simple as asking a Roomba to say I'm conscious and refusing to be talked out of it.
Could be.
And I mean, I'm almost being silly, but that's what we do. That's what we do with each other. This the kind of that consciousness is also a social construct, and a lot of our ideas of intelligence is a social construct. And so, reaching that bar involves something that's beyond. Doesn't necessarily involve the fundamental understanding of how you go from electrons to neurons to cognition.
No, actually, I think that is an extremely good point. And in fact, what it suggests is, so yeah, we referred to Kate Darling, who I had on the podcast, and who does these experiments with very simple robots, but they look like animals, and they can look like they're experiencing pain, and we human beings react very negatively to these little robots looking like they're experiencing pain. And what you want to say is, they're just robots, it's not really pain, right? It's just some electrons going around. But then you realize, you and I are just electrons going around, and that's what pain is also. And so what I would have an easy time imagining is that there is a spectrum between simple little robots that Kate works with and a human being, where there are things that sort of by some strict definition, Turing test level thing are not conscious, but nevertheless walk and talk like they're conscious. And it could be that the future is, Siri is close, right? And so it could be the future has a lot more agents like that. And in fact, rather than someday going, aha, we have consciousness, just creep up on it with more and more accurate reflections.
And in the future, maybe the present, for example, we haven't met before, and you're basically assuming that I'm human. As it's
a high probability
at this time, because but in the future there might be question marks on that, right?
Yeah, no, absolutely. Certainly, videos are almost to the point where you shouldn't trust them already. Photos you can't trust, right? Videos is easier to trust, but we're getting worse. But, we're getting better at faking them, right? So physical body people, what's so hard about faking that? So this is very depressing, this conversation we're having. So,
to me, it's exciting.
To me, you're doing it, so it's exciting to you, but it's a sobering thought. We're very bad, right, at imagining what the next 50 years are going to be like when we're in the middle of a phase transition as we are right now.
Yeah, and in general, I'm not blind to all the threats.
Yeah.
I am excited by the power of technology to protect us against the threats as they evolve. I'm not as much as Steven Pinker optimistic about the world, but in everything I've seen, all the brilliant people in the world that I've met are good people. So the army of the good, in terms of the development of technology, is large.
Okay, you're way more optimistic than I am. I think that goodness and badness are equally distributed among intelligent and unintelligent people. I don't see much of a correlation.
Interesting. Neither of us have proof.
Yeah, exactly. Opinions are free, right?
Nor definitions of good and evil. We come without definitions or without data, opinions. So, what kind of question can science not currently answer, may never be able to answer in the review?
Well, the obvious one is what is good and bad. What is right and wrong. I think that there are questions that science tells us what happens, what the world is and what it does. It doesn't say what the world should do or what we should do because we're part of the world. But we are part of the world, and we have the ability to feel like something's right, something's wrong, and to make a very long story very short, I think that the idea of moral philosophy is systematizing our intuitions of what is right. And science might be able to predict ahead of time what we will do, but it won't ever be able to judge whether we should have done it.
So, you're kind of unique in terms of scientists. It doesn't have to do with podcasts, but even just reaching out, I think you referred to as sort of doing interdisciplinary science. So you reach out and talk to people that are outside of your discipline, which I always hope that's what science is for. In fact, I was a little disillusioned when I realized that academia is very siloed. Yeah. And so the question is, at your own level, how do you prepare for these conversations? How do you think about these conversations? How do you open your mind enough to have these conversations? And it may be a little bit broader, how can you advise other scientists to have these kinds of conversations? Not at the podcast. The fact that you're doing a podcast is awesome. Other people get to hear them. Yeah. But it's also good to have it without mics in general.
It's a good question, but a tough one to answer. I think about, a guy I know is a personal trainer, and he was asked on the podcast, how do we, psych ourselves up to do a workout? How do we make that discipline to go and work out? And he's like, why are you asking me? Like, I can't stop working out. Like, I don't need to psych myself up. So, and likewise, he asked me, like, how do you get to have interdisciplinary conversations and all sorts of different things, all sorts of different people? Like, that's what makes me go, right? Like, I couldn't stop doing that. I did that long before any of them were recorded. In fact, a lot of the motivation for starting recording it was making sure I would read all these books that I had purchased, right? Like, I had all these books I wanted to read, not enough time to read them. And now, if I have motivation, because I'm going to interview Pat Churchland, I'm going to finally read her book, And it's absolutely true that academia is extraordinary, right? We don't talk to people. We rarely do. And in fact, when we do, is punished. Like the people who do it successfully generally first became very successful within their little silo discipline, and only then did they start expanding out. If you're a young person, I have graduate students. I try to be very, very candid with them about this. That it's most graduate students do not become faculty members, right? It's a tough road, and so live the life you want to live, but do it with your eyes open about what it does to your job chances. And the more broad you are, and the less time you spend hyper specializing in your field, the lower your job chances. That's just an academic reality. It's terrible. I don't like it, but it's a reality. And for some people, that's fine. Like, there's plenty of people who are wonderful scientists who have zero interest in branching out and talking to anyone outside their field. But it is disillusioning to me. Some of the romantic notion I had of the intellectual academic life is belied by the reality of it. The idea that we should reach out beyond our discipline, and that is a positive good, is just so rare in universities that it may as well not exist at all.
But that said, even though you're saying you're doing it like the personal trainer because you just can't help it, you're also an inspiration to others. Like, I can speak for myself. I also have a career I'm thinking about, right? Yeah. And without your podcast, I may have not have been doing this at all, right? So it makes me realize that these kinds of conversations is kind of what science is about. In many ways, the reason we write papers, this exchange of ideas, is much harder to do interdisciplinary papers, I would say. Yeah. Right. And conversations are easier. So conversations is the beginning, and in the field of AI, it's obvious that we should think outside of pure computer vision competitions on a particular data sets. We should think about the broader impact of how this can be, reaching out to physics, to psychology, to neuroscience, and having these conversations. So you're an inspiration, and so
thank you very much.
Never know how the world changes. I mean, the fact that this stuff is out there, and I've a huge number of people come up to me, grad students, really loving the podcast, inspired by it, and they will probably have that. There'll be ripple effects when they become faculty and so on. we can end on a balance between pessimism and optimism. And Sean, thank you so much for talking to me. It was awesome.
No, Lex, thank you very much for this conversation.
wanted to be a teacher when you were little, but you grew up and things changed. It's time to put it back on the music. Innovative things are happening in teaching today. Maybe a part.
Make one teach. Visit teach.org. Watch you teach and have music.
The free iHeartRadio app is #1 for music, radio, and podcasts all in one. Discover a new podcast from our library of over 350,000 titles. Here's an iHeartRadio podcast preview.
How do you take on the shadows? I tell them that I know that they're the ones who are ready. The largest electronic news websites on the darknet.
The following is a conversation with Kai-Fu Lee. He's the chairman and CEO of Sinovation Ventures that manages a $2 billion dual currency investment fund with a focus on developing the next generation of Chinese high-tech companies. He's the former president of Google China and the founder of what is now called Microsoft Research Asia, an institute that trained many of the artificial intelligence leaders in China, including CTOs or AI execs at Baidu, Tencent, Alibaba, Lenovo, and Huawei. He was named one of the 100 most influential people in the world by Time magazine. He's the author of 7 best-selling books in Chinese, and most recently, the New York Times bestseller called AI Superpowers, China, Silicon Valley, and the New World Order. He has unparalleled experience in working across major tech companies and governments on applications of AI. So, he has a unique perspective on global innovation and the future of AI that I think is important to listen to and think about. This is the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube and iTunes, support it on Patreon, or simply connect with me on Twitter at Lex Friedman. And now, here's my conversation with Kai-Fu Lee. I immigrated from Russia to U.S. when I was 13. You immigrated to U.S. at about the same age. The Russian people, the American people, the Chinese people, each have a certain soul, a spirit that permeates throughout the generations. So maybe it's a little bit of a poetic question, but could you describe your sense of what defines the Chinese soul?
I think the Chinese soul of people today, right? We're talking about people who have had centuries of burden because of the poverty that the country has gone through, and suddenly shined with hope of prosperity in the past 40 years as China opened up and embraced market economy. And undoubtedly, there are 2 sets of pressures on the people, that of the tradition, that of facing difficult situations, and that of hope of wanting to be the first to become successful and wealthy. So that's a very strong hunger and a strong desire, a strong work ethic that drives China forward.
And is there roots to not just this generation, but before, that's deeper than just new economic developments? Is there something that's unique to China that you could speak to that's in the people?
Yeah. Well, the Chinese tradition is about excellence, dedication, and results. And the Chinese exams and study subjects in schools have traditionally started from memorizing 10,000 characters. Not an easy task to start with. And further by memorizing his historic philosophers, literature, poetry. So it really is probably the strongest rote learning mechanism created to make sure people have good memory and remember things extremely well. That, I think, at the same time, suppresses the breakthrough innovation and also enhances the speed, execution, get results. And that, I think, characterizes the historic basis of China.
That's interesting because there's echoes of that in Russian education as well as rote memorization. So you have to memorize a lot of poetry. I mean, there's just an emphasis on perfection in all forms that's not conducive to perhaps what you're speaking to, which is creativity. But you think that kind of education holds back the innovative spirit that you might see in the United States?
Well, it holds back the breakthrough innovative spirit that we see in the United States, but it does not hold back the valuable execution-oriented, result-oriented, value-creating engines, which we see China being very successful.
So, is there a difference between a Chinese AI engineer today and an American AI engineer, perhaps rooted in the culture that we just talked about, or the education, or the very soul of the people, or no? And what would your advice be to each if there's a difference?
Well, there's a lot that's similar because AI is about mastering sciences, about using known technologies and trying new things, but it's also about picking from many parts of possible networks to use and different types of parameters to tune, and that part is somewhat rote. And it is also, as anyone who's built AI products can tell you, a lot about cleansing the data because AI runs better with more data, and data is generally unstructured, errorful, and unclean, and the effort to clean the data is immense. So I think the better part of American engineering, AI engineering process is to try new things, to do things people haven't done before, and to use technology to solve most, if not all, problems. So to make the algorithm work despite not so great data, find error tolerant ways to deal with the data. The Chinese way would be to basically enumerate to the fullest extent all the possible ways by a lot of machines, try lots of different ways to get it to work, and spend a lot of resources and money and time cleaning up data. That means the AI engineer may be writing data cleansing algorithms, working with thousands of people who label or correct or do things with the data. That is the incredible hard work that might lead to better results. So the Chinese engineer would rely on and ask for more and more and more data and find ways to cleanse them and make them work in the system, and probably less time thinking about new algorithms that can overcome data or other issues.
So where's your intuition? Where do you think the biggest impact in the next 10 years lies? Is it in some breakthrough algorithms, or is it in just this at scale rigor, a rigorous approach to data, cleaning data, organizing data onto the same algorithm? What do you think the big impact in the applied world is?
Well, if you're really in a company and you have to deliver results using known techniques and enhancing data, seems like the more expedient approach that's very low risk and likely to generate better results. And that's why the Chinese approach has done quite well. Now, there are a lot of more challenging startups and problems, such as autonomous vehicles, medical diagnosis, that existing algorithms may probably won't solve. And that would put the Chinese approach more challenged and give the more breakthrough innovation approach more of an edge on those kinds of problems.
So let me talk to that a little more. So, my intuition personally is that data can take us extremely far. So you brought up autonomous vehicles and medical diagnosis. So your intuition is that huge amounts of data might not be able to completely help us solve that problem.
Right. So breaking that down further, in autonomous vehicle, I think huge amounts of data probably will solve trucks driving on highways, which will deliver significant value, and China will probably lead in that. Full L5 autonomous is likely to require new technologies we don't yet know, and that might require academia and great industrial research, both innovating and working together, and in that case, US has an advantage.
So the interesting question there is, I don't know if you're familiar on the autonomous vehicle space and the developments with Tesla and Elon Musk, where they are in fact full steam ahead into this mysterious complex world of full autonomy, L5, L4, L5. and they're trying to solve that purely with data. So the same kind of thing that you're saying is just for highway, which is what a lot of people share your intuition.
Yeah.
They're trying to solve with data. Just to linger on that moment further, do you think possible for them to achieve success with simply just a huge amount of this training on edge cases and difficult cases in urban environments, not just highway and so on?
I think it would be very hard. One could characterize Tesla's approach as kind of a Chinese strength approach, right? Gather all the data you can and hope that will overcome the problems. But in autonomous driving, clearly a lot of the decisions aren't merely solved by aggregating data and having feedback. There are things that are more akin to human thinking. And how would those be integrated and built? There has not yet been a lot of success integrating human intelligence, or call it expert systems, if you will, even though that's a taboo word, with the machine learning. And the integration of the two types of thinking hasn't yet been demonstrated. And the question is, how much can you push a purely machine learning approach? And of course, Tesla also has an additional constraint that they don't have all the sensors. I know that they think it's foolish to use LiDARs, but that's clearly one less very valuable and reliable source of input that they're foregoing, which may also have consequences. I think the advantage, of course, is capturing data no one has ever seen before. And in some cases, such as computer vision and speech recognition, I have seen Chinese companies accumulate data that's not seen anywhere in the Western world, and they have delivered superior results. But then speech recognition and object recognition are relatively suitable problems for deep learning and don't have the potentially need for the human intelligence analytical planning elements.
And the same on the speech recognition side, your intuition that speech recognition and the machine learning approaches to speech recognition won't take us to a conversational system that can pass the Turing test, which is sort of maybe akin to what driving is. So it needs to have something more than just simply simple language understanding, simple language generation.
Roughly right. I would say that based on purely machine learning approaches, it's hard to imagine it could lead to a full conversational experience across arbitrary domains, which is akin to L5. I'm a little hesitant to use the word Turing test because the original definition was probably too easy. Probably do that.
The spirit of the Turing test.
That's what I was referring to.
Of course. So you've had major leadership research positions at Apple, Microsoft, Google. So continuing on the discussion of America, Russia, Chinese soul and culture and so on, what is the culture of Silicon Valley in contrast to China, maybe US broadly, and what is the unique culture of each of these three major companies in your view?
I think in aggregate, Silicon Valley companies, we could probably include Microsoft in that, even though they're not in the Valley, is really dream big and have visionary goals and believe that technology will conquer all, and also the self-confidence and the self-entitlement that whatever they produce, the whole world should use and must use. And those are historically important, I think. Steve Jobs' famous quote that he doesn't do focus groups, he looks in the mirror and asks the person in the mirror, what do you want? And that really is an inspirational comment that says the great company shouldn't just ask users what they want, but develop something that users will know they want when they see it, but they could never come up with themselves. I think that is probably the most exhilarating description of what the essence of Silicon Valley is, that this brilliant idea could cause you to build something that couldn't come out of focus groups or A/B tests. And iPhone would be an example of that. No one in the age of BlackBerry would write down they want an iPhone or multi-touch. A browser might be another example. No one would say they want that in the days of FTP, but once they see it, they want it. So I think that is what Silicon Valley is best at.
but it also comes with it came with a lot of success. These products became global platforms, and there were basically no competitors anywhere. And that has also led to a belief that these are the only things that one should do, that companies should not tread on other companies' territory, so that a Groupon and a Yelp and then Open Table and Grubhub would each feel, okay, I'm not going to do the other company's business because that would not be the pride of innovating whatever each of these four companies have innovated. But I think the Chinese approach is do whatever it takes to win. And it's a winner-take-all market. And in fact, in the internet space, the market leader will get predominantly all the value extracted out of the system. So, and the system isn't just defined as one narrow category, but gets broader and broader. So it's amazing ambition for success and domination of increasingly larger product categories, leading to clear market winner status and the opportunity to extract tremendous value. And that develops a practical, result-oriented, ultra-ambitious, winner-take-all, gladiatorial mentality. And if what it takes is to build what the competitors built, essentially a copycat, that can be done without infringing laws. If what it takes is to